Not done yet, because I only called free earlier in cases of error, and that was just to be safe. I can now free the list. And now, if I want to inform the computer that I want list, quote unquote, my variable called list, to point at not the old chunk like it originally did, but the new chunk, I think I can just do this. List equals TMP. And again, that's just saying that if list is a pointer, which it was, because look at the very top line here. On line 6, I declared list to be a pointer to a chunk of memory. Temp, meanwhile, is a separate pointer to a chunk of memory. So down here, this line 33 is just a matter of my saying, OK, now, henceforth, because I've already freed the old chunk of memory, my list variable should point not at this chunk of 3 bytes, but this chunk of 4 bytes, or really 12 in total now. Or rather, 16 now, because we have 4 such bytes. Questions now on this code, the point of which was quite simply to demonstrate how we could implement in code this idea of fairly correctly but inefficiently allocating a new array of sufficient size and then populating it with a new 4th value. Questions on what we've just done here? No? Yeah. Good question. At this point in the story, with line 33, do I not have 2 different variables pointing at the same chunk of memory? Short answer, yes. But here's where the semantics are perhaps compelling. List is the variable that I intend to use longer term and keep around in memory. And again, assume that there's even more code going on here that we just didn't write yet. So it's useful to have that variable. Temp was just kind of a necessary evil, because up here, it would not have been correct to do this. It would not have been correct to say list on line 18 equals the new chunk of memory, because this would have represented a memory leak. If I prematurely change temp to point not at the old chunk but the new chunk, at that point, no one's pointing at the old chunk, and so I've lost those 3 bytes. Valgrind, for instance, would yell at you for having lost as many bytes in memory. So in this case here, I do leave this as temp. Yes, it's duplicative at this point, but it's not a huge deal if it was just meant semantically to be a temporary value. But down here, at the risk of one more line of code, I still want to be a good citizen, free list, and maybe just for good measure, return 0 explicitly. But notice, it's not doing it twice per se. On line 31, what am I freeing? The original address of list, the 3 integer version. Then I change what list points at. So it's pointing at a completely different chunk of memory, this one of size 4. So eventually, when I'm all done using this memory for this demonstration, I still need to free list. But at this point in the story, line 40, it's pointing at the new chunk of memory, which I similarly need to hand back to the operating system by free. Yeah? When would temp equal null? So let me scroll back up slightly. This is being a good citizen and a good programmer. Whenever it comes to using malloc, malloc can return null if the computer is out of memory. So this is maybe a much bigger program. You've got other things going on in it. And so you just don't have enough memory available to be handed. Malloc needs to signal to you that there's some error. And so it will, by convention, per the documentation, per the manual pages, return null. So this is just me being a good citizen. Otherwise, here's another error that might cause your program to crash with a segmentation fault. If you get back null, but you assume that it's good memory, going to address 0, aka null, will crash your program intentionally. Yeah? Correct. If I were to change my final line 40 here to be free temp, this would also work as well. And here, this is really a matter of design. It's a very nitpicky thing. We could probably debate it. But because at this point in the story, my main variable for remembering where the list is called list, this is sort of the more responsible way to do it, freeing the list, just so that my colleagues, my TA, doesn't sort of wonder, why are you freeing temporary memory that you already freed? Like, it just is a semantic thing at this point. But good instinct. It would also work, correct? Maybe just not good design. All right, so it turns out that this gets annoying quickly, as it did in the picture of doing all of this duplication. And even though technically it's necessary to copy those values if you need a newer, bigger chunk of memory, there is at least a function in C that simplifies a lot of this for us. And in fact, let me go ahead and do this. Instead of using malloc this second time on line 18, in addition to the first time I used it on line 6, I'm actually going to try and introduce another function called realloc, which, as the name suggests, tries to reallocate memory for you. And it works a little differently from malloc. Realloc expects 2 arguments. The first one is, what is the chunk of memory that you want to try to grow or shrink? That is, reallocate to be a different size. And then you specify what size you would want. And indeed, in this case, I want 4 times size of int. And that will now give me, hopefully, a new address of a chunk of memory that's big enough to fit all 4 numbers. But what's wonderful about realloc is that it will handle all of the copying for me. So in fact, I'm going to go down here. I'm going to get rid of all of this extra for loop. And what I'm simply going to do instead is this. Once I can trust, after lines 18 through 23, that realloc worked and it didn't return null because I'm out of memory, I can just say, OK, just immediately remember that the new list points at this new chunk of memory instead. And then I can still now do this line, but I can tweak the semantics here and just say list bracket 3, the new final location in the new list is 4. I don't need to free this here. I don't need to do this. All I need now at the bottom is the final for loop to just print out these values. So in short, even though that was somewhat quick, using realloc just moves the entire copying process that I implemented myself a moment ago using a for loop. It just moves it to realloc and lets it deal with the copying for me. It's no more efficient, but at least means I'm writing less code, which is more pleasant. And hopefully the people who wrote malloc or realloc are smarter than me, and they just will introduce bugs with lower probability too. All right, that was a lot. Any questions? Good question. Why do you still need to make list equal temp as I did on line 24? So ideally, I would do this. Ideally, I would just change this line 18 to be list. That is to say, or actually, even better, ideally, I would just say realloc this list to be of this new size. But again, things can go wrong when allocating memory. You need to check a return value to see if it was successful or not. And so we need to use a return value. OK, so let's not introduce temp. Let's just use list. But here's where a memory leak might happen. In the off chance realloc fails and doesn't have enough memory for your 4 bytes, therefore, it returns by definition null. You can't overwrite the original value of list with null to then check it. Why? Because now who remembers where the original 3 bytes were? If you prematurely change the value of list, you've lost. You've leaked memory in that sense. And so that's why, let me undo this change, I declare a temporary pointer for the sole purpose of making sure I can check the return value. And then once it's good, now I'll update the value of list. So it's sort of doing a switcheroo by making sure first that you have a new value to swap with the old. Other questions on this code? Yeah? Indeed, realloc automatically frees the previous memory for you. And better yet, it's even smarter than that. If you get lucky and there happens to be space right after your existing chunk of memory, so 1, 2, 3 garbage value, instead of 1, 2, 3 hello world, realloc won't even bother copying things from old to new. It will just say, OK, I'm going to now reserve for you more bytes than you originally asked for, so it doesn't have to waste time doing that copying. And so in that sense, this version is now not only still correct, it's even better designed because we're not wasting time with that for loop. We might have to resort to it if there is, in fact, hello world or something else in the way, but hopefully we'll get lucky and save those steps. Other questions on this manipulation of code here? Yeah, in the middle. What if you want to resize a two-dimensional array? So very similar in spirit, whereby you can use the same trickery. Let me wave my hand at that for now, just because I think that's going to sort of significantly increase the complexity, but very same primitives. Ultimately, a two-dimensional array is essentially just a doubly long or quadratically longer list of memory that, using square bracket notation, is doing some of that mental math for you. But it's fundamentally no different of what's going on underneath the hood. All right, so with that said, and that code under our belt, even though that's not going to be something you'll frequently need to code yourself, let's propose now how we might go about building some actual data structures ourselves. The new ingredient here being this reality that if you want to resize a chunk of memory so as to make room for things, we now have that ability. Memory addresses and pointers just give us the ability to like point around at things and move things around in memory. But now that we have malloc and even realloc, you can imagine maybe rewinding, and you could implement that stack, that queue, using not an array per se, because you have to commit to an array size in advance, but if you implement your stack or your queue using a pointer, and then malloc and realloc, and maybe someone else writes all that code for you, perhaps now you can imagine that, OK, now the stack can grow or shrink by using realloc accordingly. You don't have to preemptively say, give me 5 bytes or 50 or 500 or 5,000. You can say, just give me 1 initially. And if I need more, I'll realloc, realloc, realloc. And if you keep popping things off the stack, you can realloc in the other direction and ask for fewer and fewer bytes. And the operating system can take that memory back as well. So we now have this building block. Let's see what we can do with it. So we've had a few pieces of syntax in recent weeks, all of which we're going to combine now in just a slightly more clever way. So struct is this keyword in C that lets us build our own structure in memory, like a collection of 2 or 3 or more variables, like a person that we've seen before. The dot operator, recall we've used when you do have a struct, like a person, and you want to go inside of it. So like person.name or person.number. We did this a few weeks ago now. But the dot operator just allows you to go inside of a structure and get the individual variables within. And then the star operator, unfortunately, has a lot of uses now. One was multiplication. My God, that was easy back in the day. Now it's used to declare pointers. It's also used to dereference pointers, so to make one exist and then go to that address. Unfortunately, it's the same symbol for all of those, but it's all related. But with these 3 symbols, it turns out you're going to get one last one today. And my God, it finally looks like the concept. It turns out there's a clever way anytime you want to use the dot and the star together, that is to go somewhere and go to an address and then look inside of a structure, you can actually literally use an arrow symbol on your keyboard. It's not a single keystroke. It's a hyphen and then an open angle bracket. But at least it looks like an arrow. And we'll see indeed in code today, the things I was drawing pictorially on the screen last time with yellow arrows, you can actually now express as well in code. And so here we have our next data structure called a linked list. And this is one of the most useful, powerful concepts in C. It's the kind of thing that you can take for granted in Java and Python and higher level languages. But today we'll see how we or others can actually build these things just using these same primitives. So a linked list is going to allow us to actually do what we used a foam finger for last week, allow us to link together, for instance, these 3 values, maybe with that 4th value over there. And then if there's a 5th, maybe this other foam finger points even farther over way to that 5th value. The key being that you can stitch together fancier data structures without having to like pick all of these up and find new space. You just have to at least connect the dots somehow. We just need to somehow point from one to the other. And that's going to make things much more efficient, it would seem. So how do we get there? So here's my computer's memory as always. Suppose that I'm storing the value 1 somewhere in there, and it's at 0x123 address, whatever. And I'm storing the number 2 somewhere else in memory, 0x456, and number 3 at address 0x789. This is not an array by definition. Why? Even though it's the only 3 things on the screen, what makes this not an array? It's not contiguous. So this violates the definition of an array. But especially since they're sequential, it kind of looks to a human like a list. So it would be nice if there were a data type called list. And there isn't in C. There will be in Python. But you know what? If I could somehow like stitch together these 3 values so I can get from one to the next, then I think we could achieve the idea, the concept of a list, without this really annoying constraint that they all be contiguous as in an array. So how do I do that? Well, at the end of the day, I only have memory at my disposal, right? There's no more training wheels to take off here. This is what we've got underneath the hood of a computer. So if all I have is memory, I think the solution to this problem of stitching together those values in a list must be to spend a bit more memory. That's literally the only resource we have right now. So let me propose that if we want to create a list conceptually out of 3 values that are in random, although pictorially pretty, positions in memory, let me just add a little bit more memory to the picture. So in addition to storing the 1, I'm going to leave myself some room, a little scratch pad, if you will, to use some other bits as well. Same for the 2, same for the 3. And you can perhaps see where this is going based on last week. If I want to somehow connect the 1 to the 2, any instincts as to what I should write in this box here that would lead me effectively from 1 to the 2? What could go here? Yeah? We could store the address of 2. And so specifically, what would you have me write here? Perfect. Ideally, I would just put in this box another integer, one that happens to be represented in hexadecimal, but that's just a base system. It's just a human thing for us to look at. I'm going to put the value 0x456 here. So let me go ahead and reveal that. 0x456 goes there. You can perhaps see further where this is going. Well, if I want to get from the 2 to the 3, I think I need to put below the 2 the address of the 3, which gives me 0x789. Now, if 3 is the end of the list, I don't want to let it be some garbage value, because that would imply that who knows where it's pointing. I need some definitive value. And just what would your instincts be? If I want to make clear with some special sentinel value that the buck stops here, what do I put? What might my options be? Yeah, so null, not NUL per se, but NULL, which was the new keyword we introduced last week, which just represents an empty pointer, if you will. Technically, the address 0x0. So literally the 0 address. And what humans did years ago, they just decided, you know what? Nothing should ever live at address 0 in memory. We're just going to reserve that one special byte to be a special signal, a sentinel value, such that if you ever see a 0 address in a pointer, it just means it's invalid. It does not exist. Now, we write that, though, a little more pleasantly for the eyes as just NULL in all caps. And that's a keyword in C as well. But of course, last week I claimed that who cares where things are in memory? And honestly, like, this quickly gets tedious even worrying about these values. So let me abstract this away and propose that if we want to remember where all of these numbers are in memory, let's give ourselves one final piece of memory that just allows us to start the whole process. Let me allocate on the left-hand side here, not room for a number like 1, 2, 3, just room for a pointer that henceforth I think I'll call list by convention, and then store in that one additional pointer a value that just kickstarts the whole process. This is the sort of treasure map, if you will, that you get handed. And this has the address of the very first actual node in memory. Now, technically, we could just start with this, but it turns out, we'll see, it's just a little cleaner to use a simple single pointer that leads to the things you care about, as opposed to just starting with the first element. Why? Well, if you ever want to get rid of this element, it'd be nice if you could at least still hang on to an empty sheet of paper that indicates that the list is empty, would be one argument for that. So again, who cares about these addresses now? Now, with a wave of the hand, let's just abstract it away. And there are our pointers. Each of those addresses in the squares at the bottom are simply pointing to the next element in the list. The jargon to introduce here would be that now that we have these integers, 1, 2, 3, but they're in these like wrappers, if you will, these structures that have metadata, that is additional data that is related to, but not the data you actually care about. This is data, this is metadata. This thing here, rectangularly, we'll call a node, N-O-D-E, and it's just a term of art that means it's like a container in code for storing some values. This then is a linked list, and this then is the sort of graphical incarnation of like one node pointing to the other. In this case, they happen to be, by chance and by design of this desk, contiguous initially, but there's no requirement that they be such. The 1 could be over there, the 2 over there, the 3 over there. I would just need more foam fingers to point at one to the next. Questions on this concept of a linked list? Yeah, and back. Can you say that again? A good question. Do traditional arrays start with a pointer that's outside of the structure? Short answer, no. Arrays are special in C and certain other languages. And the name of an array is technically a symbol, if you will, that the program knows maps to a specific location in memory. It's just a label, a synonym for a memory address. It does not take up space. So to be clear, the name of an array does not take up space like that extra square on the left, but you do need that extra square on the left when implementing a linked list so that you can determine if the list is of size 0, there's nothing being pointed at, or size 3 in this case. We're sort of taking on more responsibility ourselves. Yeah? How do you point to the next element? Can you elaborate?
Each element is pointing to the next one. How does 3 per se point to the first or the next?
Good question. If each of these elements is pointing to the next, how does 3 point to the others? Short answer, it doesn't. At least in this design, we have more technically what's called a singly linked list. And as the arrows imply, it only goes in one direction. So if you somehow find in code, maybe a for loop, maybe a while loop, somehow you're sort of in code over here, you have no way in code to go backwards unless we change this to a doubly linked list where I add another box that lets me have arrows in both directions. Or maybe I just kind of make it circular and I connect the 3 back to the 1, which you can totally do, but that tends to make life harder because now you have to figure out when you're stuck in a loop in your data structure, but it's doable as well. But as is, it's a dead end by design. Other questions on this design here? All right, well, how might we implement this structure in code? Well, let me just connect the dots to something like we've seen before here. Like this is how, a couple of weeks ago, we introduced the notion of a person, and we claimed a person might have a name and a number. Last week, of course, we took off some of these training wheels, and a string is really technically a char star in both cases, but really there's no conceptual difference beyond that. But let's use this same paradigm to implement a node as I described it in that picture. So let me get rid of the name and the number, because that's related only to a person. And let me rename this structure, for discussion's sake, to node. That then invites the question, well, what needs to go inside of a node? Well, minimally, an integer. But this is now where we need to think a little harder, just conceptually, even if you have no idea how to type it at the keyboard, what else needs to be part of a node based on these rectangular pictures that we've drawn? What more do we need? Yeah? Yeah, we need a pointer to another node. So if I don't know how to implement this yet, it could be something like, pointer to another node. How do I do that? Well, you know what? It turns out you would ideally say this. If you know that the next node is itself a node by definition, well, anytime we've needed a pointer, we just use the data type and a star. And I'm going to arbitrarily, but I think reasonably, call this second square at the bottom of those rectangles next as the name of my attribute here. But node star just connotes that the next variable is going to be not a node per se, but the address of a node. And that's exactly what we did. You had me put 0x456, 0x789 in that box, which is the address of another node. So the way we would express this in code would be node star next. But we could call the variable anything we want. Now, this is a bit of a white lie, but we'll fix this right now. This code won't actually compile. C takes you pretty literally, recall. And if you use some term at the top of your file that you don't define until later in your file, you're going to see some error message, right? We've seen this when I've messed up and I forgot to include the function prototypes at the top of my code. This is related in spirit. I seem here on my 1, 2, 3, 4th line of code, I'm trying to use this new term of art that I invented here in my code called node, even though it's a CS term as well. But nowhere above this, it would seem, did I even define what a node is. It's not a data type in C. Every computer scientist knows what a node is, but it doesn't come for free with the language. So I need to do something else. Like I need this word here to come first so that I can use it here. And so we have this sort of catch-22. Like how can a structure be self-referential, that is, point to another version of itself if the word doesn't yet exist? So the solution to this in C, which we didn't need for a person because there was no notion of listing, connecting as a list, we need one more keyword here that we didn't need for a person, and we reuse that keyword here. So kind of an annoying detail, but if we preemptively call this whole thing struct node, you can now refer to the thing on the inside as a struct node star, but then you can shorten the name of the whole thing from struct node to just node. Sort of an annoying sequence of steps, but in short, anytime you're building a node, a linked list in memory, this is just the paradigm. You use typedef, struct, the name of the thing you want to define, like node. You use that name on the inside if you want to point from one to another, and then you can shorten it down here to just be called node. Questions then on this code here? Questions on what we just did? Well, if I rewind just a moment to that final picture, what would be the upside, to be clear, of having jumped through these hoops and added this complexity, if you will? What problem did we just solve by linking together these three values, to be clear? Yeah? Making lists that are not contiguous, if you will. So making lists that are not contiguous in memory, the upside of which is that if I want to add the number 4 to this list, it looks like I could choose from any chunks of available memory on the screen. I just need to sort of point from the end of the current list to wherever that other one is in memory. What I don't need to do, to be clear, is copy the 1, the 2, or the 3. Everything can just stay put, which means time-wise, I can do this much more quickly, it would seem, without copying things again and again, and even without using realloc to let it do all of the copying potentially for me. All right, but as we'll start seeing even more in the coming weeks, every time we benefit and solve some problem, we pay a price. There's a trade-off. What is a downside, as you might perceive now, of using a linked list instead of an array? Yeah? Yeah, I mean, we use twice as much memory because now, in addition to storing the integers 1, 2, 3, I also need to store a pointer for each of those. And honestly, even this picture is a bit of simplification. Technically, in most systems today, each int would be 4 bytes. Technically today, most pointers, though, would be 8 bytes. I just didn't want to draw this weird shape on the board where the bottom square is even bigger than the top square. But technically, we're using even more than twice as much space for these pointers. So there's that trade-off. Now, thankfully, decades after C was invented, memory is generally much cheaper nowadays. And so it's OK to sort of spend more of it if you need to. And it depends on what you want to optimize for. But that's absolutely here a downside. What's another downside of having transitioned to a linked list? You can't index into it. Now, I haven't even tried in code, but when you have a linked list, you can no longer use square bracket notation. Because why? Well, square bracket notation just assumes the contiguousness of memory. Location 0 is here. Location 1 is literally 1 to the right. Location 2 is literally 1 to the right, 1 to the right. These things, even though I've drawn it from right to left to just keep things pretty, there are gaps here. And this is just my interpretation of this. These gaps could be big. They could be narrow. They could be down here, up here. They could be anywhere so long as we're linking things together in this list. The computer can't just use bracket 0, bracket 1, bracket 2 anymore because it can't do simple arithmetic and jump to like the middle. And now here's perhaps the worst price we've paid. If you don't have square bracket notation, or really you don't have contiguousness, what algorithm did we just sacrifice for this dynamism? If you rewind even back to week 0, and we gave it a name in week 3, what algorithm can we not use now if we can't assume that the memory is back to back to back to back? Binary search. Why? Because binary search, just like the phone book back in the first week, requires being able to arithmetically jump right to the middle. Right? Take the total length of it, divide by 2, and boom, you're right there in the middle with some simple arithmetic. Here, they might be laid out, again, with these big or small gaps. There's no simple math I can do to just jump immediately to the one in the middle. And in fact, again, if this TV were bigger, the 2 could technically be in memory, be way down here, or even way over here. The foam finger could be pointing in any number of directions, depending on where malloc put the thing. There's just no way to do binary search. And so it would seem that we've paid another price, indeed, in terms of its performance. We're now talking about linear time again. So that's a regression. Now, that's also a lot. Feels like a good time for some muffins and fruit out in the lobby. And when we come back, we'll try to solve the problem we just created. So see you in 10. So we are back. And let's see if we can't now take some of these higher level concepts of like stitching together these nodes in memory and translate it to some actual code. But we'll do it step by step first before I actually start writing it in VS Code. So if Carter, you wouldn't mind helping me step through with some visuals, let me propose that line by line we solve some of the problems that we've just created for ourselves in building this thing in memory. So let's go ahead and first consider how we could build a linked list containing the numbers, indeed, 1, then 2, then 3. And let's translate each of those steps to code, and then we'll put it all together into something that actually runs. So how about the first step here will just be this, to declare a pointer called list that initially has no value, at least at this point in the story. List is the name of the variable. Node star just means that this is essentially going to be our little square over here that points to the beginning of the list. Of course, it's ideal if it ultimately has a value, because when we initially call this line of code, it just gives us, indeed, that square over here on the left, but it's got a garbage value because there's no equal sign on the other side there. So let's propose that we do one more step here and actually initialize it to null, so that if only we know that it's not garbage, it at least has some known value. And null is a good way of signifying that at this point in the story, the list is empty. Indeed, null indicates there's no nodes in the list. So that picture would now look like this, whereby let's just draw, instead of writing null everywhere, I'll just leave the squares blank when it's not a garbage value per se. It's literally OX0 or null. All right, so that's it for building a linked list of size 0. Like, we're sort of done then, but we want to now add a 1, and then a 2, then a 3. So next step here might be this. If I want to allocate the first of my rectangles on our previous picture, I'm going to call malloc, and I'm going to ask for enough memory to fit a whole node. Now, technically, I think that's going to be like 4 bytes for the int and 8 bytes for the pointer, even though I did not draw it to scale on the board. So that's technically going to be, what, 12 bytes? But again, size of node just figures out how many bytes I actually need dynamically. That's going to return to me the address of that chunk of memory, which apparently I'm going to store inside of a temporary variable called n for short, for node. But let's see what this does pictorially. So when this line of code is executed, I first get on the left that variable n. It's got a garbage value by default because I haven't executed the whole thing from right to left. Meanwhile, on the right-hand side of the expression, I've got now a node somewhere in memory. It happened to be free here. This is where malloc put it for me. But it does have 2 garbage values initially. But because it's a node, per my type def earlier, every node I proposed is going to have a number and a next pointer. So we can see those labeled here. But they've got 2 garbage values initially. But all I care about initially is that ultimately n is pointing at that chunk of code. So initially, if we could back up 2 steps, we have 2 steps. So we have one step forward. We have this line of code gives us this variable here, which has garbage. When this side of the expression is executed, that allocates the memory. And then when we copy from right to left the address of that chunk of memory, that's what gives us conceptually this arrow, and the garbage goes away because that's a valid pointer now. Of course, there's still 2 garbage values there because we haven't set this node to store a number like the number 1. So let's go ahead and execute one other line of code like this, which, while cryptic looking, is just an application of ideas we've seen in week 4 and prior. Star n means to start at this variable and go there. Follow the arrow is what the star or the dereference operator does for us. And then the dot operator, recall, when we first introduced structs, like for a person struct, allows us to go at the number field or the next field. So if I do star n, and then in parentheses to make sure order of operations is preserved, dot number, and then assign it the actual number 1, which puts the 1 in the top of that rectangle. Now, admittedly, this syntax is not very user-friendly. It's annoying to remember. You have to have the parentheses. So there's another syntax for this. Whenever you're doing 2 things like this in code, dereferencing a pointer that is going to an address, and then further using the dot notation to go inside of the structure you find that, wonderfully C gives us this syntax whereby you can just change the star and the parentheses and the dot to just be an arrow. And again, it's not a single character on your keyboard. It's a hyphen and then an open angled bracket. But I kind of like the semantics of this because this code now pretty much matches the picture. N arrow leads you to the value that you want to access or ultimately change in this way. There's one step, though, we've forgotten, of course, which is that we can't leave this garbage value here because the garbage value is some unknown value that effectively is pointing who knows where. And we don't want to accidentally misinterpret that garbage value as being a valid address and risk going there. So, of course, what value should we put here instead? Our old friend null, just to signify that this is indeed the end of the list. And we could do that with a line of code like this. And again, we'll connote as much by just leaving that empty box blank. So now we have a list of size 1. Let's go ahead and add the second number to it, as with these lines here. List equals n allows us to remember that indeed we have this list here. So if we can step one step forward, here's what the picture now looks like. And technically, let's go one step further here. This is now really what's going on in memory once my list of size 1 exists. My main variable called list is pointing at exactly that first node. At this point in the story, I don't need to know or care about the temporary variable that I called n, even though it might very well still be there. But indeed, this now represents that linked list. Let's now indeed add the number 2. So with the same line of code as before, I'm going to allocate another node, size of node. Ideally, I would be checking for null here, but we're doing the juicy parts only on the slides. Let's now go ahead and depict that. So what happens with this? This brings back our n pointer, which might have been there the whole time, but we're doing this step by step. It's a garbage value, though, because we haven't yet copied from right to left. Malloc, of course, gives us a second chunk of memory, which maybe ends up there with 2 garbage values by default. I've omitted the labels now just because they're still going to be number and next, respectively. Once we copy from right to left, the garbage value indeed becomes an arrow. Oscar disappears because it's now indeed a valid pointer pointing here. Now, the values themselves, number and next, are invalid garbage values. So here is where we can now start using our new syntax, like the arrow notation, or the star and the dot if you prefer. And we can change the value of n, follow the arrow, to number, and that becomes 2. Similarly, we can do this again and set n arrow next. So start at n, follow the arrow, access the next field, and set that equal to null. Now, we're not quite done yet because we haven't actually linked things together. So here's now where things get interesting. How do I combine these two? Well, let me propose this. Let me propose on our next line here, we actually update for now list equal to n. That is to say, whatever address this is, whatever it's pointing at, change list to be the same address. That is, point at the same thing. So if n is pointing here, let's change list to point here. And go ahead and do that, Carter, if you could. I don't like this. Can you go one further step? This is bad. What is wrong about my sequence of operations here where I updated list to point at my new node? Yeah. Yeah, we lost the pointer to the other node. So I don't even care about the ordering, 2, 1 or 1, 2. The bigger problem now, as the lack of arrows over there suggests, is that I have a memory leak. I have orphaned my original node in the sense that nothing is pointing at it anymore. Now, absolutely, I could fix this by adding some temporary variables. I could add it to the mix. But at this point in the story, I have not done any such recollection thereof. So let me back this up, and let's go forward in the slides. This is where we left off a moment ago. I think I need to take into account order of operations. And I'm going to keep this simple. I'm not going to care about the order of the numbers for now. I'm fine with a list that is 2 and then 1. So with that said, let me go ahead and update, I think, this box here to point at my original node. So let's see how we can do this in code. OK, n arrow next. So n arrow next should equal the current list. And this is a little weird again, but recall what list is. List is this pointer here that just contains the address of the original address of the list. Or, equivalently, it contains this arrow, whatever it's pointing at. So what this means in this line of code, n bracket next means start at n, follow the arrow, access the next pointer, and set it equal to whatever list equals. So if list is pointing here, then next should point there as well. This, I think, is safe because now we have redundancy. Now we've got 2 pointers pointing at the original list. And now I think we can do another step whereby we update list to equal n. Same line of code before that got us into trouble, but I'm doing it second now instead of first. When I execute list equals n, this now sets list equal to the same thing that n equals. And so now I have successfully inserted my new node containing 2 into the list. And in fact, if we advance one more, we can just clear up the clutter, assume that the temporary variable is gone from the story. Now we have a linked list where, admittedly, ordering is wrong. It's 2, 1 instead of 1, 2. But at least it's linked correctly, and I didn't orphan or leak any memory. Questions on this sequence of steps here? Yeah, and back. Yeah, spot on. So this would fall under that category of a stack, if you will, although I've not called it that by name because I just pushed the number 2 onto this data structure, if you will. And indeed, it ended up at the beginning of the list instead of the end. And so here's where we see a distinction between an abstract data structure, which is where we began. A stack is a thing like the pile of sweaters that just has push and pop properties and LIFO access, last in, first out. How do you implement something like that in memory? Well, it would seem that you could implement the notion of a stack here, not for sweaters, but for numbers, using a linked list, so long as you implement insertion, aka pushing, by prepending new values to the list, by prepending again and again. And if, Carter, you don't mind hitting the keyboard one more time, if I wanted to add the number 3 now, you could imagine prepending it to the list. Why? Well, honestly, especially as this list gets longer and longer, I kind of like the appeal of prepending these elements. Why? Because even if this list gets crazy long and way, way out here, you didn't notice me following all of the arrows earlier to do the insertions. If I want to insert a 4th number, a 5th number, a 6th number, all I have to do is like insert it here, if you will, point it at the original start of the list, then update this pointer, and done. And I would say that's like 2 steps, give or take. It's not going to be n steps, as it would be if I had to append the new nodes to the end of the list. Now, of course, we've sacrificed ordering of these numbers. They're literally in the opposite order, or whatever order they were inserted in, but that might very well be OK, depending on the goal at hand. All right, thank you to Carter for stepping through this. What if now we wanted to translate this? Oh, sure, thank you. It's all for you, none for me in this example. So here we have perhaps a way of translating this now to some actual code. And this will be the last of like the sort of intense code here, just to give you a sense of how we can translate this idea now to actual steps. So this is list.c in VS Code here. Let me go ahead and make a couple of changes up top. Let me go ahead and how about declaring a node using typedef, struct node using our new framing as before. I'm going to give every node a number, as I proposed, and every node a pointer to the next element, which is going to be implemented just as before. And I'm going to simplify the whole name as just node. So all of that is the exact same typedef that we proposed earlier. Now, let me go ahead and get rid of all of this code, which we wrote earlier, and recall that this was the most recent version that was not a linked list. This was just an array that we allocated and then reallocated. So this is sort of the old way of doing things, but it was inefficient because we might have to lean on a for loop or lean on realloc to copy everything around. We're now going to re-implement the notion of a list as an actual linked list, not as an array. So my main function now might do something like this. And I'm going to really just copy the lines of code that we just stepped through on the board. So let me give myself a special variable called list that's going to be initialized to null. And this is just my pointer, the square on the left-hand side of the screen, that represents the start of the list. And if it's null, it means the list is empty. So done. I'm done implementing a linked list of size 0. Well, now, how do I want to run this code? Well, let me propose, for the sake of discussion, that this version of the program will take command line arguments. So I want to be able to do something like this. I want to run this program ultimately and type in 3 command line arguments like this, 1, 2, 3. And I want my program in a couple minutes to allocate 1, 2, 3 nodes and stitch them together, just like the visualization on the board. I could use getInt, but it's just going to be faster if we use command line arguments. So again, I'm just borrowing some concepts from week 2. But none of that's possible yet until I change my code here. So let's do this. Int argc string argv. But you know what? We know that strings are not actually a thing anymore. So I can change my command line argument definition to be what it really is. It's really char star. But it's the exact same thing as in week 2. Just strings are no more, at least without the training wheels on anymore like last week. And now let me do this. For int I equals 1, I is less than argc, I++. So what I'm doing with this loop is I just want to iterate over the command line argument. So I have one number at a time from the prompt. What else do I want to do here? Well, let's go ahead and how about do this? Let's get a number. So int number equals argv bracket I. So a couple of notes here. 1, I'm starting my for loop at 1 instead of 0, but I'm going up to argc. Argc is argument count, how many words are at the prompt. Why am I starting at 1 instead of 0, though, given my goal? Why am I starting at 1? Yeah. Yeah, so the first value in argv is actually the name of the program. That's obviously not a number, so I want the second value. So I'm going to start iterating over those command line arguments at I equals 1. So that's all. I just want to get the actual numbers at the prompt. Unfortunately, argv bracket I is a string, aka char star. That is not an int. So this line of code won't work. But can anyone think back to like week 2 where we had a function for converting strings to integers? Anyone? Yeah, so a to I is a function that converts ASCII to an integer, assuming what you give it as an argument looks like a number, like 1 or 2 or 3. So let me fix this. Let me actually do the conversion. If I were really being careful, I would error check this, make sure that there's no digits, just like you might have in problem set 2. But for today's purposes, I'm just going to assume the honor system that the user, me, is going to run the program correctly. All right, so now that I have a variable containing the number from the command line, let's just allocate a node for it. So let me do node star n, just like we did in the visualization. And let's malloc enough space for the size of one such node here. I now need to just be super safe. So if n equals null, like if I'm out of memory, you know what? Let me go ahead and just immediately return 1 here. Otherwise, if that's not the case, let me go ahead and update the number field of this new node, which at line 24 does exist because it did not return null. So I did not exit early with return. And let me just store whatever number the human typed in first. So the return value of a to I, which per line 17 is in my variable called number. And then let me go ahead and just prepend this to the list. Let me go ahead and say that this next field first has a known value null, just so that we get rid of that second garbage value. And let me go ahead and now prepend it to the list. So if I want to prepend it, that means this new node must have a next field that points to the current beginning of the list. And again, the goal here is to prepend. So whatever the current list is, let's change it so that this new node points to that existing list. And now, step 2, as before, was to update the actual list to point at this node. So recall in red on the screen before, I screwed up originally, and I only did this line by moving the pointer too early, if you will. But I fixed that once Carter helped me rewind, and we got rid of the red line, which indicated error. And I just do n arrow next to change the next field of this new node to point to the existing list. So I'm not orphaning anything. All right, at this point in the story, I think my code is correct. Not batting very well, though, today. But I think my code is correct. But the program doesn't do anything interesting. So it would be nice to kind of now iterate over this linked list in memory, whatever its order is, and print things out. Well, how do we do that? Well, it turns out if you want to iterate over a linked list, the general paradigm is to do something like this. To define a temporary variable, I could call it temp, but another convention that you might as well see is called pointer, PTR, for short. But you can call it anything you want. And you can have a temporary variable first point at the first node in the list. And then in some kind of loop, like a while loop, you point it at the second node in the list. And then you keep iterating. You point it at the last node in the list. And then eventually you iterate too far, effectively pointing at null, at which point your while loop can presumably terminate. So how do I implement that idea of allocating a temporary pointer that just points at each node in the list and lets me print out, ultimately, each of those numbers? Well, let's go back to my code here. And let me do this. Let me go ahead and declare this temporary pointer, which is going to be a node star also. Why? Because it's the address of a node, the first, the second, the third. And I'm going to set that equal to whatever the beginning of the list is. So that is going to be equivalent to this version of the picture here, where pointer is just temporarily pointing at the first node in the list. It's not pointing at list per se. It's pointing at the first node in the list, which list is also pointing at itself. All right, once I've done this, I think I can translate this to code that's a little new, but it's conceptually familiar perhaps now, while that pointer does not equal null. So while I have a valid pointer, like my finger or that arrow is pointing at an actual node in memory, well, let me go ahead and print it out. So let me print out with %i\n whatever is in the current node at the number field within. And again, this is going to have the effect, hopefully, of first printing the 3. And I think I just need to now update the pointer so that on the next iteration, it's pointing at the next value. So if this is where the story is, how do I update pointer to point at the second element of the list? Well, I want pointer to point at the 2, and I want pointer to eventually point at the 3. Well, how do I do that? Well, the way in code I can follow these arrows is as follows. If I currently have pointer pointing at this node, but I want to point it at the next node, I can borrow this pointer here. So whatever this address is in the first node, aka the next field, I can copy that into pointer, because then pointer will point at whatever this is pointing at by just setting one equal to the other. So once I've done that, the picture will become this. And how do I translate that to code? While new syntax is surprisingly straightforward, all I need do is say pointer after printing it equals whatever pointer currently is, but grab its next field instead. And this is a very common paradigm when iterating over a linked list and you're using some temporary variable like pointer. You can simply set pointer equal to pointer next. And what that means here is as follows. If this is pointer pointing from here down to here, pointer next is follow the arrow, grab the next field. So if you set pointer equal to this thing, that's the same thing as pointing this at this same box. And indeed, if I advance to the next slide, even though the arrows are technically pointing at different parts of the rectangles, that's just for graphics sake, pointer is now pointing at the second node. And when I do this again on my next iteration, it points at this. And then this last step, notice, when I keep doing pointer equals pointer next, this will become eventually this value. But what's this value in this linked list? It's null, technically. So this arrow will eventually take on this value when I set pointer equal to pointer next. And at that point, PTR, my temporary pointer, is going to be null. So it might as well look like this pictorially. And what does that mean for my loop? Once pointer is null, because you've walked off the end of the linked list, what's going to be true of this loop here, started in line 32? Any observations here? What's going to be true? What will happen now as soon as we hit the end of the list? Yeah, sorry. The loop is going to break out. Why? Because line 32, which is constantly asking, while pointer does not equal null, well, if pointer finally equals null 3 steps later, the while loop is now done. And so what I can do at the end of this program, once I've printed out those values, well, first let's go ahead and open my terminal window. Let's make list. OK, compile /list. And let me try the same values, 1 and 2 and 3. That's going to, again, allocate 1 node, 2 node, 3 nodes by prepending, prepending, prepending each of those values. And it's then going to iterate over them from left to right. And so when I hit enter now, what should I see on the screen if my code is correct? What will I see if I were to just call it out? 3, 2, 1, because I've prepended presumably. And here we go. I indeed see 3, 2, 1. So the list is backwards, but all of the elements are there. Now, technically, if I ran Valgrind on this, Valgrind would not be happy because I have never freed any of my memory. So I should probably now have a second loop here that does something like this. Let me again set pointer equal to list. I don't need to redeclare it because I've already created this thing on line 31. I just want to reset it to be the beginning of the list again. And now I can do the same kind of thing. While PTR not equals null, go ahead and do this. Well, I don't want to just do free pointer and then do pointer gets pointer next. Why? My goal is to free all of my memory, but I think this is going to get me in trouble. Pointer equals list just gives me a temporary pointer that points at the 3, and then eventually the 2, and then the 1. How? Well, while pointer not equal null, I'm freeing the pointer. So this is like saying to malloc, free that node, free that node, free that node. But what's the problem with what I've just done here? This code is technically buggy. Yeah. Exactly. After you call free on pointer, you are, by social contract with C, not allowed to touch pointer anymore. It is invalid. Now, it's still going to be a number. It's still going to be a pattern of bits, but it's invalid. And you'll very often get a segmentation fault if you tempt fate in that way. So I can't free the pointer and then use it literally the next line. The solution here, kind of like our swapping of the liquids last time, was to maybe just have a temporary variable. So I can do a switcheroo. And so a common way to solve this problem to get the order of operations right would be to do something like this. Give yourself a temporary pointer like node star next. Set it equal to the place you want to go next. So one step ahead. Now you can free pointer. And then you can update pointer to be that next value. So essentially, you need like 2 hands now. You create on line 41 another pointer that if this is pointing at the first node, the 3, your new pointer is pointing at the 2 temporarily. So now you can tell malloc via free, release this memory. but I haven't forgotten where I want to go next. And so I can now continue on. So a common paradigm for just iterating over these nodes and then freeing them. A couple of observations. Strictly speaking, I could have consolidated this. I don't need 2 loops to print the nodes and then free the nodes. I could do that all at once, but let's assume that there's other stuff of interest in my program, and I don't want to just immediately free it. There's one other bug that I should probably address here. There is still a potential memory leak up here, and this one is super subtle, though Valgrind would help you find it. Notice that in this loop here, when I'm calling malloc, this line of code is fine if the first line of malloc fails and returns null, because I immediately return and I'm done. But what if the second call, but not the first, or the third call, but not the first or second fail? This line of code has me returning immediately. You really need to do some garbage collection, so to speak, whereby you really need to go in and free any nodes that you did allocate successfully earlier. Honestly, that's going to be a pain in the neck. We won't do that here. But probably what I'd want to do is write a function called freelist or something like that, and call that function to free any nodes I had previously created. So it's not quite at the finish line, but the building blocks are indeed here. Questions on this code? And I think it's safe for me to promise that it won't escalate further from that. Questions on this? No? Well, let me show you one alternative that you might prefer. And I'm pretty sure this isn't an escalation. It's just an alternative formulation. Another way you can iterate over nodes in a list could be this. Instead of a while loop, for instance, let me actually show you one other piece of syntax here. You could technically use a for loop. You could give yourself a node pointer here that is initialized to the list. You can then check in your for loop that it's not equal to null. And then you can do your update as usual like this. Either of these are equivalent, even though this one I suspect looks scarier. It's doing the exact same thing in one line instead of 2, but there's no reason we can't use for loops instead of while loops to achieve the same idea. But I'll leave these two as demonstrations of one approach or the other. But that's just like in week 1, for loops, while loops, whatever looks simpler to you, even though admittedly neither of these probably looks super clean. All right, so let's take things back to things more conceptual here. Up until now, we've been inserting elements into this linked list by prepending them. Let's consider what the running time then is of these operations. So if I've got a linked list of size 3 or size n more generally, time has passed and I've added a lot of things to it, what's going to be the running time, for instance, of searching a linked list for some value? And I'll tell you already, it's not log n, because again, binary search is off the table as per before break. So what might the running time be of searching a linked list for some value, like 2 or 3 or 1 or 50? What might the running time be? Oh, O of, I heard it over here, O of n, and y. Who was that? Oh, in the middle here? Why O of n? Exactly. You're going to have to go through every item in the list, starting from the left, from the beginning, which is how we've been drawing things and connecting the dots. And in the worst case, the element might very well be at the very end, so it's going to be big O of n. What about insertion? How many steps in terms of big O notation has it been taking me to insert elements into the linked list using this prepend design? Yeah, so it's technically constant time, big O of 1. And again, 1 is just representative of any constant. It could technically be 2 steps or 3 steps or even 10 steps or 100 steps. But if it's always finite and fixed, then indeed you can say it's in big O of 1. Now, why is that? Well, again, no matter how long this list gets, so long as there's memory available for me, I can just kind of create a little splice at the beginning of the list to put in the new node, update the original list, and I'm on my way. And it keeps getting longer, even though it might not be spread out in memory. So big O of 1 is possible with these linked lists if I indeed prepend things. Of course, if I prepend things, everything's going to get out of order, potentially. And we're going to have maybe the stack property instead of a queue property. So we might want to do things slightly differently. So instead of doing this, whereby we kept prepending, 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 suppose we append to the end of the list instead. So if we now insert the 1, the 2, and the 3, as we might want to for a queue to maintain that fairness property, we might start with an empty list. We might add the 1. We might append the 2, append the 3. And so it just is sort of laid out differently in memory. And again, if I can come to you in the middle, what's the running time of search? Again, when the linked list uses this append implementation. Yeah, still big O of n, because in the worst case, you're going to have to go through the whole list just to find it. And notice, it doesn't matter if you have an intuition now that the bigger numbers might very well be at the end. You have no way to jump to the end. You have no way to jump to the middle or do anything resembling binary search. Every search has to start from the left and follow the arrows again and again. All right, so I don't think we've done any better there. And in fact, what is insertion's running time now in big O, when we're appending to the list in this way, as we might to implement a queue instead of a stack? What's the running time of inserting a new value? Big O of? So not big O of 1 in this case, but big O of n, because if I'm appending, by definition, I have to start here and traverse the whole thing looking for the end. Now, this is a bit of an overstatement, right? You could obviously optimize this slightly by maybe adding another variable that always points to the last element, sort of a cheat sheet, a shortcut that gets you all the way to the end. That's totally fine. It doesn't really fit the traditional definition of a singly linked list, but there's absolutely smart engineering solutions to these kinds of problems. But as designed, it would indeed be big O of n to insert to if you've got to go all the way to the end and you're not using a little extra memory to get yourself there quickly. Well, what if we want to take things one last step and not just append blindly? Because even though I inserted 1, 2, 3, if I inserted them in random order, they would end up in random order. What if you want to maintain a sorted list from smallest to largest? Well, then you might want to insert numbers like this. Starting from an empty list, we might have a 2. Then we might try inserting a 1, but we want to keep it sorted. So now we're going to prepend in our code. But then you might want to insert a 4. So you would append the 4, because you're probably going to look for the right spot to insert it. Then we're going to insert a 3. And this one's getting a little annoying, because now you have to iterate over the list, look for the right spot, and then do a little smarter of a splice. But it's possible. But you don't want to orphan the 4, for instance. And then ultimately, we get back to this question. What would the performance be of your linked list if you're trying to maintain sorted order? Well, search, I think, is going to be big O of n for the same reasons as before. What about insertion? Big O of what for inserting into a sorted linked list? Yeah, in the worst case? Yeah, it's still big O of n. So it's no worse than, but it's not really any better than appending. But we gain the additional property of maintaining a sorted list, which might very well be useful if you're sorting your contacts in your phone or something like that, where it just makes sense to maintain sorted order. Now, in the code for online today, if you take a look at some of the final versions of code, like list6.c and list5.c, as we'll post on the website, you can actually see code that will solve all 3 of these problems. The prepend version that we wrote live, the append version, which we talked through, as well as this sorted order one. But I think I'll avoid showing it live just because I do think that starts to escalate quickly. But I think we have enough of a building block, if we're comfortable with prepending, to at least solve some real world problems with these linked lists. Questions then on linked lists, which we'll now leave behind on their own, but now use this technique to solve fancier problems, but much less code. Questions on linked lists? All right, so to recap, we've kind of taken a sidestep with linked lists. We have this dynamism now where we can grow and shrink our chunks of memory without over-allocating or accidentally under-allocating, as in the world of an array. We don't have to worry about copying values endlessly, because once you allocate the node, it can just stay wherever it is in memory, and you can just you can just stitch it together somehow. But unfortunately, we've sacrificed what we started the class with in week 0, which was binary search, divide and conquer, which was gave us that log n running time, which was really compelling if you think back to the demonstrations and the visuals. Can we get the best of both worlds? Can we get the sort of speed of binary search, something logarithmic, but the dynamism of something like a linked list? Well, we can actually, I think, if we start to think not in a single dimension, just the x-axis, if you will, but 2 dimensions, such that our data structures can maybe now have width and height, if you will. And so a tree is perhaps the right term here, much like a family tree. If you have sort of your elders up here in the tree and then the branches below them for their children and grandchildren and the like, that's actually what a computer scientist means when they talk about trees. Not a tree that grows up like this, but really one that typically is depicted growing down, although this is just an artist's depiction no matter what. But there are certain types of trees in the world called called binary search trees that are structured on paper and visually like a family tree, but they have a special property that lends themselves to exactly that feature, binary search. So for instance, here is an array back from week 2, and I've sorted a whole bunch of numbers herein from 1 to 7. We know we can do binary search on this structure if it's implemented as an array. But what feature do arrays, to be clear, not have that linked lists do? Today's kind of a seesaw. Like, what did we just gain by adding linked lists that arrays do not allow? Yeah. Yeah, you can insert more elements without having to copy or moving everything else around. Like right now in this single dimension, if these values to the left and or right are already used, then you have to move everything. And that's where we started today's story. So arrays kind of paint you into a corner because you have to, by definition, decide in advance how big they are. Well, couldn't we have some kind of array that can still grow but still is contiguous so we can do binary search in some way? Well, yes, if we sort of rethink how we implement binary search. Let me propose that I've chosen these 7 elements in the array, much like the lockers from week 2, to be ordered from smallest to largest. I've highlighted now in yellow the middle elements here. And if we were telling the story of week 2 going left or going right, let me highlight in red the middle elements of the left half and the right half. And then let me further highlight in green the other elements in between those. And there's actually a pattern here, as you might notice, whereby there's 1 yellow in the middle, and then there's the 2 red and the 4 green. There's kind of an implicit structure there, if you will. And what if I do start to think in 2 dimensions, and instead of laying out an array of lockers like this on the x-axis only, what if I kind of like slide the 4 up and pull the 1, the 3, the 5 down, and kind of draw this in 2 dimensions instead? Well, let me do that as by separating these things like this, such that now let me propose that each of these squares, maybe it doesn't have to be contiguous. It can be anywhere in the computer's memory. But I can't have these crazy gaps among them. How could I perhaps keep these things connected conceptually? What should I add to the picture, if you will? Yeah. Say again? So branches, metaphorically here, and more technically in the language of C, maybe just some arrows, some pointers. So I won't bother drawing things as rectangles constantly. Let me propose that we're now just abstracting away what a node is. But let me claim that each of these squares now is a node. And a node might have a number, but it might also have a pointer. Heck, maybe even 2 or more pointers. And let me draw those now. I don't care about addresses like 0x1, 2, 3, 4, 5, 6, 7, 8, 9 anymore. Let's just draw our pointers with arrows. But now let me propose that we could very well think about this as a tree storing what was previously array data, but now each of these nodes can be anywhere in memory. And moreover, even though I've kind of painted myself into a corner visually on the screen, so long as there's more memory in the computer, I could put the number 0 over here. I could put the number 8 over here. And if I'm smart, I could probably, if I want to insert other numbers like 2.5 or 1.5 or values in between, I bet we could kind of make room by swiveling things around and just kind of hanging things off of these branches slightly differently. And so what does this gain me? Well, if I instead start to model my data not single dimensionally, but in 2 dimensions, and I connect those nodes with these pointers, what can I now do? I think I just gave myself back binary search. Why? Suppose I'm searching for the number 5. How do I find it? Well, just like in a family tree where you might visually start reading from top to bottom, I'm always going to start from the so-called root of a binary search tree. This is just like the list pointer that kicks off the whole linked list process. This is the so-called root. All right, here I am at the number 4. I want to find the number 5. What decision can I make when I see that I'm currently at the number 4? Just like the phone book from week 0. Where is 5 not? It's not to the left. And if I had built a little mobile here or something, we could very dramatically snip off this branch. This is like very low budget animation. These nodes could like fall to the ground, and we're left with half of essentially a tree. But what do I now know? It's obviously the 5 to the right. So let me go to the right. 6 is obviously not the one I'm looking for, but what do I now know about the 5? Well, 5 is less than the 6. So I can sort of snip this off here because I know it's not going to be down there, and I can follow the remaining arrow here, and voila, I just found it. And now without getting into the weeds of the math, I've got here, what, 7 elements. That's roughly 8 if I round up. And if I do some log base 2, 1, 2, 3 is the key detail here. The height of this tree is 3 because I took a list of size 7 and I halved it and I halved it in order to let it dangle in these 2 dimensions, plus or minus 1 for rounding's sake. So what do I get back? I now have binary search, but it's not like the middle of the middle of the middle. I now follow these arrows in one of 2 directions. So each of these nodes now has an int and maybe a left pointer and a right pointer, but you could call them anything you want. And so I've gotten back binary search and dynamism, because if you want to add 0 or 8 or 9 or 10, we can just dangle them at the bottom of the binary search tree. So what would this look like in code, but we won't actually implement it line by line? Well, here was previously our definition of a node for a linked list, which was one-dimensional, if you will. Even though it might bounce up and down on the screen, it was still just a line, if you will. Well, let me get rid of the single pointer in the linked list. Let me make a little bit of room here in this type def, and let me propose that we just add 2 pointers, each of which is a struct node star. One will be called left by convention. One will be called right by convention. And so long as someone, not me, not today, not in class, writes the code that stitches together this data structure too, handling both the left child and the right child, so to speak, I think we can indeed stitch together that 2-dimensional structure. And moreover, once you have this in memory, you can translate pretty elegantly to code binary search itself using a principle we talked about recently too. Here is, for instance, a function that I'll write by just clicking through steps called search, whose purpose in life is to return a Boolean, true or false. The number I'm looking for is in the tree. This search function, therefore, takes 2 arguments: the number I'm looking for, called number, and then a pointer to the tree, the so-called root of the tree. Now, how can I implement binary search in code? Well, recall our brief discussion of recursion. It turns out recursion is a beautiful technique, and honestly, more obvious technique when you have 2-dimensional structures, which finally, after 5+ weeks, we now do. Here's maybe my first line of code here. If the tree is null, then obviously return false. You've handed me an empty tree. There's nothing going on. Obviously, the number you're looking for is not going to be here. So that's my safe base case to make sure I don't screw up and recurse infinitely. Well, what else might be the case? Well, if the number I'm looking for is less than the tree's own number. And now recall that tree is a node star. So even though I'm calling it a tree, it's really the current node that's been passed in. So if the number I'm looking for is less than the current node's number, then I must know that the number I'm looking for is to the left, so to speak. So how can I solve that? Well, this is where the magic of recursion. Just return whatever the answer is to calling search again, but on a subtree, if you will. This is the sort of equivalent of snipping off half of the tree. Pass in the left subtree, if you will, with the same number. Else, if the number you're looking for isn't less than the current node's number, but greater than, snip off the other subtree instead and just return whatever search says it finds in the right subtree here. And then there's a fourth and final case. What else could be true logically? Yeah? Perfect. If the number you're looking for equals the number in this node, then I'm just going to return true. And you might recall from our recurring discussions of design, I don't strictly need to ask that explicitly. Either there's no node, it's to the left, it's to the right, or you found it. So I can just whittle that down as usual to an else. And this now returns my true. So here too, this is where recursion, once you get comfy with it, sort of gets pretty elegant and cool in the sense that, wow, even though there's a lot of lines here, I mean, there's only a few interesting lines. A lot of it's like curly braces at that, which strictly speaking I could get rid of. And so recursion lends itself to elegance when it comes to traversing these 2-dimensional data structures as well. So that is in code how you might implement something like search. Questions then on these trees? We have dynamism. We can insert more nodes to them. They're faster because we get binary search back. But there's got to be a price paid. Any downsides or question or downside? OK, let me come back to that in just one sec. Downside, though, what price have we paid for this dynamism and for this binary searchability? Even though I've abstracted it away in the picture. Say again? we're using a lot of memory, right? I'm kind of misleading you now because I'm just drawing these little squares with the simple numbers, but there's actually 3 things in there: a 4-byte integer, an 8-byte left pointer, a 8-byte right pointer. So we're already up to 16, 20 bytes now to store individual ints. That's probably OK, though, if memory is relatively cheap and voluminous as it nowadays is. But these are the kinds of trade-offs. And here, too, you see a hint of why some people still do like and use C. And in fact, it's so omnipresent because when you have C, you can really fine-tune how much memory is being used, for better or for worse, under the hood. As we transition soon to Python, these decisions get made for you. And you have much, much less control about how much memory is being used by your program because someone else made those design decisions for you. Question? Is it bad if we don't know the parent node? Not necessarily. There's no reason why you need to have pointers in both directions. However, that can lend itself to efficiency. By spending more space and having arrows go up too, you can actually save more time when searching the tree in other contexts. This, though, would be the canonical way, the typical way to implement it. But absolutely, just like a doubly linked list, that could help you solve other problems too. All right, so turns out I'm kind of overselling binary search trees. There are perversions of them, so to speak, whereby they won't actually behave as advertised. For instance, here's a good situation. Suppose you've got an empty tree initially, and you insert the number 2. Well, it's got to go somewhere, so it might as well become the root of this binary search tree. And let's assume that someone wrote the code to do this. Now you want to insert the number 1, and you want to maintain the searchability of this tree. Well, it's important to note that binary search tree is different from tree. If you've just got a tree in memory, there is no social contract with where the numbers need to go. They can be completely random all over the place. Binary search tree means that you can do binary search. Means that any node here is going to be greater than every node here and less than every node here. And that's a definition. It's a recursive structural definition that must be true to be a binary search tree, or BST. So if we maintain that property ourselves, let me insert 2. Let me insert 1. 1 belongs there by that definition. Let me insert 3. 3 belongs there by that definition. But I kind of got lucky in that I, in the story, inserted 2 and then 1 and then 3. Let me propose a sort of perversion of the algorithm whereby we just get unlucky. Let me propose that we insert 1 first. And then we insert 2. Well, where does 2 go? Well, logically, it goes to the right because it's larger. All right, now the user inserts 3. Where does it go? OK, it goes there, logically. And how does this story unfold? The user inserts 4, 5, 6. It's wonderfully sorted in advance by luck. But this is a perversion of the structure in what sense? It's still technically a binary search tree. But what does it look more like? It really is devolving, if you will, into a linked list. And so if you, the programmer, don't implement a binary search tree with some kind of repairs going on, such that as soon as something gets, whoa, a little too long and stringy, I think I can fix this. It's going to be an annoying a number of lines of code, which we're not going to write here or in a pset. But we could kind of pivot this thing, right? And we could just rejigger things so that the 2 becomes the new root, the 1 becomes the left child, the 3 becomes the right child. But that's what, like 2, 3 plus lines of code. It's possible, it's doable, but it's extra work, it's extra code. So unless you write that code, though, and maintain balance of these trees, just because it's a binary search tree does not mean its height is going to be log base 2 of n. The height could be n, in which case you don't get those properties. So when it comes to looking up in a balanced binary search tree, yes, it's log n. But if it's unbalanced, if you don't add that additional logic and those repairs, so to speak, it could devolve into big O of n. And this is a whole category of algorithms and fanciness that you would explore in a higher level course on algorithms and data structures. There's lots of way to do that sort of fixing that I'm alluding to in the picture there on the screen. All right, a few other data structures, if you will, toward an end of a sort of computer science holy grail. So log n is repeatedly a really good place to end up. We started in week 0 when we got log n. We lost it earlier today by introducing linked lists, but we just got it back, albeit at the price of spending more space. But the holy grail, so to speak, when it comes to algorithms would not be big O of n, certainly. Definitely not n squared, like our bubble sorts and selection sorts, and not even big O of log n. What's better than all of those? big O of 1, constant time, right? That's the holy grail, because if we could store huge amounts of data but find it instantly in 1 step, or 2 steps, or heck, even 10 or 20 steps, but independent of the size of the data structure, that's pretty powerful. I mean, that's the secret sauce of the Googles and the Twitters of the world, trying to get back results really, really fast. Well, it turns out another abstract data type or abstract data structure might be something called a dictionary, just like the Merriam-Webster or Oxford English dictionaries that you might know, which associate, say, words with definitions. Well, you can think of a dictionary really abstractly as this, like 2 columns, maybe on a spreadsheet of sorts, where the left column represents something and the right column represents something else, like the word is on the left and its definition is on the right. And that's almost literally what a dictionary is on paper. You've got all the words and all of the definitions right next to it. But more generally, in computing, a dictionary really just has not words and definitions per se, but key value pairs. This is a term of art, and we're going to see this again and again, especially as we transition to web programming, keys and values. Key is what you use to look for something. The value is what you find ultimately via that key. So that's the generic term there. We've seen key value pairs really in the past. In week 0, we talked about your contacts in your iPhone or Android phone being an app that has a whole bunch of contacts, presumably alphabetized by first name or last name or the like. Well, one of those contact cards ultimately has someone's number, for instance, like John Harvard in this case. So in that type of application, the keys is the name, like John Harvard, that you use to find information, and the value is the number that you find there. Or if there's more information, like where he lives and email address and the like, the whole contact card could be the value thereof. The key is what you use to look up John Harvard. Now, back in week 0, and rather, the corresponding table then, if we draw this in 2 columns, wouldn't be word and definition or key value generically. It would be name and number, for instance. So we're just slapping some new terminology on this old contacts problem. Well, this is the picture we drew way back in week 0, whereby I claimed that log of n was really, really good. And indeed it was, and has been since. But the holy grail would indeed be something more like this, in this dashed green line, constant time. And maybe not literally 1 step, but a fixed number of steps that even as the problem gets huge and you go way, way out on the right of the x-axis, the problem does not depend on the the time to solve the problem does not depend at all on the size of the problem itself. You can have 1,000 contacts or 100,000 contacts. Constant time means it takes the same number of steps no matter what. Well, how can we get to that point? Well, there's a couple of final building blocks today, and there's one called hashing. And this is something that will recur a few times. But for now, hashing is all about taking as input some value and outputting a simpler version thereof. So for instance, here's a gratuitously large deck of cards, which are all the more visible as a result. And in a deck of cards, typically you've got like, 52 cards, plus maybe the jokers and whatnot. And each of those cards has a number of sorts and a suit on it. And here are literally 4 buckets on the stage. And how might I go about sorting these cards? Not just by number, but also by suit. Well, you could certainly like spread them all out and sort of make a mess of things and just kind of reason your way through it and get everything in order according to suit and ordered by number. But most of us, even if you don't have 4 buckets at home, probably are going to do something a little more intuitive, feels like an optimization, where if I find like the 9 of hearts, I'm going to put that into the hearts bucket. The king of spades, I'm going to put that into the spades bucket. The jack of diamonds over here. And I'll do this with the queen of diamonds and the ace of clubs here and the 3 here and the 10 here. And even though it's still going to be 52 steps, why am I, and maybe at home, like why would you perhaps do this step first? What's the value of bucketizing the values in this way? And that actually is kind of a term of art. What's the value of doing this first before you sift through and try to sort the numbers? Yeah. Yeah, it's easier to make sure you're not missing anything. And it's taking a problem of size 52 and shrinking it into 4 problems of size 13, if you will. And so that just kind of helps simplify things, maybe reduces the probability of errors or the like. And what I'm doing here, to give it a technical term, is that I'm hashing the values. I'm taking as input a card like this, and I'm reducing it more simply from a larger domain to a much smaller range, if you will. So here's a domain of like 52 possibilities. I want to map that to a range of 4 possible outcomes: the diamonds, the clubs, the hearts, or the spades here. And by doing that, I'm just shrinking the size of the problem. So hashing does that. It's like literally an f of x type arrangement, whereby you pass something in and you get back a simpler known value. Well, a hash function, more technically, is the algorithm or even the math or even the code that implements that idea, converting something bigger to something smaller to this indeed finite range of values. And it turns out that hash tables are a wonderful application of arrays and linked lists to try to leverage the best of both worlds. The goal being theoretically to achieve that holy grail of constant time. And that's going to be a bit of an overstatement because you're not always going to achieve it exactly, but at least we can get a little closer there too. So with hash tables, you have something that looks like this. This is just an array. This is an artist's rendition of drawing it vertically instead of horizontally, but that's just a detail graphically. And this array, for instance, maybe is of size 26. And where am I going with this? Well, how does Apple, how does Google store your contacts alphabetically in your phone and search for things quickly? Well, they probably alphabetize, at least in English, according to A through Z. Or if we convert that to numbers, it's like, what, 65 through whatever. Or really, 0 through 25 suffices. If we're using an array of size 26, we start counting at 0, and we count up to 25. But let's abstract that away as just letters of the alphabet. So maybe what Google and Apple are doing in your phone is storing all of the A's up there, all of the Z's down there, and everything else in between. And so this works pretty well if you start adding your friends and your family. So for instance, and I'll get rid of the letters so as to not distract, Albus might go in that first spot because A, you subtract the 65, maps to 0. So we put him in the first bucket, the A bucket. Maybe Zacharias ends up all the way at the end there. And then in the middle might here be Hermione. And if we do this ... you keep adding all of your classmates, you might get a contacts database that has all of this data herein. Now, each of these nodes, they're drawn differently because this is just another artist's rendition. These rectangles, these long rectangles, represent a contact card, like John Harvard's that's got the name, maybe email, definitely phone number, and things like that. So this seems great. Why? How can I find Albus? Well, I go to the A bucket. How do I find Zacharias? I go to the Z bucket. How do I find Hermione? I go to the H bucket. But, I've done this very deliberately. What problem will arise eventually, assuming you have enough classmates? Yeah, there'll be too many people, too many contacts for all of the available spaces in the array. There's still some room here, but I'm pretty sure if I think back to this particular class, we've got not Hermione, but also Harry, who's also an H, Hagrid, who's also an H. So where do I put them? I could just put them arbitrarily in any of the open spots, but then you lose the immediacy of jumping right to the H, right to the A, right to the Z. But now that we have linked lists, we can kind of combine these ideas, right? Use an array to get to the first letter of the name you care about. And then if you have a collision, so to speak, whereby someone's already there, you don't do something stupid like put Harry down here just because it's available, or maybe Hagrid down here just because it's available, because then you're losing the immediacy of the lookup. Why don't you just kind of stitch them together in a linked list? Now, what does this mean? This means for most of the characters here, you have constant time lookup. You look up Albus, boom, you're done. Zacharias, boom, you're done. OK, Harry, Hermione, Hagrid, it might be 1, 2, or 3 steps. So that's actually devolving into something linear. But here we make a distinction today between theoretical running times, which we keep talking about, and honestly, clock on the wall running times that actual humans care about. This is way faster than a linked list, because you don't have to search every name. It's even faster than an array because you don't need to do binary search. You can literally, for most of the names, find them in constant time, one step. And again, it's not theoretically constant because if you only befriend people who have H names, it's going to be a crazy long linked list anyway. So again, it really kind of depends on what the nature of the data is here. But this is pretty close to constant time. And in fact, how could we get even closer? How could we reduce the probability of collisions for the H's or any other letters? How could we avoid putting too many H names together? Say a little louder. OK, yeah, so we could add another dimension, if you will, but let's not add a third dimension per se. But let's indeed look at not just the first letter of everyone's name, but the first and the second. And in fact, let's see if that gets us a little further along. So let me go ahead and propose, if you go through the whole Harry Potter universe, there's actually a lot of collisions if we keep going. And so we've got the L's here, the R's, the S's, and so forth. Well, let's clean this up here. Hermione originally went to the H location, but let's decrease the probability of collisions there and everywhere else. Instead of putting Hermione, Harry, and Hagrid all together, let's go ahead and do this instead. Instead of labeling these buckets A through Z, let's just give ourselves more buckets. So in fact, this might be H. Well, instead of H, maybe this should be HA. And then this should be HB, HC, HD, HE, HF. Now, some of those are a little nonsensical because I can't think of names that match most of those. But it's deterministic. At least we know the bucket will be there, which is important even if it's empty. And now we can put Hermione here. We can put Harry here. But uh-oh, we didn't do this perfectly well. Hagrid still collides. So let me come back to you. How can we reduce the probability of Harry and Hagrid colliding? Yeah, so we could look at the third letter. OK, so let me try that. Instead of HA, let's look at HAA, HAB, HAC, dot, 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 HAQ, dot, 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 HEQ, HER, HES, and so forth. And now I think those names, and probably all of the others we saw, are now much more cleanly distributed. There's much lower probability of collisions unless two people have like almost the same names, or one is like a prefix of the other. But, even though we're now closer than ever to constant time, because the odds that we hit a collision and have to devolve to a linked list are much lower, what's the downside? That's not completely obvious from how I've depicted this on screen. What's the price I'm paying here? Yeah. This is a huge amount of memory. The number of cells here in the array is now, what, 26 times 26 times 26 for the first, the second, and the third possible characters, all combinatorically combined here. That's a lot. I didn't even draw them. I have the dot, dot, dot to evoke that instead. That's a huge amount of memory. This is a very sparse data set now, and odds are you're going to waste so much memory, even for the names like HAE, HA, like HEQ. Like, I can't even think of names. So many of those buckets are going to be empty, not to mention the AAA and the ZZZ and everything else in between. So it's a trade-off, and it might be too expensive a trade-off, and so you might have to tolerate something like the collisions we had earlier, whereby even though they might very well happen, at least you are decreasing the probability by perhaps having more buckets like this. And in fact, if I rewind now to where we might have gone with this, here's how we might represent these nodes in the tree. Previously, in the past, we've had a person who had a string name and a string number, aka now char star. And so here now might be how, in this hash table, we represent someone's name and number, as well as a pointer to the next element in the list. Let me rewind just to the picture here. We keep drawing different shapes because, again, these are abstractions. Who really cares if they're to scale now? We've got enough room for the person's name. Not pictured on the screen is Hermione's number, but that's somewhere in this rectangle. But yes, pictured here in this little square is a pointer to the next node in the list. So by storing name and number, maybe her address, maybe her mailing address, whatever, in addition to a pointer, allows each of these nodes to be connectable, just like the nodes in a linked list. But where they're starting is in an array. So the array gets us like 1/26, or gets us narrows the problem from size 26 to 1, gets us to the linked list in question. Hopefully it's a single person, or perhaps it has more than that. Meanwhile, what is the hash table itself? The hash table, the whole thing, is literally just an array. I've hard-coded the simplest version of size 26, but what do each of those boxes in the vertical array represent? Just a pointer to potentially a node in a linked list. And if there's no one there, if there's no one in location Y or X or the like in that universe, well, it's just a null pointer, signifying there's no one there. But if there is, it's going to be a pointer to a valid node, from which we can get to any of the others as well. And that so-called hash function, just like the one I did with the greeting cards, well, it's just a black box, if you will, but implemented somewhere in code, like in C. And so if you pass in Albus, what is the hash value of Albus? Well, in the first version of the story with 26 buckets, it should be a 0. If you pass in Zacharias, it should be 25. And so just as my cards were being hashed to one of 1, 2, 3, 4 values, now these names are being hashed to one of 26 possibilities, or 26 times 26, or 26 to the third power if you have more and more granularity than that. questions on this implementation now of this idea of a hash table? If you say that again with the null? Oh, a good question. So if there's so much sparseness, there's all of these empty cells in the array, couldn't you just go in and free them or delete them or just kind of shrink the array and not have AAA and AAB and AAC only have the prefixes, 2 or 3 characters that you need? You absolutely could do that. But now what you lose is the arithmetic benefit of being able to map each letter to a number. If you start freeing up unused space, you don't know that Zacharias is necessarily at location 25. Albus is still going to be at location 0, but if you've deleted some of the elements in the middle, Zacharias could be at 24 if you've deleted one, 23 if you've deleted another, and so you don't have that arithmetic immediacy that you need in order to index into the array with constant time. And the same is going to be true if it's 2 letters or 3 letters. You need to be able to trust that you can do some quick math and jump to the right index in constant time. And that's, again, the appeal of these arrays. So when it comes to the running time of a hash table, inserting values into it, searching for values therein, at the end of the day, it technically is big O of n. Because in the craziest case, you might have a huge, fancy hash table, but everyone in the universe has a name starting with H. And then it just evolves into a really long linked list, just like a binary search tree could do the same. But if you choose a smarter hash function, maybe you mitigate that and you don't rely only on the first letter, but on the second or the third as well, or some other combination of that input and make your hash function smarter. Odds are, if you get a good hash function, you want to get it to be more of like order of n divided by k, where k means constant mathematically, and so k is the number of buckets. So ideally, you want like a uniform distribution. You want like this many people here, this many people here. You don't want there to be some or no people. You want a uniform statistical distribution. And maybe you get that from human names, maybe you don't, but that's kind of the challenge of a hash function. Of course, big O of n over k is not a thing, because we always throw away constants like k, so it's still big O of n. But again, the distinction today is that, OK, yes, academically, you learned in CS50 that, sure, it's big O of n. But my God, it's 26 times faster if you do the hash function well and you spread everyone out over the hash table. And that's the appeal of these kinds of structures. And we've got one more for you, if I may, and something now known as a trie. So it turns out that a trie is even cooler, if you like this kind of thing, in that it does not devolve into big O of n. It is truly constant time. But there's going to be a price. There's going to be a gotcha. A trie is sort of a fancier tree. And it's short for retrieval, but pronounced trie for weird historical reasons. But a trie is a tree, each of whose nodes is an array. Right? So this is all like crazy mashups now. People started inventing data structures just by combining different ones. So unfortunately, a lot of the good ideas are taken, but you just have benefits from certain aspects of those data structures, and combining them ideally gives you the best of both worlds, so to speak. So here might be the root of a trie. It's literally a big node, a big rectangle, but it's actually an array. So there's like 26 locations in this picture here. And here's how you use a trie, for instance, to store names just like the hash table. You treat each of the elements of that array in that node as like a letter of the alphabet, so A through Z, or 0 through 25. And if you want to store someone's name in here, you do so as follows. If you want to store like an H, you index into the H location. And if you want to store the second letter of someone's name, like an A, well, you add another node below it, and such one is connected to the other. And you then identify the A in that array. And then you go on and maybe put a G, if the goal is to store, spoiler now, Hagrid in this data structure. And then the R and the I and then the D. But when you get to the D, the end of the name, you have to somehow flag that this is the end of a name that we've embedded into this data structure. So whereas all of these are called out in white just to make obvious what we're connecting to what, green has to be like a bool that's true, that just indicates like the buck stops here. Like D is the last letter in someone's actual name. And what's kind of cool now about a trie is that we can repeat this for other names as well. So for instance, here's where we might put Harry as well. And notice they share a common prefix, HA for Hagrid, HA for Harry. So we're reusing some of these nodes, some of these arrays. We can even slip Hermione in here too, borrowing only the H, but she gets the H, then the E, then R, R-M-I-O-N-E, and so forth. And we mark at the end of her name too that she's in there. Now, what's the takeaway here? Well, what is the running time of a trie? How many steps does it take to find someone in this data structure? And let me zoom out so that it sort of suddenly becomes a massive data structure with even more in it. Maybe it looks, sorry. No, I'll keep it on this one. Maybe it looks a little something like this with just these 3 names. But how many steps does it take to find Hagrid or Harry or Hermione? No matter how many names are in this data structure. There's 3 at the moment, but it takes what? H-A-G-R-I-D. So 6 steps to find Hagrid. H-A-R-R-Y. 5 steps to find Harry. H-E-R-M-I-O-N-E. 8 steps to find Hermione. But notice that those steps are only dependent on what? The lengths of the humans' names. And let's assume that no one's going to have a infinitely long name. It's going to max out at what, like 8, maybe 18, maybe 20, 30. There's actually some pretty long human names out there, but it's going to be finite. You know it's bounded, whereas most contexts, n could grow forever. So what's compelling here is if you assume that the longest name is, I don't know, 50 for the sake of a theme here, then you know that finding anyone in this data structure will take you no more than 50 steps. 50 is thus a constant, which means you have big O of 1 running time. It doesn't matter if there's 1 million people in this phone book or 1 billion people in this phone book. That's going to definitely add more nodes to it, but it's still going to take you H-A-G-R-I-D, 6 steps to find Hagrid, H-A-R-R-Y, 5 steps to find Harry, even if there's 1 billion other people in that data structure. So now we actually do seem to have constant time if you assume that there's going to be a bound on the length of the name. Why don't we use tries for everything then? What's the price we're paying for this data structure, even though we've represented just 3 characters here? Yeah. It's a lot of memory, yeah, and you can see it even with these 3 names. Most of the squares on the screen are empty, like bytes and bits that are there and are allocated, and they need to be there because you need to be able to do that arithmetic thing of this being 0, this being 25, so you can jump from boom, 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 boom based on each of the letters. But it's a hugely sparse data structure, which means it takes up a crazy amount of memory. Now, maybe that's tolerable, especially for short names, but that's going to be the trade-off as well. And this is such a tension in computing. Almost any time you want to improve time, you want to speed up the efficiency, the speed of your algorithm, you're going to spend space. If by contrast you want to decrease the amount of space, you might very well have to increase the running time. It is indeed this seesaw back and forth, and you, your colleagues, your company need to decide what resource is the most precious. Heck, it might be just much harder to code one of these data structures than another. You're a human. Your time is valuable. Do you really want to spend hours implementing a trie when, hey, in 30 minutes I can bang out an array nowadays, or a linked list even? There too, development time is going to be yet another resource, and why sometimes there's good code or bad code, it depends on what you're prioritizing. So what do each of these nodes look like in a trie? Well, we can keep calling it a node. This is a very generic term for just a container in these data structures. In this story, though, let me claim that everyone has a number, like a phone number, a string, aka char star. Every node has 26 children, or technically an array of size 26, that can point to more of these nodes. Notice that I don't need to store the name of someone in a trie because it's implicit in the path that you take to find them. So that's a minor optimization, but it saves us some space. But this would be just a different data structure we could use to actually solve this problem as well, albeit at a very expensive cost. And what do we need our variable to be that stores the trie? Just like before, we just need a single pointer that hangs on to the root of this structure that's null if it's empty, or non-null if it's actually pointing at something. Any questions then on tries? And if it's feeling like a lot, the fire hydrant, it is. We started with arrays, then linked lists, then tries. But questions on how we've just assembled from these basic building blocks? Yeah?
Why isn't the root of try have a size of 26? Why isn't that an array?
A good question. Why is this not size 26? It's just like with the linked list before. It just tends to be in code convenient to have a separate additional pointer that's small that just points to the beginning of the data structure, because that way it can be null, thereby clearly indicating there are no nodes, the whole structure is empty. If you allocated one of those nodes, you absolutely could, but then you'd be just wasting space even if it's empty, and it creates an ambiguity. So just having a single pointer linked to the beginnings of all of these things is a good thing. Other questions now on tries, or trees, or hash tables, or arrays. So what problems might arise? Well, here's a counter example. What names are manifest in this try here? Feel free to just call it out. What do you see? Danielle and Daniel. So presumably, if these are two names here, one of which is a prefix of another, notice that the data structure still works. And I chose, a friend's name and then appended a couple of more characters to it that's also a name, because we have here D-A-N-I-E-L, and the green technically is implemented as a bool or something like that that indicates a word stops here. But we don't want to preclude storing Danielle as well, who's a superstring, if you will, of Daniel. And so that's OK, too, so long as the structure allows for the pointers to keep going. So even that works out OK, whereas it might not have otherwise. And in terms of the running time, just to be clear, at the end of the day, tries do give you actual constant time for insertions, lookups, deletions, and the like, because it's dependent only on the length of the input, the key, if you will, and not on how many other people are in your phone or address book. And now thought we'd conclude with a visual. If you've gotten out into the square, anyone recognize this? OK, Sweetgreen, a local salad place. What are we looking at here, and what's its connection to today? You're about to become all the geekier in the real world, because you will start to see data structures everywhere. What is this? Or how does this work maybe in salad form? Who's been to Sweetgreen? OK, either of you. So how does this work? OK, good. So if you order a salad for someone named L, when it's ready, they put it in the L section here. And so this is kind of a set of key value pairs, right? If L is the first letter of someone's name, the value hopefully is the salad. And so what you kind of have here is a dictionary, key value pairs, where it's not words and definitions, it's names and salads. And you can think of this, too, as kind of a hash table. Why? Even though it actually doesn't fit on one long shelf, because the store is only so big, this is really an array. And apparently, A is missing, or maybe it's around the corner, but this array just happens to wrap onto multiple lines, but it's still conceptually a single dimension. But suppose two people have the name L. What do they do typically? Yeah, so maybe if they put that much effort into it, they might look at the second letter and then the third letter. Odds are this is not that interesting a problem to solve optimally in that way. But they probably do start stacking the salads on top of each other, or maybe scooching it over just a little bit. And so what do you have there? Well, now if you start to view the lens through like CS50 glasses, like, OK, you have an array, and then you have like these linked lists that are sort of growing here. But even then you run into a problem. Why? Because it's not really a linked list, because at some point you're going to hit the boundary here. So it's kind of like an array of arrays, because you can only fit, like 3 or 4 salads here. And so long story short, we started today deliberately talking about real world things like stacks and queues. And even though it did escalate quickly into binary search trees and hash tables and tries, even those things are everywhere, even though they don't call them as such. These are just solutions to problems. And now, with this final week of C under your belt, you have all the more of a technical toolkit by which to implement these things in code. Next week, we'll be able to trust that someone else solved all these problems. We'll introduce Python, and lines of code like this will finally become lines of code like that. So that's the promise ahead, and we'll see you next time. This is CS50, and this is week 6, wherein we finally transition from Scratch to C to now Python. And indeed, this is going to be somewhat of a unique experience in that just like a few weeks past, perhaps for the first time, and now today, you're going to learn a new language. But the goal isn't just to throw another fire hose of content and syntax and whatnot at you, but rather to really equip you all to actually teach yourself new languages in the future. And so indeed, what we'll do today, what we'll do this coming week, is sort of prepare you to stand on your own. And once Python is passé and the world has moved on to some other language in some number of years, you'll be well equipped to figure out how to wrap your mind around some new syntax, some new language, and solve problems as well. Now, you'll recall in week 0, this is where we started, just saying hello to the world. And that quickly escalated just a week later in C to be something much, much more cryptic. And if you've still sort of struggled with some of the syntax, find yourself checking your notes or your previous code, like that's totally normal. And that's one of the reasons why there are languages besides C out there, among them this language called Python. Humans over the decades have realized, gee, that wasn't necessarily the best design decision. Or humans have realized, wow, you know what? Now that computers have gotten faster with more memory and faster CPUs, we can actually do more with our programming languages. So just as human languages evolve, so do actual programming languages. And even within a programming language, there's typically different versions. We, for instance, have been using version C11 of C, which was updated in 2011. But Python itself continues to evolve, and it's now up to version 3+. And so there, too, these things will evolve in the coming days. Thankfully, what you're about to see is Hello World for the 3rd time, but it's going to be literally this. None of the crazy syntax above or below, fewer semicolons, if any, fewer curly braces, and really a lot of the distractions get out of the way. So to get there, let's consider exactly how we've been programming up until now. So you write a program in C, and you've got hopefully no syntax error, so you're ready to build it. That is, compile it. And so you've run make, and then you've run the program like /hello. Or if you think back to week 2, where we took a peek underneath the hood of what make is doing, it's really running the actual compiler, something called Clang, maybe with some command line arguments, creating a program called hello, and then you could do /hello. So today, you're going to start doing something similar in spirit, but fewer steps. No longer will you have to compile your code and then run it, and then maybe fix or change it, and then compile your code and run it, and then repeat, repeat. The process of running your code is going to be distilled into just a single step. And the way to think of this for now is that whereas C is frequently used as indeed a compiled language, whereby you convert it first to zeros and ones, Python's going to let you speed things up, whereby you, the human programmer, don't have to compile it. You're just going to run what's called an interpreter, which by design is named the exact same thing as the language itself. And by running this program installed in VS Code or eventually on your own Macs or PCs, this is just going to tell your computer to interpret this code and figure out how to get down to that lower level of zeros and ones. But you don't have to compile the code yourself anymore. So with that said, let's consider what the code is going to look like side by side. In fact, let's look back at some Scratch blocks, just like we did with C in week 1, and do some side by sides. Because even though some of the syntax this week and beyond is going to be different, like the ideas are truly going to be the same. There's not all that much intellectually new just yet. So whereas in week 0, we might have said hello to the world with this purple puzzle piece, today, of course, or rather in week 1, it looked like this in C. But today, moving forward, it's going to quite simply look like this instead. And if we go back and forth for just a moment, here again is the version in C, noticing the very C-like characteristics. And just at a glance here, in Python, I claim it's now this. What do you apparently need not worry about anymore? What's gone? So semicolon is gone, and indeed you don't need those to finish most of your thoughts anymore. Anything else? So the \n is absent, and that's kind of curious because we're still going to get a new line, but we'll see that it's become the default. And this one's a little more subtle, but now the function is called print instead of printf. So it's a little more familiar in that sense. All right, so when it comes to using libraries, that is code that other people have written, in the past we've done things like #include cs50.h to use cs50's own header file, or standard IO, or standard lib, or string, or any number of other header files you have all used. Well, moving forward, we're going to give you for this first week a similar CS50 library, just very short-term training wheels that will quickly take off, because in reality it's a lot easier to do things in Python, as we'll see. But the syntax for this now is going to be to import the CS50 library in this way. And when we have now this ability, we can actually start writing some code right away. In fact, let me switch over to VS Code here. And just as in the past, I'll create a new file. But instead of creating something called .c, I'm going to go ahead and create my first program called hello.py, using code space hello.py. That, of course, gives me this new tab. And let me actually quite simply do what I proposed, print, quote unquote, hello world, without the \n, without the semicolon, without the f in print. And now let me go down to my terminal window, and I don't have to compile it. I don't have to do /. I instead run a program called Python, whose purpose in life is now to interpret my code, top to bottom, left to right. And if I run Python of hello.py, crossing my fingers as always, voila. Now I have printed out hello world. So we seem to have gotten the new line for free in this sense, where it's automatically happening. The $sign isn't weirdly on the same line like it once was in week 1, but that's just a minor detail here. If we switch back to now some other capabilities, well, indeed, with the CS50 library, you can also not just import the library itself, but specific functions. And you'll see that temporarily, we're going to give you a helper function called getString, just like in C, that just makes it work exactly the same way as in C. And we'll see a couple of other functions that will just make life easier initially, but quickly will we take those training wheels off so that nothing is indeed CS50 specific. All right, well, how about functions more generally in Python? Let's do a whirlwind tour, if you will, much like we did in that first week of C, comparing one to the other. So back in our world of Scratch, one of the first programs we wrote was this one here, whereby we asked the human their name. We then used the return value that was sort of automatically stored in this answer variable as a second argument to join, so that we could say hello David or hello Carter. So this was back in week 0. In week 1, we converted it to this. And here's a perfect example of things like escalating quickly. And again, this is why we start in Scratch. There's just so much distraction here to achieve the same idea. But even today, we're going to chip away at some of that syntax. So in C, we had to declare the argument as we had to declare the variable as a string here. We, of course, had the semicolon and more. Well, in Python, the comparable code now is going to look more simply like this. So semicolon is again gone on both lines, for that matter. So that's good. What else appears to have changed or disappeared? Yeah? Yeah, so I didn't have to specifically say that answer is now a string. And indeed, Python is dynamically typed. And in fact, it will infer from context exactly what it is you are storing in that variable. Other details that seem a little bit different. A little bit different. What else jumps out at you here? I'll go back. This was the C version. And maybe focus now on the second line, because we've rather exhausted the first. Here's now the Python version. What's different here? Yeah? Yeah, there's no %s anymore. There's no second argument at the moment, per se, to print. Now, it is still a little weird. It's as though I've deployed some addition here arithmetically, but that's not the case. Some of you have programmed before, and plus, some of you might know, means what in this context? So to combine, or more technically, anyone know the buzzword? Yeah. To concatenate. So to concatenate is like the fancy way of what Scratch calls joining, which is to take one string on the left, one string on the right, and to join them together, to glue them together, if you will. So this is not addition. It would be if it were numbers involved instead. But because we've got a string, hello, comma, and another string implicitly in this variable based on what the human typed in response to this getString function, that's going to concatenate hello, comma, space, and then David or Carter or whatever the human has typed in. But it turns out there's going to be different ways to do this in Python. And we'll show you a few different ones. And here, too, try not to get too hung up on or frustrated by like all of the different ways you can solve problems. Odds are you're going to be picking up tips and techniques for years to come if you continue programming. So let's just give you a few of the possible ways. So here's a second way. You could print out hello, comma, David or hello, comma, Carter. But what has changed? In the previous version, I used concatenation explicitly. And the space here is important grammatically, just so we get that in the final phrase. Now I'm proposing to get rid of that space, to add a comma outside of the double quotes as well. But if you think back to C, this probably just means that print, similar in spirit to printf, can take not just one argument, but even two. And in fact, because of this comma in the middle that's outside of the double quotes, it's hello, comma, and then it will be automatically concatenated with, even without using the plus, to whatever the value of answer is. And by default, just for grammatical prettiness, the print function always gives you a space for free in between each of the multiple arguments you pass in. We'll see how you can override that down the line. But for now, that's just another way to do it. Now, perhaps the better, if slightly cryptic way to do this, or just the increasingly common way, is probably this third version, which looks a little weird too. And probably the weirdness jumps out. We've suddenly introduced these like curly braces, which I promised were mostly gone, and they are. But inside of this string here, I've done a curly brace, which might mean what, just intuitively? And here's sort of an example of how you learn a new language. Just kind of infer from context how Python probably works. What might this mean? Yeah?
Able to tell that this is not one of the actual statements inside the double quotes. It's a variable that's being put in.
Yeah, so this is an indication, because of the curly braces, because this is the way Python was designed, that we want to plug in the value of answer, not literally ANSWER. And the fancy word here is that the answer variable will be interpolated. That is, substituted with its actual value. But, and this is actually weird looking. This was introduced a few years ago to Python. What else did I have to change to make these curly braces work, apparently? Yeah? Yeah, there's this weird f. And so it's sort of like part of printf, but now it's inside the curly, it's inside the parenthesis there. This is just the way Python designed this. So a few years ago, when they introduced what are called format strings, or f strings, you literally prefix your quoted string with the letter f. And then you can use trickery like this, like putting curly braces so that the value will be substituted automatically. If you forget the f, you're going to literally see hello, comma, curly brace, answer, close curly brace. If you add the f, it's indeed interpolated. The value is plugged in. All right, questions on how we can just say hello to the world via Python in this case? Yeah? If you do this without the f, if you omit the f, you will literally see HELLO, comma, curly brace, ANSWER, close curly brace. So in fact, let's do this. Let me go back to VS Code here quickly. I've still got my file called hello.py open. And let me go ahead and change this ever so slightly. So I'm going to go ahead and let's say from CS50 import getString. And that's just the new syntax I propose using to import a function from someone else's library. I'm going to now go ahead and ask the question, let's go ahead and use getString, storing the result and answer. So getString, quote unquote, what's your name, question mark. And then on this line, I'm going to deliberately make a mistake here, exactly to your question. Let me just say hello, comma, answer. And just this. Now, even though answer is a variable, Python's not going to be so presumptuous as to just plug in the value of a variable called answer. What it's going to do, of course, is if I type in my name, whoops, I typed too fast. Let me go ahead and rerun that again. If I run python of hello.py, type in my name and hit enter, I get hello, comma, answer. Well, let me do one better. Let me apply these curly braces as before. Let me rerun python of hello.py. What's your name? DAVID. And here's again the answer to your question. Now we get literally the curly braces. So the fix here ultimately is just going to be to add the f there, rerun my program again with DAVID, and now hello, comma, David. So this is admittedly a little more cryptic than the ones with the plus or the comma, but this is just increasingly common. Why? Because you can read it left to right. It's nice and convenient. It's less cryptic than the %s. So it's sort of a new and improved version, if you will, of printf in C, based on decades of experience of programmers doing things like this. Questions on printing in this way? We're now on our way to programming in Python. Anything? All right. Well, what more can we do with this language here? Well, let me propose that we consider that we have, for instance, a few other features that we can add to the mix as well. Namely, let's say some data types as well. So let me flip over here to back to the slides. And there's different data types in Python, as we'll soon see. But they're not as explicit as we already saw by using a string from getString. You don't have to explicitly state what it is. But you saw, recall in C, all of these various data types. And then in Python, kind of nicely enough, this list is about to get shorter. And so here is our list in C. Here is an abbreviated list in Python. So we're still going to have strings, but they're going to be more succinctly called strs now, str. We're still going to have ints for integers. We're still going to have floats for floating point values. We're even going to have bools for true and false. But what's missing now from the list is long and floats. And why is that? Or rather, long and double. Well, recall that in C, those used more bits. Well, in Python, the smaller data types previously, int and float, themselves just use more bits for you. And so you don't need to distinguish between small and large. You just use one data type, and the language gives you a bigger range than before. It turns out, though, there's going to be some other features as well of Python, these data types, one of which will be called range, another of which will be list. So gone will be arrays. We'll actually use something literally called a list. Tuples, sort of like XY pairs for coordinates and things like that. Dict for dictionaries. So we'll have built-in capabilities for storing keys and values, we'll see. And even a set. Sort of mathematically, a set is like a collection of values, but it automatically gets rid of duplicates for you. So all of these things we could absolutely implement in C if we wanted. And indeed, in problem set 5, you've been implementing your very own spell checker using some form of hash table. Well, it turns out that in Python, you can solve those same problems, but perhaps a little more readily. In fact, let me go back over here to VS Code, and let me propose that I do the following. Let me go ahead and create a file called dictionary.py. Let me propose that I try to implement, say, problem set 5, our spell checker, in Python instead of C, and achieve ultimately the same kind of behavior whereby I'll be able to spell check a whole bunch of words. So this is jumping the gun a little bit, because you're about to see syntax we'll revisit over the course of today. But for now, I've got a new file called dictionary.py. And let me begin to create some placeholders for functions. We'll see in just a bit that in Python, you can define a function called check. And that check function can take a word as its input. And I'll come back to this in just a moment. In Python, I can define a second function like load, which itself will take a whole dictionary, just like in problem set 5. And I'll go ahead and come back to the implementation of this. Meanwhile, we might similarly implement a function called size, which takes no arguments, but ultimately is going to return the size of my dictionary of words. And then lastly, for consistency with problem set 5, we might define an unload function whose purpose in life is to free any memory that you've been using just to give it back to the computer. Now, odds are, whether you're still working on Speller or have finished Speller, like you wrote a decent amount of lines of code. And indeed, it's been, by design, a challenge. But one of the reasons for these higher level languages like Python is that you can stand on the shoulders of programmers before you and solve very common problems much more quickly, so that you can focus on building your new app or your web application or your own project to solve problems of interest to you. So at the risk of crushing some spirits, let me propose that in Python, if you want a dictionary for something like a spell checker, well, that's fine. Go ahead and give yourself a variable like words to store all of those words, and just assign it equal to a dictionary, or dict for short, in Python. That will give you a hash table. Now, it turns out in Speller, recall, you don't need to worry about words and definitions. It's just about spell checking the words. So strictly speaking, we don't need keys and values. We just need keys. So I'm going to save myself a few more keystrokes by just saying that technically in Python, using a set suffices. Again, a set is just a collection of values with no duplicates. But they don't necessarily have keys and values. It's just one or the other. But now that I have, on line 1, I claim, the equivalent in Python of a hash table, I can actually do something like this. Here's how I might implement the check function in Python. If the word passed into this function is in my variable called words, well, return true. Else, go ahead and return false. Done. Wait, you're thinking, if anything at all, maybe we want to handle lowercase instead of just uppercase and lowercase. Well, you know what? In Python, if you want to force a whole word to lowercase, you don't have to iterate over it with a loop. You don't have to use any of that C-type functions or anything. Just say word.lower, and that will convert the whole thing to lowercase for parity with the dictionary. All right, how about something like the load function in Python? Well, in Python, you can open files just like in C. For instance, in Python, I might do open the dictionary argument in read mode, just like fopen in Python. I might do something like this. For each line in that file, let me go ahead and add to my words variable that line. And then let me go ahead and close that file. And I think I'm done. I'm just going to go ahead and return true just because I think I'm already done. Now here too, I could nitpick a little bit. Technically, if I'm reading in every line from the file, every line in the dictionary ends with technically a \n. But there's an easy way to get rid of that, just like you might in C with an alternative syntax. What I'm actually going to do is this. Let me grab from the current line the current word by stripping off with reverse strip. rstrip, a function we'll again see, that just gets rid of the trailing new line, the \n at the end of that line. And what I really want to do then is add this word to that dictionary. Meanwhile, if I want to figure out what the size is of my dictionary, well, in C, you're probably writing code to iterate over all of those lines, and you're just going to count them up using a variable. Not so in Python. You can just return the length of those words. And better still, in Python, you don't have to manage your own memory. No more malloc, no more free, no more manual thinking about memory. The language just deals with all of that for you. So you know what? It suffices for me to just return true and claim that unloading is done for me. And that's it. Again, whether you're in the middle of or already finished, this might perhaps suggest some frustration, but also enlightenment in that this is why higher level languages exist. You can build on top of the same principles, the same ideas with which you've been struggling even this past week, but you can now express yourself all the more succinctly. Like this one line implements a hash table for you, and all of this now just uses that hash table in a simpler way. Any questions now on this? Keeping in mind that the point, nonetheless, of Speller and PSET 5 is to understand what's really going on underneath the hood, and better still, to notice this. This might seem all rather amazing, but let me go ahead and do this. I've actually got a couple of versions of Speller written here, and I've got a version written in C that I won't show the source code for, but I'm going to go ahead and make that version of Speller in C. And I'm going to go ahead here and, let's say, split my window here for just a moment. And I'm going to go into a Python version of Speller, really that I just wrote. And on the left-hand side here, let me go ahead and run Speller, the version I compiled in C, using a big text like the Sherlock Holmes text, which is a whole lot of words in it. And on the right-hand side, let me run Python of speller.py, which is a separate file I wrote in advance, just like we give you speller.c. And I'll similarly run this on the Sherlock Holmes text. And I'm going to do my best to hit enter on the left and the right of my screen at the same time. But we should see, hopefully, the same list of misspelled words and the timings thereof. So here we go on the right. Here we go on the left. All right. Sort of a race to see which one wins here. C is on the left. Python is on the right. OK. Interesting. Hopefully, Python's close behind. Note that some of this is internet delay, and so it might not necessarily be a crazy number of seconds, but the system is indeed using, if we measure at a low level, how much time the CPU spent executing my code. C took a total of 1.64 seconds. That was pretty fast, even though it took a moment more for all of the bytes to come over the internet. The Python version, though, took what? 2.44 seconds. So what might an inference be? I mean, one, maybe I'm just better at programming in C than I am in Python, which is probably not true. But what else might you infer from this example? Should we maybe give up on Python, stick with C? No? So what might be going on here? Like, why is the Python version that I claim is correct, and I think the numbers all line up, just not the times, Where's the trade-off here? Well, here again is sort of this design trade-off. Yeah? Yeah, exactly. In order to save the human programmer time, there's a lot more features built into Python, more functions, more automatic management of memory, and so forth. And you have to pay a price. Like, someone else's code is doing all of that work for you. But if they've written some number of lines of code, those are just more lines of code that need to be executed for you. Whereas here, the computer is, at the risk of oversimplifying, only running my lines of code. So there's just less overhead. And so this is a perpetual trade-off. Typically, when using a more user-friendly, a more modern language, one of the prices you might pay is performance. Now, there's a lot of smart computer scientists in the world, though, trying to push back on those same trade-offs. And so these interpreters, like the command I wrote, Python, technically can, especially if you run a program again and again, they can actually sort of secretly behind the scenes compile your code for you down to zeros and ones. And then the second, the third, the fourth time you run that program, it might very well be faster. So this is a bit of a head fake here in that I'm running them once and only once, but we could get benefit over time if we kept running the Python version again and again and perhaps fine-tune the performance. But in general, there's going to be this trade-off. Now, would you rather spend the 60 seconds I wrote implementing a spell checker, or the 6 hours, 16 hours you might be or have spent implementing the same in C? You know, probably not. For productivity's sake, this is why we have these additional languages. Just for fun, let me flip over to another screen here and open up a version of Python that's actually on in just a second, on my own Mac instead of the cloud, so that I can actually do something with graphics. So here I just have a black and white terminal window on my very own Mac, and I've pre-installed Python just like we've done so for VS Code in the cloud for you. Notice that I've got this photo of perhaps one of your favorite TV shows here with the cast of The Office. Notice all of the faces in this image here. And let me propose that we try to find one face in the crowd, sort of CSI style, whereby we want to find perhaps the Scranton Strangler, so to speak. And so here is an example of this guy's face. Now, how do we go about finding this specific face in the crowd? Well, our human eyes obviously can pluck him out, especially if you're familiar with the show. But let me go ahead and do this instead. Let me go ahead and propose that we run code that I already wrote in advance here. This is a Python program with more lines of code that we won't dwell on for today, but it's meant to motivate what we can do from a Pillow library, implying a Python image library. I want to import some type of information, some feature called image, so that I can manipulate images, not unlike our own problem set 4. And this is kind of powerful. In Python, you can just import face recognition as a library that someone else wrote. From there, I'm going to create a variable called image. I'm going to use this face recognition's library's load image file function. It's a little verbose, but it's similar in spirit to fopen. And I'm going to open office.jpg. I'm going to then declare a second variable called face locations, plural, because what I'm expecting to get back, per the documentation for this library, is a list of all of the faces locations that are detected. All right, then I'm going to iterate over each of those faces using a for loop that we'll see in more detail. I'm going to then infer what the top, right, bottom, and left corners are of that face. And then what I'm going to do here is show that face alone if I've detected the face in question. So let me go ahead here and run detect.py. And we'll see not just the one face we're looking for, but if I run python of detect.py, it's going to do all of the analysis. I'll see a big opening here now of all of the faces that were detected in this here program. OK, some better than others, I guess, if you zoom in on catching someone, typical Angela. If you now want to find that one face, I think we need to train the software a bit more. So let me actually open up a second program called Recognize that's got more going on. But let me, with a wave of a hand, point out that I'm now loading not only the office.jpg, but also toby.jpg to sort of train the algorithm to find that specific face. And so now, if I run this second version, recognize.py, with Python of recognize.py, hold my breath for just a moment. It's analyzing presumably all of the faces. You see the same original photo, but do you see one such face highlighted here? This version of the code found Toby, highlighted him with this green, and voila, we have face recognition. So for better or for worse, this is what's happening increasingly societally nowadays. And honestly, even though I didn't write the code live, because it's a good dozen or more lines of code, it's not terribly many. And literally all the authorities, all we have to do is import face recognition, and voila, you have access. Like, these technologies are here already. But let's consider for just a moment, how did we find Toby? Like, how might that library, even though we're not going to look at its implementation details, how does it find Toby and distinguish him from all of these other faces in the crowd? What might it be doing intuitively? Think back even to pset 4, like what you yourselves have access to data-wise. Yeah?
Since you gave it an image of Toby's face before,
Mm-hmm.
it probably looks at, like, are the pixels in one area same as in another area? And a lot of them are the same from that reference image to this new image. And it's going to say, hey, a lot of similar pixel arrangements are here and here. So we can safely guess that this is the same person.
Yeah, exactly. And to summarize for camera here, we have trained the software, if you will, by giving it a photo of Toby's face. So by looking for the same or really similar pixels, especially if it's a slightly different image of Toby, we can perhaps identify him in the crowd. And what really is a human face? Well, at the end of the day, the computer only knows it as a pattern of bits, or really at a higher level, a pattern of pixels. So maybe a human face is perhaps best defined in general as like 2 eyes and a nose and a mouth, that even though all of us look similar structurally, odds are the measurement between the eyes and the nose and the width of the mouth, the skin tone, and all of these other physical characteristics are patterns that software could perhaps detect and then look sort of statistically through the image, looking for the closest possible match to these various measurement shapes, colors, and sizes, and the like. And indeed, that might be the intuition, but what's powerful here again is just how easy and readily available this technology now is. All right, so with that said, let's propose to consider what more we can do with Python itself, get back to the fundamentals so that you yourselves can start to implement something along those same lines. So besides having access to things like a getString function, the CS50 library provides a few other things as well. Namely, in C, we had these. But in Python, we're going to have fewer. In Python, our library short term is going to give you not only getString, but also getInt and getFloat. Why? It's actually just kind of annoying, as we'll soon see, to get back an integer or a float from a user and just make sure that it's an int and a float and not like a word like cat or dog or some string that's not actually a number. Well, we can import not just the specific function getString, but we can actually import all of these functions one at a time like this, as we'll soon see. Or you can even in Python import specific functions from a file. One of you asked a while back, when you include something like cs50.h or standardio.h, you're actually getting all of the code in that file, which potentially can add bulk to your own program or time. In this case, when you import specific functions from Python, you can be a little more narrowly precise as to what it is you want to have access to. All right, so with that said, let's go ahead and see what conditionals look like in Python. So in the left-hand side, again, here we'll see Scratch. And here, for instance, was just kind of a contrived example asking if x is less than y, then say x is less than y. In C, it looked like this. In Python now, it's going to look like this instead. And here's before in C, and here's after. And just to call out a few of the obvious differences, what has changed in Python for conditionals, it would seem? Sort of, what's the difference? Yeah? Yeah, so there's no more curly braces, and indeed you don't use those. What appears to be taking their place, if you might infer? What seems to have taken their place? What do you think? So the colon at the start of this line here, but also even more important now is this indentation below it. So some of you, and we know this from office hours, have a habit of like indenting everything on the left, right? And it's just kind of this crazy mess to look at. Frustrating for you, surely. But C and Clang is pretty tolerant when it comes to things like white space in a program. Python, They realized years ago that let's help humans help themselves and just require standard indentation. So 4 spaces would be the norm here. But because it's indented below that colon, that indeed indicates that this now is part of that condition. Something else has gone missing versus C in this conditional. What else is a little simplified? Yeah, so no more parentheses. You can still use them, especially when you need to logically to do order of operations like in math. But in this case, if you just want to ask a simple question like if x less than y, you can just do it like that. How about when you have an if else? Well, this is almost the same here with these same changes. In C, this looked like this. And it's starting to get a bit bulky, at least if we use our curly braces in this way. In Python, we can tighten things up further, even though strictly speaking in C, you don't always need the curly braces. But here, gone are the parentheses again. Gone are the curly braces. Indentation is consistent. And we've just added another keyword else with a colon, but no more semicolons as well. How about something larger like this? An if, else. This one's a little curious, but in C it looked like this. If, else. In Python, it now looks like this. And there's perhaps one curiosity here that honestly, all these years later, I still can't remember how to spell it half the time. What's weird about this? What do you spot as different? Yeah, over here. Yeah, instead of else if, it's elif. Why? Apparently else space if was just too many keystrokes for humans to type, so they condensed it into this way. Probably means it's a little more distinguishable too for the computer between the if and the else too, but just something to remember now. It's indeed elif and not else if. All right, so what about variables in Python? I've used a couple of them already, but let's distill exactly how you define and declare these things as well. So in Scratch, if we wanted to create a variable called counter and set it equal initially to 0, we would do something like this. Specify that it's an int, use the assignment operator, end the thought with a semicolon. In Python, it's just simpler. You name the variable, use the assignment operator as before, you set it equal to some value, and that's it. You don't mention the type, you don't mention the semicolon or anything more. What if you want to change a variable like the counter by 1, that is incremented by 1? You have a few different ways here in C. We saw syntax like this, where you can say counter equals counter plus 1, which again feels like illogical. How can counter equal counter plus 1? But again, we read this code really right to left, updating its value by 1. In Python, it's almost the same. You just get rid of the semicolon. So that logic is there. But recall in C, we could do something slightly different that we can also do in Python. In Python, you can also more succinctly do this. Plus equals, and then whatever number you want to add, or you can even change it to subtract if you prefer. Sadly, gone is something you've probably typed a whole lot. What was the other way you can add 1? Plus is no more, sadly, in Python. Just too many ways to do the same thing, so they got rid of it in favor of just this syntax here. So keep that in mind as well. What about loops? When you want to do something in Python again and again? Well, in Scratch, in week 0, here's how we meowed 3 times specifically. In C, we had a couple of ways of doing this. This was like the more mechanical approach where you create a variable called I, you set it equal to 0. You then do while I is less than 3, the following, and then you yourself increment I again and again. Mechanical in the sense that like you have to implement all of these gears and make them turn yourself, but this was a correct way to do that. In Python, we can still achieve the same idea, but we don't need the int keyword. We don't need any of the semicolons. We don't need the parentheses. We don't need the curly braces. We can't use the plus plus, so maybe that's a minor step backwards if you're a fan. But otherwise, the code, the logic is exactly the same. But there's other ways to achieve this same idea. Recall that in C, we could also do this. You could use a for loop, which it does exactly the same thing. Both are correct. Both are arguably well designed. It's kind of to each their own when it comes to choosing between these. In Python, though, we're going to have to think through how to do this. So you don't do the same for loop as in C. The closest I could come up with is this, where you say for I, or whatever variable you want to do the counting, in, literally, the preposition, and then you use square brackets here. And we've used square brackets before in the context of like arrays and things like that. And the 0, 1, 2 looks like an array in some sense, even though we've also seen arrays with curly braces. But these square brackets for now denote a list. Python does not have arrays. An array is that contiguous chunk of memory back to back to back that you have to resize somehow by moving things around in memory, as per 2 weeks ago. In Python, though, you can just create a list like this using square brackets. And better still, as we'll see, you can add or even remove things from that list down the road. This, though, is not going to be very well designed. This will work. This will iterate in Python 3 times. But what might rub you the wrong way about this design, even if you've never seen Python before? How does this example not end well? Yeah? Yeah, like if you're making a large list, you have to type out each one of these numbers, like comma 3, comma 4, comma 5, comma dot 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 50, comma dot 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 500. Like surely that's not the best solution to have all of these numbers on the screen wrapping endlessly on the screen. So in Python, another way to do this would be to use a function called range, which technically is a data type unto itself. And this returns to you as many values as you ask for it. Range takes some other arguments as well, but the simplest use case here is if you want back the numbers 0, 1, and 2, a total of 3 values, you say, hey, Python, please give me a range of 3 values. And by default, they start at 0 on up. But this is more efficient than it would be to hard code the entire list at once. And the best metaphor I could come up with is something like this. Like here, for instance, is a deck of cards. This is sort of normal human size. And there's presumably 52 cards here. So writing out 0 through 51 on code would be a little ridiculous for the reasons you note. It would just be very unwieldy and ugly and wrapping and all of that. It would be the virtual equivalent of me like handing you all of these cards at once to just deal with. And right, they're not that big, but like it's a lot of cards to hold on to. It requires a lot of memory or physical storage, if you will. What range does metaphorically is if you ask me for 3 cards, I hand you them one at a time like this, so that at any point in time, you only have one number in the computer's memory until you're handed the next. The alternative, the previous version, would be to hand me all 3 cards at once or all 52 cards at once. But in this case, range is just way more efficient. You can do range of 1,000. That's not going to give you a list of 1,000 values all at once. It's going to give you 1,000 values one at a time, reducing memory significantly in the computer itself. All right, so besides this, what about doing something forever in Scratch? Well, we could do this literally with a forever block, which didn't quite exist in C. In C, we kind of had to hack it together by saying while true, because true is by definition, TRUE, always true. So this just deliberately induces an infinite loop for us. In Python, the logic's going to be almost the same. And infinite loops in Python tend to actually be even more common because you can always break out of them, as you could in C. In Python, it looks like this. And this is slightly more subtle, but gone are the curly braces, gone are the parentheses, but ever so slight difference too. A capital T for true, and it's going to be a capital F for false. Stupid little differences. Eventually, you're going to mistype one or the other. But these are the kinds of things to keep an eye out and to start recognizing in your mind's eye when you read code. Questions now on any of these building blocks? Yeah? In the for loop was it was set to 0 on the first iteration, then 1 on the next, then 2 on the third. And the same thing for range. It just doesn't use up as much memory all at once. Other questions now on any of these building blocks of Python? No? All right, well, let's go ahead and build something a little more than hello. Let me propose that over here we implement maybe the simplest of calculators here. So let me go back to VS Code here, open my terminal window, and open up, say, a file called calculator.py. And in calculator.py, we'll have an opportunity to explore some of these building blocks, but we'll allow things to escalate pretty quickly to more interesting examples so that we can do the same thing ultimately as well. And in fact, let me go ahead and do this moreover. I've brought some code with me in advance. For instance, something called calculator0.c from the first week of C. And let me go ahead and split my window here, in fact, so that I can now do something like this. Let me move this over here. Calculator.py. So now I have on the left of my screen calculator.c, or calculator0.c, because that's the first version I made, and calculator.py on the right. Let me go ahead and implement really the same idea here. So on the right-hand side, the analog of including cs50.h would be from cs50 import getInt, if I want to indeed use this function. Now I'm going to go ahead and give myself a variable x without defining its type. I'm going to use this getInt function, and I'm going to prompt the user for x, just like in C. I'm then going to go ahead and prompt the user for another int, like y, here, just like in C. And at the very end, I'm going to go ahead and do print x plus y. And that's it. Now, granted, I have some comments in my C version of the code, just to remind you of what each line is doing. But I've still distilled this into like 6 lines, or really 4 if I get rid of the blank line. So it's already perhaps a bit tighter here. But there's also, it's tighter because something really important historically is missing. What did I seem to omit altogether that we haven't really highlighted yet? Yeah? Yeah, the main function is gone. And in fact, maybe you took for granted that it just worked a moment ago when I wrote hello, but I didn't have a main function in hello either. And this too is a feature of Python and a lot of other languages as well. Instead of having to adhere to these long-standing traditions, if you just want to write code and get something done, fine. Just write code and get something done without necessarily all of this same boilerplate. So whatever is in your Python file, left indented, if you will, by default, is just going to be the code that the interpreter runs top to bottom, left to right. Well, let me go ahead now and run code like this. Let me go ahead and open back up my terminal window, run python of calculator.py, and I'll do x is 1, y is 2. And as you might expect, it gives me 3. Slight aesthetic bug. I put my space in the wrong place here, so that's a newbie mistake. Let me fix that aesthetically. Let me rerun python of calculator.py, type in 1, type in 2, and voila, there is now my same version again. But let me propose now that we get rid of this training wheel. We don't want to keep taking one step forward and then 2 steps back by adding these training wheels. So let me instead do this. In my version of calculator.py, suppose that we take away already the training wheel that is the CS50 library here. And let me instead then use just Python's built-in function called input, which literally does just that. It gets input from the user. And it stores it, as before, in x and y. So this is not CS50 specific. This is real-world Python programming. Well, let me go ahead and run, again, python of calculator.py. And of course, if x is 1 and y is 2, x plus y should, of course, still be 3. It's apparently 12, according to Python, until CS50's library gets involved. But does anyone want to infer what just went wrong? Yeah. Exactly. The input function, by design, always returns a string of text. After all, that's what the human typed in. And even though, yes, I typed the number keys on the keyboard, it's still coming back as all text. Now, maybe we should use like a getInt function. Well, that doesn't exist in Python. All you can do is get textual input, a string from the user. But we can convert one to the other. And so a fix for this, so that we don't accidentally concatenate, that is, join x plus y together, would be to do something like this. Let me go back to my Python code here. And whereas in C, we could previously do typecasting. We could convert one type to another. That generally wasn't the case when you were doing something complex like a string to an int. You could do a char to an int and vice versa. But for a string, recall there was a special function in the C-type library called a to I, like ASCII to integer. That's the closest analog here. And in fact, the way to do this in Python would be to use a function called int, which indeed is the name of the data type too, even though I have not yet had to type it. And I can convert the output of the input function automatically from a string immediately to an int. And now, if I go back to my terminal window, rerun python of calculator.py with 1 and 2 for x and y, now I'm back in business. So that then is, for instance, what the CS50 library does, if temporarily this week, is it just deals with the conversion for you. And in fact, bad things could happen if I type the wrong thing, like dog or cat instead of a number. But we'll cross that bridge in just a moment as well. All right, what if we do something slightly different now with our calculator? Instead of just addition, let me go ahead and do, how about, instead of addition, let's do division instead. So z equals x divided by y, thereby giving me a third variable z. Let me go ahead and run python of calculator.py again. I'll type in 1. I'll type in 3 this time. And what problem do you think we're about to see? Or is it gone? What happened when I did this in C, albeit with some slightly more cryptic syntax? When I divided one number, like 1 divided by 3. Anyone recall? Yeah. Yeah, so it would round down to the nearest integer, whereby you experience truncation. So if you take an integer like 1, you divide it by another integer like 3, that technically should be 0.33333 infinitely long. But in C, recall, you truncate the value. If you divide an int by an int, you get back an int, which means you get only the integer part, which was the 0. Now, Python actually handles this for us and avoids the truncation, but it leaves us still with one other problem here, which is going to be, for instance, not necessarily visible at a glance. This looks correct. This has solved the problem in C. So truncation does not happen. The integers are automatically converted to a floating point value. But what other problem did we trip over back in week 1. What else got a little dicey when dealing with simple arithmetic? Anyone recall? Well, the syntax in Python's a little different, but let me go ahead and do this. It turns out in Python, if you want to see more significant digits than what I'm seeing here by default, which is a dozen or so, let me go ahead and print out z as follows. Let me first print out a format string, because I want to format z in an interesting way. And notice this would have no effect on the difference. This is just a format string that for no compelling reason at the moment is interpolating z in those curly braces using an f string or format string. If I run this again with 1 and 3, we'll see indeed the exact same thing. But when you use an f string, you indeed have the ability to format that string more precisely. Just like with %f in Python, you could start to fine tune how many significant digits you see. In C, in Python, you can do the same, but the syntax is a little different. If you want the computer to interpolate z and show you 50 significant digits, that is 50 numbers after the decimal point, syntax is similar to C, but it's a little different. You literally put a colon after the variable's name. .50 means show me the decimal point and then 50 digits to the right. And the f just indicates, please treat this as a floating point value. So now if I rerun Python of calculator.py, divide 1 by 3, unfortunately, Python has not solved all of the world's problems for us. This, again, was an example of floating point imprecision. So that problem is still latent. So just because the world has advanced doesn't necessarily mean that all of our problems from C have gone away. There are solutions using third-party libraries for scientific calculations and the like. But out of the box, floating point imprecision is still an issue. Meanwhile, there was one other problem in C that we ran into involving numbers, and that was this, integer overflow. Recall that an integer in C only took up, what, like 32 bits typically, which meant you could count as high as 4 billion, or maybe if you're doing positive and negatives, as high as 2 billion. After which, weird things would happen. The number would go to 0 or negative, or just it would overflow or wrap back around. Well, wonderfully in Python, they did at least address this, whereby you can count as high as you want. And Python will just use more and more and more and more bits and bytes to store really big numbers, so integer overflow is not a thing. With that said, Python is limited to how many digits it will show you on the screen at once as a string. But mathematically, your math will be correct now. So we've taken a couple steps forward, one step sideways. But indeed, we've solved some of our problems here. All right, questions now on any of these examples thus far? Question. All right, well, how about another problem that we encountered in C? Let's revisit it here in Python as well. So let me go ahead and on the left-hand side here, let me open up a file called, say, compare. Let's see. How about a file called compare3.c on the left? And let me go ahead and create a new file on the right called compare.py. Because recall that bad things happened when we needed to compare two values in C. So on the left here is a reminder of what we once did in C, whereby if we want to compare values, we can get an int in C, stored in x, a getInt in C, stored in y. We then have our familiar conditional logic here, just printing out if x is less than y or not. Well, we can certainly do the same thing ultimately in Python by using some fairly familiar syntax. And let's just demonstrate this one quickly. Let me go over here too. I'll do from CS50 import getInt, even though I could do this instead with the input function itself. X equals getInt, and I'll prompt the user for that. Y equals getInt, and I'll prompt the user for that. After that, recall that I can say without parentheses, if x is less than y, then print out, without the f, x is less than y. Then I can go ahead and say else if x is greater than y, I can print out quote unquote x is greater than y. If you'd like to interject now. What did I screw up? Anyone? Yeah. elif, right? So elif x is greater than y, else, this part's the same, print x is equal to y. So there's not all that much there's no new logic going on here, but at least syntactically it's a little cleaner. Indeed, this program's only 11 lines long, albeit without any comments. Let me go ahead and run Python of compare.py. Let's see, is 1 less than 2? Indeed. Let's run it again. Is 2 less than 1? No, it's greater than. And let's lastly type in 1 and 1 twice. X is equal to y. So we've got a pretty side-by-side one-to-one conversion here. Let's do something a little more interesting than in C. How about I open instead something where we actually compared for a purpose? So if I open up from from earlier in the course, how about agree.c, which prompt the user to agree to something or not. And let me code up a new version here called agree.py. And I'll do this on the right-hand side with agree.py. But on agree.c on the left, notice that this is how we did this sort of yes-no thing in C. We compared C, a character, equal to single quotes y, or equal to single quotes little y. And then the same thing for n. Now in Python, this one's actually going to be a little bit different here. Let me go ahead and in the Python version of this, let me do something like this. We'll use getString. Well, actually, no, we'll just use input in this case. So let's do s equals input. And we'll ask the user the same thing. Do you agree? Question mark. Then let's go ahead and say if s equals, how about y? How do I do this? Well, a few things. Turns out I'm going to do this. S equals little y. Then I'm going to go ahead and print out agreed. And if s equals capital N or s equals lowercase n, I'm going to go ahead and print out not agreed. And I claim for the moment that this is identical now to the program on the right, the program on the left in C. But what's different? So we're still doing the same kind of logic, these equals for comparing for equality. But notice that nicely enough, Python got rid of the 2 vertical bars. And it's just literally the word or. If you recall seeing ampersand to express a logical and in C, you can just write literally the word and. And so here's a hint of why Python tends to be pretty popular. People just like that it's a little closer to English. There's a little less of the cryptic syntax here. Now this is correct, as this code will now work. But I've also used double quotes instead of single quotes. And I also omitted a few minutes ago from my list of data types in Python the word char. In Python, there are no chars. There are no individual characters. If you want to manipulate an individual character, you use a string, that is to say a str, of size 1. Now, in Python, you can use single quotes or double quotes. I'm deliberately using double quotes everywhere just for consistency with how we treat strings in C. It's pretty common, though, to use single quotes instead, if only because on most keyboards you don't have to hold the shift key anymore. I mean, humans have really started to optimize just how quickly they want to be able to code. So using a single quote tends to be pretty popular in Python and other languages as well. They are fundamentally the same, single or double, unlike in C where they have meaning. So this is correct, I claim. And in fact, let me run this real quick. I'll open up my terminal window here. Let me get rid of the version in C and run Python of agree.py. And I'll type in y. OK, I'll run it again and type in little y. And I'll stipulate it's going to work for no as well. But this isn't necessarily the only way we can do this. There are other ways to implement the same idea. And in fact, I can go about doing this instead. Let me go back up to my code here. And we saw a hint of this earlier. We know that lists exist in Python, and you can create them just by using square brackets. So what if I simplify the code a little bit and just say if s is in the following list of values, capital Y or lowercase y? It's not all that different logically, but it's a little tighter. It's a little more compact. So if s is in capital N or lowercase n, I can express that same idea too. So here again, it's just getting a little more pleasant to write code. There's less like hitting of the keyboard. You can express yourself a little more succinctly. And using the keyword in, Python will figure out how to search the entire list for whatever the value of s is. And if it finds it, it will return true automatically, else it will return false. So if I run agree.py again and type in capital Y or lowercase y, that still now works. Well, I can tighten this up further if I want to add more features. Well, what if I want to support not just y, big Y and little y, but how about yes, or in case the user's yelling, or someone who isn't good with caps lock types in yes. Wait a minute, but it could be weird. Like, do we want to support this? or this. I mean, this just gets really tedious quickly, combinatorically, if you consider all of these possible permutations. What would be smarter than doing something like this if you want to just be able to tolerate yes in any form of capitalization? Like logically, what would be nice?
Maybe whatever the input is, you just transfer it over to all lowercase or all uppercase and then read it.
Exactly. Super common paradigm. Why don't we just force the user's input to all lowercase or all uppercase? Doesn't matter so long as we're self-consistent, and just compare against all uppercase or all lowercase. And that will get rid of all of the possible permutations otherwise. Now in C, we might have done something like this. We might have simplified this whole list and just said, let's say we'll do, how about lowercase? So y or yes, and we'll just leave it at that. But we need to force now s to lowercase. Well, in C, we would have used the C-type library. We would have done like toLower and called that function, passing it in, although not really, because in C-type, those operate on individual characters or chars, not whole strings. We actually didn't see a function that could convert a whole string in C to lowercase. But in Python, we're going to benefit from some other feature as well. It turns out that Python supports what's called object-oriented programming. And we're only going to scratch the surface of this in CS50. But if you take a higher level course in programming or CS, you'll explore this as a different paradigm. Up until now in C, we've been focusing on what's called really procedural programming. You write procedures. You write functions, top to bottom, left to right. And when you want to change some value, we were in the habit of using a procedure. That is a function. You would pass something, like a variable, into a function, like toUpper or toLower, and it would do its thing and hand you back a value. Well, it turns out that it would be nicer, programming-wise, if some data types just had built-in functionality. Like, why do we have our variables over here and all of our helper functions, like toUpper and toLower over here, such that we constantly have to pass one into the other? It would be nice to sort of bake into our data types some built-in functionality so that you can change variables using their own default built-in functionality. And so object-oriented programming, otherwise known as OOP, is a technique whereby certain types of values, like a string, aka str, not only have properties inside of them, attributes, just like a struct in C, your data can also have functions built into them as well. So whereas in C, which is not object-oriented, you have structs, and structs can only store data, like a name and a number when implementing a person, in Python, you can, for instance, have not just a structure, otherwise known as a class, storing a name and a number. You can have a function like call that person or email that person or actual verbs or actions associated with that piece of data. Now, in the context of strings, it turns out that strings come with a lot of useful functionality. And in fact, at this URL here, which is in docs.python.org, which is the official documentation for Python, you'll see a whole list of methods, that is, functions that come with strings that you can actually use to modify their values. And what I mean by this is the following. If we go through the documentation, poke around, it turns out that strings come with a function called lower. And if you want to use that function, you just have to use slightly different syntax than in C. You do not do toLower, and you do not say, as I just did, lower, because this function is built into S itself. And just like in C, when you want to go inside of a variable, like a structure, and access a piece of data inside of it, like name or number, when you also have functions built into data types, aka methods. A method is just a function that is built into a piece of data. You can do s dot lower, open paren, close paren in this case. And I can do this down here as well. If s dot lower in quote unquote n, or no, the whole thing, I can force this whole thing to lowercase. So the only difference here now is in object-oriented programming, instead of constantly passing a value into a function, you just access a function that's inside of the value. It just works because of how the language itself is defined. And the only way you know whether these functions exist is the documentation, a class, a book, a website, or the like. Questions now on this technique? All right, I claim this is correct. Now, even though you've never programmed, most of you, in Python before, not super well designed. There's a subtle inefficiency now on lines 3 and 5 together. What's dumb about how I've used lower, might you think? Yeah. Yeah. Yeah, if you're going to use the same function twice and ask the same question, expecting the same answer, why are you calling the function itself twice? Maybe we should just store the result in a variable. So we could do this in a couple of different ways. We, for instance, could go up here and create another variable called t and set that equal to s.lower. And then we could just change this to be t here. But honestly, I don't think we technically need another variable altogether here. I could just do something like this. Let's change the value of s to be the lowercase version thereof. And so now I can quite simply refer to s again and again like this, reusing that same value. Now, to be sure, I have now just lost the user's original input. And if I care about that, if they typed in all caps, I have no idea anymore. So maybe I do want to use a separate variable altogether. But a takeaway here, too, is that strings in Python are technically what we'll call immutable. That is, they cannot be changed. This was not true in C. Once we gave you arrays in week 2 or memory in week 4, you could go to town on a string and change any of the characters you want, uppercasing, lowercasing, changing it, shortening it, and so forth. But in this case, this returns a copy of s forced to lowercase. It doesn't change the original string, that is the memory, the bytes in the computer's memory. When you assign it back to s, you're essentially forgetting about the old version of s. But because Python does memory management for you, there's no malloc, there's no free, Python automatically frees up the original bytes, like YES, and hands them back to the operating system for you. All right, questions now on this technique. Questions on this. In general, I'll call out the Python documentation will start to be your friend, because in class we'll only scratch the surface with some of these things. But in docs.python.org, for instance, there's a whole reference of all of the built-in functions that come with the language, as well as, for instance, those with the string. All right, well, let me go ahead and, before we take a break, let's go ahead and create something a little familiar too, based on our weeks here in C. Let me propose that we revisit those examples involving some meows. So for instance, when we had our cat meow back in the first week and then second in C, we did something that was a little stupid at first, whereby we created a file, as I'll do here, this time called meow.py. And if I want a cat to meow 3 times, I could run it once like this, little copy paste, and now Python of meow.py, and I'm done. Now, we've visited this example like 2 times at least now in Scratch and in C. It's correct, I'll stipulate, but what's obviously poorly designed? What's the fault here? Yeah. It should just be a loop, right? Like, why type it 3 times? Literally copying and pasting is almost always a bad thing, except in C when you have the function prototypes that you need to borrow. But in this case, this is just inefficient. So what could we do better here in Python? Well, in Python, we could probably change this in a few different ways. We could borrow some of the syntax we proposed in slide form earlier, like give me a variable called I, set it to 0, no semicolon. While I is less than 3, if I want to do this 3 times, I can go ahead and print out meow, and then I can do I plus equals 1. And I think this would do the trick, Python of meow.py, and we're back in business already. Well, if I wanted to change this to a for loop, well, in Python, it would be a little tighter, but this would not be the best approach. So for I in 0, 1, 2, I could just do print meow like this, and that too would get the job done. But to our discussion earlier, this would get stupid pretty quickly if you had to keep enumerating all of these values. Like, what did we introduce instead? The range function, exactly. So that hands me back way more efficiently just the values I want, indeed 1 at a time. So even this, if I run it a third or fourth time, we've got the same result. But now let's transition to where we went with this back in the day. How can we start to modularize this? Like, just like it would be nice, I claimed, if MIT had given us a meow function, wouldn't it be nice if, like, Python had given us a meow function? Maybe less compelling in Python, but how can I build my own function? Well, I did this briefly with the spell checker earlier, but let me go ahead and propose that we could implement now our own version of this in Python as follows. Let me go ahead and start fresh here and use the keyword def. So this did not exist in C. You had the return value, the function name, the arguments. In Python, you literally say def to define a function. You give it a name like meow. And now I'm going to go ahead and in this function just print out meow. And this lets me change it to anything else I want in the future. But for now, it's an abstraction. And in fact, I can move it out of sight, out of mind. Just going to hit enter a bunch of times to pretend like now it exists, but I don't care how it is implemented. And up here now I can do something like this. For I in range of 3, let me go ahead and not print meow anymore. Let me just call meow, and tightening up my code further. But I think, let's see, Python of meow.py, this is, I think, going to be the first time it does not work correctly. OK, so here we have, sadly, our first Python error. And let's see. The syntax is going to be different from C or Clang's output. Traceback is like the term of art here. This is like a trace back of all of the lines of code that were just executed, or really functions you called. The file name is uninteresting. This is like my code space specifically, but the file name is important here, meow.py. Line 2 is the issue. OK, I didn't get very far before I screwed up. And then there's a name error. And you'll see in Python there's typically these capitalized keywords that hint at what the issue is. It's something related to names of variables. Meow is not defined. All right, you're programming Python for the first time. You've screwed up. You're following some online tutorial. You're seeing this. Reason through it. Like, why might meow not be defined? What can we infer about Python? How to troubleshoot logically. Maybe. Is it because meow is defined after? You know, as smart as Python seems to be vis-a-vis C, they have some similar design characteristics. So let's try that. So let me scroll all the way back down to where I moved this earlier. Let me get rid of it way down there. I'll copy it to my clipboard. And let me just kind of hack something together. Let me just put it up here. And let's see if this works. So now let me clear my terminal, run Python of meow.py. OK. We're back in business. So that was actually really good intuition, good debugging technique to sort of reason through it. Now, this is kind of contradicting what I claimed back in week 1, which was that, you know, the main part of your program ideally should just be at the top of the file. Like, don't make me look for it. It's not a huge deal with like a 4-line program. But if you've got 40 lines, 400 lines, you don't want like the juicy part of your program to be way down here and all of these functions way up here. So it would be nice maybe if we actually have a main function. And so it actually turns out to be a convention in Python to define a main function. It's not a special function that's automatically called like in C. But humans realized, you know what, that was a pretty useful feature. Let me define a function called main. Let me indent these lines underneath it. Let me practice what I'm preaching, which is put the main code at the top of the file. And wonderfully in Python now, you do not need prototypes. There's none of that hackish copying and pasting of the return type, the name, and the arguments to a function like we needed in C. This is now OK instead, except for one minor detail. Let me go ahead and run Python of meow.py. Hopefully now I've solved this problem by having a main function, but now nothing has happened. All right, even if you've never programmed in Python before, what might explain this behavior? And how do I fix? Again, when you're off in the real world learning some new language, all you have is deductive logic to debug. Yeah?
I remember in C, we actually, even though we put functions underneath the main, we still have to call just the name of the function right above main so that we knew what the function was.
Right. So the solution, to be clear, in C was that we had to put the prototype up here. Otherwise, we'd get an error message. In this case, I'm actually not getting an error message. And indeed, I'll claim that you don't need the prototypes in Python. Just not necessary, because that was annoying, if nothing else. But what else might explain? Yeah, and back? Yeah, maybe you have to call main itself. If main is not some special status in Python, maybe just because it exists isn't enough. And indeed, if you want to call main, the new convention is actually going to be, as the very last line of your program typically, to literally call main. It's a little stupid looking, but you know, they made a design decision, and this is how now we work around it. Python of meow.py now. We're back in business. But now logically, why does this work the way it does? Well, in this case, top to bottom, line 1 is telling Python to define a function called main, and then define it as follows, lines 2 and 3. But it's not calling main yet. Line 6 is telling Python how to define a function called meow, but it's not calling these lines yet. Now, on line 10, you're telling Python call main. And at that point, Python has been trained, if you will, to know what main is on line 1, to know what meow is on line 6. And so it's now perfectly OK for main to be above meow, because you never called them yet. You defined, and then you called. And that's the logic behind this. Any questions now on the structure of this technique here? Now, let's do one more then. Recall that the last thing we did in Scratch and in Python, Scratch and in C was to actually parameterize these same functions. So suppose that you don't want main to be responsible for the loop here. You instead want to very simply do something like meow 3 times and be done with it. Well, in Python, it's going to be similar in spirit to C, but again, we don't need to keep mentioning data types. If you want meow to take some argument, like a number, n, you can just specify n as the name of that argument. Or you could call it anything else, of course, that you want. You don't have to specify int or anything else. In your code now, inside of meow, you can do something like for I in, let's say, I definitely now can't do this, because like that would be weird to start the list and end it with n. So if I can come back over here, what's the solution? How can I do something n times? Yeah, using range. So range is nice because I can pass in now this variable n, and now I can meow, whoops, now I can print out, quote unquote, meow. So it's almost the same as in Scratch, almost the same as in C, but it's a little simpler. And if now I run meow.py, I'll have the ability now to do this here as well. All right, questions on any of this? Right now, we're sort of like taking the stroll through week 1. We're going to momentarily escalate things to look not only at some of these basics, but also other features like we saw with face recognition, with the speller or the like. Because of how many of us are here, we have a huge amount of candy out in the lobby. So why don't we go ahead and take a 10-minute break, and when we come back, we'll do even fancier, more powerful things with Python in 10. All right, so we are back. Among our goals now are to introduce a few more building blocks so that we can solve more interesting problems at the end, much like those that we began with. You'll recall from a few weeks ago, we played with this sort of 2-dimensional Super Mario world, and we tried to print a vertical column of like 3 or more bricks. Well, let me propose that we use this as an opportunity to now tinker with some of Python's more useful, more user-friendly functionality as well. So let me code a file called mario.py, and let's just print out like that, the equivalent of that vertical column. So it's of height 3. Each one is a hash. So let's do for I in range of 3 initially, and let's just print out a single hash. And I think now Python of mario.py, voila, we're in business, printing out just that same pyramid there, or just that same column there. What if, though, we want to print a column of like some variable height where the user tells us how tall they want it to be? Well, let me go up here, for instance, and instead, how about we'll use, let's do this. How about from CS50 import, how about the getInt function as before? So it will deal with making sure the user gives us an integer. And now, in the past, whenever we wanted to get a number from a user, we've actually followed a certain paradigm. In fact, if I open up here, for instance, how about Mario 1.c from a while back, you might recall that we had code like this. And we specifically use the do while loop in C whenever we want to like get something from the user, maybe again and again and again until they cooperate, at which point we finally break out of the loop. So it turns out Python does have while loops, does have for loops, does not have do while loops. And yet pretty much any time you've gotten user input, you've probably used this paradigm. So it turns out that the Python equivalent of this is to do similar in spirit, but using only a while loop. And a common paradigm in Python, as I alluded earlier, is to actually deliberately induce an infinite loop while true, capital T, and then do what you want to do, like get an int from the user and prompt them for the height, for instance, in question. And then if you're sure that the user has given you what you want, like n is greater than 0, which is what I want in this case because I want a positive integer, otherwise there's nothing to print, you literally just break out of the loop. And so we could actually use this technique in C. It's just not really done in C. You could absolutely in C have done a while true loop with the parentheses, lowercase true. You could break out of it and so forth. But in Python, this is like the Python way. And this is actually a term of art. This way in Python is Pythonic. Like this is the way everyone does it, quote unquote. Doesn't mean you have to, but that's sort of the way like the cool Python programmers would implement an idea like this, trying to do something again and again and again until the user actually cooperates. But all we've done is take away the do while loop, but still logically we can implement the same idea. Now below this, let me go ahead and just print out for I in range of n this time, because I want it to be variable and not 3. I can go ahead and print out the hash. Let me go ahead and get rid of the C version here. Open my terminal window, and I'll run again Python of mario.py. I'll type in 3. and I get back those 3 hashes. But if I instead type in 4, I now get 4 hashes instead. So the takeaway here is quite simply that this would be the way, for instance, to actually get back a value in Python that is consistent with some parameter, like greater than 0. How about this? Let's actually practice what we preached a moment ago with our meowing examples and kind of factoring all this out. Let me go ahead and define a main function as before. Let me go ahead and assume for the moment that a getHeight function exists, which is not a thing in Python. I'm going to invent it in just a moment. And now I'm going to go ahead and do something like this. For I in the range of that height, well, let's go ahead and print out those hashes. So I'm assuming that getHeight exists. Let me go ahead and implement that abstraction. So define a function now called getHeight. It's not going to take any arguments in this design. While true, I can go ahead and do the same thing as before. Assign a variable n, the return value of getInt, prompting the user for that height. And then if n is greater than 0, I can go ahead and break. But if I break here, I logically, just like in C, end up executing below the loop in question, but there's nothing there. But if I want getHeight to return the height, what should I type here on line 14 logically? What do I want to return, to be clear? Yeah, so I actually want to return n. And here's another curiosity of Python vis-a-vis C. There doesn't seem to be an issue of scope anymore, right? In C, it was super important to not only declare your variables with the data types, you also had to be mindful of like where they exist inside of those curly braces. In Python, it turns out you can be a little looser with things, for better or for worse. And so on line 11, if I create a variable called n, it exists on line 11, 12, and even 13 outside of the while loop. So to be clear, in C with a while loop, we would have ordinarily had not a colon. We would have had the curly brace like here and over here. And a week ago, I would have claimed that in C, n does not exist outside of the while loop by nature of those curly braces. Even though the curly braces are gone, Python actually allows you to use a variable anytime after you have assigned it a value. So slightly more powerful as such. However, I can tighten this up a little bit. Logically, and this is true in C, I don't really need to break out of the loop by using break. Recall that or know that I can actually, once I'm ready to go, I can just return the value I care about even inside of the loop. And that will have the side effect of breaking me out of the loop and also breaking me out of and returning from the entire function. So nothing too new here in terms of C versus Python except for this issue of scope. And I indeed returned n at the bottom there just to make clear that n would still exist. So either of those are correct. Now I just have a Python program that I think is going to allow me to implement this same Mario idea. So let's run Python of Mario.py and OK, so nothing happened. Python of Mario.py. What did I do wrong? Yeah, I have to call main. So at the bottom of my code, I have to call main here. And this is a stylistic detail that's been subtle. Generally speaking, when you are writing in Python, there's not a CS50 style guide per se. There's actually a Python style guide that most people adhere to. And in this case, double blank lines between functions is the norm. I'm doing that deliberately, although it might otherwise not be obvious. But now that I've called main on line 16, let's run Mario.py once more. Aha, now we get there. Now we see it. Type in 3, and I'm back in business printing out the values there. Yeah? Sure, why do I need the if condition at all? Why can't I just return n here as by doing return n? Or if I really want to be succinct, I could technically just do this. The only reason I added the if condition is because if the user types in -1, -2, I wanted to prompt them again and again. That's all. But that would be totally acceptable too if you were OK with that result instead. Well, let me do one other thing here to point out why we are using getInt so frequently, this new training wheel, albeit temporarily. So let me go back to the way it was a moment ago. And let me propose now to take away getInt. I claimed earlier that if you're not using getInt, you can just use the input function itself from Python. But that always returns a string or a str. And so recall that you have to pass the output of the input function to an int, either on the same line or, if you prefer, on another line instead. But it turns out what I didn't do was show you what happens if you don't cooperate with the user, with the program. So if I run Python of Mario.py now, works great, even without the getInt function. And I can do it with 4. Still works great. But let me clear my terminal and be difficult now as the user and type in cat for the height instead. Enter. Now we see one of those tracebacks again. This one is different. This isn't a name error, but apparently a value error. And if I kind of ignore the stuff I don't understand, I can see invalid literal for int with base 10 cat. That's a super cryptic way of saying that cat is not a number in decimal notation. And so I would seem to have to somehow handle this case. And if you want to be more curious, you'll see that this is indeed a trace back. And C tends to do this too, or the debugger would do this for you too. You can see all of the functions that have been called to get you to this point. So apparently my problem is initially in line 14. But line 14, if I keep scrolling, is uninteresting. It's main. But line 14 leads me to execute line 2, which is indeed in main. That leads me to execute line 9, which is in get height. And so, OK, here's the issue. So the closest line number to the error message is the one that probably reveals the most. Line 9 is where my issue is. So I can't just blindly ask the user for input and then convert it to an int if they're not going to give me an int. Now, how do we deal with this? Well, back in problem set 2, you might recall validating that the user typed in a number and using a for loop and the like. Well, it turns out there's a better way to do this in Python, and the semantics are kind of there. If you want to try to convert something for a number to a number that might not actually be a number, turns out Python and certain other languages literally have a keyword called try. And if only this existed for the past few weeks, I know. But like, you can try to do the following with your code. What do I want to try to do? Well, I want to try to execute those few lines, except if there's an error. So I can say except if there's a value error, specifically the one I screwed up and created a moment ago. And if there is a value error, I can print out an informative message to the user like not an integer or anything else. And what's happening here now is literally this operative word try. Python is going to try to get input and try to convert it to an int. And it's going to try to check if it's greater than 0 and then try to return it. Why? All of 3 of those lines are indented underneath the try block. Except if something goes wrong, specifically a value error happens, then it prints this. But it doesn't return anything. And because I'm in a loop, that means it's going to do it again and again and again until the human actually cooperates and gives me an actual number. And so this, too, is what the world would call Pythonic. In Python, you don't necessarily rigorously try to validate the user's input, make sure they haven't screwed up. You honestly take a more lackadaisical approach and just try to do something, but catch an error if it happens. So catch is also a term of art, even though it's not a keyword here. Except if something happens, you handle it. So you try and you handle it. So you sort of best effort programming, if you will. But this is baked into the mindset of the Python programming community. So now if I do Python of Mario.py and I cooperate, works great as before. Try and succeed. 3 works, 4 works. If, though, I try and fail by typing in cat, it doesn't crash, per se. It doesn't show me an error. It shows me something more user-friendly, like not an integer. And then I can try again with dog. Not an integer. I can try again with 5. And now it works. So we won't generally have you write much in the way of these try except blocks, only because they get a little sophisticated quickly. But that is to reveal what the getInt function is doing. This is why we give you the training wheels, so that when you want to get an int, you don't have to jump through all these annoying hoops to do so. But that's all the library is really doing for you, is just try and accept. You won't be left with any training wheels ultimately. Questions now on getting input and trying in this way? Anything at all? Yeah? Say that, oh, could you put the condition outside of the try block? Short answer, yes. And in fact, I struggled with this last night when tweaking this example to show the simplest version. I will disclaim that really, I should only be trying, literally, to do the fragile part. And then down here, I should be really doing what you're proposing, which is do the condition out here. The problem is, though, that logically, this gets messy quickly, right? Because except if there's a value error, I want to print out not an integer. I can't compare n against 0 then, because n doesn't exist because there was an error. So it turns out, and I'll show you this. This is now the advanced version of Python. There's actually an else keyword you can use in Python that does not accompany if or elif. It accompanies try and except, which I think is weirdly confusing. A different word would have been better. But if you really prefer I could have done this instead. And this is one of these design things where like reasonable people will disagree. Generally speaking, you should only try to do the one line that might very well fail. But honestly, this looks kind of stupid now. It's just unnecessarily complicated. And so my own preference was actually the original, which was, yeah, I'm trying a few extra lines that really aren't going to fail mathematically, but it's just tighter. It's cleaner this way. And here's, again, the sort of like, arguments you'll start to make yourself as you get more comfortable with programming. You'll have an opinion. You'll disagree with someone. And so long as you can back your argument up, it's pretty reasonable, probably. All right, so how about we now take away some piece of magic that's been here for a while. Let me go ahead and delete all of this here. And let me propose that we revisit not that vertical column and the exceptions that might result from getting input, but these like horizontal question marks that we saw a while ago. So I want all of those question marks on the same line. And yet I worry we're about to see a challenge here because print up until now has been putting new lines everywhere automatically, even without those \n's. Well, let me propose that we do this. For I in the range of 4, if I want 4 question marks, let me just print 4 question marks. Unfortunately, I don't think this is correct yet. Let me run Python of Mario.py. And of course, this gives me a column instead of the row of question marks that I want. So how do we do this? Well, it turns out if you read the documentation for the print function, it turns out that print, not surprisingly perhaps, takes a lot of different arguments as well. And in fact, if you go to the documentation for it, you'll see that it takes not just positional arguments, that is from left to right, separated by commas. It turns out Python supports a fancier feature with arguments where you can pass the names of arguments to functions too. So what do I mean by this? If I go back to VS Code here, and I've read the documentation, it turns out that yes, as before, you can pass multiple arguments to Python like this, like hello, comma, David, comma, Malin. That will just automatically concatenate all 3 of those positional arguments together. They're positional in the sense that they literally flow from left to right, separated by commas. But if you don't want to just pass in values like that, you want to actually print out, as I did before, a question mark. But you want to override the default behavior of print by changing the line ending. You can actually do this. You can use the name of an argument that you know exists from the documentation and set it equal to some alternative value. And in fact, even though this looks cryptic, this is how I would override the end of each line to be quote unquote, that is nothing. Because if you read the documentation, the default value for this end argument, does someone want to guess, is \n. So if you read the documentation, you'll see that \n is the implied default for this end argument. And so if you want to change it, you just say end equals something else. And so here, I can change it to nothing and now rerun Python of Mario.py. And now they're all on the same line. Now, it looks a little stupid because I made that sort of week 1 mistake where I still need to move the cursor to the next line. That's just a different problem. I'm just going to go over here and print nothing. I don't even need to print \n, because if print automatically gives you a \n, just call print with nothing, and you'll get that for free. So let me rerun Python of Mario.py, and now it looks a little prettier at the prompt. And to be super clear as to what's going on, suppose I want to sort of make an exclamation here. I could change the \n default to like an exclamation point just for kicks. And if I run Python of Mario.py again, now I get this sort of exclamation with question marks and exclamation points as well. So that's all that's going on here. And this is what's called a named argument. It literally has a name that you can specify when calling it in. And it's different from positional in that you're literally using the name. Let me propose something else, though. And this is why people kind of like Python. There's just kind of cool ways to do things. That's kind of a, it's a 3-line verbose way of printing out 4 question marks. I could certainly take the, shortcut and just do this, but that's not really that interesting for anyone, especially if I want to do it a variable number of times. But Python does let you do this. If you want to multiply a character some number of times, not only can you use plus for concatenation, you can use star or an asterisk for multiplication, if you will. That is concatenation again and again and again. So if I just print out quote unquote question mark times 4, that's actually going to be the tightest way, the most succinct way I can print 4 question marks instead. And if I don't use 4, I use n, where I get n from the user. Bang, like now I've gotten rid of the for loop entirely, and I'm using the star operator to manipulate it instead. And to be super clear here, insofar as Python does not have malloc or free or memory management that you have to do. Guess what Python also doesn't have? Anything on your minds the past couple of weeks? Doesn't have pointers. Yeah, so Python does not have pointers, which just means that all of that happens for you automatically underneath the hood, again, by way of code that someone else wrote. How about one more throwback with Mario? We talked about in week 1 this sort of 2-dimensional structure where it's like, I claim, like 3 by 3, a grid of bricks, if you will. Well, how can we do this in Python? We can do this in a couple of ways now. Let me go back to my mario.py, and let me do something like for I in range of, we'll just do 3, even though I know now I could use getInt, or I could use input and int. And if I want to do something 2-dimensionally, just like in C, you can nest your for loops. So maybe I could do for j in range of 3. And then in here, I could print out a hash symbol. And then let's see if that gives me 9 total. So if I've got a nested loop like this, Python of mario.py hopefully gives me a grid. No, it gave me a column of 9. Why, logically? Even though I've got my row and my columns. Yeah. Yeah, the line ending. So in my row, I can't let print just keep adding new line, adding new line. So I just have to override this here. And let me not screw up like before. Let me print one at the end of the whole row just to move the cursor down. And I think now together, now we've got our 3 by 3. Of course, we could tighten this up further. Like if I don't like the nested loop, I probably could go in here and just print out, for instance, a brick times 3, or I could change the 3 to a variable if I've gotten it from the user. So I can tighten this up further. So again, just different ways to solve the same problem. And again, sort of evidence of why a lot of people like Python. There's just some more pleasant ways to solve problems without getting into the weeds constantly of doing things like with for loops and while loops endlessly. All right, well, how about some other building blocks? Lists are going to be so incredibly useful in Python, just as arrays were in C. But arrays are annoying because you have to manage the memory yourself. You have to know in advance how big they are, or you have to use pointers and malloc or realloc to resize them. Like, oh my god, like the past 2 weeks have been painful in that sense. But Python does this all for free for you. In fact, there's a whole bunch of functions that come with Python that involve lists, and they'll allow us ultimately to do things again and again and again within the same data structure. And for instance, we'll be able to get the length of a list. You don't have to remember it yourself in a variable. You can just ask Python how many elements are in this list. And with this, I think we can solve some old problems too. So let me go back here to VS Code. Let me close Mario and give us a new program called scores.py. And rather than show the C and the Python now, let's just focus on Python. And in scores.c, way back when, we just averaged like 3 test scores or something like that, 72, 73, and 33 a few weeks ago. So if I want to create a list in this Python version of 72, 73, 33, I just use my square bracket notation. C let you use curly braces if you know the values in advance, but Python's just this. And now if I want to compute the average, in C, recall, I did something with a loop. I added all the values together. I then divided by the total number of values, just like you would in grade school, and that gave me the average. Well, Python comes with a lot of super handy functions, not just length, but others as well. And so in fact, if you want to compute the average, you can take the sum of all of those scores and divide it by the length of all of those scores. So Python comes with length, comes with sum. You can just pass in a whole list of any size and let it deal with that problem for you. So if I want to now print out this average, I can print out average colon, and then I'll plug in my average string for a variable for interpolation. Let me make this an f string so that it gets formatted. And let me just run Python of scores.py. And there's my average. It's sort of rounding weird because we're still vulnerable to some floating point imprecision. But at least I didn't need loops and I didn't have to write all this darn code just to do something that, you know, Excel and Google Spreadsheets can just do like that. Well, Python is closer to those kinds of tools, but more powerful in that you can manipulate the data yourself. How about, though, if I want to get a bunch of scores manually from the user and then sum them together? Well, let's combine a few ideas here. How about this? First, let me go ahead and import the CS50 getInt function from the CS50 library, just so we don't have to deal with try and accept or all of that. And let me go ahead and give myself an empty list. And this is powerful. In C, there's no point to an empty array, because if you create an empty array with square bracket notation, like, it's not useful for anything. But in Python, you can create it empty, because Python will grow and shrink the list for you automatically as you add things to it. So if I want to get 3 scores from the user, I could do something like this. For I in range of 3. And then I can grab a variable called score or anything. I could call getInt, prompt the human for the score that they want to type in. And then once they do, I can do this, thinking back to our object-oriented programming capability now. I could do scores dot append, and I can append that score to it. And you would only know this from having read the documentation, heard it in class in a book or whatnot. But it turns out that just like strings have functions like lower built into them, lists have functions like append built into them that just literally appends to the end of the list for you. And Python will grow or shrink it as needed. No more malloc or realloc or the like. So this just appends to the scores array, the scores list, that score, and then again and again and again. So the array starts at, the list starts at size 0, then grows to 1, then 2, then 3, without you having to do anything else. And so now down here, I can compute an average with the sum of those scores divided by the length of the total number of scores. And to be clear, length is the total number of elements in the list. Doesn't matter how big the values themselves are. Now I can go ahead and print out an f string with something like average, colon average in curly braces. And if I run python of scores.py, I'll type in, just for the sake of discussion, the 3 values. I still get the same answer. But that would have been painful to do in C unless you committed in advance to a fixed size array, which we already decided weeks ago was annoying, or you grew it dynamically using malloc or realloc or the like. All right, what else can I do? Well, there's some nice things you might as well know exist. Instead of scores.append, you can do slight fanciness like this. Like if you want to append something to a list, you can actually do plus equals and then put that thing in a temporary list of its own and just use what is essentially concatenation, but not concatenation of strings, but concatenation of lists. So this new line 6 appends to the scores list this tiny little list I'm temporarily creating with just the current new score. So just another piece of syntax that's worth seeing that allows you to do something like that as well. All right, well, how about we go back to strings for a moment? And all of these examples, as always, are on the course's website afterward. Suppose we want to do something like converting characters to uppercase. Well, to be clear, I could do something like this. Let me create a program called uppercase.py. Let me prompt the user for a before string, as by using the input function or getString, which is almost the same. And I'll prompt the user for a string beforehand. Then let me go ahead and print out, how about the keyword after, and then end the new line with nothing, just so that I can see before on one line and after on the next line. And then let me do this. And here's where Python gets pleasant too with loops. For C in before, print c.upper end equals quote unquote, and then I'll print this here. All right, that was fast, but let's try to infer what's going on. So line 1 just gets input from the user, stores it in a variable called before. Line 2 literally just prints after, but doesn't move the new line, the cursor to the next line. What it then does is this. And in C, this was a little more annoying. You needed a for loop with I. You needed array notation with the square brackets. But Python, if you say for variable in string, so for C, for character in string, Python's going to automatically assign C to the first letter that the user types in. Then on the next iteration, the second letter, the third letter, and the fourth. So you don't need any square bracket notation. You just use C, and Python will do it for you and just hand you back one at a time each of the letters that the user has typed in. So if I go back over here and I run, for instance, python of uppercase.py, and I'll type in, how about David in all lowercase and hit enter, you'll now see that it's all uppercase instead by iterating over it, indeed one character at a time. But we already know, thanks to object-oriented programming, strings themselves have the functionality built in to not just uppercase single characters, but the whole string. So honestly, this was a bit of a silly exercise. I don't need to use a loop anymore like in C. And so some of the habits you've only just developed in recent weeks, it's time to start breaking them when they're not necessary. I can create a variable called after, set it equal to before dot upper, which indeed exists, just like dot lower exists. And then what I can go ahead and print out is, for instance, let's get rid of this print line here and do it at the end, after, and print the value of that variable. So now if I rerun uppercase.py, type in David in all lowercase, I can just uppercase the whole thing all at once, because again, in Python, you don't have to operate on characters individually. Questions on any of these tricks up until now? No? All right, how about a few other techniques that we saw in C that we'll bring back now in Python? So it turns out in Python, there are other libraries you can use too that unlock even more functionality. So in C, if you wanted command line arguments, you just change the signature for main to be void, instead of void, to be int argc, comma, string argv, open brackets for an array, or char star eventually. Well, it turns out in Python that if you want to access command line arguments, it's a little simpler, but they're tucked away in a library, otherwise known as a module called sys, the sys or system module. Now, this is similar in spirit to the CS50 library in that it's got a bunch of functionality built in, but this one comes with Python itself. So if I want to create a program like greet.py in VS Code here, let me go ahead and do this. From the sys library, let's import argv. And that's just a thing that exists. It's not built into main because there is no main per se anymore. So it's tucked away in that library. And now I can do something like this. If the length of argv equals 2, well, let's go ahead and print out something friendly like hello, comma, argv bracket 1, and then close quotes. Else, if the length of argv is not equal to 2, let's just go ahead and print out hello world. Now, at a glance, this might look a little cryptic, but it's identical to what we did a few weeks ago. When I run this Python of greet.py with no arguments, it just says hello world. But if I instead add a command line argument, like my first name, and hit enter, now the length of argv is no longer 1, it's going to be 2. And so it prints out hello David instead. So the takeaway here is that whereas in C, argv technically contained the name of your program, like /hello or /greet, and then everything the human typed. Python's a little different in that because we're using the interpreter in this way, technically when you run Python of greet.py, the length of argv is only 1. It contains only greet.py. So the name of the file, it does not unnecessarily contain Python itself, because what's the point of that being there omnipresently? It does contain the number of words that the human typed after Python itself. So argv is length 1 here, argv is length 2 here, and that's why when it did equal 2, I saw hello David instead of the default hello world. So same ability to access command line arguments, add these kinds of inputs to your functions, but you have to unlock it by way of using argv instead in this way. If you want to see all of the words, you could do something like this. Just as if we combine ideas here, for I in range of, how about length of argv, then I can do this, print argv bracket I. All right, a little cryptic. But line 3 is just a for loop, iterating over the range of length of argv. So if the human types in 2 words, the length of argv will be 2. So this is just a way of saying iterate over all of the words in argv, printing them one at a time. So Python of greet.py, enter, just prints out the name of the program. Python of greet.py with David prints out greet.py and then David. I can keep running it, though, with more words, and they'll each get printed one at a time. But what's nice, too, about Python, and this is the point of this exercise, honestly, this looks pretty cryptic. This is not very pleasant to look at. If you just want to iterate over every word in a list, which argv is, watch what I can do. I can do for arg, or any variable name, in argv. Let me just now print out that argument. I could keep calling it I, but I seems weird when it's not a number, so I'm changing to arg as a word instead. If I now do Python of greet.py, it does this. If I do Python of greet.py David, it does that again. David Malin, it does that again. So this is, again, why Python is just very appealing. You want to do something this many times, iterate over a list, just say it. And it reads a little more like English. And there's even other fanciness, too, if I may. It's a little stupid that I keep seeing the name of the program, greet.py. So it'd be nice if I could remove that. Python also supports what are called slices of arrays. Slices of lists. Even I get the terminology confused. If argv is a list, then it's going to print out everything in it. But if I want a slice of it that starts at location 1 all the way to the end, you can use this funky syntax in between the square brackets, which we've not seen yet, that's going to start at item 1 and go all the way to the end. And so this is a nice, clever way of slicing off, if you will, the very first element, because now when I run greet.py David Malan, I should only see David and Malan. If I only want one element, I could do 1 to 2. If I want all of them, I could do 0 onward. I could give myself just one of them in this way, so you can play with the start value and the end value in this way to sort of slice and dice these lists in different ways. That would have been a pain in C just because we didn't really have the built-in support for manipulating arrays as cleanly as this. All right, just so you've seen it too, though this one is less exciting to see live, if I go ahead and create a quick program here, it turns out there's something else in the sys library, the ability to exit programs, either exiting with status code 1 or 0, as we've been doing anytime something goes right or wrong. So for instance, let me whip up a quick program that just says if the length of sys.argv does not equal 2, then let's yell at the user and say, you're missing a command line argument. Otherwise, command line argument. And let's then return sys.exit1. Else, let's go ahead and logically just say print a formatted string that says hello as before, sys.argv1. Now, things look different all of a sudden, but I'm doing something deliberately. First, let's see what this does. So on line 1, I'm importing not argv specifically. I'm importing the whole sys library. And we'll see why in a second. Well, it turns out that this argv, the sys library, has not only the argv list, it also has a function called exit, which I'd like to be able to use as well. So it turns out that if you import a whole library in this way, that's fine, but you have to refer to the things inside of it by using that same library's name and a dot to sort of namespace it, so to speak. So here I'm just saying if the user does not type in 2 words, yell at them with missing command line argument and then exit with 1. Just like in C, when you do exit 1, just means something went wrong. Otherwise, print out hello to this. And this is starting to look cryptic, but it's just a combination of ideas. The curly braces mean interpolate this value, plug it in here. Sys.argv is just the verbose way of saying go into the sys library and get the argv variable therein. And bracket 1, of course, just like arrays in C, is just the second element at the prompt. So when I run this version now, Python of exit.py, with no arguments, I get yelled at in this way. If, however, I type in 2 arguments total, the name of the file and my own name, now I get greeted with hello, David. And it's the same idea before. This was a very low-level technique, but same thing here. If you do echo $? Enter, you'll see the exit code of your program. So if I do this incorrectly again, let me rerun it without my name, enter, I get yelled at. But if I do echo $? There's the secret one that's returned. Again, just to show you parity with C in this case. Questions now on any of these techniques here? All right, how about something that's a little more powerful too? We spent so much time in week 0 and 1 doing searching and then eventually sorting in week 3. Well, it turns out Python can help with some of this too. Let me go ahead and create a program called names.py that's just going to be an opportunity to maybe search over a whole bunch of names. Let me go ahead and import sys. And then just so I have access to exit. And let me go ahead and create a variable called names that's going to be a list with a whole bunch of names. How about here? Charlie and Fred and George and Ginny and Percy and lastly Ron. So a whole bunch of names here. And it'd be a little annoying to implement code that iterates over that from left to right in C, searching for one of those names. In fact, what name? Well, let's go ahead and ask the user to input the name that they want to search for so that we can tell them if the name is there or not. And we could do this similar to C in Python, doing something like this. So for n in names, where n is just a variable to iterate over each name, if how about the name I'm looking for equals the current name in the list, aka n, well, let's print out something friendly like found. And then let's do sys.exit0 to indicate that we found whoever that is. Otherwise, if we get all the way to the bottom here outside of this loop, let's just print not found, because if we haven't exited yet, and then let's just exit with 1. Just to be clear, I can continue importing all of sys, or I could do from sys import exit, and then I could get rid of sys dot everywhere else. But sometimes it's helpful to know exactly where functions came from. So this too is just a matter of style in this case. All right, so let's go ahead and run this. Python of names.py, and let's look for like Ron all the way at the end. All right, he's found. And let's search for someone outside of the family here, like Hermione, not found. OK, so it seems to be working in this way. But I've essentially implemented what algorithm? What algorithm would this seem to be per lines 7 and 8 and 9 and 10? Yeah, so it's just linear search. It's a loop, even though the syntax is a little more succinct today. And it's just iterating over the whole thing. Well, honestly, we've seen an even more terse way to do this in Python. And this, again, is what makes it a more pleasant language sometimes. Why don't I just do this? Instead of iterating one at a time, why don't I just say this? Let me go ahead and change my condition to just be, how about if the name we're looking for is in the names list, we're done. We found it. Use the in preposition that we've seen a couple of times now that itself asks the question, is something in something else? And Python will take care of linear search for us. And it's going to work exactly the same. If I do Python of names.py, search for Ron, it's still going to find him. And it's still going to do it linearly in this case. But I don't have to write all of the lower level code myself in this case. Questions now on any of this? The code's just getting shorter and shorter. Now, what about, let's see, what else might we have here? How about this? It turns out, let's go ahead and implement that phone book that we started metaphorically with in the beginning of the course. Let's code up a program called phonebook.py. And in this case, let's go ahead and let's create a dictionary this time. Recall that a dictionary is a little something that implements something like this, like a 2-column table that's got keys and values, words and definitions, names and numbers. And let's focus on the last of those, names and numbers in this case. Well, I claimed earlier that Python has built-in support for dictionaries, dict objects that you can create with one line. I didn't need it for Speller because a set is sufficient when you only want one of the keys or the values, not both. But now I want some names and numbers. So it turns out in Python, you can create an empty dictionary by saying dict open parenthesis close, and that just gives you essentially a chart that looks like this with nothing in it. Or there's more succinct syntax. You can alternatively do this with 2 curly braces instead. And in fact, I've been using a shortcut all this time. When I had a list earlier where my variable was called scores, and I did this, that was actually the shorthand version of this. Hey, Python, give me an empty list. So there's different syntax for achieving the same goal. In this case, if I want a dictionary for people, I can either do this or, more commonly, just 2 curly braces like that. All right, well, what do I want to put in this? Well, let me actually put some things in this. And I'm going to just move my close curly brace to a new line. If I want to implement this idea of keys and values, the way you do this in Python is key, colon, value, comma, key, colon, value. So you'd implement it more in code. So for instance, if I want Carter to be the first key in my phone book, and I want his number to be +1 617 495 1000, I can put that as the corresponding value. The colon is in between. Both are strings or strs, so I've quoted both deliberately. If I want to add myself, I can put a comma. And then just to keep things pretty, I'm moving the cursor to the next line. But that's not strictly required aesthetically. It's just good style. And here I might do +1 949 468 2750. And now I have a dictionary that essentially has 2 rows here, Carter and his number, and David and his number as well. And if I kept adding to this chart would just get longer and longer. Suppose I want to search for one of our numbers. Well, let's prompt the user for the name for whose number you want to search by getting string. Or you know what? We don't need the CS50 library. Let's just use input and prompt the user for a name. And now we can use this super terse syntax and just say if name in people print the formatted string number, colon, and here we can do this, people bracket name. OK, so this is getting kind of cool, kind of quickly, kind of confusingly. So let me run this. Python of phonebook.py. Let's type in Carter, and indeed I see his number. Let's run it again with David, and I see my number here. So what's going on? Well, it turns out that a dictionary is very similar in spirit to a list. It's actually very similar in spirit to an array in C, but instead of being limited to keys that are numbers, like bracket 0, bracket 1, bracket 2, you can actually use words. And that's all I'm doing here on line 8. If I want to check for the name Carter, which is currently in this variable called name, I can index into my people dictionary using not a number, but using literally a string, the name Carter or David or anything else. To make this clear too, notice that I'm at the moment using this format string, which is adding some undue complexity, but I could clarify this perhaps further as this. I could give myself another variable called number, set it equal to the people dictionary, indexing into it using the current name, and now I can shorten this to make it clearer that all I'm doing is printing the value of that. And in fact, I can do this even more cryptically if this would be weird to do, but if I only ever want to show David's phone number and never Carter's, I can literally, quote unquote, index into the people dictionary, because now when I run this, even if I type Carter, I'm going to get back my number instead. But that's all that's happening if I undo that, because that's now a bug, but I index into it using the value of name. Dictionaries are just so wonderfully convenient because now you can associate anything with anything else, but not using numbers, but entire keywords instead. So here's how if in Speller we gave you not just words, but hundreds of thousands of definitions as well, you could essentially store them as this, and then when the human wants to look up a definition in a proper dictionary, not just for spell checking, you could index into the dictionary using square brackets and get back the definition in English as well. Questions on this? Yeah?
Is the way that this code does it, because I know you're saying that Python has functions already made for you, is the if preposition actually iterate through an array to find the value? Or because you're calling the value here, it must still find a way to go to location and find it?
A really good question. So to summarize, how is Python finding that name within that dictionary? This is where, honestly, Speller and pset 5 is what Python's all about. So you are struggling with implementing your own spell checker and implementing your own hash table. And recall that per last week, the goal of a hash table is to ideally get constant time access, not something linear, which is slow, and even better than something logarithmic like log base 2 of n. So Python and the really smart people who invented it, they have written the code that does its best to give you constant time searches of dictionaries. And they're not always going to succeed, just as you in your own problem set probably going to have some collisions once in a while and start to have chains of linked lists of words. But this is where, again, you defer to someone else, someone smarter than you, someone with more time than you to solve these problems for you. And if you read Python's documentation, you'll see that it doesn't guarantee constant time, but it's going to ideally optimize the data structure for you to get as fast as possible. And of all of the data structures, like a dictionary, a hash table is really like the Swiss Army knife of computing, because it just lets you associate something with something else. And even though we keep focusing on names and numbers, that's a really powerful thing, because it's more powerful than lists and arrays, which are only numbers and something else. Now you can have any sorts of relationships instead. All right, let me show a few other examples before we culminate with some more powerful techniques in Python thanks to libraries. How about this problem we encountered in week 4, which was this? Let me code up a program called, again, compare.py here. But this time, compare two strings and not numbers. So let me, for instance, get one string from the user called s. Just for the sake of discussion, let me get another string from the user called t, so that we can actually do some comparison here. And if s equals t, let's go ahead and print out that they're the same. Else, let's go ahead and print out that they're different. So this is very similar to what we did in week 4. But in week 4, recall, we did this specifically because we had encountered a problem. For instance, if I run, what's going on? Input T. Come on. Oh, OK. Wow. OK. Long day. All right. If I run the proper command, Python of compare.py, then let's go ahead and type in something like cat in all lowercase, cat in all lowercase, and they're the same. If, though, I do this again with dog and dog, they're the same. And of course, cat and dog, they're different. But does anyone recall from 2 weeks ago when I typed in my name twice, both identically capitalized, what did it say? That they were, in fact, Different. And why was that? Like, why were two strings in C different, even though I typed literally the same thing? Two different places in memory. So each string might look the same aesthetically, but of course was stored elsewhere in memory. And yet Python appears to be using the equality operator, equals equals, like you and I would expect as humans, actually comparing for us char by char in each of those strings for actual equality. So this is a feature of Python in that it's just easier to do. And why? Well, this derives from the reality that in Python there are no pointers anymore. There's no underlying memory management. It's not up to you now to worry about those lower level details. The language itself takes care of that for you. And so similarly, if I do this and don't ask the user for two strings, but just one, and then I do something like this, how about give myself a second variable t, set it equal to s.capitalize, which note is not the same as upper. Capitalize by design per Python's documentation will only capitalize the first letter for you. I can now print out, say, two f strings here, what the value of s is. And then let me print out with another f string what the value of t is. And recall that in C, this was a problem because if you capitalize s and store it in t, we accidentally capitalized both s and t. But in this case, in Python, when I actually run this and type in cat in all lowercase, the original s is unchanged, because when I use capitalize on line 3, this is indeed capitalizing s, but it's returning a copy of the result. It cannot change s itself because, again, for that technical term, s is immutable. Strings, once they exist, cannot be changed themselves, but you can return copies and modified, mutated copies of those same strings. So in short, all of those headaches we encountered in week 4 are now solved really in the way you might expect. And here's another one that we dwelled on in week 4 with the colored liquid in glasses. Let me code up a program called swap.py. And in swap.py, let me set x equal to 1, y equal to 2. And then let me just print out an f string here. So how about x is this, comma, y is that. And then let me do that twice just for the sake of demonstration. And in here, recall that we had to create a swap function, but then we had to pass it in by reference with the ampersand. And like, oh my God, like that was kind of peak complexity in C. Well, if you want to swap x and y in Python, you could do x comma y equals y comma x. And now Python of swap.py, and there we go. All of that's handled for you. It's sort of like a shell game without even a temporary variable in mind. So what more can we do here? How about a few final building blocks? And these related now to files from that week 4. Suppose that I want to save some names and numbers in like a CSV file, comma separated values, which is like a very lightweight spreadsheet. Well, first, let me create a phonebook.csv file that just has name, comma, number as like the first row there. But after that, I'm going to go ahead now and code up a phonebook.py program that actually allows me to add things to this phone book. So let me split my screen here so that we can see the old and the new. And down here in my code for phonebook.py, in this new and improved version, I'm going to actually import a whole other library, this one called CSV. And here too, especially for people in data science and the like, really like being able to manipulate files and data that might very well be stored in spreadsheets or CSVs, comma, separated values, which we saw briefly in week 4. In phonebook.py then, it suffices to just import CSV after reading the documentation therefore, because this is going to give me functionality in code related to CSV files. So here's how I might open a file in Python. I literally call open. It's not fopen now. It's just open. And I open this file called phonebook.csv. And just as in C, I'm going to open it in append mode. Not write, where it would change the whole thing. I want to append, new line at a time. After this, I want to get maybe, how about a name from the user? So let's prompt the user for some input for their name. And then let's prompt the user for a number as well using input, prompting for number. All right, and now this is a little cryptic, and you'd only know this from the documentation. But if you want to write rows to a CSV file that you can then view in Excel or the like, you can do this. Give me a variable called writer, but I could call it anything I want. Let me use a csv.writer function that comes with this CSV library, passing in the file. This is like saying, hey, Python, treat this open file as a CSV file so that things are separated with commas and nicely formatted in rows and columns. Now I'm going to do this. Use that writer to write a row. Well, what do I want to write? I want to write a short list, namely the current name and the current number to that file. But I don't want to use fprintf and %s and all of that stuff that we might have had in the past. And now I just want to close the file. Let me reopen my terminal. Let me run Python of phonebook.py. And let me type in, how about David, and then +1 949 468 2750, and crossing my fingers, watching the actual CSV at top left, my code has just added me to the file. And if I were to run it again, for instance, with Carter and +1 617 495 1000, crossing my fingers again, we've updated the file. And it turns out there's code now via which I can even read that file, but I can first tighten this up just so you've seen it. It turns out in Python, it's so common to open files and close them. You know, humans make mistakes, and they often forget to close files, which might then end up using more memory than you intend. So you can alternatively do this in Python so that you don't have to worry about closing files. You can use this keyword instead. You can say with the opening of this file as a variable called file, do all of the following underneath. So I'm indenting most of my code. I'm using this new Python-specific keyword called with. And this is just a matter of saying, with the following opening of the file, do those next 4 lines of code, and then automatically close it for me at the end of the indentation. It's a minor optimization, but this, again, is sort of the Pythonic way to do things instead. How else might I do this too? Well, it turns out that the code I've written here, on line 9 especially, is a little fragile, right? If any human opens this spreadsheet, the CSV file in Excel, Google Spreadsheets, Apple Numbers, and maybe like moves the columns around just because maybe they're futzing, they save it, and they don't realize they've now changed my assumptions, I don't want to necessarily write name and number always in that order, because what if someone screws up and flips those 2 columns by literally dragging and dropping? So it turns out that instead of using a list here, we can use another feature of this library as follows. Instead of using a writer, there's something called a dictionary writer or dict writer that takes the same argument as input, the file that's opened. But now the one difference here is that you need to tell this dictionary writer that your field names are name and number. And let me close the CSV here. Name and number are the names of the fields, the columns in this CSV file. And when it comes time to write a new row, the syntax here is going to be a little uglier, but it's just a dictionary. The name I want to write to the dictionary is going to be whatever name the human typed in. The number that I want to write to the CSV file is going to be whatever the number the human typed in. But what's different now about this code is by simply using a dictionary writer here instead of the generic writer, now the columns can be in this order or any order. And the dictionary writer is going to figure out, based on the first line of text in that CSV, where to put name, where to put number. So if you flip them, no big deal. It's going to notice, oh, wait, the columns changed. And it's going to insert the columns correctly. So just, again, another more powerful feature that lets you focus on real work as opposed to actually getting tied up in the weeds of writing code like this otherwise. Questions on this one as well? But what we will do now is come full circle to some of the more sophisticated examples with which we began. And I'm going to go back over to my own Mac laptop here, where I've got my own terminal window up and running. And I was just going to introduce a couple of final libraries that really speak to just how powerful Python can be and how quickly you can get up and running. To be fair, can't necessarily do all of these things in the cloud, like in code spaces, because you need access to your own speakers or microphone or the like. So that's why I'm doing it on my own Mac here. But let me go ahead and open up a program called speech.py. And I'm not using VS Code here. I'm using a program called VI that's entirely terminal window based. But it's going to allow me, for instance, to import the Python text-to-speech version 3 library. I'm going to give myself a variable called engine that's going to be set equal to the Python text-to-speech 3 libraries init method, which is just going to initialize this library that relates to text to speech. I'm going to then use the engine's say function to say something like, how about hello, comma, world? And then as my last line, I'm going to say engine.run and wait, capitalized as such, to tell my program now to run that speech and wait until it's done. All right, I'm going to save this file. I'm going to run Python of speech.py, and I'm going to cross my fingers as always, and
hello, world.
All right, so now I have a program that's actually synthesizing speech using a library like this. How can I now modify this to be a little more interesting? Well, how about this? Let me go ahead and prompt the user for their name, like we've done several times here using Python's built-in name function. And now let me go ahead and use a format string in conjunction with this library, interpolating the value of name there. And at least if my name is somewhat phonetically pronounceable, let's go ahead and run python of speech.py, type in my name, and
hello, David.
OK, it's a sort of weird choice of inflection, but we're starting to synthesize voice, not unlike Siri or Google Assistant or Alexa or the like. Now we can maybe do something a little more advanced too. In addition to synthesizing speech in this way, we could synthesize, for instance, an actual graphic. Let me go ahead now and do something like this. Let me create a program called qr.py. I'm going to go ahead and import a library called OS, which gives you access to operating system related functionality in Python. I'm going to import a library I've pre-installed called QR code, which is a two-dimensional barcode that you might have seen in the real world. I'm going to go ahead and create an image variable using this QR code library's make function, which per its documentation takes a URL like one of CS50's own videos. So we'll do this with YouTube /XVFZO5PGG0. So hopefully that's the right lecture. And now we've got image.save, which is going to allow me to create a file called qr.ping. Think back now on problem set 4 and how painful it was to save files. We'll just use the save function now in Python and save this as a ping file, portable network graphic. And then lastly, let's just go ahead and open with the command open qr.ping on my Mac so that hopefully this just automatically opens. All right, I'm going to go ahead and just double check my syntax here so that I haven't made any mistakes. I'm going to go ahead and run python of qr.py, enter. That opens up this. Let me go ahead and zoom in. If you've got a phone handy and you'd like to scan this code here, whether in person or online, I apologize. You won't appreciate it. Amazing. OK. And lastly, let me go back into our speech example here, create a final ending here in our final moments. And how about we just say something like this was CS50, like this. Let's go ahead here, fix my capitalization just for tidiness, get rid of the name. And now with our final flourish and your introduction to Python equipped, here we go.
This was CS50.
All right, we'll see you next time. right, this is CS50, and this is already week 7. And this is the week where we'll continue where we left off with Python, introducing you to a bit more syntax and capabilities of the language so you can solve like interesting problems. But a lot of those problems increasingly are now going to involve data in some form. After all, if you think of most any website or mobile app or process nowadays that involves solving problems, it almost always involves some amount of data, and often data at scale, lots and lots of data. And so what we're going to see first today is that, yes, you can use Python to solve all the problems past that we've seen, and also some data-specific ones, but sometimes it's just going to be annoying. It's going to be a little painful. It's just going to be more work than you might like to just get to some answer. And so today we'll, too, introduce you to a new language called SQL, Structured Query Language. And this is a language that, rest assured, is actually much smaller, relatively speaking, than C and Python. It sort of does less, but it does it really well. And it's a language for querying databases, storing data in it, updating it, inserting it, deleting it, and so much more. And it's the kind of technology that's used nowadays in, indeed, web apps and mobile apps, data science, analytics, and so much more. It's really good at storing lots and lots of data. Now, this is yet another language. And believe it or not, next week we'll introduce you to 3 more languages, HTML and CSS, which are not technically programming languages. They're all about aesthetics and markup of information, but also JavaScript, which is, in fact, a programming language. But the goals here in CS50 really are going to be to empower you to program more generally. And indeed, when you're out there in the real world, some years from now, invariably, there's going to be some new, other popular language out there. And hopefully, in this week and next week and beyond, among the goals is not just to teach you these languages specifically, but again, like how to teach yourself the future languages that we've not even heard about just yet. So with that said, let's begin with a survey of sorts. If you go to this URL on your phone or laptop, cs50.ly/favorites, a very simple Google form awaits you that's just going to ask you a couple of multiple choice questions. So go to cs50.ly/favorites, and that should lead you to a Google form that looks a little something like this, asking you first, as of now in week 7, what is your favorite language among those options here? And then further down, one more question. If you think back on problem sets 0 through 6, what was, if any, your favorite problem set problem, be it in Scratch or C or Python? So answer those 2 questions. And in a moment, I'll flip over to my screen here where you'll see, and anyone who's used Google Forms knows, the spreadsheet that's collecting now this data. Microsoft Office 365 can do the same if you use one of those forms. And what you see here now is a spreadsheet in Google Sheets enumerating all of the audience's questions. Language is in column B, problem is in column C, and each row represents one student who has responded. A few of you were super eager for class today at 8:33 a.m. Eastern Time, 10:32, 11:10. OK, so now we're getting into the actual class time here. And if I scroll down, we'll probably see a few dozen, couple hundred answers by now. And yeah, so we're getting a whole lot of answers here, and I'm seeing some patterns emerge, but it's not necessarily obvious to the human eyes what those patterns are. Now, of course, you can use Google Spreadsheets. You can like highlight the data, and you can create charts magically out of it. But you can only do what Google lets you do with the data. And same thing for Microsoft Excel or Apple Numbers. But wouldn't it be nice to just be able to manipulate the raw data, relatively simple though it is, to just answer questions about the data? Maybe long-term create your own charts, customize it just the way you want, rather than beholden to like software that's off the shelf like this. Well, how could we go about doing this? Well, let me propose that we treat this data set now as what we're going to call, for now, a flat file database. We'll see today that there's fancier databases, but the simplest database in the world is really just like a .csv file. And we saw that a couple of weeks ago in C. We wrote a bit of C code that used fprintf to write data to a file using commas as the separator. We didn't really do much more with CSVs at the time, though, because it's really annoying, painful, time-consuming, not fun to use C for something like that because of malloc and memory and all of that stuff. But with Python, it's going to be much easier. And so anytime you have access to some data set where you can just like download it to your own Mac or PC or your cloud environment, it's sort of a candidate for now writing code to do something with the data. Maybe analyze it right away. If it's been human inputted manually, maybe you have to clean it up by doing a lot of find and replace, but not with your keyboard, but rather with code. And so let me go ahead and do this. Let me go back to my Google Sheet here that has all of the data that's come in now. And let me go ahead and download this via the File menu here. And let's see, download. And you can see a whole bunch of options. If most formats might be familiar, but today we'll focus just on this one, comma, separated values, or CSV. That's going to go ahead and download it on my Mac here into my own downloads folder. And now I'm going to go ahead and do this. Let me go ahead and pull up VS Code in the cloud here. And if you've never done this before, there's a couple of ways to do it. But the simplest way to upload a file to your code space, so to speak, is just to sort of drag and drop. That's going to magically upload it to the server there. And we'll see that, one, it has a very long file name, which I'm actually going to clean this up because that's going to be very tedious to type in my code. So I could either right-click, of course, up here, but I'm going to use my Linux command. So let's move this file called CS50 2022 something or other, and let's just name it more simply favorites.csv. So all lowercase, no spaces, sort of good basics. And let me go ahead now and open up this file with code favorites.csv. I'll close my file explorer, and we'll see exactly the same data as before, but not quite as pretty as Google Sheets makes it be. Rather, we see here that I still have 3 columns, timestamp, language, problem, and then all of the values down below, including the timestamps and the answers therefore, but it doesn't have proper columns. It just has commas separating them. Now, we could very easily write Python code, just like we wrote C code, to manipulate files like this, either to write or read. But instead, let's do something that's a little more pleasant, which is indeed in the form of Python. So Python actually comes with native support for CSVs. It has indeed a package called CSV that just lets you read and write and do a whole bunch of useful stuff when it comes to CSV files. So let's go ahead and do something with this file. Let me go back here to VS Code. I'm going to close favorites.csv for now, but just remember in your mind that timestamp was the first column, language was the second column, and problem was the third. And notice because we're using commas, they don't, again, line up perfectly, but that's not a problem. There are 2 commas in every line, presumably. And I'm going to go ahead and now create a file called, how about, favorites.py, so that I can start writing some code to manipulate this data. And let's do something simple. Let's just write a simple program in Python that opens this file, reads it, and prints something out, just as like a safety check that I know what I'm doing, even though it's not going to be useful. So in Python, if you want CSV support, you import CSV. And that gives you access to all the magical capabilities thereof. Let me now go ahead and use this technique to open a file in Python, which is similar in C. But with Python, I'm going to do this. The keyword with. I'm going to open a file called favorites.csv, which was the shorter name I gave it. This is optional, but just for explicitness, I'm going to open it in read mode explicitly, just like fopen took a second argument as well. And I'm going to name this file, once opened, quite simply file, though I could call it anything I want. And now it's just an open file. So far as Python knows at this moment, it's just text, or better yet, it's just zeros and ones. If you want this Python package called CSV to actually do something useful with it, you have to load this file now into the library. And the simplest way to do this is to give myself like a variable called reader, because I want to read this file, though this too I could call anything else. I'm going to then set that equal to the return value of a function called csv.reader, and I pass to that, per the documentation, the open file. So step 1, I open the file, and this just gives me access to the bytes therein. Step 2 now, with csv.reader, tells the Python package called CSV to do something useful with it and start analyzing the commas and allow me to parse it further. So let's go ahead and do this. Let me go ahead now, and within this loop, let's say this. Within this open file, let's do this. For every row, if you will, or line in the file, aka reader, let's go ahead and print out just, how about, row bracket 1. Now, what's going on here? Well, it turns out if you read the documentation for the CSV reader function, what it hands you back is essentially this special object, so to speak, that allows you to treat it as though it's just a really big list of lines from the file, aka reader. So by saying for row in reader, this is a way more succinct way of saying, give me the first line in the file, plus plus. Give me the second line in the file, plus plus, and so forth. That we would have done much more mechanically in C. This is just much more Pythonic and English friendly, if you will. So in every iteration of this loop, row is going to contain all of the data from the current row. But better yet, what the reader function does for me is it hands me each row not just as a big string or str of text in Python. It gives me what, apparently, based on the syntax on line 6? Any instinct? Yeah. It's giving me back indeed a list. And I presume the visual clue for you was the fact that we're using square brackets here. And indeed, row bracket 1 is going to be not the first, but the second element in that list. And so just take a guess. When I run this code in a moment, what's going to get printed? The timestamp, the language, or the problem? The language, because it's the second column that is in the file delimited by those commas. So let me go ahead and do this. Let me clear my terminal down here. Let me run Python of favorites.py and enter. And there's everything. It was super fast, but there's a really long list here. And in fact, if I increase the size of my terminal and start scrolling up, you'll just see all of the raw data. Now, this isn't that useful yet. I could have just glanced at the CSV, but clearly now I have the ability to open the file, parse it, so to speak, that is, break it up into its constituent parts, and do something with specific parts therein. All right, so if I want to do this a little more pleasantly, though, let me at least make this semantically a little cleaner. And you know what? Just for clarity, let me just give myself a variable. It's not strictly necessary, but I know that this is the favorite, for instance, language. So let's just call it favorite, set it equal to row bracket 1. And now just to be more explicit in my code, even though, again, we don't need the variable per se, this code's, of course, going to do the same thing. It's just using an additional variable called favorite. If I go down here, scroll up, run the program again, I get back the exact same data. But this is a stepping stone to something that's even more powerful about Python support for CSV files, is that you don't have to just treat the return value as a list with 0 and 1 and 2. So just thinking intuitively here, why is this maybe not the best design to hand you, the programmer, back the data in a list that's numerically indexed with 0, 1, 2? It clearly works, but critique this. What could go wrong? What's a little poorly designed? Yeah.
You have to always remember like what the things are, like what the order is.
Yeah.
Language, and then I forgot the last.
Exactly. So it's up to you to repeat. It's up to you to remember like what column the data is actually in. And God forbid you're collaborating with someone else on the spreadsheet. If you've used Google Spreadsheets, you can move columns around, maybe just because you want to visually reorganize things. And if you do this, and then someone else downloads that same data, all of their code is going to break. So that's just really bad design. It's fragile just because you're sort of on the honor system that 1 means the data that you want. So wouldn't it be nice if we could be a little more explicit? Well, recall that the very first line in this file is actually this. And I paused the output this time so that we can see more optionally. I just reran favorites.py. And notice one of these things is not like the other. Every output was either Scratch or C or Python, except for this first one. Why am I seeing the word language here? Where did language come from? You didn't have the ability to manually input. Oh, no? Where did it come from? Yeah. Yeah, the header, the very first row in the file, which by human convention generally just defines what the columns represent so that there's some human useful information there. Now, that's not really intended to be part of my output at the moment. So there is a way to skip this. If you want to skip the first row, you can actually do something like this. You can say next row, and that will just ignore that row so that I'm starting really with every row thereafter. But there's a better way to handle this than that. That will get rid of the row in the output. But let me go ahead and use a different feature of the CSV package that's just going to make this a little cleaner altogether. So let me clear my terminal window here. Let me undo this next thing that I just added. And instead of using a reader, let me go ahead and use a dictionary reader, abbreviated dict reader, that's going to now return me the equivalent of all of the rows, one at a time. So I can still call it reader just as before. But as the name implies, what this reader is going to return is not a list after list after list, but a dictionary, a dictionary, a dictionary. And remember, a dictionary is just a collection of key value pairs. So what does that mean? What are the keys? What are the values? Well, now that I'm using a dictionary reader, I can actually do this. Instead of sort of on the honor system remembering that I want column 1, I can treat row now, not as a list, but as a dictionary. And that means I can go in here and say, quote unquote, language. And we saw that back in week 6. Python allows you to index into dictionaries using square bracket notation in strings, or strs on the inside, just like lists allow for numbers. But this now, I think, is going to be a little more robust. If I run this again, Python of favorites.py, all of that worked out fine. And let me pause the output too by using this program called more. Now I don't even see the header. So now whoever works with Python wrote the code for this package to just analyze that first line of code, use the header, as you just called it, as the keys. And then every time you iterate through this loop, it updates the values, but the keys stay the same. Any questions then on this technique? Suffice it to say, this would be painful in C. Yes? Exactly. So the keys are always going to be, quote unquote, timestamp, language, and problem. But on each iteration of this loop here, the row is going to contain a different row of values, different row of values, different row of values. So you're going to get back one dictionary for every student who submitted the Google form, if you will, while iterating through it there. All right, so once we have this ability here, why don't we go ahead and transition to, how about not just using that dictionary reader, which makes the code a little more robust, because now if you move the columns around, no big deal. It doesn't matter if the numeric indices change. You can still use those keywords instead. But let's actually analyze the data now. I'm just spitting it out, which is not solving any problems for anyone. So let's go ahead and count the popularity of Scratch, C, and Python and see what everyone's been thinking here. All right, so how might I do this? Well, let me go ahead and do this up here. Before I start iterating, let me give myself, let's say, 3 variables. And to keep things simple, I'll say one variable called Scratch, set it equal to 0 for 0 students so far. C is going to equal 0, and Python is going to equal 0. There's a slightly prettier way of doing this, just because this is like 3 lines of code to do something very simple. You could alternatively, in Python, but not C, do Scratch, comma, C, comma, Python equals 0, comma, 0. So kind of slightly more elegant, just to fit it all into one line. But now let's just do something more interesting. On line 7, I'm still going to figure out what the current favorite language is. And now I'm just going to do some conditional checks. How about if that favorite equals, quote unquote, Scratch? Let's go ahead and increment Scratch by 1. We can't do plus plus in Python, but we can do plus equals 1. How about elif favorite equals C? Then let's do C plus equals 1. We could do else. This is actually a good design question. Should I do else? Should I do elif? Any instincts here? Yeah. Yeah, really good instincts. Just in case someone goes and adds another language to the form next week, because we're obviously going to introduce another language today, you don't want your code to now artificially inflate the scores for Python just because you're conflating multiple languages together. So the more defensive, sort of better way to write this code, I agree, would be elif favorite equals Python. Then let's go ahead and increment Python plus equals 1. And if there's a new language next week, we're obviously going to have to update the code, but at least we're not miscounting. We're just missing the new language. So I think that's slightly more robust. All right, now at the very bottom of this program and outside of the loop, when I'm all done counting, let me go ahead and print out using some f strings. How about the total number of people whose favorite is Scratch? So this is just week 6 f string syntax. Let me go ahead and print out another f string for C. And I'm, of course, putting the variables in curly braces, all lowercase, but the English words I'm doing capitalization for. Let's do a final one with f, Python, colon, and then in curly braces, Python, close quote. And I think I'm done. So let me just hide my terminal for a second. Here's the total program. Same stuff as before. Open favorites.csv. Open it further with the dictionary reader to do that processing for us. Initialize 3 variables to 0 just so we have something to count with. And then iterate over the file row by row. And this is just some sort of week 1 style conditional logic, albeit in Python, counting things. All right, so how can we now execute this? Let me go back to my terminal, Python of favorites.py. And here we go. As of today, everyone who's reporting in live via the Google form, their favorite languages are... Interesting. That's pretty interesting, too, after just 1 week of Python, no less. But Scratch is a healthy contender there, a lot of C, so a pretty good mix here. So is this going to be the best way to write this program long term? Well, as you noted, if there's a new language next week, this week, we're going to have to constantly update this. And here's where you should let your mind wander to like the future. Like if we have a 4th language, 5th language, 6th, 7th, 8th, which aspect here might kind of have some code smell to it. Like this probably isn't the best design to set us up for the future. What might be better than this? Yeah? Yeah, we have to keep adding a language to line 5. And OK, not a big deal. We could add like SQL today and maybe JavaScript next week. But anytime a line of code, a line of logic is just going to kind of grow out of control, and we've had this chat a couple of times with different syntax, there's probably a better way than that. So let's do that. Instead of using these individual variables, we could maybe use a list. But a list would be a little confusing because, like, what does bracket 0 mean? What does bracket 1, bracket 2? But a dictionary, recall, is like this Swiss Army knife of data structures whereby you can associate anything with anything else, keys with values. So I dare say a cleaner way to solve this problem that sets us up for less work or confusion later would be to create like a new variable called counts, if that's what we're doing, counting things up, and just set it equal to an empty dictionary. And you can literally say dict with the open parenthesis, close parenthesis, and nothing. Or the more Pythonic, just use open and close curly braces with nothing inside. That gives me an empty dictionary, just like square brackets gives me a list. Now, my logic down here has to change a little bit. But what's nice is I don't need one conditional for every language. Because again, if we have a fourth, a fifth, a sixth, that chunk of code is also going to grow a bit out of control too. So I can get rid of this here. And what I think I'm going to do is say this. Whatever the current favorite is from the current row in the file, why don't we go into our counts variable at that key. And again, favorite is a variable. It's not quote unquote favorite. It's going to be Scratch or C or Python. And then why don't we go ahead and just increment whatever the value of that count is at that key. Now, this is technically buggy. We're really close, but there is a bug. Does anyone want to conjecture what the bug is? Yeah?
Well, this is more a question, but like, will that automatically add a new key value pair for each favorite, for each like language?
A good question that answers my question nonetheless. So no, like the magic you described will not happen. And to repeat the hypothesis, will this automatically create a key for every language that we try plugging into those square brackets? Short answer, no. Odds are this is going to create a key error, one of those traceback error messages that you've probably seen by now, either in class or in problem sets, whereby if Scratch hasn't appeared in the dictionary before, or C or Python, then the dictionary has no clue what you're talking about. So I think we actually still need some conditional logic, but not that's going to grow longer and longer with each language. What I think we probably want to do is this. If the current favorite is in the counts dictionary, and this is the Pythonic way of just saying, is this key in this dictionary, then go ahead and safely do counts favorite plus equals 1. Else, to your conjecture now, else what do I want to do? Counts favorite equals, 1. So initialize a brand new key to a brand new value of 1, because I'm obviously just seeing this language. Otherwise, increment again and again. And now down here, I just need to tweak my syntax a little bit. I don't need to print out all of these things one at a time manually. I can actually get away, I think, with another loop at the very bottom here. So how about I do this? For each favorite in those counts, and this is, again, the Pythonic way to iterate over all of the keys in a dictionary, go ahead and print out, using an F string, whatever the current favorite is, Scratch or C or Python, and then a colon, and then figure out what its count is. And you can do that by going into the counts dictionary, looking at the favorite key, and get back its value. So I close my curly braces, I close my quotes, and even though this looks ugly at the moment, now this is much more dynamic, because if we go and add SQL to the CSV file tomorrow, or we add JavaScript next week, this will just work. It will keep working now automatically. All I change is the Google form, not my actual code. All right, let's try Python of favorites.py. Cross my fingers as always, and there now is the data as of now. Questions on this code here? Yeah? Really good question. What if you wanted to print it in a particular order? Well, I could give you a couple of solutions. Like if you want to print it out in It's already coincidentally in alphabetical order, so you got that for free, although that's just by chance here. But there is a way to do this. And let me propose that we go down here to my loop, and I explicitly use a function you might not have seen in Python yet, but it's literally called sorted, which is going to take either a list or, in this case, a dictionary, and by default, sort it by key alphabetically. Now, if my intuition's correct, this is not going to change the output because it's already alphabetical. But if you read the documentation for the sorted function, it takes multiple parameters potentially, some of which are named parameters. And so you can actually do this. If you want to sort the counts, but you want to reverse the order for whatever reason here so that it's reverse alphabetical order, now let me go ahead and rerun this. And I'll keep the previous output on the screen. Enter. And now it's backwards alphabetically, if you will. Other questions on this here? No? How about then we transition to sorting by value. And this is going to escalate a little quickly, briefly, but then we'll tone it down again. Notice that right now this is indeed sorting by key. What if, especially if I have lots of data, it'd be nice to make like a top 10 list, or in this case, a top 3 list, and actually see in order of the counts, the values, what these popular ones are. So it's not C, Python, Scratch. It should ideally be Python, then C, then Scratch because of the values and the magnitude thereof. So how can I do this? Well, it turns out there's another parameter that you can pass to the sorted function that is typically implemented as a function itself. And so I'm going to go ahead and do this. I'm going to temporarily define a function called getValue, just to make my life easier. And this getValue function is going to take, I'll say, a language parameter. And then all I'm going to do is return whatever the count is of that language. So out of context, this is just a super simple function that you handed a language like Scratch or C or Python. It's just going to tell you what the count is thereof in that dictionary called counts. But what I can do now down here in my newly introduced call to sorted is I can tell it what to use as its key. Instead of using literally the key, Scratch, C, Python, I can sort of override that behavior and say, you know what? To figure out what to sort by, go ahead and call this function called getValue. Notice that I have not put parentheses after getValue because I don't want to call getValue right then and there. I want to pass the getValue function as itself an argument to the sorted function so that the sorted function, written years ago by the people at Python, can call my version of getValue again and again and again when they try to sort this actual data. So now, if I add that and I leave reverse equals true, let's see what happens. Python of favorites.py, enter, and now I get my top 10, or in this case, top 3 list. And if I had more sophisticated data with like more columns altogether that I actually care about, I could even sort this more powerfully as well. But let me clean this up a little bit just so you've seen it, even though we won't use these that often in CS50 until the end of the class will they come up again. Technically, this is a little bit, this isn't necessarily the best design to spend all this time implementing a function and then only use it in one place. In general, we've argued that you don't necessarily need a variable if you're only going to use it in one place. You don't really need a function if you're only going to use it in one place. And here, we kind of have a good candidate for that. And so it turns out in Python, if you don't want to bother creating a function just to use it once, you can create what's called an anonymous function, aka a lambda function, like the lambda symbol, familiar. And a lambda function, the syntax is a little strange looking, but you say this. You literally say lambda. You literally then say the name of the argument that you want this anonymous function with no name to take. Then you have a colon. And then, quite simply, you write what you want the return value of this function to be. You don't even say return literally. These lambda functions are meant to be used super tersely so that you can, in one line, express something like this. And I admit this looks more cryptic, I think, than the previous version. But as you get more comfortable with Python or other languages that support this feature, it allows you to not bother with lines of code like that and just tighten up your code a little bit. So this line here, lambda, language, colon, counts language, is the one-line version of this. And you don't even need to bother picking a name for it. Lambda tells Python, I didn't waste any time thinking of a name for this function. So questions then on this technique of using Python to analyze data like this? Any questions? We're almost done with Python. Questions? No? OK. So why don't we make things a little more interesting, because we had a much juicier data set with the problems that we've assigned over the past several weeks. Why don't we go ahead and quite simply, I think we wrote pretty darn good code here. So I think we can pretty much just change a bit of it to say, let's see, if I don't want language, I want problem. And if I want to sort by not language but problem, I think that's it. I think if I didn't overlook something here, just by changing what column I'm reading the data from, and then just to be consistent, renaming my variables just so I know what I'm looking at, what will this program now do after those minor changes? What will I see when I run this? What would be the first thing I see when I run this? Tough crowd today. Yes? Yeah, the problem, the top problem. So the most popular problem, which I'm a little worried it might be hello or just scratch, but let's go ahead and see. So let me go ahead and open my terminal window. I'll even maximize my terminal window so we can see a lot. Let me go ahead and run Python of favorites.py. I'm going to go ahead now and cross my fingers that I didn't mess up and hit enter. And OK, great. We peaked early. So Scratch was the most popular program according to the data at the time I downloaded it. I'm sure other votes have come in since. Filter in week 4 was tied then with Tiedemann as well. Mario is a close third there, and so forth. So this is helpful for us on staff. That's not so much love down here at the bottom of the list. So it was a bunch of code to write, but now that we've written it in this very versatile, dynamic way, it's pretty good for just like crunching data and doing some analytics. But it's still a decent number of lines to have had to write manually. And this is where sometimes it isn't necessarily the right tool for the job, but rather the job that but rather a candidate for using some other language altogether, especially when it's not just a one-time program that you run and you want to see the answer. What if you want to take input from the user and answer questions dynamically, like a mobile app would, like a website would, like Microsoft Excel or Apple Numbers or Google Sheets would for you? Well, let's make one final change for now to this version of the program and actually take in some user input. So besides just loading all of the data into memory, let's go ahead and down below here, not just print out the top 10 list, if you will, but prompt the user for their favorite. So I'm going to use Python's input function, and I'm just going to prompt them with favorite, quote unquote, like tell me what your favorite problem, what problem you're interested in. And now let me go ahead and say if that favorite is in the counts variable, so you didn't type in something random that we didn't actually assign as a problem, then let me go ahead and print with a format string whatever that favorite is of yours and show you the actual popularity thereof by indexing into counts using that favorite as the key and printing this. So now it's a dynamic program. It doesn't dump all of the data and all of the summations. Rather, it's going to allow me to see what my choice of favorite is. And I'm going to go ahead and say, let's see, I'm a fan of Mario here, so enter. And indeed, we see the same value we saw a moment ago, but just for Mario. But the point now is that, 1, all of this is possible. 2, it's way easier and more pleasant than this would have been in C. This is still only 15 lines of code. And in C, again, there's the memory management. There's the iterating over the strings, trying to find the commas. There's just a lot more work. But honestly, even when you just want to answer a question like this in Excel, in Apple Numbers, Google Sheets, generally you can just highlight things. You can click a button and boom, you get your answer for summation or max or min or any of those sort of basics. Wouldn't it be nice if we weren't taking a step backwards as programmers and being sort of more powerful, and yet we now have to do more of the work? So maybe sometimes Python's not, or any language is not, the best tool for the job. And that's going to now allow us to introduce more generally something called a relational database, graduating from mere flat file databases like text files or binary files in which all of your data is stored to something more proper. But first, questions. Really good question. To reiterate, if I were to, is this case sensitive? So if I were to type in Mario in all lowercase and hit enter, I actually get no such response. Now, that might be acceptable because the problem technically what is a capital M, but that's a little ridiculous to be that pedantic about the input. So how could we solve this? Any tips for how we could make this a little more robust? Yeah. OK, yeah. Yeah, so we could use a few different functions, one of which is called title, which will change it to title case, where it capitalizes, like in most English sentences, the first letter of that sentence. We could use capitalize, we could use upper, we could use lower. But indeed, we could just decide how we want to standardize the capitalization, either uppercase, lowercase, or some combination thereof, and just make sure that you change the counts themselves, make sure that you do the same to favorite, and make sure that maybe you keep a backup of the data if you want to show the original version that came from the CSV without presuming to just capitalize everything for the user. But indeed, that would be the most common scenario. You just make things case insensitive when doing those matches. Other questions now on Python before we leave it behind for the coming week? All right, well then let's introduce these relational databases. So relational database is what is a super popular way of storing lots of data. Like this is what the Twitters of the world, the Googles of the world, the Metas of the world use to store some of their data at scale. There are alternatives to relational databases. Indeed, today we'll talk about a language called SQL. There's also a movement, if you will, or an alternative generally called NoSQL, which is just the opposite. You don't use SQL. There are things called object-oriented databases and the like. But if you've ever heard of MySQL or PostgreSQL or Microsoft SQL Server or Oracle or MariaDB or a bunch of other products, both free and commercial, this is what they're talking about. Databases that are designed to store lots of data. And what's nice about relational databases is that they're really similar to the spreadsheets with which you were presumably familiar long before today's class. So a relational database is going to store, as you'll see, all of the data in rows and columns. Now, the terminology will thereafter be a little different. Instead of having sheets, you're going to have tables. But those tables are still going to have rows and columns. And you're going to have even more control over the performance of your data when you start to access it using this structured query language, or SQL. This is a language you can use for web apps, mobile apps. A lot of analysts would sit down at their Mac or PC and actually ask questions of data to get back the answer. And wonderfully, even though there will be some new syntax today, SQL really just does 4 basic things. CRUD is the sort of crude acronym here. CRUD is a way of remembering that a relational database supports ultimately creating data, reading data, updating data, and deleting data. So even if you're feeling like, wow, this is a lot of new syntax, which it isn't relative to our past languages, the only things you're doing really are creating data, reading data, updating, and deleting the same. Now, a little confusingly, in SQL, the corresponding functions or commands that exist that map to CRUD are actually this. So it's still create, but there's another one called insert. It's not read, which is more of the computer scientist way of saying it, but select, which is a little more explicit, like select data you care about. Update is still update. Delete is still delete. But there's another command called drop, which lets you drop, that is, delete entire tables as well. So you can create tables using syntax that's generally going to look like this. You'll say create table. You'll give the name of the table, which you can call most anything you want, but generally all lowercase, no spaces is best. Then in parentheses, you can specify a comma-separated list of the columns that you might want in this table. So this is the code equivalent in the SQL language of like manually opening Google Sheets or Excel or Numbers and like clicking in the top left cell and like typing timestamp. And then in the next typing language. And then in the third typing problem. This is the way to sort of define what your headers are, if you will, in a spreadsheet, but now it's called a table. Now, we won't use this command manually first. Let's do something a little simpler. We're going to start off by just importing this data ourselves. And I'm going to go ahead and do this. Let me go back to VS Code here. I'm going to leave behind favorites.py for now, because now we're going to transition to this other language called SQL. And to do this, I'm going to create a new database file. And I'm going to do so using a command called SQLite3, which is just the third version thereof. And I'm going to give the database a name of favorites.db. There's different conventions, but this is one of the most common. When I hit enter, this is going to create for me a new empty database, just like opening an untitled spreadsheet in Excel, Google Sheets, or Apple Numbers. I'm being prompted, do I want to create favorites.db? I'll hit Y for yes. OK. we're up and running. Now you're going to notice a different prompt. I'm not in my Linux prompt per se, which is always the $sign. I'm now inside of the program called SQLite. And we're going to use SQLite 3, as just an interactive way for now of playing with SQL code. At the end of today, we'll show you how you can use SQL in Python code so that you still write Python code to do whatever you want, but you can talk to databases using Python. And this is exactly how web apps, mobile apps work. For instance, on iOS, on an iPhone, an iPad, or the like, if you want to store data, it's very often stored in a SQL database, as we're about to do. But you might use a language called Swift or Objective-C. And the same exists in the world of Android using Java or Kotlin or something else to query the database. So we're going to see SQL in isolation for now, like an analyst might just use it at their Mac or PC, but we're going to tie it together by day's end. So at this terminal, SQLite, let me go ahead and execute this command first. I'm going to first put SQLite into CSV mode because I'm going to cut some corners initially. And I'm just going to automatically import all of the data that was submitted via that Google form, which I exported as a CSV and uploaded to my code space. And I'm just going to automatically say, turn this CSV file into a SQL database for me, just so I don't have to figure out what those create table commands are. So to do this, I'm going to say mode CSV, so that SQLite knows that this is the command, knows that this is a CSV file. It's literally dot mode, so the dot comes before the keyword there. And now I'm going to say dot import, and then the name of the file I want to import, which is favorites.csv. And now the name of the table that I want to create with that data. And just for consistency, I'm going to call it favorites. I could change these things to be anything I want, but I'm going to do that. And voila, nothing seems to have happened. But just like in C and in Python and Linux, when nothing seems to happen, that's usually a good thing. It means I didn't mess up. So if I want to see what just happened, there's this other command. And these commands that start with dots, these are SQLite specific, which is indeed a lightweight version of SQL. They're not SQL per se. So if you're using Oracle or something else like that, you're not going to use these exact commands. You'll see the ones we use in just a moment. And here's the first. When I type .schema, the schema of a database is the design of the database. What are the tables? What are the columns? And all of that. So when I type .schema, this actually, in this case, shows me the create table command that was automatically run for me by just doing this import line. Once I get more comfortable with SQL, I could literally type this out myself or use some program to generate that as well. But what it's creating for me is this: create table. If it doesn't exist, even though it's more terse than that, I want to create a table called favorites. And then the columns for that table are going to be timestamp, which is going to be text, comma, language, which is also going to be text, comma, problem, which is also going to be text. That was just inferred very trivially by the .import command to just figure out that, yes, just give me a 3-column database table based on the Google form. Okay, questions on this? These are commands you run once to get up and running. You don't run these commands frequently. But we have them on the slide just for reference. All right, so now let's do something a little more interesting. I'm going to clear my SQLite terminal here, but I'm still in SQLite. I'm going to now use some of my first SQL commands, which recall were among them select. So CRUD, C-R-U-D, the R was select. This is maybe the most common, the most useful, the most powerful thing to use with a SQL database, selecting data to answer questions akin to the ones we were trying to answer with Python. This is the general syntax. Anytime you want to select data from a SQL database, you literally say select. You then specify the column or columns that you want to select data from. You literally write the word from, and then you specify the name of the table you want to get that data from, semicolon, in this case. Everything that's in capitals here is a SQL keyword. Strictly speaking, you don't have to capitalize things, but we would encourage you to do so stylistically. And especially as you're learning and even as you're writing it, it just helps to distinguish SQL from like words you chose, like the names of the columns and the data therein. So do adopt early on this convention. So let me go back now to my code space here. I'm running my terminal window with SQLite 3 inside of it. Suppose that I just want to get all of the data from the favorites table, which was automatically imported. Let's do this. Select. I want everything. Well, I can do timestamp, comma, language, comma, problem. But you know what? Here's a convenience already. If you want everything, there's what's called a wildcard character in SQL, which is just a star, an asterisk, which means give me every column without my knowing even what they're called. Let me go ahead now and say from favorites, semicolon. And this is the SQL way of opening the database, iterating over every row therein, printing out every row therein, done. So those 3 steps, which was like 9 lines of Python code, give or take earlier, is now 1 line of SQL. I hit enter. There is all of the data. So I see now all of the data just outputted as a CSV here. But it's not the CSV file. It's now actually the table. And in fact, just for good measure, let me do this, because you'll see the behavior a little differently the next time we open the file. I've just exited out of SQLite 3. I'm going to rerun it. But I'm not going to re-import the data or do anything like that, because my file now exists. In fact, let me take one step back. If I type ls at my Linux prompt, there's my favorites.py from before. There's my favorites.csv from before. And here's a third file that I did create a moment ago when I first ran SQLite 3. So the data is persistent. It's not using RAM or memory. Anything I do now is saved there. So let's go ahead and rerun SQLite 3 with the same file. But I don't have to re-import everything because the file already exists. Let me now do that same thing again. Select star from favorites to get all of the data. And what you'll see now is the same data, but it's a little prettier now. Because I reran it, I effectively disabled CSV mode this time. And what I'm now seeing is the entire contents of this database table called favorites. Now, there's nothing new here, but you're just seeing now like an ASCII or Unicode version of all of the same data from that database. Well, suppose I want to get a subset of the data. Well, let me clear my screen. And just like in Linux, I can hit Control-L just to clean things up aesthetically. Suppose I want to get just the languages. So I could do select language from favorites. And this will now select not all 3 columns, aka star. This will only select the language column and all of the data therein. If I hit enter, voila, now I just see those there. No timestamps, no problems. It's just a slice of the table, if you will. All right, not that interesting still, because it's just a big column of data. But now things get more interesting. It turns out in SQL that there are functions that come with this language, just like C, just like Python. In SQL, some of the more useful ones, some of the simpler ones are these here: average, count, distinct, lower, max, min, upper, which pretty much do what they say. And count is a particularly useful one. Let's start with that. You know, it's a reasonable question to be asked, how many people submitted the Google form by the time I actually downloaded the CSV? Well, why don't we go ahead and do this? Let me go back to VS Code here in my terminal window. Let me select not star, but the count of star. So give me the count of the rows that are being returned from the database called the database table called favorites. Now when I hit enter, I'm not going to get all of the data. I'm just going to get simply a number. 430 rows came back. So that's pretty good. I now know how much data is in there. Well, what languages were in there? Well, I could do select language from favorites just as before, but that's not that useful, especially if I'm inheriting the data. Like I'm the analyst who's been handed a data set by my boss, and they want me to like crunch some numbers. OK, I could like load this into Excel. I could sort it. But you can use SQL now to answer pretty basic questions too. If you want to select the distinct languages in the data set because you weren't privy to the Google form, let me go ahead and select only the distinct languages from the favorites table. And now I hit enter, and I get back a much more succinct answer. Just the 3 languages in question. Not really that useful since I created the Google form, but certainly if you're inheriting data from someone else, you've just downloaded a data set, at least now I'm arguably wrapping my mind around what's going on. Now, this is not necessary for such a small data set, but I can combine these things. Select the count of the distinct languages in this data set called favorites, and now I should get back what answer? So hopefully, indeed, an answer called 3. And what you're getting back, notice, aesthetically too, is like a mini temporary table. When I asked for just the distinct languages, what SQL hands me back is this temporary table in memory that has 1 column called language and then 3 rows. Now, this is not saved anywhere. It's just executed ephemerally like this. But that's why it's depicted in this way. What you're getting is subsets of your data, smaller tables containing some of your data. And same thing down here. This is like a crazy long column name. You can rename it if you really want. But that's all we're seeing there. And in fact, if that's a little ugly, we can actually alias these things. N is a common name for a variable, a number in any programming language. So I can actually alias this to be a column called n, hit enter, and now I'm getting a tiny, tiny table whose column is called n that just has the one value there. All right, questions on these, application of these functions here? No? Questions? Yeah. Say a little louder. Oh, as, literally in English. So name this column, rename this column as this. Technically, it creates an alias for the column. So that's all. Yeah. Exactly. Distinct will operate on whatever you handed in parentheses and get rid of all of the duplicates, giving you back just the uniques. Correct. Other questions here? Yeah. Good question. When you define an alias like n, which I just did, does it become like a variable you can reuse? Short answer, no, in this case, but you can reuse it within your same query. Even though these queries are getting a little longer, admittedly, statements that they are, you can actually reuse n in even longer queries, so later in your query. And we'll see a few that are going to start to grow in length. So it's a nice way of nicknaming things just to be a little more terse in your query. So we can transition to some of these more sophisticated queries because it turns out there's some other techniques we can introduce as well. Here are some other keywords in SQL. And again, even though like this is another list of things, there's only 4 things fundamentally we're doing: creating, reading, updating, and deleting data. These are just allowing us to like fine tune how we do it exactly. So where is going to allow us to filter data, as we'll do in just a moment. Like select data where this conditional is true. Like is going to be an alternative to an equal sign. So instead of looking for exactly Scratch or exactly Python or exactly C, you can look for something like ... And it can be a little bit of a fuzzier match, if you will, with other characters as well. Order by is going to deal with sorting. Limit is going to just let me limit the total number of rows that come back to 1 or 10 or finite if I don't want to see all 400 plus rows all at once, because I'm just trying to wrap my mind around it. And group by is best shown by example. So let's play with just a couple of these as well. Let me go back to VS Code here. I'll clear my screen. I'm still in the same SQLite instance. And let's count how many of you liked C without writing Python code as before. So let me go ahead and select the count of the rows from favorites where the language in each row equals C. And the convention in SQLite is to use single quotes anytime you're surrounding a string that's meant to represent a literal piece of text, as opposed to C, which was double quotes, or Python, which was either. So this is selecting the count of rows from favorites table where the language in question is C. Enter, and this gives me 98. Notice, though, if I omit that predicate like we did before, you'll get back the total number of rows that were in the table. So where is what's called a predicate that just allows me to filter things, just like an if condition or the like in a language that we've seen before. You can be a little more specific, like how many people really liked C and the Mario problem specifically. Well, let's do this. Let's go ahead and do select the number of rows from the favorites table where the language is C. And, so it's still literally the word ands and or, just like in Python, but not like in C. And problem equals Mario. So let's see if there's any fans of both C and the Mario problem. And 3 of us really like those 2 things together in this case. All right, what else can we do? Well, more compelling might be to see, kind of like in Python, for each language, what was the popularity thereof? And at the moment, we don't really have a way of doing that except in Python, where we had the loop and we had those variables or the dictionary that did all of that counting for us. You know, totally doable, but tedious, especially if your job is to analyze data. My God, like even writing 15 lines of code to answer simple questions is kind of ridiculous. SQL can do better for us. So let me go ahead and do this. Let me go ahead and select every language and the count thereof from the favorites table, but this time group by language. So this was another one of the keywords that we can use in this abbreviated list of extra features of SQL. And this one's takes a moment to wrap your mind around, but this is going to give me a 2-column temporary table where the first column is a language and the second column is the count thereof from this data set. And group by language just means that only show me Scratch once, only show me C once, only show me Python once. That is, group all of the identical values together, but keep track of how many of them there are. And so now, if I go over to SQLite and I hit Enter, now I have, in SQL version, the exact same output that I had from Python that took me, what, 15 plus lines before. Now we're down to just one, because SQL, structured query language, is all about constructing queries like this to answer questions and get back answers quickly. If we want to clean this up a little bit, you asked earlier about sorting order. Well, we can do that too. There's another key phrase we can use here. We can order by the count of those rows, and then run that query here. So now, unfortunately, they're from smallest to biggest, but we can reverse that. It turns out, and my query is starting to wrap here. I'll zoom out for a moment. If you want to order by count, the default is in ascending order, abbreviated ASC. If you want to reverse the sort in SQL, instead of using reverse equals true like we did in Python, you say DESC for descending order. And now we get almost the same output, but flipped in reverse. So it's just a lot faster to answer questions once, of course, you get some muscle memory and some comfort with it. Well, what else can I do? You know, what if I just care about the most popular language? I don't care about the second place or the third place languages or anything else. Well, let me add one more clause here. Limit the answer to 1. And no matter how many rows should come back now, I just get the number 1 language as of the data set we collected with 270 votes for it. Questions on this? Any questions here? No? Well, what if, we're starting to introduce SQL, and it was kind of too late to make it into the Google form. So it turns out there's syntax for this too. You can create data, of course, not just the tables, but the data they're in. And here's like the typical syntax for inserting data into a SQL database. You literally say insert into the name of the table. And then in parentheses, you specify one or more columns for which you have values that you want to insert. This is to say, you don't have to give values for every column in the given row. If you only have answers to some of those questions, you can enumerate them here like this. But the values you insert are going to be these. So you literally say after the close parenthesis, values, and then in a second set of parentheses with the same length comma separated list, you specify what values do you want to insert. So it's a little verbose. And frankly, longer term, you're going to use like Python code to automatically do these kinds of insertions. But let's go ahead and try this. Right now, if I do select distinct language from favorites again, we see this, just these 3 candidates. But we've now taught you a bit of SQL, so let's do insert into favorites, the column called language. And you know what? I'm going to give a problem here. The values for which, and let me zoom back out, are going to be quote unquote SQL and quote unquote 50ville. You'll soon see what that's all about. Semicolon. Nothing seems to happen, but that's usually a good thing. And now if I scroll back up in my queries, in SQLite 3, you can scroll back and forth in time and, to avoid retyping things. Now I should see, indeed, 4 candidate languages here. Now suppose that you were never really a fan of C, and maybe you programmed a little bit in high school or in the real world, and you liked C++. Well, there's a whole lot of answers for C. So select star from favorites where language equals quote unquote C. So here's everyone who submitted the answer for C. Let's presume that no, they didn't really want C. They wanted C++, which is not a language we teach in the class. But I could also now do this. You can use the update command to set a column or columns to different values where some condition is met. So if I do update table name, set column name equal to some value, filtering it perhaps by where some condition is true. So suppose I've changed my mind, or you know what, let's go ahead and do update favorites, set language equal to maybe C++ where language equals C. Now, this is destructive, so you generally don't want to do this unless you have a backup of your data too, overriding what people's answers are. This seems to have been successful because no error messages. And if I rerun the previous select, that gives me all of the favorites where language equals C. Now, indeed, I get none. But if I search for C++, now I get a lot. And if I get rid of that where clause altogether and just look at the contents of my database, now you see that indeed C++ is commingled with all the other data. This is not what you all intended, of course, so I can undo this. Let me go ahead and undo what I just did. Let me set my favorite language to C, where language equals C++, but the predicate is important. This I'm not going to do. What if I accidentally omitted this predicate, the where clause? How would that screw things up, might you think? Yeah, and back. It would set every row's language to indeed C. And this is dangerous. And if you start Googling around for like SQL mistakes or the like, people in the real world have accidentally run commands like this. And without naming names, a former member of our teaching staff at one point accidentally ran a command like this and changed every student's name in our database to Bobby, I think it was. The same name for every row because they simply forgot a predicate. So here too, like there's dangers in code. And you should adopt the habit quite quickly of always, one, backing up your data, like with CP, for instance, in Linux, or any other technique, or just making sure before you hit enter that, yes, this is indeed the query I want to execute. And generally speaking, in the real world, there should be process controls in place, like the intern should not have access to the database, the production database, the live database, and the like. But you have a lot of power now with these queries, so just be all the more careful, because very easily can you do bad things. So let me undo this. Where language equals, quote unquote, C++, and I'll zoom back out, enter, and now I think we're back in business. C is among the answers. Yeah? Is essentially doing what at the end? It's essentially find and replace. Yes, in like layperson's terms, this is find and replace implemented with SQL. And in fact, the authors of Microsoft Word or Google Docs might very well be using language like this SQL. When you go to the nice graphical, user-friendly find and replace box, this may very well be what they're doing underneath the hood. Or, of course, they could be using some other language altogether. There's one last syntax that's worth knowing, delete, which for better or for worse is even more destructive, whereby it allows you to delete rows from tables. It's distinct from drop, which lets you delete tables themselves. This focuses on rows. So suppose that you really didn't like, let's say, Tiedemann was a little challenging if you tackle that more comfortable problem. So if you really don't want to even think about Tiedemann anymore, so why don't we do delete from favorites where problem equals, and I won't execute it for real, Tiedemann. This would have the effect of deleting every row, including the language therein and the timestamp, where the student answered Tiedemann. Worse than this would be this. Why might this be bad? Okay, chuckling, because like there's no predicate, there's no filter, which means literally this would delete all of the data. So again, with great power here comes great responsibility. Now, this has just been a data set of what, 430 rows by us dynamically created. There's, of course, some really juicy data sets in the real world. And one website you might have heard or an app you might have used is IMDb, the Internet Movie Database, which wonderfully makes some of their data available for download as CSV files or technically TSV files, tab-separated values. But what we did in advance of class was download some of that data for both TV shows in the real world and movies in the real world. And what's wonderful about this data set is it's not just dozens or hundreds or even thousands of lines. There are millions of rows of juicy data, TV shows and movies with which most folks are probably familiar, at least with a subset. And we'll see in just a little bit that this data comes in the form of now 6 different tables that we've given you. And the tables in question for today are going to be the people in the TV business, the stars therein, the shows that people are producing and the like. This is a picture we'll revisit to enable you to wrap your minds around what the actual data is. This feels like a good opportunity, though, for a snack. In fact, in just a moment, we have a whole lot of Rice Krispie treats out in the lobby. But if folks could perhaps acknowledge this mini wedding cake here. CS50's own Carter Zenke is getting married this week. So congratulations to Carter as well. Congrats. All right, there's only... OK, there's only one piece of cake in that box, but a lot of Rice Krispie treats in the transept. Let's take 10 minutes, and we'll be back with Internet Movie Database in 10. All right, we are back. So if you've never been, like, you can actually go to imdb.com right now and play around or download the mobile app. And it's just big database of a lot of TV shows and movies and actors and the like. But what indeed is nice is you can download some of that data. And that's what I've done in advance. And what we've done is we wrote some Python code to convert some of the flat file databases that they let you download. And we converted it into a SQL database with 6 tables. So not just one, but 6. That ultimately are these here. And let me just help you wrap your minds around what this picture is, which is an entity relationship diagram, which is just to say each of these boxes on the screen represents a table, and each of the arrows or edges represents some kind of relationship across the tables. Because up until now, the only data we had were those 3 columns in the favorites table. But what gets really useful about SQL databases, just like a Google spreadsheet or an Excel file, is you can have multiple sheets, or in a database, multiple tables. And so what we're about to see is that in this IMDb database for TV shows, there's going to be a dedicated table for all the people in the TV business. There's going to be a dedicated table for all of the TV shows that are in their database as of right now. There's going to be a dedicated table for writers in that industry, for the ratings of shows, for the genres to which shows belong, comedy and the like. And then lastly, there's going to be this table which somehow associates people with the TV shows that they star in, and vice versa. And so let's consider first what this looks like in code. And we'll see that it's going to overwhelm intentionally at first, but I'm going to do this. I'm going to go back to my terminal window, and during the break, I downloaded from the course's website a file called shows.db, which we made in advance for you. And if I type ls, I'll see all of my favorites files from before, the CSV, the DB, and the Python file. But now there's shows.db. So I'm going to go ahead in my full screen terminal window here. I'm not using actual tabs or code files now. I'm going to run SQLite 3 on the file called shows.db. And I'm just going to see this version information here. Let me clear my screen and run the one command I ran earlier to show us the schema of the favorites database. Now we'll see the schema for the shows database. And there's a lot going on here, but let me scroll back up to the very top, the beginning, and we see this here. So when I run .schema, we see a dump, really, of all of the SQL create table commands that were run in order to create this database for you. And one of those tables is called genres, and another people, ratings, shows, stars, and so forth. And the columns therein, even though it's formatted a little more prettily than the automatically generated create table statement for favorites, whereby we have 1 column per line of output here. In the, for instance, people table, there's going to be an ID column, like a unique identifier, like a Harvard ID, a Yale ID, or the like, a name column, a birth year, and then some other stuff. If I scroll down to shows, every show in the world is going to have a unique ID as well, a title, of course, the year in which it debuted, and the total number of episodes as of the time we downloaded the data. And then what else is there? Some of these are a little less obvious, like ratings here. So ratings don't have an ID column, but they have a show ID column and a rating, like a 5-point scale or 10-point scale or the like, and then the total number of votes that were collected to contribute to that rating. IMDb allows people to like upvote and downvote shows and movies and the like. And then similarly is genre structured. There's a show ID, and then there's a genre, which is going to be like an English word like comedy or drama or something else. And then what else? Let's go a little further at the bottom here for stars and writers. If we go to the very bottom here, stars and writers are similarly structured too. They have a show ID and a person ID. So show and person. And then this writers table has a show ID and a person ID. And there's a whole lot of other words that we'll come to in just a moment. But what is this code hinting at? Well, if I go back to the picture from earlier here, you'll see that this picture captures the relationships among these various tables. So for instance, if we focus on shows for just a moment, a show, again, has a unique ID, a title, a year in which it debuted, and a total number of episodes. If you want to figure out what genre or genres a show belongs to, because some shows are just comedies, some shows are just dramas, but some shows are arguably comedies and dramas depending on the episode or the like. So you can imagine wanting to associate 2 or 3 or even more genres with a show. This line here in this second table allows us to do that. Every row in the genres table, we'll see, has two items, a show ID, which relates to the ID of a show, and that's why these lines literally line up with that specific column name, and a genre, which is going to be like quote-unquote comedy, quote-unquote drama, or something else. Now, with that said, design question, why have we deliberately not just gotten rid of this genres table and made our lives simpler by just adding a genre column to this shows table? And again, a table is just like a sheet with rows and columns. At the moment, shows only have 4 columns: ID, title, year, episodes. Why not just add a 5th column called genre and put the show's genre there? Any intuition here? Why not just keep things simple? Like, yeah, and back. Exactly. If you add a 5th column here and call it genre, then you have to pick a genre specifically. You have to put in that cell, presumably, comedy, or drama, or musical, or something else. Now, you could write multiple words in the cell, but generally speaking, that would be sloppy, bad design. Like every cell, just like in a spreadsheet, should really have one value. It might have multiple words, but it shouldn't be like a weirdly comma-separated list of multiple things. It should just be in a different cell in that case. So if you instead were to design this with just a single column called genre, you're imposing what a computer scientist would call a one-to-one relationship. Every show has one genre. And that's not necessarily a good thing. Or strictly speaking, it would be a many-to-one, because the same genre could belong to multiple shows. But each show could only have one genre in that case. What a relational database allows you to do, and relational is indeed the operative word, it allows you to factor out some of your information and then have maybe one show here in one row. But then in this genres table, you could have one row for that one show genre, or you could have 2 rows in the genres table for comedy and for drama. Or if it has a 3rd genre, you could just add another row here. So you still have one row for the show itself with all the juiciest details, but a variable number of rows by having this relationship with another table. Meanwhile, ratings work the same way, at least in this case. A show has ID, title, year, and episodes. But if you want to figure out its rating, you have to kind of follow the arrow here, so to speak, and look up the corresponding show ID in this table, find the rating of that show, and the total number of ratings. So that's been factored out too, for better or for worse. Now let's consider people. People have just 3 columns: ID, name, and birth. But there's no mention of the TV show in which people have starred, or the TV shows that a person has written. Well, why is that? Well, if you just had a 4th column here called show, well, you would have to decide what show is that person in. And no one could ever act again in another show because there's no room to store the data. But if someone, of course, a popular actor, can star in multiple shows, well, we could have one ID for that person, one name, one birth year, obviously. Like there's only one Steve Carell as an actor in the world of people. But Steve Carell in this example could have his person ID, whatever his Harvard ID equivalent, Yale ID equivalent is, appear in multiple rows in this table so that it can be associated with multiple shows. And this allows you to create what's called a one-to-many relationship, or technically it's bidirectional. It's a many-to-many relationship. Why? Well, one show can certainly have multiple people in it and multiple people writing for it, just in the real world. But conversely, one person could certainly act in multiple shows or write multiple shows. So this is what you get with relational databases. You put your sort of canonical data for people in one place, for shows in another place, and then you use these additional tables to relate one thing to another. So we won't dwell on the pictures. That's just if you sort of can wrap your mind around the data set better that way, that's one way of thinking about it. But recall that the code we just saw for the schema, again, escalated quickly. Like there's a lot of keywords I haven't mentioned yet, but some of these are perhaps familiar. They're capitalized differently here, but integer is on the list here. Null is on the list, albeit technically not null. So let's tease apart some of these keywords and consider what they're actually doing for your database, because now we're exploring features that do not exist in the world of spreadsheets alone. So it turns out in a SQL database, specifically SQLite, which is the version of SQL we use in CS50 and which is commonly used for for things like mobile applications nowadays. It's like a lightweight version of SQL. It's when you aren't trying to run Twitter and have billions and billions of rows necessarily. You've got hundreds, thousands, tens of thousands, maybe even a few million, but not crazy numbers, crazy amounts of data. In the world of SQLite specifically, there's these 5 data types. So just like in C, we had int and char and the like, in SQL, we have these. Blob, which is kind of funny, but it just means binary large object. So it's like a binary data type, zeros and ones that aren't necessarily fitting into the other categories. Integer, which of course is an integer as we know it. Numeric, which is kind of a catch-all for numbers that are formatted specially. So like a date would be like year, dash month, dash day. And this is actually a wonderful thing. Depending on the country you're from, you might think your date system in your country is great or it's horrible. The US system is horrible because we have month, day, and then year, which is impossible to sort. It is the wrong way objectively to store data, and yet here we are using this at scale. Other countries have gotten this better. Numeric and SQL itself standardizes that stuff. So it doesn't matter what country you're from, you're storing your data in this particular way, for instance. Times are standardized in other types of numeric data as well. Real is synonymous with float, so something with a decimal point and some number of digits thereafter. And then text is just for strings and the like. With other even fancier databases like MySQL, PostgreSQL, Oracle, and other products you might have heard of, there's even more data types where you have to make even finer grained decisions. But for SQLite, it's indeed pretty lightweight, and you or we just have to decide the data types for each column in a table. But there's these additional constraints in the world of SQL. You can additionally say that cells in this column may or may not be null. So if you want to protect yourself from yourself so you don't screw up and insert a null, that is a blank value, you can explicitly design a table to have a column that cannot be null. And so in fact, someone came up during the break to ask me about my having manually inserted SQL, quote unquote, SQL into our favorites database. You might recall that I kind of cheated. I just inserted SQL, quote unquote, and 50ville, the name of a new problem, quote unquote. But what did I not insert into the database? A timestamp. And I could have put like the current day and time a few minutes ago, but I didn't. And that's fine if it's acceptable to you and the product you're building. But I could have prevented that. If we had defined the table to have a timestamp column that isn't just text, but it's text that's not null, SQL would have complained and would not have let me complete that insertion. So there's these kinds of built-in defenses that you don't necessarily get with a spreadsheet alone. And unique means exactly that. If you want to make sure that every row in that column is unique, maybe for email addresses, or in the US, social security numbers, or anything that you want to make sure you don't have 2 versions of, you can specify that the column is unique. And there's other such constraints as well. But again, this is just a list of features that you get from a proper relational database. But perhaps the most intellectually interesting one and the most powerful one is what's called here a primary key and a foreign key. And let me go back now to this output. If we look at shows, you'll see that a show, again, has an ID, a title, a year, and a number of episodes. And now the data types might make sense. The ID, it turns out, just like a Harvard ID, a Yale ID is going to be an integer, so a simple number. The title, of course, is going to be text, but not null. Like, it would be weird if a TV show had no name. Like, that can't be. Like, the whole world would break, or your TV guide and whatnot. So that makes sense there to say not null. Year is numeric, so it's a standardized form. Episodes is an integer, like how many episodes have been produced. And then lastly, notice this. The primary key of the shows table is apparently the column called ID, mentioned a few lines earlier. This just means that the database will use the ID column as the unique identifier. So it's similar to the unique keyword, but primary key just means the database is going to treat it as special too and make sure that it is uniquely identifying your data. But what's interesting is this. Notice if I scroll back up to people, people were sort of similarly structured, but with different attributes. Like up here, we had a person has an ID, a name, a birth year, and a primary key of ID. So ID is, again, integer. Name is text, but not null, because it'd be weird to have a human with absolutely no name textually. Birth is going to be numeric, but the primary key of people is ID as well. So those are the unique columns that the database will just treat special. Why? Well, we just looked at shows. We just looked at people. Let's focus now on this one down here, stars. How do you determine who stars in a TV show? Well, we had two columns, the show ID and the person ID. This is the incarnation of a many-to-many relationship. One person could be in many shows. One show could certainly have many people in it or writing for it. But notice this. Within this table of two columns, show ID and person ID, there's what's going to be called a foreign key called show ID that references the shows table's ID column. And then another foreign key called person ID, though I could call these things in parentheses anything I want, that references the people table's ID column. Now, you're not going to often have to type commands like this. Again, you set the database up once in the beginning, typically, maybe with some help from a TF, maybe with help of Google or the like. But once your database is designed, it's back to the CRUD, like create, read, update, delete, the selects, the inserts, the deletions, and the like. But what's this implying? These keywords like primary key and foreign key are what are doing in code what this picture was painting a moment ago. These lines here are drawn literally to line up with the corresponding things. People's ID lines up with person ID. Show's ID lines up with show ID. And so you're just seeing graphical version, graphical code that creates these relationships. Now, given that, let's actually see what these things look like. So let me go back to VS Code here. Let me clear my screen. I'm still within SQLite with shows.db. Let me go ahead and do what I do with like any new database. If I ever download something or I'm trying to wrap my mind around a problem, usually it doesn't come with a pretty picture or a 3-hour lecture to explain what the data set is. Rather, you just have the data set and your own knowledge of SQL. So let me play around. So .schema shows me all of the tables. That might be a starting point. OK, this is interesting. I know what people are. Let's go ahead and show me all the people. So select star from people. I'm just trying to wrap my mind around what this data set looks like in a more user-friendly way. OK, that's already a lot of people. As you see the years flying by, there's been a lot of people in the TV business. So this was maybe not the best query to run, but this is indicative of just how large this data set is from IMDb. OK, when in doubt, and whenever you lose control over your computer, Control-C is your friend to interrupt. What would have been better? Because I don't think I need to know all of the million people in the world. I could do like, limit me to 10 people. All right, and that's enough now to get a sense of like Fred Astaire. It has an ID of 1, first person ever. Birth year of 1899. Lauren Bacall and all of these other people from yesteryear, you see that they are the first 10 people in the database. So there's an example of some of the data. Now, if I want to wrap my mind around what a show is, I know it technically, I know it from the picture, but let's just look at some raw data. So instead of saying select star from people, let me go ahead and select star from shows, limit 10. And OK, I've only heard of or seen a couple of these, but these are older shows at that. But I see that every show has an ID, a title, a year in which it debuted, and a number of episodes. But perhaps most opaque is going to be this. Select star from stars, where this is the table that associates people with shows. Am I going to see any names or show titles here? Not according to the definition we saw earlier. Oh, I should have done my limit. Let me interrupt that. Let me do that again. Limit 10. No. And this is where now you're definitely in the programmer world, because like this would be the most annoying spreadsheet to use on your Mac or PC ever. If you just had like a sheet with all of these numbers that associates one thing with the other, like my God, how do you figure out who this is or what this is? You have to like manually Control F or Command F looking for the data. But a database doesn't care. Once you know SQL, you can sort of stitch these things back together. So what you're seeing here are foreign keys. Foreign keys. Why? Because show ID corresponds to the same numbers from that other table called shows that has a proper primary key called ID. Person ID is a foreign key in this context because it refers to numbers that belong to, really, the people table and its ID column. So this is just a way of somehow linking them. And so if you think of, I always like think of this in my mind's eye as this. If this is like the people table, this is the shows table, and there's this middle table in between, the stars table, there's some way of like stitching those two together by lining up the IDs of one with the other and getting back some more data. So let's actually play with some of this data. How about we start where we emphasized earlier, genres. So let me go ahead and take a quick look at all of the genres in this database. So select star from genres. Star is usually going to be a little overwhelming, but it just gives me a sense of what the data is. But let's actually look at, let's go look at all of them there. OK, that's a lot. These are all official genres from IMDb. Let me, oh, OK, it went OK. It wasn't terribly long. Let me filter that down. So from genres where genre equals comedy, capital C, just based on the data I'm seeing. OK, so what am I seeing now? And in fact, let me limit this arbitrarily to 10, though I could limit it to anything I want. Here are 10 comedies. What are they? Well, who the heck knows? Like, all I know are the 10 show IDs. Now, I could do something like this. As we've seen before with SQL, I could do, all right, well, let's figure out what this show ID is. Select star from shows where the ID of the show I'm looking for equals what? 62614 semicolon. So I could like manually look it up by cross-referencing the other table. OK, so that was the show in question there, the first comedy in the data set. Let me look up the second one. So instead of that, let's do 63881, enter. OK, so that's that show. And let's do one more. And suffice it to say, this is just getting tedious and vulnerable to mistakes quickly. This surely can't be the way to do this. And indeed, SQL is going to let us do this a little more powerfully instead. Let's do this. Instead of getting this table temporarily with all these show IDs and all these genres, let's refine the query. So let's just select the show ID from the genres table where the genre equals, quote unquote, comedy. Now I have a big list of show IDs, all of which are comedy. How many? Well, I can combine ideas from earlier. I can just count all of those show IDs, or star if I want to just do that too. But I can count all those show IDs, 48,706 comedies in IMDb's database for TV shows. So it feels like a lot. But how can I now use that information and get back the titles of comedies in the database without doing it manually? Well, let's do this. I have a moment ago this query. Select the show ID from genres where the current genre is, quote unquote, comedy. What if I kind of nest these queries, kind of like grade school math in parentheses? What if I combine this whole thing in parentheses? And now let me select what I really want. Let me go ahead and select, how about the title of all shows where the ID of the show is in this list of show IDs. So if you agree that the shows table has an ID column, which is its otherwise known as its primary key, the unique ID that identifies it, just like our Harvard IDs, our Yale IDs, and you agree that per a moment ago, this shorter query will give me back just the show IDs of all of the comedies in the database, you can actually combine or nest these queries together. It's going to respect SQLite order of operations with parentheses, just like grade school math. So the thing in parentheses will be executed first. That gives it back a list of IDs, like what, 48,000 IDs. And then this query, the outer query, is going to get the title from all of the shows where the ID of the show is in that big list of 48,000. So if I now execute these together, I think the list is still going to be a little long, but let me execute it together. Now I see this long list of outputs, a little overwhelming. Let's go ahead and maybe limit it to just 10, as before for discussion's sake. And now I see 10 comedies ordered arbitrarily from however they're in the database that happen to indeed have comedy as their genre. If I want to do this a little more cleanly, I could do this. Let's see. Why don't I order by title, ascending order, which is alphabetically, or the default is also ascending, limit 10. Now I see the top 10, weirdly named things with hash symbols, presumably to get their titles up to the beginning, or maybe these are hashtags. Here now we have alphabetically the top first 10 shows that are comedies. Any questions on these kinds of queries? It's kind of a lot, but at the same time, it's just like composing the smaller ideas from before into slightly more useful queries. Yeah? Do foreign keys have to set the relationship? When you create the table, the programmer or the database administrator would create that relationship by using those keywords primary key and foreign key that teaches the database what is related to what per the picture. So you do that once. And now, I being the sort of programmer who's familiar with the database, I am just using these foreign keys in a manner consistent with their design. And this is where it's useful at some point, even if no one hands you a picture, to make sure you understand the database, because that's going to inform literally what you type in SQL to get the data you care about. Well, let's do something a little more precise. How about, very reasonable question, and honestly, this is exactly what imdb.com and the app are for. What if you want to find all of the shows that Steve Carell is in? Like, kind of a reasonable query, like literally something someone might type into Google, or more specifically IMDb. It's not really obvious at first glance how to do that, though, because, right, like from my database, if these are my 6 tables, well, I can pretty easily get Steve Carell from here. But I can really only get his ID number, whatever that is, his name, which I know already, and his birth year. OK, interesting, but has nothing to do with the shows that he's in. I can look at shows over here. But there's no mention of Steve Carell, right? Because there's no person ID here. Where is that relationship implemented? Well, it's implemented down here. So how do we do this? Well, here's the perfect example of a lesson we've been trying to emphasize for weeks, of taking these baby steps, like break larger problems down into smaller ones. And let's do something like this. Let's just get everything I know about Steve Carell from the database. Let's select star from people, where the name of the person is, quote unquote, Steve Carell. I just want to see what data we've got. And here's what we have. OK, there's only one Steve Carell, born in 1962, and his unique ID is 136797, according to IMDb. This isn't some like global actor identifier per se. All right, well, how do I get now all of the shows that Steve Carell is in? Well, I could do this. Select star from stars, not to confuse the two. One's the symbol, one's the table name, where person ID equals 136797. So I think this will now give me everything from the stars table that relates to Steve Carell. OK, and you'll see person ID is the same, because I'm literally searching for just Steve Carell. But there are, what, like 20 or so shows that he's been in. All right, well, here's where things would get tedious. What are those shows? Well, I could do select title from shows where the ID of the show equals, and here's, whenever you copy paste, you're probably doing something wrong. OK, he was in the Dana Carvey show. Familiar with that? Well, let's do another one. We'll copy paste this, where ID equals this. Over the top, another. And if we keep digging, we'll probably find The Office. But my God, like that's going to take forever to do 20 queries manually. It's not very dynamic. But what if we just nest these queries a little more dynamically? So let me start from the beginning again. What if we go ahead and select everything we know about people whose name equals Steve Carell. That gave us earlier this data. I don't need all of that data. I know his name. I don't care about his birth year. So let's change this to just be, give me the ID of Steve Carell. And that gives me back now this smaller temporary data set. All right, can I now use this inside of another query? Well, let me wrap the whole thing with parentheses. And now let me say select star from the stars table, where the person ID equals this. So I'm deliberately not using in, because I'm assuming there's indeed only one Steve Carell in the world. So I'm not getting back a list of Steve Carells. I'm getting back the one and only in this case. So equal is fine. In is when you have multiple. Equal is when you have one. Let me go ahead and hit enter now. OK, that's more data than I need. I don't need like 20 copies of Steve Carell's person ID. So let me hit up. Let me go back and let me just get show ID from Steve Carell. And now I have a list of just the 20 or so show IDs that he has been in. All right, how can I now use this? Well, let me hit up. Let me put the whole thing in parentheses. And now let me select what I really want. Select title from shows where, and here's the final flourish, the shows table has an ID, has a title, has a year, and has an episode. And what I really want, though, is to check which shows have ID that is what? Anyone want to finish the thought? I just want to, yeah. Exactly, ID in this. And this is getting ugly, and when you actually write your queries in like a text file, you can format them nicely and indent them. My font is just getting, I don't want to make it too small to fit everything, but now we have 3 queries. One is in doubly nested parentheses, then there's the middle one, then there's the outer one. So this last query is going to get me the title from shows where the ID of the show is in this big list of 20 or so show IDs that Steve Carell is in, and I knew that because I looked up his name here. And notice what I did not do this time is I didn't manually hard code his ID number. There's no need. That would be kind of a bad way to implement a website if you're using a database underneath the hood. You want the IMDb for real to search for whatever the human typed in, and no one's going to know Steve Carell's person ID or anything else. So here, we've done this all dynamically. And now, if I hit enter, I think I get all of his shows. Let's go ahead and order this by title just to make it tidy. And you probably will see at least one or more shows that you know. And probably the most popular is ... The Office. So this is literally the kind of query that's being executed underneath the hood when you go to websites or apps like IMDb. Your textual query is probably being plugged into a longer SQL query like this, where some programmer at IMDb probably wrote this whole query in advance, weeks, months, years ago, and they're just somehow plugging in the value that you, the human, typed into the search box or the like. Questions now on finding this data or any other? No? OK, so where else could we go with this? Well, let's consider how else we might combine data. Suppose that the next question actually, perhaps appropriately, would be focusing in on not just like people and shows and these stars, but how do we kind of like gather more information about the shows themselves, like the genres, the ratings, or the like. So indeed, let's focus on just these two tables here. Recall that every show has an ID, a title, a year, and episodes. But it also might have one or more relationships with rows in this other tables called genres. And this is so that a show can be a comedy, can be a drama, can be any number of other things, one row per. So you would see the same show ID again and again and again with a different genre written in English, like comedy, drama, or the like. Well, how do I kind of reconstitute that data? Well, turns out there's a few different ways to do this. And let me propose that we introduce this keyword here, join. And this is really the most powerful of the keywords in SQL itself. It doesn't have to be used. We've seen with nested queries that you can still select data across multiple tables. But here is another way. So let me do this. Let me go back to my SQLite database. And let me select sort of in one breath exactly the data I want. Select star from shows. And let's just limit this initially to 10 to see what it looks like. All right, that's again the shows data. Select star from genres. Let's limit that to 10 too, just to wrap our minds around it. And now this is not that useful. However, the data in the leftmost column here is the primary key in the shows table. These are just unique IDs. The data here in the genres table, recall, show ID is the foreign key. So it's the same numbers, but just copied into another table so that we can have this relationship across them. How do I kind of line up these numbers with these numbers to get back like a wider table that has title and year and episodes and genre and heck, ratings and all of that too if we want? Well, you can join these tables by just telling the database what to join on what. So let me do this. Select star from shows. Join that table, though, on the genres table. Well, how do you want to join those two tables? And again, the two tables from the picture looked like this. How do you tell SQL programmatically to sort of, put one of them right next to the other, line up all of the IDs so that you just get one larger data set? Well, we can use indeed this syntax called join. So back to VS Code here. And let me join these two tables. Sorry, typo here. Join genres on the shows tables ID column, aka its primary key, equaling the genres tables show ID column, aka the foreign key. So in other words, it looks a little cryptic, but I'm just telling SQL how to line up these two tables and what column to match with the other so that the numbers line up and I get essentially a wider table. Let me go ahead and hit semicolon and enter. And this is now going to give me a lot of data. We might have to interrupt it. But notice, even at a glance, we're getting the ID, the title, the year, the number of episodes, the ID again, redundantly, but that's to be expected if I'm joining them, and the genre all the way on the right. Let me hit Control-C to interrupt. Let me just limit this to The Office. So where title equals, quote unquote, The Office. So we can focus on just one sample datum. And here, fun fact, there's been more than one Office. The one that you all probably like is this one that started in 2005 with 188 episodes. Its ID in the shows table is 386676. That's confirmed over here too. So again, we've just joined the two tables. How? By lining up those fields. But now that we can see that almost all of the Offices produced over the decades are comedies, except for this one. There was a version of The Office produced in 2001 that was considered more of a drama. No, unsure if it's related to the other. How can we link in other data? Well, let's go ahead and link in ratings too, or instead. So instead of joining this with genres, let me go ahead and rewind here and join shows on ratings on shows.id equals ratings.showid. And let's limit it to The Office 2 for discussion's sake, where title equals quote unquote The Office, semicolon. And now you can see that among the various offices, it looks like the one that most of us probably know and love is the highest rated, also with a 9.0, with like 585,000 people having cast votes for it, whereas these other shows seem to have been less popular, and perhaps that's why, indeed, you see fewer episodes for them as well. So even though we've put the data in multiple places, you can still kind of reconstitute it by lining things up in this way and rejoining the tables. Questions now on this? Like, this is the heart of what SQL does and what relational databases do for you. Questions? All right, a few final features. Like, there's not all that much that, SQL takes practice like anything else. But in terms of syntax and capabilities, let's just introduce you to a couple of final features here and how problems that arise and how we might solve them. Let's do this as well. So let me go back into VS Code here, and let's just find out Steve Carell's information again. Last time we did it with this nested query by getting his ID and then the show IDs and then the titles for those show IDs. With join, you can do it a little differently. And any of these ways are fine. One might become easier to you mentally than another. Let's go ahead and select the titles from what? Let's select the title from the people table. And I'm going to hit enter. And when you're using SQLite 3 interactively, if you ever find yourself with a prompt that says ... angle bracket, it means you're continuing your thought onto the next line. If you didn't intend that, you can sometimes hit semicolon to just end the thought and hit enter, and just even if it triggers an error. But this is one way of formatting my queries now a little more nicely. I'm just going to add some white space so that it's a little easier to read. What do I want to select? Well, I want to select the title of shows from the people table joined with the stars table on the people table's ID column equaling the stars table's person ID column. So in other words, if you think back to what people are and what stars are, one has an ID, one has a person ID. I'm just now connecting those two tables. I'm joining those two. But I want to do this as well with another table. Let me additionally join in. So now I only have two hands, but now I'm putting a third table joined in together here. Join shows on stars.showid equals shows.id. So this is now linking three tables together. But I only care about this for one person, so where the name of the person equals quote unquote Steve Carell. So more cryptic to be sure, but what we're doing with this query is just taking all three tables that we care about, and we're joining them all together at once using this new join syntax, literally telling the database what columns to line up with what. And then we filter at the very end, just like before, to get back, if I hit enter, the answer we want, which in this case is a little slower at the moment, but that same list of 20 or so shows that he's been in. There's one other way to do this. And again, these are all in the slides online, so you can repeat them without having to jot down everything, and we'll put them in the notes too. But there's another way to do this. I could also use an implicit join. So that was an explicit join because I literally typed the word join multiple times at that. But let me go ahead and select the title from these three tables: people, stars, and shows. And this might just be nicer because if you know what tables you want to select data from, just enumerate them, separated by commas, which you might prefer in your mind, where the people ID equals the stars person ID, and the stars show ID equals the show's ID, and the name of the person equals Steve Carell. So this is an implicit join. And honestly, I constantly reference my notes for some of this stuff too. It's not the kind of thing that's going to come like this to you after just one day. But it's just a different way of expressing the same thing. I want to select data from three different tables. And hey, SQL, here is how I want you to line those tables up so that I can get like-related data for Steve Carell. And this now will achieve the same results, ultimately. Let me hit enter. And there we go. So a little slower, and the performance might vary based on computer, based on implementation of SQL, but I think I still have the same answers. Now suppose, as I'm often do, and I had to look it up again last time, suppose you forget how to spell Steve Carell's name. Is it 2 R's, 2 L's, or the like? Well, I could also do something like this. Select, well, let's just keep this simple. Select star from people where name equals. I've been deliberately getting it right so as to not embarrass myself. That's the Steve Carell I keep querying. If you forget, well, you could try searching for just Steves, but interestingly, there's a bunch of Steves. We don't know when they were born. But that's probably not the Steve Carell we want if we don't have his last name. So I could alternatively do, well, it's Steve, and then it starts with a C, I think. Well, it turns out there's another wildcard you can use in SQL. We used the asterisk to select all of the columns. You can, in quotes, use a % to say C something. So there's 0 or more characters after the letter C. And now this doesn't work, because now I would be literally looking for Steve space C something. But recall earlier I mentioned that one other keyword, which is for fuzzier matching, so to speak, where it's like not exactly what you're looking for, but it's like what you're looking for. If you instead say where his name is like Steve space C something, now we'll get back a whole bunch of Steves, but I think now I could probably find the one I'm actually looking for if I don't remember his name. You can use multiple %. If you forget what his first name is, you could reverse the order. But that, too, is a very powerful SQL feature at that. Questions on these queries here? Yeah? Sorry? What about it? Oh, yeah, sure. So the query I used here, there's a lot of Steves whose last name starts with C. Oops, too far. The last query I executed was this one here. So where the name is like, quote unquote, Steve C %. So that's just another tool for your toolkit here. But you'll perhaps have noticed that those two, prior to that query, the joins I did were sort of slow. And honestly, this database isn't even that big. Like, yes, it has tens of thousands of rows in it. But like in the real world, and most of the apps you and I use a lot every day, or websites, like there's millions, even billions of rows of data. And like if I had to wait on like my computer here or my code space like a second or two to get the data, like that's not going to work for millions of users or customers, certainly. So how can we actually improve things? Well, it turns out another upside of a proper relational database is that it's not just a spreadsheet where the onus is on like you to like find the data you're looking for. You can also tell the database to index the data for you. An index is an efficient cheat sheet for finding data fast. Like books in the real world often have indices at the end of the book where you can look things up alphabetically, and then you can cross-reference it for the pages that that topic appears on. Same idea in a database. If you tell the database in advance that you want to search on a certain column frequently, you can tell it to build a fancy index that will just allow you to search that column faster. By default, these columns are going to be searched most likely by a linear search, like not even binary search, because the data might not be sorted because it came in any order. But if you create an index, you're probably going to get something closer to logarithmic than linear, and that's going to be a big plus overall. So let me do something simple here. First, let me turn on a SQLite specific feature that just is going to time all of my queries by writing .timer on. I just want to keep track of how long each of these commands takes. This one is not a slow command, so this is just going to be relative. But let's just select everything from the shows table where the title thereof is The Office. Let's see how long this relatively simple query takes. All right, not very long at all. In real terms, like less than a second, 0.035 seconds. So not slow by any means. But if you've got hundreds, thousands, millions of users, like every one of those milliseconds could very well add up. So can we do better? Well, we can if I do this. If I use syntax like this once in the beginning of the design of my database, I create not a table, but an index with some name on a specific table on one or more columns. I can give a clue, a hint to the database in advance saying, please optimize with some secret sauce searching or selecting on this column in this table so that my searches are faster. So let me do this. Let me go back to VS Code here. Let me create an index called, how about title index? I could call it anything I want, but I want to search faster on titles. So I'm going to call this a title index where, title index on the table called shows. And then in parentheses is the syntax, the column called title. So again, I've just borrowed this canonical syntax, and I've just translated it into something that's TV show specific. All right, what is this going to do for me? Once I hit enter, this is going to create in the computer's memory, the database's memory, something called a B tree. It's not a binary tree. A B tree is actually a potentially more efficient data structure that we didn't talk about a few weeks back in week 5, but it looks a little something like this, which looks similar to a binary tree. But does anyone notice what makes this not a binary tree? Exactly. Binary tree, by implying 2, has no more than 2 children per node. But here's a perfect example, 1, 2, 3. And there could be 4 children, 5 children, or more. But the effect of that, if you have a very wide tree, the upside is that it's like very short. Like it pulls the data higher up, closer to the node, to the root node. And recall that the root node is where we began our searches in the past. Whether it was a BST, a binary search tree, even a trie, or other data structures, we always began at the top. So the higher up you can pull the data, even if it makes the data structure very wide, you're going to be able to do boom, 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 look up queries, look up data probably much faster, certainly than if it's just a very long list, like a column by default. So with that said, let me go back to VS Code. I didn't create the index yet. Let me go ahead and hit enter and create it. All right, it took a moment. It took like half a second, which obviously is not that slow, but with more data, that could have been even slower. But it's a one-time operation as of now. And now, let me hit up. And let me select the same data from shows where title equals The Office. Last time, just a moment ago, it took 0.035 seconds. No, not slow, but also that's going to add up if I have lots of users of IMDb. Let's go ahead now and execute the same query again. How long did that take? 0.001 seconds now. I mean, practically nothing. And so that's the sort of opportunity now. When you've got lots of data and you want to really speed up these searches, these indexes, these indices that just create for you these magical data structures in the database's memory, it allows you to search on columns that you are pretty sure you want to search on more effectively. Now, by contrast, if you've ever used like Google or Bing or some search engine that has advanced search, some of those text boxes that you can search more precisely and might very well be slower. Why? Well, probably you don't want to go crazy and just index every column on every table. Why? What might be the intuition? Like if logically indexes speed things up, why not index everything? There's always going to be a trade-off here. What might that be? Yeah. Yeah, it's going to take a lot of storage, right? This is just a slide on the screen, but like this has to go somewhere. Like this needs space in the computer's memory or on the hard drive or the like, and that's fine if you have unlimited space, but odds are like you don't, and that's going to get expensive for different reasons. So maybe you only want to index certain columns and certain tables and not all of them, because you know what? Even if a user really wants to search, maybe via advanced search on some other column or table altogether, fine. If once in a while a query is slow, like we're probably getting the bigger bang for our buck by optimizing the common cases, the more popular queries that people actually care about too. All right, so let's come full circle and bring this now back to how we actually began, which was with some Python code. So it turns out these are not either or decisions. It turns out in the real world, developers are constantly using 1, 2, 3 languages at once. In fact, next week I rattled off HTML, CSS, and JavaScript, one of which is a proper programming language, but those languages are often used together. Totally normal and common to use Python and SQL, or Java in SQL, or Swift in SQL, or any number of different combinations with a database language. You might use your preferred programming language, Java, Python, C++, to create the user interface and the logic that builds that implements the program itself. But for your data, like SQL is a really good candidate. And indeed, we've seen already that SQL can just speed up certain operations. You can collapse 15 lines of code into just one, and you can use these things together. So let me come back to, I'm going to quit out of SQLite. I'm going to minimize my terminal window. And here's where we left off before with favorites.py. With favorites.py, everything was being stored in favorites.csv. And recall that we eventually imported that CSV file into favorites.db automatically with .import, just so we can start playing around with SQL. But we can now tie these two together. And a way to do that is as follows. CS50 has a library for Python. You might recall having available getString, getInt, getFloat. You don't strictly need to use them in Python because it's much easier to just use the input function and then try, accept, and convert things to int or float or the like. But it's a lot more work to use SQL in Python without a third-party library. A lot of the commercial options or popular open source options are actually just complicated to use. So CS50 does have a very useful function inside of its library for Python that you should use and must use for the problem set that just makes it easy to execute execute SQL inside of your Python code. But it's built on top of a very popular open source alternative. So you can use that too in the real world. So the documentation for that's at this URL here, but I'll show you what we need to know here by focusing back on favorites.py. So what I'm going to do here as follows is this. Let me delete everything from favorites.py except for, let's say, this. From CS50, import SQL in all caps. So that's importing a SQL feature from CS50's library that's going to allow me to open a DB file in code. How do I do that? Well, let me create a variable called DB for database, though I could call it anything I want. Let me call this SQL function and pass in, using special syntax that's not CS50 specific, it's an industry thing, SQLite : ///. Unlike every other URL you type, this one literally has 3 in this context here. And then the name of the database, which in this case is favorites.db. So this is just a way of telling this SQL library that we wrote, but that works exactly like third-party alternatives, open favorites.db using the SQLite technology, if you will. All right, let's just ask the user a question. Give me your favorite problem. So we're going to use input instead of getString, but we could use getString, but they're pretty much the same for our purposes. Let's ask the user for their favorite. And now, in Python code, let us select from favorites.db all of the rows where students specified that problem as their favorite. So in SQL alone, it would be this. Select star from favorites where problem equals, and I'll do, well, whatever my favorite's going to be, like problem equals Mario, for instance. So if I were just using SQL, I would literally write something like that. But I'm in a .py file now. Like I have to use Python syntax. But Python supports strings. SQL is just text. It's just a string. So I could certainly just put my SQL code in a string, perhaps, and then pass it to a Python function. And here's the bridge between the two. If you just treat SQL as any old text, we can put it in a string and execute it. So let me actually do this. Let me go ahead and create a variable called rows, which is eventually going to contain all the rows from the database. Let me go ahead and select db.execute. This is the one function you need to know about inside of CS50's library, and it literally executes a SQL statement. And then in quotes, you pass it literally what you want to execute. And let me go ahead and close the parenthesis at the end there. And now let me just try this. So for row in rows, let's iterate over all of the rows. Let me go ahead and print out, how about row, quote unquote. And what do I want here? Let's print out the timestamp of that person for kicks. All right, let me open my terminal window. Python of favorites.py, crossing my fingers here for sure. Enter. There we go, favorite. So I'll type in Mario. OK, so I got back, it's not very interesting, but I got back all of the timestamps of students who typed in Mario that we imported into this database. Well, what I really care about is how popular Mario is. So let me change this a little bit. Let me change this to count the number of rows. And let me keep it simple. Let me give an alias like I proposed earlier, like as n, where n is a number, so that now down here, I can actually just do this, print out the value of n. All right, let me go back to my terminal window, run Python of favorites.py. Let me type in Mario, enter. OK, 39. Now, technically, I'm cheating. Like, honestly, if I'm executing select count, we've seen before, it only ever returns one row, not multiple. So there's really nothing to iterate over. But it's working fine. It's just iterating once, but I'm getting lucky. So technically, what I should probably just do is this. I should probably give myself like a variable called row, set it equal to the very first row and only row that came back, and now print out that row's n column. Let me rerun the program. I'll type in Mario again, enter, and I still see 39. So this, of course, I don't strictly need to do this. I don't really need a variable. I can do rows bracket 0 instead. But let me focus on what this library is now doing. So per the documentation, what the CS50 execute function always does for you is it returns a list of dictionaries. So if your query returns nothing, like no matches, you get back an empty list. Like open bracket, close bracket, nothing in it. Any loop is not going to execute anything useful because there's nothing in it. If, though, you get back one row, you're going to get back a list of size 1, inside of which is a single dictionary. That dictionary is going to have keys that correspond to whatever you selected, be it the columns or the count. So when I selected star before, I would have gotten all of the columns. That's how I was able to access timestamp. Here, I'm just selecting count, and I don't want to have to type this down here. That would just look kind of atrocious. It would work, but it would look weird to just keep retyping count, paren, star, close paren. So I just created an alias called n, just to make my life easier or cleaner down here. So to be clear, the CS50 execute function returns a list of dictionaries when you're using select, and that is how I can now get back the first and only row and then print out that row's n value. It is identical to, let me do this. Let me highlight this whole line of text. Let me, in my terminal window, run SQLite 3 of favorites.db like we did before break. Let me just copy paste this query, enter. That's the table I got back earlier when we played with SQL manually. And so when I get back this table, here's the key, here's the value. And I only have one row, which is why I'm just blindly indexing into rows bracket 0, because I know there's always going to be an answer there. It's going to be 0 or 1 or more. But I know now it's going to be called n because of this here. So what have I just done? Well, this is SQL down here. And this is just me being like a data scientist asking questions about my data, just using like black and white SQL queries. This is me now being a Python programmer who wants to talk to a SQL database using Python. And the bridge we're using happens to be this CS50 library. But again, there's third-party free libraries you can also use as well. Ours is just very simple. And indeed, the documentation will explain how execute behaves a little differently for inserts, updates, and deletes. You don't get back a list because you're not selecting anything, but you do get back some return values. Questions on this? That's the last of our Python code that ties everything together in spirit. Yeah? What this one here? Yes, so db.execute, by definition, returns a list of rows. And each of those rows happens to be a dictionary because it's convenient, key value pairs. If I'm selecting the count of rows, I just know from having learned SQL an hour ago that this is always going to give me a single row whose column in this case is called n. So if I know it's a single row, I can just blindly, just like in C, go into that list or an array in C and go to the first location and then treat that as the single row. What you don't want to do is this. Even if you, the human, know the query returns one row, you can't just magically change the variable name to be singular and expect to have only one value. You will always have a list. So even if there is only one value in it, it's up to you to do something like this to get at it. Or if you prefer more succinctness, you can do rows bracket I bracket n. That'll achieve the same thing without a variable. Yeah? Good. So I have been misleading this whole time and cheating because this is only ever going to return Mario. I'm ignoring the favorite that the human typed in here on line 5. So let me fix that. And that's going to lead us to some of the problems that arise ultimately with SQL. The right way to solve that problem, let me get rid of my terminal window here. The right way to solve this problem is not to use an F string like we did in Python generally, because SQL queries, as we'll see in a moment, can be dangerous. When you want to plug in users' data into a query that you've written most of in advance, you had better use a placeholder, namely a question mark in this case. This is somewhat specific to CS50's library, but we just borrowed the convention that like every other library uses too. In the world of SQL, single question marks are used as placeholders. And the way you do this is as follows. If you want to plug in a value for that question mark, just like in printf in C, You specify as a second or a third or a fourth argument all of the values you want plugged into this. So in C, weeks ago, we were using %s. Same exact idea. In SQL, it's a question mark that you use instead. This now, if I open back my terminal window and I run python of favorites.py, type in Mario, I should still get 39, but now I can also type in Scratch perhaps and get 44 for that very first piece at 0. And that one is even more popular here. So this now is correct. It would work to use an f string here and then plug in a value like favorite here, but you'll see in just a moment, don't do that. You will expose yourself to potential hack or attacks by trusting the user's input. And so in fact, let's transition from that to exactly some of these kinds of challenges, namely 2, before we wrap up. So in the world of SQL, especially when it's used at scale, at the Twitters and the Googles of the world, like lots of data is probably coming into the database all at once because multiple people are opening their phones at the same time around the world. They're clicking on the same links roughly at the same time around the world. When you have thousands of people all using your site at once, like order of operations is going to be important. But unfortunately, in SQL and in other contexts of computing, there's this risk of what's known as a race condition. So for instance, has anyone ever seen or liked this? This is like, yes, the world record egg. All right, it's like this thing that was very popular a while back. It's still kind of going strong. But if you go to the Instagram profile for world record egg, the goal was to make the most liked Instagram post ever. And they did pretty well. It's just this. It's just a picture of an egg. Now, at the height of the popularity, like there might have been hundreds, thousands, tens of thousands of people clicking pretty much at the same time on this egg. So it actually creates a potential problem with the integrity of Instagram's data. Why? Well, if you're having all these requests coming in at once, how do you possibly keep track of all of them and update your counter in a way that can keep up with all of that traffic? Why? Well, let's just hypothesize what Meta, formerly Facebook, was doing underneath the hood with Instagram if this were their code. So suppose, for the sake of discussion, that Instagram servers are using a mix of Python and SQL. Probably not using the CS50 library, but they could absolutely be using those 2 languages or 2 others together. Suppose they do this in order to update the number of likes for that post. They first execute a SQL query like select the current number of likes from a table called posts, where the ID of the post equals whatever the unique identifier is for that specific egg in the table. And then they store the result in this rows variable, just like I did. And then they do this. They create a variable called likes. They set it equal to rows bracket 0, so the very first row in the result set. And they get the likes key. So this is literally what I just did with the count. Let me hypothesize that Instagram does something similar with the total number of likes. Why are they doing this? Because they then want to execute a third line of code that executes update the posts table, set the new number of likes equal to something where the ID of the post equals this other thing. Now notice, just like in printf, there's the comma-separated list of values. They want to update the current number of likes from the current value to the current value plus 1. So it's likes plus 1. And then we plug in the ID for this. So suppose this is what Instagram's doing. Unfortunately, whenever you execute multiple lines of code independently, and you're so popular like Instagram that you have thousands, hundreds of thousands of servers potentially, it is quite possible that if you and I and everyone else in the room clicks that egg at the same time, it's not going to be the case statistically that like 3 lines of code are executed for me, and then 3 lines for you, and then 3 lines for you. They're probably going to get interspersed. Like this gets executed for me, and then this gets executed for you, and then they get back to doing work for me, and so forth, just to kind of multitask, just like a human might, but at a super speed here. The problem, though, is if these lines of code get interrupted, what could go wrong? Well, suppose that Carter and I both click the egg at the same time, and suppose the current number of likes back in the day is 100. That stores in this variable the value 100. But if we click so close in time, we might get back the same answer to this select query. As of that moment in time when David and Carter clicked, it had 100 likes. But then this last line of code is executed for me and then maybe Carter. Because that answer, the state of the database, was stored in this variable, then both Carter and I will result in this line of code being executed with the same value. Update the posts table, setting the likes equal to 101 for that post's ID. Why? Because again, if each of these lines of code running on different servers are checking the value of the current number of likes, but then getting interrupted because Carter clicked the darn thing too, and then resuming their work on my behalf, we might have a race condition where the code is sort of racing to finish but getting interrupted by other users' clicks. And the problem with that is that if you are inspecting the value of some variable, or in this case a database cell, and making a decision based on it, like how to update it, you might now lose data. And Instagram, probably not good for advertising if they're losing likes. And so that's probably a problem, not to retain the value 102 and instead insert the number 101 twice. It's actually similar in spirit to a story that was told in a databases course I took myself years ago, whereby it's somewhat analogous to kind of a contrived scenario involving like a refrigerator. And this is the closest thing to a refrigerator we could get on stage. But imagine you've got like one of these little dorm fridges in your dorm too, and your roommate. And maybe both of you, as the story was told to me, really like milk. And one of you's at class, but the other of you comes home and you open your dorm fridge and you're like, oh, darn it, we're out of milk. And so you close the fridge, you walk across the street to CVS or some other store, and you get in line to buy some milk. Meanwhile, your roommate gets out of class, they come back to your dorm room, they're really thirsty for some milk, they open up the fridge, they say, oh, we're out of milk, and then they take a different route perhaps to CVS or some other store nearby, get in line to buy some milk. Fast forward some amount of time in this very contrived story, and what happens, oh, damn it, we now ended up with like 2 gallons of milk, and there's no way we can fit gallons of milk in there, let alone 2 of them. So that's a problem. But what's the relationship to this here? Well, both of us, did what? Exactly. Exactly. So to summarize, both of us had a very similar thought process, made a similar decision based on the same information, not realizing that the information, the fridge, was in the process of being updated. And it, of course, in the Instagram world happens like this. In the fridge world, it might take a few minutes, but the problem is ultimately the result of our having made a decision about the state of the world, and the state of the world was in the middle of being updated. The queries got commingled with others, or in this case, someone was already on their way to the store. So what's the solution in the real world? Well, you could, very simply like take a Post-it note and put like gone for milk so as to communicate to your roommate that they should not inspect the value of that variable and make a decision on it. Why? Because it's not yet consistent with the outcome that's about to happen. You could be more dramatic and you could actually lock the fridge somehow, put a padlock around it or the like, so they can't even get in there, and that would achieve the result, the same effect too. And that is actually pretty much the solution to this problem in code too. It's not safe, it's not sufficient to only execute 3 lines of code like this. Rather, what you probably want to do is use additional SQL keywords that we won't spend much time on in the class itself, but these. There are solutions to this problem. You can begin what's called a transaction, and you can more explicitly commit to making a decision, like updating the database to 101 or 102. Or if you realize, wait a minute, Carter's query is interrupting mine, let me roll back to the previous state and just rewind. Let me undo, Control Z, if you will. There's also another keyword that's not so much used anymore in SQL, which is locking. You could literally, back in the day, lock the entire database table, preventing anyone from updating it or making changes or even reading it while someone else was accessing it. That was a very heavy-handed solution because it slowed everything down. But in short, transactions are now a feature of SQL that you won't necessarily need to use yourselves that do solve this problem by doing the equivalent of saying, while David's like counter is in the process of being updated, keep Carter at bay, ideally briefly, and then let his data go through too. It's equivalent to putting a note or a lock on the fridge. And indeed, I mean lock literally. They were once upon a time called, and still are in some texts, called locks on databases too. And the last and the code for which you might do this is almost the same. You simply wrap the 3 queries with a transaction statement and a commit. And the term of art here is that this makes your statements atomic. So atomic means they're either all executed or not at all. That is, they're all very tightly coupled together without interruption. Transactions solves that problem and avoid having 2 gallons of milk. And the last problem that arises, that is tragically so darn common in the real world today, is what's called a SQL injection attack. And it's what I alluded to earlier with the question mark. So suppose you're in the habit of logging in to Yale websites with your NetID or password, or at Harvard, your Harvard key and password as well. Suppose, for the sake of discussion, that the people that implemented like Harvard key login allow you to type in your email address, of course, and your password. But suppose that they are using SQL underneath the hood to check your username and password to make sure that you are David Malan or Carter Zinke or whoever you claim to be. I haven't shown you the syntax yet, but it turns out that in SQL, -- is a special way of indicating a comment. It means ignore everything to the right. So it's just like // in C or the hash symbol in Python. -- just means ignore everything to the right. And we've, of course, seen single quotes. So one way to wage a SQL injection attack is to try to inject malicious SQL code into someone else's database without them realizing it. How do you do this? Well, suppose I log in as malan@harvard.edu, single quote, -- I'm not double quoting anything clearly, and there's nothing to the right of the -- anyway. But this imbalance is going to be useful. Why? Because if I'm a hacker and I'm presuming, someone at Harvard probably is using single quotes to wrap the user's email address and wrap the user's password, what if I try to complete their thought for them and close one of those quotes for them? What might happen? Well, we could do this. Here, for instance, let me hypothesize is the code that Harvard wrote, hopefully not, underneath the hood. So they're using CS50's library in Python, and they're using SQL inside. Suppose that they have a query like this. Select star from users where username equals question mark and password equals question mark. And then suppose they just plug in whatever username and password was typed in. And then if they get back some number of rows, .. they assume I am David. They assume Carter is Carter if both the username and password are in the database. Just end of story there. This is good. This has the question mark placeholders we discussed earlier. But what if you don't quite remember that? You don't quite take that to heart, and you use your more familiar last week f strings, whereby we use these curly braces to plug in values. What if you do this instead? So it's almost the same idea. It's still db execute, but now it's select star from users where username equals. And now notice I'm doing the single quotes, which is required by SQL, but I'm using f strings with the curly braces. And the password equals single quote, password, and then close single quote. The problem is if you're just blindly pasting effectively the user's input into that web form into the username field and the password field, there's nothing stopping a malicious user, student, faculty, staff from including a single quote in their name. Or maybe even, benevolently, if their name happens to have a single quote, as some last names in particular do. So this is very fragile. Why? Well, suppose that if we plug in my malicious value, malan@harvard.edu, single quote, -- notice what happens to username here. The username variable inside of the curly quotes will get replaced with this. And notice, single quote, which the Harvard programmer wrote, malan@harvard.edu, single quote, which I wrote, -- which I wrote, single quote, which Harvard wrote, and whatever else they want after that. What's the implication, though, of the -- Everything to the right is going to be ignored. So the password is never even checked in this scenario. I'm tricking the server into ignoring everything after the -- but I have constructed very cleverly, very maliciously, a syntactically valid query. Why? Because I provided the single quote that's going to finish the thought of that first single quote. And now, I would only know how to do this if I saw the code or if I just randomly try putting apostrophes into web forms and see if things break. That's often how adversaries attack systems. They type in potentially dangerous characters, hit enter. If something breaks, they're not necessarily into the system, but they know that there might be a vulnerability. And then they start trying more methodically things like this. So this then is going to be bad because it effectively grays out the rest of the query. And this query is surely going to return some rows without even knowing my password. And so this logic here, .. means, well, if data came back from this query, Harvard is presumably going to assume that Malan logged in, show him his account or whatever is being protected here. So in short, using f-strings, bad. Using any equivalent like %s in C, bad when it comes to SQL. Using question marks or whatever a third-party library like CS50s prescribes is the way to solve this. Why? Because libraries like ours are designed to at least be smart and be paranoid. And what we will do is this. When you use the question marks and the values are plugged in, we will escape any potentially dangerous characters inside of those placeholders. And so effectively, the single quote will no longer be considered a grammatical single quote. It will just be literally a character in the username or password. So the library takes care of this for you because you're plugging in the username and password as separate arguments. And then we, or the third party you're using, actually sanitize. That is, clean up the data and prevent those bad characters. Now, this is kind of an internet meme that went around for a while. If you've ever driven a car, been in a car where there's like the automatic readers for tolls, this person thought it might be funny to try doing something like this. What are they presumably doing? The presumption here is, whether or not it worked is unclear, is that here's like the end of an actual license plate number, but here's an interesting single quote and a semicolon. That's especially bad because it means you can maybe execute a second query on the database. This is someone having fun trying to drop the entire database table for whatever municipality is scanning through cameras their license plate code. And I would be remiss if we didn't end on this note. At least in computer science circles, there is someone named, no relation to the TF name we put in the database earlier, Little Bobby Tables, which ends with this XKCD comic. And if you chuckle, if you laugh, you're now legit SQL programmers. Nice. Nice. Like every CS student out there knows about Little Bobby Tables. So if you name drop Little Bobby Tables now, like you're in. All right, that's it though for today. We will see you next time.
We're here to cheer for Harvard.
Pass them down.
It's not going to say something like great. Hey, let's go Harvard.
We're nice.
You see that? Look at them. They have the over. It's going to happen. It's actually going to happen. I can't believe this.
What do you think of Yale?
They don't think good. Does everyone have it? Does everyone have their stuff? Does everyone have their stuff?
Probably that it's gonna be legible. It's very small.
I agree.
I know, but it's too complicated.
What houses?
How many extra? How many extra are there? Sometimes.
Yeah.
No, Foho. Four-timer.
Yeah, but you said hope.
Alright, let's just make sure everyone has it.
Probably drunk.
It looks like they're still passing out. Are all the cards distributed? Alright, we can do it now.
What do you think of Yale, sir?
Go on the wing. Do it one more
They
time.
suck?
One more time! One more
Do it
time!
again!
Oh, and there it goes again!
All right. This is CS50. Welcome to week 8. Last week, we learned how to create, read, update, and delete databases using SQL. But this week,
Adam, everyone, happy Halloween. All right, so this is CS50, and this is week 8 already. My thanks to Adam on today, this happy Halloween. In the coming moments, we're going to learn all about how the internet itself works, which of course is a technology that we all use every day, probably using in some form right now. But we'll see that if you start to understand some of the underlying building blocks that power the internet itself, we can actually start to build interesting things on top of it. And a lot of the apps, the websites that you all use every day should become all the more familiar, things that you yourselves can create. And honestly, when things go wrong, you'll have all the more of a mental model for how things work or are not in fact working, so that you can ultimately diagnose all the more issues yourselves. So if we take a look at the internet in the early days, it pretty much was just this. This happens to be, of course, the geography of the United States, and just some of the first points on the internet were these here. This was so-called ARPANET back in 1969, and indeed the internet had its origins here in the United States with just a few computers interconnected somehow initially. That, of course, began to grow over time, such that we eventually had the West Coast connected to the East Coast, and nowadays what you can think of, these dots on the screen it's representing, are these things called routers, sort of computers, or really servers, that somehow have wires or maybe wireless connections between them that allow data to flow from point A to B to C. And then this, of course, has been now magnified across the entire globe, and even above ground as well, so that we can connect all the more readily to systems anywhere. Now, in order to route the data from one router to another, we need to somehow make routing decisions. And this is the kind of thing that the internet service providers, the ISPs of the world, just handle for us. You and I plug our Macs, our PCs into the network here at Harvard, or equivalently at Yale, or we somehow get online via Wi-Fi or cellular technology. And then some of these larger entities, these bigger companies or countries, handle most of the data getting from point A to point B. And if you think about what these routers represent, they're indeed just servers somehow interconnected, not unlike this grid of tiles here, for instance, back in the Zoom days. And in fact, here we have, I claim, a grid of routers implemented here by the course's teaching fellows and course assistants and TAs. And if the goal at hand, for instance, is for Phyllis to route some piece of information, maybe it's an email, maybe it's a request for a web page in the bottom right-hand corner, all the way up to, say, Brian here in the top left-hand corner, suffice it to say, each of these tiles represents a router, a server that can move the data back, forth, left, and right. That packet of information, so to speak, from Phyllis to Brian could take any number of different possible routes, up, down, left, right, to go from the one corner to another. So let me go ahead and hit play on this video here, wherein the teaching fellows play this same role. right, so in this particular case, the data was routed pretty straightforwardly up and then to the left. But suppose that one or more of the staff were a bit busy. Maybe one of the routers is congested. That is to say, just got way more envelopes at a moment in time than it can handle. Thankfully, the design of the internet is such that there's often multiple ways that data can get from point A to point B, maybe going through point C or point D instead. And so there's a resilience there, even as some of the servers themselves might go down. So allow me to propose that we use the same grid of routers now to route the data in a slightly different way this time. So success. You'll see perhaps later just how many takes it took us to actually get that routing right. But it does, in fact, manifest that you can travel different paths in order to get the data from point A to point B. So as we talk about routers, as you think of the internet, I mean, think of those humans as just representing these routers, points A to P and everywhere in between. Now, how did the teaching staff know to route that packet up and then down or left and right in order to get to the destination? Well, all of them were programmed, so to speak, to understand protocols. It's called TCP and IP, otherwise known together typically as TCP/IP. And you've probably seen these acronyms at some point in the real world, on the internet, on some kind of documentation, a text, even if you haven't really thought hard about it. But IP is certainly the more common of the two, perhaps, in common culture. So what does TCP and IP do for us? Well, really two primary things. Any computer or any teaching staff member who understands TCP/IP knows how to get data from point A to point B. But how? Well, let's break down what that problem to be solved is. IP, otherwise known as Internet Protocol, is a protocol that computers speak that allow them to know how to address computers on the internet. And a protocol is just a set of conventions that computers adhere to. So someone wrote code that probably has a whole lot of conditionals that tells the computer what to do if something happens. Like, if I receive a packet, then send it to the next server, or something like that. In the human world, we have protocols too. You know, in healthier times, it was quite common to sort of extend your hand to another human in order to greet them. And if they're following human protocol, they would presumably grab your hand and shake it, at least in a culture like this one here on campus. And now that is a human protocol in that someone initiates it, someone responds to it, and you both sort of know what to do. You're programmed to know what to do. So same idea with Internet Protocol. Computers just know what to do when they've been programmed to do so. So what does this mean? IP decides that every computer in the world will have a unique address, just like the Science Center around the corner might have a unique address of 1 Oxford Street, Cambridge, Massachusetts, 02138 USA. IP dictates that every computer on the internet have a unique address of this form. And this, too, is probably something you've seen in the real world, even if you haven't thought too hard about it. It's a number in what's called dotted decimal notation, which means it's a decimal number, dot something, dot something, dot something. So 4 digits separated by convention by decimal points, although there are newer and bigger versions of the same. And these so-called IP addresses that might be as simple as 1.2.3.4 uniquely identify a computer on the internet. The numbers have to range from 0 to 255 each. And that's a bit of a hint just as you start to think more computationally. If each of these is a number from 0 to 255, how many bits does that suggest each number is using? Feel free to shout it out. How many bits gives us 256 total possibilities? So 8 bits. That should just be sort of a heuristic in your mind anytime you hear something that's in the range of 0 to 255 or 256 values total. Think back to week 0, which gives us 8 bits plus another 8 bits, another 8 bits, and another 8 bits, which is to say an IP address typically is 32 bits in total. Now, if we do another bit of quick mental math or think back to week 0, if every IP address is 32 bits, how many computers can we have on the internet at once, give or take? Roughly 4 billion is the ballpark. And we don't need to be super precise for discussion's sake, but roughly 4 billion is how high you can count, assuming no negative numbers, if you have 32 bits in total. Now, that's not terribly many number numbers of addresses, especially considering the number of humans in the world, the number of us that do have laptops or desktops or devices more generally, phones in our pockets and the like. So let me just stipulate for today's purposes that there's even a newer and improved version of IP, otherwise known as version 6. This is version 4, but still super popular. Version 6 uses 128 bits, which is a huge number of possible permutations. I dare say I can't even pronounce that number. It's so big. So there are ways around even this limitation already. So every computer has an address like this. What does that really mean? Well, suppose that I was Phyllis in the story told visually earlier, and I want to send a message to Brian. Well, both Phyllis and Brian have IP addresses. And suppose that Brian's IP address happens to be 1.2.3.4 in that top left-hand corner. Well, Phyllis's Mac or PC or phone would essentially do the equivalent on this human envelope by writing the to address in the middle of the envelope, as is our human convention, like this. So this is an envelope, a piece of information, an email, a text message, whatever, destined for Brian. And so she would have her computer put Brian's IP address in the middle. Her IP address is maybe 5.6.7.8. So just like our human convention, I might write 5.6.7.8 at the top of the envelope. 5, 6, 7, 8, thereby indicating what the return address is. And this is helpful because if Brian's computer needs to acknowledge receipt, if he needs to reply in some form, this way the envelope has all the information we need. But in the real world, servers do a lot of things nowadays, not just email, but maybe chat, maybe video conferencing, maybe any number of other services as well. And so it turns out that an address alone might not be sufficient, because how does Brian's computer know when he opens the envelope, so to speak, that this should be interpreted as an email, or interpreted as a chat message, or interpreted as like a video attachment that Phyllis has sent? Well, we need some other mechanism, some other hint on this envelope to distinguish one type of internet service from another. And so that's where the other acronym in TCP/IP comes in, which is TCP. So this stands for Transmission Control Protocol, which is just a different set of conventions that computers adhere to in order to solve a couple of different problems. One is this problem of distinguishing one type of service from another. Now, what does that mean? Well, humans decades ago decided, as they started inventing all of these various internet services, the web being the first one, how they might, or the web now being one of the most popular ones, they decided to assign different services that can be used on the internet unique numbers. And so two of the most common are these. 80 is the number that a bunch of humans decided years ago will represent what you and I know as HTTP. And we'll talk more technically in a bit about what HTTP is, but obviously it's the thing that's in the beginning of every URL nowadays. Or HTTPS, which of course has the S added to it, and that has its own unique number. And for now, the S just means secure. One is encrypted or scrambled somehow for privacy's sake, and the other is unencrypted. It's a little more vulnerable to interception. So these two numbers are what the world decided when implementing TCP shall uniquely identify those services. So what does this mean? Well, this means that if Brian's computer in the story from before is hosting not like an email server, but maybe he has a website, and Phyllis is requesting Brian's homepage or something like that, she would have her Mac or PC or phone not only write Brian's IP address in the middle of the envelope, but also the number, otherwise known as a port number, that she wants this envelope to be routed to. Now, 80 would be insecure nowadays. HTTP:// is sort of passé, and we almost always see HTTPS:// now. So I'm just going to go with best practice, and I'm going to add a colon and then the number 443 at the end of Brian's IP address. So now I have an IP address for Brian, the port number for the service that this is relevant to, and I'm not going to bother writing it, but it turns out that Phyllis's computer would also choose a port number, maybe a random port number, so that Brian can conversely reply. And then the computer can know which response is coming back for which request. But the most important one is this one in the to field, whereby this distinguishes this from like an email, a chat message, a video conference session, or a Zoom or whatnot from anything else happening on Brian's computer at the same time. So all this time, if you've seen these terms TCP and IP, those are really two of the most important things that they do. But TCP does one other thing that's super useful too. It turns out that it's super common nowadays, especially, to transmit a lot of media on the internet, whether it's an image or maybe it's a movie file. And it would be a little obnoxious, to say the least, if you're downloading a really big file meant that no one else in your dorm room or your household could actually download anything until you're actually done. So of course, multiple people nowadays can be on the internet at once, even if all of the connections are a little slower, but like one person's usage does not block someone else's. Now, how does this work? Well, TCP in conjunction with IP can also allow you to take like a really big image of a cat, which is the internet, of course, is filled with, and take a big image of a cat or a big video file of a cat and fragment it into multiple pieces. So I'm just going to sort of roughly tear it down the middle and then maybe tear it down the middle again. So now it's 4 different fragments. And I'm sorry, but the computer will be reassembling these for us. And what Phyllis's computer could do now, if she's like uploading this picture of a cat to Brian's web server, well, she could put one fragment in this envelope and then have 3 separate envelopes for the other 3 fragments. And what she could then do on the outside of this envelope is just kind of number them somehow. And in fact, this is something else that TCP and IP together would do for us. This first envelope now might say something like 1 out of 4 in the memo field, so to speak, of the metaphorical envelope here. Now, this should be enough information, because now if Brian gets all 4 of these envelopes, he presumably knows how to reassemble the picture of the cat in order, top to bottom, left to right. But more importantly, suppose that one of the routers, one of the TFs in the video, is sort of distracted and they sort of drop one of the packets. And that's a metaphor actually in practice for when a router gets really busy, it's got way too much data coming in, it might metaphorically drop packets. What does that mean in practice? I mean, it literally just ignores the zeros and ones. It doesn't save them to its memory because there's just no room left. So it's equivalent to sort of dropping the packet. So suppose now that Brian gets 1 of 4, 3 of 4, and 4 of 4. What can his computer infer now after receiving those 3 packets? 1 of 4, 3 of 4, and 4 of 4. What's the use there? Yeah, I think you're signaling with your fingers. Which one can I call on you? Yeah, so he's missing 2 out of 4, the second of the packets. And this is useful now because you could imagine he can send some message back to Phyllis saying, hey, please retransmit number 2 of 4 without having to re-download the entirety of the cat. So there's an efficiency there as well. So TCP/IP allows data really to go from point A to point B while solving a bunch of these problems along the way. So nowadays, if you ever see mention on your Mac or PC of your so-called IP address, that is the sort of problem that's being solved. Questions now on these protocols, these conventions called TCP and IP. That's the extent to which we'll need to understand them. Won't have to implement them per se. We'll just take them hereafter for granted. Any questions that you've ever been wondering about your home network? Yeah? A really good question. How does TCP know that a user got a message? Another aspect, another feature of TCP is that Brian's computer, by design of this protocol, will also acknowledge the packets that he's received. And it will do it efficiently. If Brian receives all 4 packets in a pretty narrow window of time, his computer will send to Phyllis's computer a quick message saying, essentially received all 4. Otherwise, he'll say the opposite, which is that I'm missing, for instance, 2 out of 4. And that just ensures ultimately that all of the data is indeed arrived so that you're not missing like a quadrant of the cat in question. All right, but that's not the only problem that needs to be solved ultimately. We also need to make the internet user-friendly, if you will. And it would be really tedious if you had to visit websites, for instance, by way of their IP addresses, right? 1.2.3.4 is pretty memorable, but there's like 4 billion other possible addresses available. And it would be super tedious to remember those. It would be bad marketing to advertise those. In fact, most of you probably don't even know the phone numbers of your closest friends and family members anymore because you instead store them in your contacts or in your address book, associating with numbers that are completely opaque with actual names or strings, if you will. The same goes for the internet too. Even though every computer does have and must have a unique IP address numerically. Why? Well, routers are computers. Computers just crunch numbers very readily, but we humans work better with strings of text. We need some system for converting user-friendly strings like harvard.edu or yale.edu or google.com to the underlying IP address. addresses. And that's where the next acronym comes in today, which is DNS, Domain Name System. So this is just another technology that's been in use for some time now. And it's a collection of servers on the internet whose purpose in life is to convert domain names to IP addresses, and maybe vice versa as well. So let me stipulate for today's purposes, there are some root DNS servers in the world that, long story short, know about all of the .coms, all of the .edus, all of the ... all of the other top-level domains around the world, as well as in the US. And then there are some smaller DNS servers owned by companies, owned by universities, and even in your apartments or homes, most likely. Indeed, if you have a home router plugged into the wall somewhere, that's not only routing your data in and out of your apartment or home or dorm room, it's also typically serving as a local, therefore faster DNS server, a cache, if you will. It's sort of locally saving your most frequently accessed websites and their IP addresses just to avoid bothering the bigger, more expensive, busier servers all day long. So there's DNS servers all over. If you poke around your settings in Windows or Mac OS or Android or iOS, you'll see mention of DNS, and you'll probably see the IP addresses of the servers whose purpose in life is to do this conversion for you. But this is a requisite feature if we just want the internet to be user-friendly and allow us to use words instead of numbers alone. What's inside of these DNS servers? You know, it's essentially a spreadsheet, or if we can say it more geekily, it's essentially like a hash table of some sort, which it has keys and values. Like the key is the domain name, harvard.edu, yale.edu, google.com, and the value is the corresponding IP address, or in many cases, IP addresses, plural, of the corresponding servers. So here already, even though I've drawn it fairly abstractly, like you would on a chalkboard, it's really probably implemented as some kind of table, maybe a hash table, maybe a database table, maybe SQL or something like that, or maybe it's even just a linked list or an array. We just have to somehow enable this computer to convert one to the other. Now, just to be super precise, DNS servers actually convert what are called fully qualified domain names, which is generally not just harvard.edu, but more verbosely www.harvard.edu and www.google.com. So the whole thing that you would see as a substring of the URL. So that's what DNS does, and that's what your university, your company, your home router are doing for you. Let me pause here to see if there are any questions. This, too, is just a technology now we'll take for granted, just works. Questions at all? No. All right, so let's now transition among our protocols really to the last for today, which will set the stage for actually solving problems with these and writing some code ultimately. HTTP. This is something that you see or hear all day long, even though you rarely have to bother typing it anymore. Odds are if you go to harvard.edu, yale.edu, google.com, you don't bother typing HTTP, let alone HTTPS manually anymore. Why? Because your browser auto-completes, that kind of thing, just to make life easier. But it is officially at the beginning of every URL you visit, either HTTP or the more secure HTTPS, whenever you're using your browser to access some website. So HTTP stands for Hypertext Transfer Protocol. And it's easily one of the most popular, dare say one of the most powerful features of the internet nowadays. But the mental model to have here is that HTTP, or the web more generally, is kind of a service that runs on top of the internet. And maybe Zoom or Microsoft Teams is another service that runs on top of the internet. And iMessage and technologies like it is another service that runs on top of the internet. So the internet is really like the lower level plumbing, the TCP/IP stuff, the DNS stuff that just gets data from point A to point B. But now, and we're in a software development class ultimately here in CS50, HTTP is the application level protocol. It's sort of what programmers use, what companies use, what developers use ultimately to use the underlying plumbing, to build interesting and powerful things. So what does this mean when it comes to accessing services via HTTP or the more secure HTTPS? Well, here is a representative URL. Even though you might not type the whole thing, if you poke around your address bar, this is what's up there. With that said, a lot of browsers nowadays are kind of simplifying, if not dumbing down, what you see with your human eyes, just to shorten the strings, especially on mobile devices. But almost always, if you click the URL or highlight it, then you see the whole thing. But on many browsers, you might only ever see example.com, but all of this information is there. It's just getting more and more hidden just for user interface's sake. Well, it turns out when you visit a URL, by default, especially if you type nothing after the .com in this case, you're technically implicitly adding a single slash. So a single slash denotes the root of the server. That is the default page or folder in the server. And the slash, whether or not you type it or not, is implicitly going to be there. And that just means give me the default. Whatever's at www.example.com, give me that page or that folder. But URLs can be longer than this. And more generally, there can be a path, so to speak. And this is a term of art. A path is some sequence of folder and or file names after a URL like this. And so you might see more specifically that a URL contains a very specific file. This isn't as common nowadays anymore, though we will begin today by using this technique. But if there is a file called literally file.html or something else on the server, that file is going to be what this URL pulls up on the computer. Meanwhile, you might have /folder/, which just means show me whatever's inside of this folder. Or you might have more verbosely /folder/file.html, which will show you that file in that folder. And meanwhile, just to give some other terms of art, this is the so-called fully qualified domain name. And again, these vocab words don't matter all that much, but you'll hear or see them over time. We generally, colloquially, just refer to this as the domain name, which is a little less precise, but gets the job done, certainly in conversation. And this part here, I described briefly earlier. What's the name for this suffix at the very end of the fully qualified domain name? Top level domain, or TLD. And this is just some form of categorization of the URLs. Now, the internet got its start within the United States, and a lot of the first websites, of course, came from the US. And so, for better or for worse, the sort of stake was planted in the ground. So generally, .com indicated, at least early on, that it was some kind of commercial enterprise, a business that owned a domain name. .edu is an educational institution. .net was some kind of network. .gov was the US government. Now, there are also country code TLDs, CCTLDs, like .uk or .jp. Every country in the world has its own two-letter TLD that might very well be restricted to only servers or companies or people in that country. Many of them can be used by anyone. You've used a lot of URLs in this class ending in cs50.io. That doesn't mean input, output. It actually is a TLD from another country that lets anyone on the internet pay for and on an annual basis using that domain. .tv, for instance, you might see in some cases, like twitch.tv and the like. That, too, is owned by another country that allows others in the English-speaking world, in this case, to use it as though it connotes TV. But those are just different types of TLDs that roughly categorize where the domain lives. But it doesn't necessarily mean it's commercial anymore. It doesn't necessarily mean it's a network anymore. For the most part, there are hundreds of TLDs now, for better or for worse, most of which are less common than these big ones. But most anyone can buy most of them, with just some restrictions on things like .edu and .gov that are still very much regulated. This, meanwhile, is what we might call the host name, www. It's obviously a super common convention. Like almost every website uses www as its host name. But that's a human convention. It's not a requirement. And indeed, some websites don't even bother having a host name. They just use their domain to advertise their website. This now is going to be the scheme or the protocol. And this is just going to indicate via what protocol the computer, your Mac, your PC, your phone, should use when accessing content at that address. Because indeed, there are other protocols you can use. But for the most part, we'll only focus on HTTP or equivalently HTTPS. All right. Any questions now on those just definitions, building blocks of URLs, just so we all sort of share a common vocabulary? Any questions at all? Yeah? Sure, we'll come back to this actually later today. There's a technical term known as localhost, which is a generic name for your computer, your Mac, your PC, your phone, especially when you're doing software development. And by convention, your own computer has not only whatever IP address you get from your university or your internet service provider, it also has a reflexive IP address, one that just always refers to itself, which is 127.0.0.1. And that's just a human convention. Humans decided that shall refer always to your computer. And it's actually going to be useful today and onward because we can use that when doing development on our own computers ultimately. Other questions on URLs, IP, DNS, or any of these building blocks? All right. So what do we mean by HTTP being a protocol? When I extended my hand earlier as a human handshake, a typical human in healthy times would know to respond in turn. Well, how does Brian's computer know to respond to Phyllis's envelope, whatever message is therein? Well, assuming that Brian is indeed still a web server in the story, and Phyllis was trying to upload a cat or maybe download a cat from Brian's web server, inside of Phyllis's envelope would have been a message, literally in text, and it's English for the most part, and it would contain at the beginning of that message literally one of these English verbs, either get, which means just that, get me the home page, get me a picture of a cat, get me a picture of a dog or a video or anything else, or post, which often means post, that is upload a picture of a cat or a dog or something else to the server instead. That's not strictly the only use cases for these, but you can generally think them as one is just getting information and the other is posting from the client, from Phyllis to the server, in this case, Brian. So those are the two keywords that we might see. And why is this useful? Well, it turns out we can start to see in our own Mac or PC some of these very same messages. For instance, if Phyllis were visiting, not Brian's, but example.com, that web server, inside of her metaphorical envelope, there would be a textual message that literally starts with get / then the word HTTP, then the version she's using. 1.1 is very common. 2 and 3 are becoming more common, but HTTP generally looks like this. The next line of text in her envelope would probably say host : then literally the fully qualified domain name of the server she's accessing, just in case, and this happens super commonly, especially on small websites, if one server is hosting multiple domain names, multiple websites, this just distinguishes which one she actually wants. And then there's usually a whole bunch of other lines of text as well. So where can you actually see this? Well, let me actually go ahead and do this. Give me just a moment, and I'm going to open up on my computer here an empty Chrome window in incognito mode. Generally speaking, incognito mode or private mode is used when you don't want there to be left remnants of what websites you visited, and it has the effect for software developers of just forgetting any things you might have tried already within your browser, including things called cookies, more on those another time, your autocomplete history and the like. So for development purposes, incognito mode is especially helpful because it's sort of like starting with a clean slate every time you open a new private or incognito mode. So there's not going to be like any remnants of previous testing or code that you've been playing with. And I'm going to go ahead and do this. I'm going to go ahead and right-click or control-click on Chrome. I'm going to choose Inspect, and it's going to pull up this window, sometimes on the side, sometimes on the bottom. I'm going to move it to the bottom just so we can see it a little more readily. And I'm going to zoom in. And it's going to look a little arcane at first. And I'm going to just highlight a few of these tabs. We'll see here along the top that there's Elements, Console, Sources, Network, and a whole bunch of other things as well. This is sort of the advanced mode in Chrome. And Safari and Firefox and Edge have their own equivalents of these features. They've always been there, even if you've never clicked the right button to enable these features. And I'm going to focus for a moment on Network like this. This is a feature of the browser that's going to allow me, the programmer in this case, or the engineer, to just kind of look at what messages my browser is actually sending to a server. So let me go ahead and do something like this. Let me go ahead and visit, for instance, in my browser here. And I'm going to shrink the window just a little bit so we can see it exactly. I'm going to visit https://www.harvard.edu. And now I'm going to hit Enter. And a whole bunch of stuff just happened along the bottom of my screen. And I'm going to try to pull my window up just a little bit so we can focus on a subset of this. Let me pull this up, covering up really the content of the page, focusing on these lower level details down here. And what I want to see first is, let me go ahead and reload this page here after retaining the log so that we can see absolutely everything on the screen. And to be clear, I just checked because I forgot earlier, preserve log, because I wanted to preserve everything on the screen. I want to see everything all at once. And we'll see this. The very first line of output is completely overwhelming with detail at first glance. But what you'll see here, if I start to scroll down and down and down and down, are the so-called request headers. And let me zoom in here. And what you're seeing inside of Chrome, inside of its Network tab, in its so-called developer tools, again, this is just for engineering types, you'll see all of the headers, all of the lines of text that magically were sent by my Mac to harvard.edu, much like from Phyllis to Brian's server in that story, so I can see exactly what messages are being sent. And a lot of this we haven't talked about yet, but we do see some mention of get, and we see some mention of slash, and a bunch of other arcane details. But notice they're all sort of key value pairs, with the colon here indicating what the corresponding value is. Now, most of this is not going to be interesting, and we're not going to focus too much on the weeds of all of this, but it indeed gives us a sense of what's inside of that virtual envelope. Now, harvard.edu is one thing, but there's other websites we might visit as well. And no matter what they are, we're going to expect ultimately an HTTP response. So in addition to a computer like my Mac or Phyllis's computer sending a request containing get and host and those details too, you'll see here in my slide form just representative response from the server. And notice that key here is that the server is responding in the same version of HTTP in this example. It's sending back this so-called status code, just a numeric code that indicates, in this case, that everything's OK. And it includes this header, this HTTP header, which again is just a key value pair saying that the type of this content that's coming back from the server is text/HTML. More on HTML in just a little bit. But for our purposes now, this just means that harvard.edu is sending me back a web page. And indeed, if we hide all of this technical stuff, that's the web page that we saw up here with all of the usual imagery and the like. And in fact, I can see this if I scroll back up, not to request headers, but response headers. You'll see up here that we get back responses, including the date that the server responded and a whole bunch of other details as well. And honestly, this has always been under your fingertips, and it will soon be useful as we start making web-based applications ultimately. But this very quickly gets overwhelming quickly. And so better than this might actually be a tool that we can use within our code space itself. So let me go back to VS Code here. I didn't open any code tabs. I'm just going to use my terminal window for a moment. And I'm going to run a couple of commands that are going to allow me to actually see what is going on when I request one website. Let me go ahead and use a command called curl for connect URL. And this is like a command line, black and white program that's going to pretend to be a browser. And it's going to connect to the URL, show me the headers, but it's not going to show me the images or the graphics, which might very well be useful to the humans, but not to me right now as the developer. So I'm going to do curl. I'm going to do -i. And then I'm going to do https://www.harvard.edu/ as though I'm pretending to be a browser requesting the home page. And what's nice about curl is, albeit overwhelming too, you'll get back a whole response from the server containing only those header values, the key value pairs inside of the envelope. And we'll ignore almost all of these, but here is the response from the server. It responded using a new and improved version of HTTP, in this case version 2, and it gave me back a 200. There's my content type, text/HTML, and then this char set happens to do with the encoding, if it's Unicode or ASCII or something else. And then there's all this other overwhelming detail for now. But this is the beginnings of my ability to just kind of poke around and see how the server works. And it turns out, too, that we'll be able to see other potential responses as well. So for instance, HTTP might not only return 100. What if I do this instead? Let me go ahead and visit curl-i http:// www.harvard.edu. So notice I deliberately use the insecure version of the URL, which maybe Harvard's administration, system administration doesn't like anymore. Well, how can they ensure that I, the end user, the student, nonetheless use HTTPS, even if I didn't type it myself? Well, let me run just that command with just HTTP, not HTTPS, and you'll see that everything is not OK. It didn't come back with a 200. It came back with 301 in this message saying Harvard moved permanently. But here's where you can look for another clue. Among all of these lines, most of which I don't care about, there's a location header, colon, that's a little hint to me that says where Harvard University has apparently moved to on the web. And what's different about this URL, just to be clear? It has the S included. And what your browser will do by default, because Google and Microsoft and Mozilla programmed it this way, whenever it sees a 301 response instead of 200, it won't show you any web page. It will look for a location header, find that URL, and then automatically, quote unquote, redirect you there too. So this is why it doesn't matter what we type in the browser. Harvard can have its server send these semi-secret messages to our browsers, and then it will just visit a second URL all automatically. And And you can do this with host names as well. Suppose that Harvard does not want to standardize on harvard.edu. Why? They just want it to always be www. Maybe it's a branding thing. Maybe it's a technical thing. We can see the exact same response here. This first tells me when I visit http harvard.edu with no www, Harvard minimally wants me to be using a secure connection. If I then, OK, fine, cooperate, let me go ahead and clear my screen. Let me add the S, but not the www. You can see here that it again responded with a 301 up here, and the location now adds the www. So it's just a way of bouncing users from one place to another. And this is all thanks to HTTP boiling down to relatively simple messages inside of the envelope that tell the computer, the browser in this case, how to respond. Now, odds are you've seen others besides 301, even though you've probably never seen that actual number unless you've done this kind of thing before. But there probably is a number that like everyone in this room has seen, even if you've never really wondered, why is it that number? I think you're smiling. What number are you thinking of? Yeah, so 404. Why is 404? Well, 404 indicates, by convention, not found. And now why the world decided years ago to show us normal humans on the internet 404 is anything significant is unclear. That's sort of like bad design. Like, what do I care if the status code is 404? But it's common enough on the internet that probably all of us have seen it. But that just means that some server, when you visit a URL that's incorrect, maybe it's outdated, the URL has been changed, if you see a 404, it just means that the virtual envelope that came from the server back to your Mac or PC or phone contains not 200 OK, not 301 moved permanently, but 404 not found instead. And it's usually accompanied by a technical message, maybe a cute picture of a cat sort of hiding because it means not found or something like that. The aesthetics are entirely up to the server, but that's what the 404 means. And there's other codes too, a few of which you'll use in the coming weeks as we transition from command line programs in C and Python to web-based ones. We've seen a few of these already, and several of them are kind of variants of the same thing, like these 300 ones here. But we'll see others, like 403 forbidden means like you probably forgot to log in or you need to log in or something like that. Internal server error, right now, no. In the coming weeks, you will absolutely encounter 500 errors, and they're always your fault. It's going to be the equivalent of like a segmentation fault in C. A 500 error means like you or I screwed up when writing some code. So we're going to see that, but it's just going to be an opportunity for us to fix it. If a server's overloaded, you often see 503, like something's unavailable because something's too popular or is maybe worse, getting attacked. This is an old April Fool's joke. 418 is not actually used in practice, but someone like took the time to write up an entire formal technical proposal so that servers can respond saying, I'm a teapot. So it's kind of part of internet lore, and there's other ones of these status codes as well. But this is useful because eventually we'll see in code you can use this understanding, high level as it might be, of HTTP to do some interesting and powerful things. So for instance, we can even send fancier URLs to servers. It turns out, as we'll soon see, if you send a message like this, get/search Q equals cat, and then HTTP 1.1 or whatever version, and you send that message to Google server, www.google.com, this is how you can specify not just the path of a web page that you want, /search in this case. The question mark, it turns out, is going to be a convention in the internet, in the web specifically, for passing human user input to the server as well. In fact, you've probably never paid close attention to URLs, but they very often have question marks. They very often have equal signs. And indeed, even google.com supports a certain key, Q in this case, for query. And you can put anything you want after that in order to search for actual cats. So if I actually go back to Chrome itself here for a moment, let me pull back open my Chrome browser here. Previously, I was using incognito mode for harvard.edu. I've gone ahead and closed that window and opened a new one so we can start fresh by visiting Google. Normally, you and I are in the habit of going to google.com and searching via the form. Or nowadays, you just type like your search query in the browser itself, and it brings you automatically to Google or Bing or something else. But I can really be pedantic here. Let me go ahead and zoom in, and I'll manually go to https://www.google.com/search. question mark Q equals maybe cats. Now, this would not be a very user-friendly experience if all of us had to manually type out something crazy like that, but that's what the form is redirecting you to when you type in more user-friendly cats into like a text box. If I hit enter here, we'll get back, indeed, a whole bunch of search results about cats. If I zoom back in and maybe I change it from cats to dogs, that too is going to change. And notice it's pre-populating the text box because Google has written its code in order to do so as well. Now, apropos of the video with which we began today from yesteryear, one of the better Yale pranks over the years, has anyone actually ever been to safetyschool.org? And to our friends at Yale watching live, hi. Safetyschool.org. So it's kind of fun if you actually visit it, depending on who you are. So if I open up a new window here and I go to http://safetyschool.org, zooming in, enter, my oh my. Look at where it goes. Now, how does that, OK, thank you. This is not a CS50 thing. Someone out there who I don't know who they are for like 20 years has been paying annually for that domain, safetyschool.org, for just this joke. But if I now go back into VS Code here in my terminal window and a little more, sophisticatedly, let me do curl-i http://safetyschool.org. The browser, of course, immediately redirected me to the website. But what's going on underneath the hood? Well, 20-some years ago, someone bought the domain, configured the server quite simply to spit this out. Safetyschool.org for years has moved permanently to www.yale.edu. So just a little demonstration of what you can do with just a little bit of understanding of HTTP. That's been a lot already. We've laid the foundation for understanding how the internet works. Now we're going to use it with a language called HTML, hypertext markup language, CSS, cascading style sheets, and JavaScript, a proper programming language. But first, it feels opportune to take a 10-minute break. We have some wonderful Halloween candy in the transept, and we'll be back in 10 with those languages.
We're headed up to Boston, checking out the stadium for the prank. A few years ago, I was at a math conference, and I was sitting around at a table at dinner with a few other mathematicians. And one of them went to Harvard and started telling the story of this amazing prank that was, against Harvard. And at that point, I felt I had to interrupt and said, well, actually, I can tell you a lot more about that. Okay.
The idea was perfected in a dorm room.
Came up with the idea, actually, to prank them with signs at the football game. We threw some ideas out there as far as what the signs would say. We eventually settled on "We suck."
And my immediate reaction was, no, this will never work. However, the problem solver in me started thinking, well, maybe we can make this work.
Problem? They had to infiltrate Harvard Stadium without getting caught, sneak in 1,800 placards, distribute them to unsuspecting Harvard fans, and then convince those fans to prank themselves.
That's great. We thought about basically every possible thing that could go wrong and tried to come up with a solution for it.
And then you put 2 reds on top of it.
They made fake Harvard IDs and fake backstories, fake placard designs, and a 28-member fake pep squad. On November 20th, 2004, a fake Harvard student smuggled the placards into the game.
What do you think of Yale, sir?
But then, trouble.
What houses?
How many extras? Sometimes.
Yeah.
No,
I, just showed him the front of this ID, and all of a sudden he just ran away, and he felt so embarrassed.
Having escaped one confrontation, they couldn't risk another. It was time.
This just looks like a total mess. We have absolutely no idea if this is going to work.
Look at them, they have the over. It's going to hurt. It's actually going to hurt. I can't believe this.
What was once a prank became a legend.
And immediately we started hearing chants from the other side, "You suck." And I think it was at that point in time that we knew we had pulled it off. I really think it didn't matter that Harvard won because of the prank. For a lot of Yale students and alumni, we definitely won that year.
Thank you all. Okay, thank you. Oh, here. Oh, all right. Here. A little Halloween candy. All right. Thank you all. So glad I wore the same thing today. So, in just a moment. Thank you. Okay, so in just a moment, we'll transition to understanding all the more now what we can do with this underlying infrastructure. So again, HTTP and below it TCP IP is all about just getting the data from point A to point B in some standardized way. But now let's talk about HTML. This is the language in which web pages themselves are written, hypertext markup language. Now, some of you might have used this before to make personal home pages. Some of you might have dabbled even if using some website to create your own home page. But understanding this language is useful certainly for creating the aesthetics of a web page, conveying data that's of interest. But at the end of the day, it and the language we'll look at next, CSS, are not programming languages. There's going to be no functions, no loops, no programming logic. But we will end today with a teaser of a proper programming language called JavaScript, via which you can manipulate all of these various other languages as well. So ultimately, HTML has like two features. And this is a language that we spend very brief amount of time on because it really boils down to just a couple of basic ideas and then vocabulary that you'll build out over time just by Googling, looking up references, looking at other pages, source code. But tags and attributes are what characterize HTML. Now, what do I mean by that? Here, for instance, is the HTML code via which you can make probably the simplest of all web pages. One that quite simply says in the browser window, hello title and hello body, for instance. Now, what does this actually mean? If you imagine opening up this code in a browser, be it on a Mac or PC or phone, you'll see typically like some kind of rectangular window, and there's usually a tab that has the title of that page, and then most of the rectangular region is the web page itself. What you're looking at then is the code that's going to put hello title in the title bar, in the tab at the very top, and down at the bottom, hello body is going to be all that's in the big black and white box that composes the rest of the browser window itself. Now, what are the salient characteristics here that we'll now start to take for granted? Well, first, first, let's go ahead and give me just a moment here and actually do something with this code. So I'm going to go ahead and do this. Back in VS Code here, I'm going to first create a file called, say, hello.html. And in this tab, I'm going to go ahead and really repeat exactly that same code. Now, I had this line first, doctype HTML. Then I had this line, HTML lang equals quote unquote en, close quote. Then I had inside of that head. Then I had inside of that title. Then inside of that, I had hello title. And I'm doing this quickly because we'll tease apart in a moment what it actually all means. And then down here, below that so-called head, I had just the text hello body. So at the moment, that I claim is the entirety of a web page. But it currently lives in my code space, so to speak, in a file called hello.html. That's fine if I want to create it, but how do you, how does anyone on the internet actually view it? Well, to serve a web page, you indeed need a web server. And it turns out that Codespaces comes with one of these pre-installed because we, CS50 staff, did so for you. And what you can do in a terminal window, once you have an HTML file ready to go that you want the world to see, you can literally run in your terminal window http-server. Single command. And what that's going to do for you is start a web server. That is to say, a program whose purpose in life is just to serve web pages. And even though probably up until now for years, you probably, if you're like me, equate server, quote unquote, with a physical device, server is really a piece of software. It just tends to run on big fancy devices. So when we say server, we often all think of in our mind's eye, big expensive devices perhaps. But a server is just a program whose purpose in life is to respond to requests with responses. promises. And that's the vernacular there. Now, once you run HTTP server, and I'm going to do a bit of magic because I set this up before class just to make sure it goes smoothly, you'll see some output like this, whereby your server is now available on a very long URL. Mine here is a very long URL that will be different from yours. But what this is a unique identifier that your code space has temporarily generated so that you can now access, and ideally only you can access, that file using your browser. Now, if I flip the URL or you flip the URL to public by right-clicking or control-clicking the right features of VS Code, you can enable anyone in the world to visit it. But we're not going to ultimately host our websites in your code space, because as soon as you log off for the night and the thing shuts down, like the website will go down. But at the end of the semester, particularly for final projects, we'll show you ways that you can put your own website, your own code on the actual internet 24/7, 365, even with your own domain name if you want to get one, so that it lives independent of your own sleep schedule and usage schedule of VS Code here. So I'm going to go ahead now and visit this URL in another tab of my browser. And what I'll see here is this. This is the output of that program called HTTP Server. And essentially what it is doing is it's using TCP and IP in conjunction with HTTP to just run your very own web server on GitHub's own servers as well. And that's because of different ports. Again, we won't go too much into the weeds of the TCP, the IP, and all of that stuff. But recall that different port numbers can allow you to distinguish one service from another. Now, one of the services is, of course, your code space, VS Code in the cloud that we've been using for weeks. But if you want to use the same physical server that GitHub controls, but actually visit your own web server that I just ran in my terminal window in another tab, that's fine. They're just going to be using different TCP ports. And you and I don't have to care what they are, but just that this is a feature that TCP supports. So what you see here is somewhat arcane. This is not like a thing that most people on the internet should ever see. I'm just doing this for development purposes. But this is the index, that is, the directory, the folder contents of my code space. And because I deleted everything from prior weeks already, all we see right now is hello.html, which I just created. So if I click on hello.html, within this folder listing, you'll be a little underwhelmed. And I'll zoom in just so there's something more interesting there. But now you see hello, comma, body. But what's interesting, perhaps, is that after this long, very cryptic and uninteresting URL, notice at the very end of it, and I'll zoom in a moment, what do you see? /hello.html, which follows the convention I claimed before break is how a browser would allow you to access a specific file on a server by doing / and then the name of the file name. Everything before it is very cryptic. It would be better if I buy a domain name that's a little more easy to remember and set that up some other time. But for now, let's just focus on only the file names that I'm actually creating. All right. So the code is up and running, underwhelming though it might be, with the body in the middle of the page. And let me zoom in up here too. Hello, comma, title is indeed in the tab, just as promised. So what's actually going on with code like this that we just created? Well, let's go back to the slide version of the same. And let me just highlight a few of these lines. The very first line is what's called your document type declaration. It doesn't really matter to remember that by phrasing. And this is just something you copy, paste, or do from memory at the top of any .html file that you create when making your own web page. It's an implicit indicator to the browser that you're using the very latest version of HTML, which is version 5. You don't mention the number 5. Just browsers nowadays are programmed to look for this to know that you're using the very latest version of the language. Languages, just like human languages, evolve over time. We're up to version 5 of HTML, but new features get added every few years. So indeed, this lecture, this class, has been evolving over time too. So let's now focus on the next line as well as the bottom line. And you'll notice some deliberate symmetry here. This here is what we're going to call a tag. And it's technically different from this. This is a document type declaration. It's got the weird exclamation point. That's the only anomaly. Everything else follows a pattern. This is a tag in HTML, and it's the HTML tag. And a tag generally both starts and stops, or opens and closes at some point. So this is the so-called start tag or open tag. And this just means essentially to the browser, hey, browser, here comes some HTML, the language in which web pages are written. This here, with the / after the angled bracket, means, hey, browser, that's it for the HTML of this page. So that's what I mean by symmetry. I started a thought here, finished it down here. What's in between those two thoughts? Well, here, browser, or rather, let me clarify one thing. This thing here is that other keyword, an attribute. An attribute is something that modifies the behavior of a tag. So it's similar to an argument in C or in Python, like a parameter to a function. These aren't functions, but it's the same idea. It just modifies the default behavior of something instead. Lang equals en, you can probably guess, just means that, hey, browser, assume that everything hereafter is in English. And that might be useful for like Google Translate or just search engine optimization, so that just the server, the browser know like what human language you have actual content in, like hello title, hello body, even though a good computer can probably infer from context often. All right, so that's an attribute. That's a tag. And the whole thing here, everything in between the start tag and end tag, we would also call an HTML element. That just means everything related to that open and close tag. All right, now notice, indented inside of, so to speak, the HTML open and close tag are another pair of tags, the head tag and the body tag, or the head element collectively and the body element collectively. And same idea. Hey, browser, here comes the head of my page. Hey, browser, that's it for the head. Hey, browser, here comes the body of my page. Hey, browser, that's it for the body. The head is essentially the tiny little strip at the very top, including the tab itself. The body is like 95% of everything else, the big rectangular region. What's inside of your title, of your head? Of the web page, at the moment, just the title. So this indicates, hey, browser, here comes my title. Hey, browser, that's it for the title. The title, of course, is literally, quote unquote, hello, comma, title. Meanwhile, if we bounce back out, here is the second element inside of the HTML tag. This says, hey, browser, here comes the body. Hey, browser, that's it for the body. And hey, browser, this is the contents. These are the contents of the body itself. Now, the indentation is a stylistic thing. I did it just to be sort of neat and tidy because it suggests what is inside of what. But it also suggests a sort of hierarchy. And in fact, we'll use terminology from like the world of family trees. If this is like a parent, so to speak, head and body would be the child elements of the HTML tag. Meanwhile, title is a child of the head tag, or equivalently, title is a grandchild of HTML. So you can use the same sort of vernacular as in the human world when it comes to familial relationships too. And that just hints at, again, this same hierarchy. So we have tags, and they include HTML, head, title, body, and that's it for now. We have attributes. We've seen one example of them, Lang. But we'll see many other examples of the same idea. But these building blocks are exactly the same. Generally, you start a thought, you finish a thought, and you might do something in between. Questions on this basic structure of any web page? Any questions at all? No? All right, so let's now allow things to ramp up a little more interestingly and do something with these building blocks. But so that you have a mental model for everything that's going on here on after, think of this same HTML being related in spirit to week 5 when we talked all about data structures. If I really wanted to, I could take to heart this idea of children and parents and grandparents and really depict this thing graphically. And in fact, this tree here, if you will, and it's not a binary tree, it's not a binary search tree, it's just a tree, using week 5's terminology. If this special node here represents the whole document, well, the root element, as I called it, is HTML. HTML has two children, head and body. The head tag has, in turn, a title child, and in turn has some text, just as the body has some text. And so this is what your browser is doing. You and I, the programmers, write this stuff. The browser reads this code, top to bottom, left to right, whenever you visit a website. And inside of the computer's memory, Chrome, Edge, Firefox, Safari, whatnot, they build this data structure in the computer's memory so as to know what it is you have told them to do. And we'll see over time, at the end of today, you can write code in an actual programming language, JavaScript, to maybe dynamically add or remove things from this tree. And this is how things like Gmail work. When you open up your Gmail inbox, if you're a Gmail user, if you just stay there long enough, you'll probably get more and more mail. And what happens? You don't have to like reload the page or rebuild the tree per se. It just all of a sudden appears at the top, at the top, at the top. What's happening there is that Google wrote some code that just keeps adding more nodes to this tree every time they realize you've got a new message again and again. So that's the relationship now, even with this world of HTML, with all of the programmatic ideas we looked at in the past. All right, so let's go ahead and do something with this that's a little more interesting than just hello itself. I'm going to go ahead and hide my terminal window because the server is now running. And all I want to do now is experiment with hello and other examples as well. Let me go ahead and, actually, before I do that, let me go ahead and run code of paragraphs.html just so I can keep my code separate. And now I'll hide the terminal window again. Paragraphs.html, I'm going to do almost exactly the same. Let me go ahead and start with something familiar, and eventually I'll start copying and pasting just to save time. So doc type HTML is always there. Open the HTML tag. And now notice, I didn't type the rest of that. Just like with C, just like with Python, we try to save you some keystrokes by closing parentheses, adding quotes. The HTML support in VS Code is pretty good too, and it tries to finish your thought when it comes to tags as well. It can screw things up if it does something you don't want it to do, so sometimes you have to delete, but it's just autocomplete, as we've seen before. Let's go ahead and let me add lang equals en, as all of my examples today will be. Let's add the head tag. Let's go and proactively add the body tag. And now let's go ahead and give this a title tag, which has I'll just call this paragraphs, just so I remember which example is what. Now notice all of this white space and all of this neat and tidy indentation, the browser ultimately is not going to care about. This is just for us humans to kind of keep ourselves sane. When we look at the code, it's just easier to read. But strictly speaking, I could minimally delete all of this white space, and I could just move all of this tag up to the same line. Both, I think, are fine. I'm just going to follow a certain convention, but this too would have the exact same meaning. But we'll see where that detail about white space could potentially get us into trouble later. In my paragraphs tag, let's do this. In advance, I've written up some Latin-like text, a really long paragraph of Latin-like text like this. It's actually random nonsense. It's not real Latin, even though a couple of the words might look familiar. And so here we have 3 paragraphs of text. And I've deliberately hit Enter in between them so that just like an essay in Google Docs or Microsoft Word, hopefully I'll see 3 separate paragraphs. Let me now change tabs. And I'll close hello.html from before. I'm going to go back to my other tab here. I'm going to click back to go back to that index of all of my files, which I started at earlier. And you'll see now that I have 2 files, because I obviously just created a second file called paragraphs.html. So let's click on this to see our 3 paragraphs of Latin-like text. And voila, I'll zoom out. All right, first bug, if you will. This just looks like one massive blob of text, not 3 blobs of text. And why might that be? Borrowing the hint I offered a moment ago. Why are we not seeing break? Yeah, so we need some kind of line breaks here because the browser, turns out, is only going to take us literally. And if you just give it text, 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 it's just going to show you text. And anytime there's more than a single white space, whether it's 2 or 20 or 200, it's going to just assume that you did that just to be neat and tidy, and it's going to collapse them into just one space visually, like this. So there are, in fact, a couple of solutions. One is this here. I could add some explicit line breaks. And it turns out that there's a BR tag like this. And just for visibility's sake, let me do 2 of them. So like hitting Enter, Enter on my keyboard. I'll do it here too, BR for break, break. And now let me go back to my other tab. Nothing's changed yet, but that's because I have to reload. I've changed it on the server, but now I need to change it in the browser by reloading. And now it looks a little better, albeit nonsensical. But you'll notice a curiosity. Per this BR tag, this is kind of poorly designed. It's a little hackish to just say Enter, Enter, and make the browser do this. Breaks, line breaks, don't actually require close tags or end tags. So not all tags need to be closed, at least those that it just makes no semantic sense to close them, right? Like the break is there or it's not. You can't imagine like starting to move to the next line and then eventually getting around to finishing. Like it's either there or it's not. So some tags do not have close tags as necessary. But there's a more elegant way here, I dare say, not just sort of hackishly putting in these line breaks. Let me do this instead. I'll delete those. And let me go ahead and, as the name of this file suggests, let me add a paragraph tag. Now here I need to fight with VS Code's autocomplete because I don't want to finish the sentence, the thought there. Let me go ahead and open the paragraph tag and close a paragraph tag. And just to keep things tidy, I'll go ahead and indent 2, even though the indentation itself doesn't matter. Let me go ahead and create another tag for opening this paragraph. And I'll close this one here. And now let me see, sometimes it's fighting with my autocomplete, but that's fine because I did this sort of the wrong way at first. And now let me go ahead and finish this thought by closing this paragraph tag here. And I've manually fixed all of my indentation. So now on line 10, I have the equivalent of, hey, browser, start a paragraph. And then it does the Latin-like text. Then on line 12, hey, browser, that's it for this paragraph. And repeat, repeat. If I now go back to my other tab, and reload again shouldn't be all that different, but semantically, it's a little bit better. Why? Because just saying break, break doesn't really mean anything, but by saying paragraph, 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 now there's some more semantic information there. Now if like Google is analyzing your page, or if the programmer is trying to understand what it is you did in the past when writing this code, you just know semantically, oh, this is a paragraph, this is a paragraph, this is a paragraph, just like in a book or an essay. So it's a little more clear, focusing more on what it is, not how you want to display it. Any questions then on these paragraphs? Now, all right, so a few more tags. And indeed, these first few examples will really just be like sort of bang, 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 just a bunch of different vocabulary words in the form of these new tags. But we won't go through the entire laundry list of tags. This is indeed the thing for which web references and books and the like are ultimately helpful, just like a dictionary in the real world. So I'm going to go ahead and do this. Let me go ahead and copy this. Let me create a new file called headings.html, just so we have a new file for this. To save time, I'm just going to paste that exact same code just to get me started. I'm going to change the title of it for clarity, for the code online, to headings. And now, just like a book or an essay or a thesis, let me actually put some actual headings here. Now, if my first heading, like chapter 1, I could do something like this up here. I could have a paragraph, like I just learned, and I could say something like chapter 1 here. But that's not really a paragraph, and so it's sort of better designed to tell the browser and really tell the world what it is. So it turns out there's another tag I can use, like h1, for heading, and like most important heading. And in here, I'm just going to keep it simple, and I'm going to say something like 1. And in fact, this is so short. Here's a good candidate for just keeping this all on the same line, but this has no functional difference, but it'll just make it a little more terse on the screen. Now let me go ahead down here, and I could have multiple headings, so h1, 2, and down here I could have another one, h1, 3. And if I go back to my other tab, I reload it now, we should see, just like a book or an essay, now we have some proper, oops, I have to go to the right file, sorry. If I go back to the index, now we see the new third file called headings.html, and now we indeed see some fairly pretty, if simple, headings as well. Now, if these aren't 3 chapters, 1, 2, 3, but maybe it's a chapter, then a section, then a subsection, such that just visually you want things to get smaller and smaller, well, those exist too. And in fact, you can do h1 through h6. h1, a little paradoxically, is the biggest and boldest. h6 is the smallest, but still bold. So it might make sense to make this h2 both open and close, and maybe this h3 open and close if, again, this is a section or a subsection inside of that chapter. If I reload now, notice, it just gets a little smaller. So it's more similar to what you'd see on the printed page. But this now is just another 3 tags that I might use in my own code. All right, well, how about lists of things? I have 3 paragraphs here, but let's do this. Let me go back to VS Code. I'm going to copy this code so I have a starting point. I'm going to create a new file called, say, list.html. Here I'm going to copy paste. I'm going to change my title to be list, just for clarity. And in here, I'm going to go ahead and get rid of this whole body, because let's move away from these massive paragraphs and keep it simpler for now. If I want to have a list of things, for instance, if you haven't seen these already, a computer scientist, when they're fishing for just some arbitrary, meaningless words, they often use foo, bar, and baz, just as their go-to, just like a mathematician might use x, y, z for variables. So foo, bar, and baz are on 3 separate lines, and maybe this is like my to-do list or my shopping list. But you can probably imagine if I go back to my other tab, go back to the index, I now see my new file, list.html, but it's probably going to look wrong. I think I'm just going to say, yeah, foo, bar, baz, all in one breath, if you will. They're not on new lines. And you can try to fight this. Like, you can be like, really want to put some line breaks there, go back and reload. It's still not going to make any change. How do I want to fix this? Well, I can do this in a few ways. I could make them paragraphs, but they're not really paragraphs. They're a list. So I'm going to use a different tag instead. I'm going to create, for instance, an unordered list using the ul tag, open and close. Inside of that, I'm going to use the list item tag, li, and I'm going to say foo. Inside of another tag, I'm going to say bar. Inside of a third tag, open and close, I'm going to say baz. So it's getting a little verbose, but it's still relatively succinct. Li is all you need type for list item. Ul is all you need type for unordered list. So there's some shorthand syntax here that's adopted. If I now reload, you're going to see a so-called unordered list, like not sorted, which means by convention to show it as bullets, though it could be displayed in different ways visually as well. If you actually change your mind and you realize, oh, I'd really like to number this, well, you could obviously like just add 1 and 2 and 3. But that's going to get annoying, especially if the list grows. You want to change something, insert something in the middle, then you have to reorder it. I mean, we're using computers here. They can do this for us. So we can change the UL to, any guesses? OL, maybe, for ordered list, which is sort of the opposite here. So let's try changing that to OL. Let me go back to my browser. And I'm just hitting Command R or Control R to reload the page instead of clicking the button every time. Now, I automatically get 1, 2, and 3. And you can even override the aesthetics using different numerables or symbology instead. But that would be perhaps the most common there as well. All right. It's a lot of tags quickly, but any questions on lists, paragraphs, headings, or the like? No? All right. So let me go ahead and propose this here. Let's go ahead and create what we'll call a table. So let me copy and paste this into a new file, code of table.html. And in table.html, let me again rename the title to table. Let me get rid of that ordered list from before. And let me now use a table tag, open and close. This one's a little weird, but inside of a table, you typically have a head of the table. So I'll say, well, let's say the first row. We'll keep this one simple. A table row, or TR. Inside of a table row, you would ideally have columns, but that's not the nomenclature. Instead, you have data. So TD for table data. And let me go ahead and just have the first datum be 1. I'm just going to arbitrarily do 1, 2, 3, just so we have something to play with. And you know what? Just for demonstration's sake, I am going to deliberately copy-paste this twice. And I'm just going to manually change the numbers, just so we can see what I'm creating. 7, 8, 9. And then maybe just for good measure, if you're seeing where this is going, let me copy this one more time and give myself a final row with an asterisk, a 0, and a pound sign, if maybe you see where this is going. Let me go back to my other tab. Let me go back to the index. There's my new file, table.html. I'll click that. And while it's not very pretty, I'll zoom in. It's indeed a table of data. I happen to mimic like a telephone keypad, but you could imagine this being much juicier, much more interesting scientific or financial data or the like laid out into these rows, TRs, and these columns, aka table data as well. So we have that ability as well for structured data. Now, of course, the internet has lots of images on it. And in fact, this is all just text. How can we introduce images? Well, let me go ahead and do this. Let me first sort of semi-secretly copy an image file that I brought from earlier, just so we have something to play with. And I have in my account here now an image called harvard.jpg. And I uploaded this semi-secretly a second ago into my account so that I can reference a second file. Let me go ahead and copy this HTML just to save myself some keystrokes. Let me go ahead and do code of image.html. And let me paste that code and hide my terminal window. I'm going to get rid of all of this table as just uninteresting now. We're going to make this even simpler by changing my title to image to keep all these demonstrations separate. And now, if I want to make a web page that, when visited, shows us a picture of Harvard, well, there's an image tag, abbreviated IMG for short. I can specify what the source of that image is. And if my file, a JPEG in this case, is literally in the same folder, I can just say, quote unquote, harvard.jpg. If it's in a folder, I should mention the folder name and a slash or something like that. If the image is on the internet somewhere with a URL, I could also have a whole URL, https:// and then the URL of the image. But I upload it in advance. Now, this is just going to visually display on the screen, but not everyone, of course, can see images. Screen readers might need a bit of assistance, and even search engines might want to analyze the page and know what this is an image of. Now, machine learning and artificial intelligence are maybe getting better, to be fair, at figuring out just by analyzing images what they are, but they're certainly imperfect. I am a human. I know pretty well what I took a photo of, for instance. So maybe what I should do proactively, which would be good for accessibility, is have this alt tag for alternative text, and then literally say like Harvard University, so that someone who can't see or so that a server can actually know with higher probability what it is they're looking at. And I could be even more detailed than just a phrase. I could describe the image as well. All right, let me go back to my index in the second tab. Let me go back and zoom back out. there's my new file, and there's my new JPEG that I quickly uploaded before. I can click now on image.html, and albeit a little overwhelming, that is a really big image of Harvard. Now, apparently, it's too big to fit on the screen, so this isn't the best user experience to have to scroll up. OK, so there's the image. Horrible, horrible design, if you will, at least in terms of my code. But there's going to be ways where I can sort of rein that in and affect the height or the width as well. But for now, it's just deliberately a little overwhelming instead. Now, we can do something a little more fun and topical today, which might be to use a video instead. So let me go ahead here and very quickly grab another file today, which is I brought in advance, and then you might have seen briefly earlier, which is an MP4, an actual video file. And what I'm going to do here, by revealing VS Code again, is I'm going to code a file called video.html. Yet another demonstration here. I'm going to change my title to video, just to keep these things straight. And instead of the image tag, you might imagine using now, indeed, a video tag. And this is a relatively newer tag that has increasing support among browsers, so it's good now to use. And inside of this, the syntax is a little different. You specify, and this is weirdly, annoyingly inconsistent, not src for source. You literally say source. And then in source, you use a source attribute. Horrible design semantically, but like this is what we're stuck with. Halloween.mp4 is the name of the video we uploaded in advance, made by some of Harvard's digital artists. And the type of this video, so that the browser knows for sure, is video/mp4. That's a so-called content type that you just know or you look up to figure it out. And just so that this is as animated as possible, I'm going to tell the video tag with a few attributes to autoplay. And it turns out that attributes often have key value pairs, whereby it's the key, the attribute name, equals quote unquote some value, just like lang equals quote unquote en for English. But not all attributes need values. In fact, if you read the documentation for HTML's video tag, there's an autoplay attribute where you can literally just say the key and it needs no value. It's just going to mean autoplay. And if you don't want to autoplay, you just omit it altogether. So you don't necessarily need a value on or off. I want the thing to loop just so it keeps going. I want it to be muted so that we don't hear any sound. In fact, there is no sound, but browsers nowadays, for anti-spam and advertising reasons, often will not play a video if it has sound, because it's just kind of obnoxious if you visit a page and all of a sudden your speakers start blaring. So I know this from having read up on this, that I should mute it so that if I want it to actually autoplay for real. And then I'll set the width manually for now to be like 128 pixels across, just from some trial and error earlier. And that width attribute does have a value. Now I'm being a little uptight here by alphabetizing all of my attributes. Not at all necessary. I do it just so I can skim things faster and know if something is there or not. So for me, it's just a matter of style. Let me go back to my other tab, go back to my index, and you'll see two new files again, the MP4 file and video.html. I'll click on the latter. And if I did this well, here we have, thanks to our friends in Harvard, our artistic friends at Harvard, very like an ooh would help with the drama here. But OK, but we have a very dramatic, nice Halloween type view here as well. So we have videos embedded as well. And suffice it to say, there's ways to embed YouTube videos or Vimeo or other services as well using yet more tags too. But the web is, of course, all about hyperlink, hypertext markup language, where you click on something and you end up somewhere else. And this is how the web is so powerfully interconnected. So how do we start creating links from one website or web page to another, either that I made or someone else? Well, let me go ahead and open back up my terminal window. And let's create a file called link.html just to demonstrate what you and I know as a link. I'll hide my terminal window now. Let me copy paste just to save myself some keystrokes. And let me get rid of the video tag so we can focus now on links. Suppose that I want you to visit Harvard virtually. Well, I could say something like visit Harvard, period. This is uninteresting because it's just going to be text. I probably want you to actually visit harvard.edu instead, more specifically. And I'll lowercase it just to be consistent with what browsers do in the address bar. All right, let me go now to the video, back to this video tab and go back where we now see my index. I'll zoom back in, and there's link.html. Unfortunately, when I click this, and I'll zoom in, you literally just see the text that I wrote. And yet, on every social media platform nowadays, except like Instagram, when you type a URL, or what looks like a URL, even if you didn't bother with the HTTP or HTTPS, it usually automatically links it for you on Facebook, on Twitter, and other sites as well. That's just a convenience. Discord and Slack do that too, but they're just doing it to make things more user-friendly. But they have to generate HTML with the proper tags and attributes. So to get this to actually work, it's not even good enough to say https://www.harvard.edu, because if I go back now and reload now, you'll literally just see all of that as text. If you want the browser to treat this as a link, you need to use the anchor tag. It'd be great if it were called the link tag, but it's not. It's called the anchor tag, or A for short. And the way you reference the URL to which you want to lead the user is via href, for hyperreference. This is one of the earliest tags, perhaps among the most arcane now. But if I then put that whole URL in quotes and close my tag, I now have an opportunity to finish my thought in between the start tag and the end tag for this anchor. And what I put in between the start and end tag is whatever the human's going to see. So here I can say Harvard. I can go back to my other tab. I can reload the page. And now you see the familiar blue underline. This now is an actual link. And if I click it, I'll be whisked away to the actual Harvard website. But there's a risk here. Can anyone imagine, pretty simply, after like, 60 seconds of the of the anchor tag, how could someone, an adversary, misuse this tag alone? How could a website run by an adversary, how could a spammer misuse this tag, do you think? Yeah. Yeah, absolutely. You could have it say one thing but lead elsewhere. So I could say Yale in here. Nothing's stopping me as the developer. Go back to the page, reload. Now it says visit Yale. You click on Yale, and voila, you end up applying to the wrong place instead. Now there's some hints of this. I could hover over this, and super small, like this isn't very good for your anti-hacking techniques, but way down here you can actually see the URL that it's going to go to, and most browsers indeed do this, at least on desktops and laptops, so it's a little bit of a hint. But what you're seeing here, even though this is kind of a silly, playful example, this is exactly how phishing attacks work, phishing work, whereby an adversary tells you to log into your PayPal account, but it doesn't go to paypal.com. It goes to some other random website that they bought and built that then tries to collect your username and password and store it in their database, so now they can log into your PayPal account as you. And it boils down to that simple primitive. And you can be even more manipulative too. You can even say the whole URL for Yale, like yale.edu, or worse, https://www.yale.edu. Reload that, and now who among you and people in your lives are necessarily going to be so paranoid as to not just blindly click on that URL? This is why just being a defensive, real-world person nowadays, digitally, is just ever more so important. So these same things that can be used for good or benign use cases can also be used for ill purposes too. And it is literally that simple. Questions now on any of these tags thus far? Just a few more to offer up. Any questions on this here? No? Well, let me open up a couple that I brought in advance just so we don't have to type all of them here. If you, for instance, have a web page that's got quite a bit of code, let me go ahead and grab from the website a couple of examples real fast here, namely one that we'll call, how about meta.html. And in this example here, give me just a moment to full screen it. We're going to have a file, so code meta.html. I'll open this up next. No relationship to what we now know as Meta, the company, but rather this is going to be a page that I copied and pasted the same chunk of Latin-like text from earlier, so it's going to be a really big paragraph of text. And this is an example where if you were to open this web page, not on my own Mac or your PC, but on your phone, the font might actually be really annoying and difficult to read. Why? Because your phone's going to try to squeeze all of the content onto the tiny viewport, the rectangular region of your phone instead. So it turns out there are ways, pretty easy ways, to make your website mobile friendly as well, otherwise known technically as responsive. And the easiest way to do this is to include this tag here, a meta tag. Again, no relationship to Facebook. This has been here much longer. And this case here, this meta tag on line 5 has its own sort of approach to key value pairs. This is a good example of where it'd be nice if it looked just like everything else, but this is what we have historically. You can have a meta tag with an attribute called name that refers to the name of some feature of the browser. In this case, viewport is the technical term for like the big rectangular region to which I keep referring, the body really of your page. The content for the viewport, you can say some esoteric details like this. The initial scale should be 1. That is, no matter who visits your site, it shouldn't start zoomed in. It shouldn't start zoomed out. It should start at just the default sizing. And then this here, width equals device width, is a very arcane way of saying if the user has a small screen, show the text proportional to that size. Don't just try to cram it all into a tiny little window. So it's super simple. But if, for the next problem set or future projects as well, you find that just things look really bad on mobile, like this kind of tag is the place to start meta. There aren't terribly many of these that you'll use, but they're useful for other mechanisms as well. In fact, let me go ahead and semi-secretly pull up one other example as well, whereby I'm going to grab another example that uses more of these tags. And in just a moment, I'll reveal it here. Give me just 1 second here. I'll propose that in this example of meta, we now add these properties instead. So I copy pasted this from an existing file just so as to not waste time typing all of these out. If you've ever shared a URL on Facebook or Twitter or Slack or Discord or any number of websites nowadays that automatically show a nice preview where you suddenly see like the default image of the page, maybe a few sentences or words of text or something like that, sometimes those applications, those websites, will just choose like the first image it finds on the website or the first sentence it sees and show that. But that might not be very user-friendly or search engine friendly. And so a developer might want to control what it is that Slack, Discord, Facebook, Twitter, and other such sites show by default. For that, you can use nowadays what are called open graph tags, which is to say there's other uses of the meta tag. And you just look these things up. Even I had to look this up to remember what the key value pairs are. The meta tag can also have a property attribute that can be these very specific strings: OG title, OG description, OG image, which denotes open graph, which again is this standard that's evolved in recent years. And what you can do here is tell browsers and in turn servers what you want them to show as the default title of the page, the description of the page, and even the default image, just so you can exercise more control when sharing things socially nowadays as well. Again, it just boils down to these key value pairs. This is absolutely the kind of thing you look up as needed to cross-check, but those capabilities are there. And so literally, the next time you paste a link into Slack or Discord or any online site that then displays it in embedded fashion, just know that all this time, a little bit of textual code like this in HTML has been there by whoever authored the site. All right, let's do one final example in HTML alone before we transition to just cleaning up the aesthetics and improving the visuals of everything we've been creating. Let me go ahead here and close meta.html. Let me code up a new file called search.html and see if we can't draw some inspiration from our cursory understanding earlier of how URLs work to see if we can't reinvent google.com itself. So recall that a canonical URL might look like this here. And in particular, if you want to pass in user input to that URL, again, you can potentially have a question mark and then a key equals value pair. Or for that matter, you can even have multiple key value pairs that by convention are separated by ampersands. These things are everywhere. Like later today, when you pull up almost any website in your browser, look at the URL, and you'll just see a lot of this. A lot of noise, too, and distractions, but there's going to be some equal signs, most likely, and or some ampersands as well. And those are just separating key value pairs. Now, what can I do here? Well, if you think back to how we manually searched for cats earlier, let me quickly do this. I'll do this one manually. Doc type HTML as my very first line. HTML tag with, how about my lang attribute for English up here. And then inside of this, I'll have a head tag. Inside of this, I'll have a title. I'll call this example search. And then down here, I'll have my beginning of a body tag. And now, let me introduce you to really a final tag for now, a form tag, which will create a web form, the thing with text boxes and buttons that you and I use every day on any number of websites. Inside of this form, I'm going to have an input, like a text box, whose name is going to be Q for query, because I'm trying to re-implement Google here. The type of that I want to be a text box, or if I know I'm using this for search, I can actually change this to a search box, and it's going to let me, it's going to generally put a little X there so you can clear it quickly. That's a nice little enhancement as well. And then I'm going to give myself a submit button by doing input. Whoops. I'm going to give myself a submit button by doing input type equals submit, and then I'll leave that as such here. All right, now I need to do a little bit more, but let's see how this looks. Let me go over to my other tab. Let me go back to my index, and if I zoom out, there is search.html. I'll click it, and there's not much going on here, even if I zoom in, but I do indeed have a really big text box and a submit button, but I haven't in my HTML told anyone anywhere that I want this input, whether I type cat or dog, to go to google.com. So for that, I need a couple of more attributes. And I know this from having done this before, and any online reference will say the same. You can add an action attribute, like what do you want the action of this form to be? And you can put the URL to which you want this form to be submitted. And I know from tinkering that it should be https://www.google.com/search. I don't need to put any question marks here myself, but I do want the browser to do that for me. So let me go back to my other tab. Let me reload, and nothing visually has happened. But watch this. When I now type in cats, but before I hit enter, notice that I'm currently at some long, crazy URL /search.html as expected. If I now go down to the submit button and click submit, watch what happens to the URL and the page itself. I'm whisked away to the actual google.com, and indeed, there are those same cats. And if I zoom in here, you'll see that my URL has changed to be indeed /search?q equals cats. So this is just how web forms work. When you submit any form on the web in this way, the browser automatically goes to that action URL, adds a question mark, puts any key value pairs that you manually typed into the text boxes, and lets the server do its thing. Now, here's where Chrome is starting to simplify things. Safari does this too. If you double click on your URL, now you see the full URL, but if any parts are missing, that's just a UI thing to eliminate visual distractions nowadays. Meanwhile, if I go back to my own form, if I search this time for dogs and hit enter, now again, the URL changes to be q equals dogs. And it all reduces to this basic building block of using a form tag. Now, I can be more explicit. If I know I want to use get, which is actually the default, I can literally say, quote unquote, get in all lowercase, even though the verb earlier was by design in uppercase. But here now, I'm just being ever more explicit. If I don't want the label of this button to be very generically submit, maybe I want it to be Google search, quote unquote. Well, if you read the documentation for forms, you can actually change the value of the button to be, quote unquote, Google search. And if I now go back here and reload, I get a fresh form. And now I get a button that literally says Google search. And if I tinker with this further, because this isn't very user-friendly, there's even more attributes I can do. I can add on my search input a autocomplete equals off if I don't want to see my own history for whatever reason. I don't want people knowing I'm searching for cats and dogs on this page. I can autofocus on the text box so that it shows the cursor blinking in that box by default. And I can even do something like this. I can have a placeholder attribute that says something like query or some other documentation for the user. And if I now go back and reload, you'll see, notice, it says query, and it's subtle, but my cursor is already positioned there. It gave it focus, and I can type cats now without having to click in the box manually, which is just marginally better for the user's experience. Any questions now on all of this here? Any questions? All right, that too was a lot. Why don't we take a casual 5-minute break, and when we resume, we'll take a look at CSS, add in some JavaScript, and then wrap up. So 5 minutes only for now. All right, we are back. So that's technically it for HTML. Like here on out, it'll be up to like online resources and references we point you to just to fill in your vocabulary for more tags and attributes. But like conceptually, that's it. There's attributes, there are tags, and there are attributes, and the rest of it really is just kind of a laundry list of capable, possible features. But it turns out too, you'll see over time that you can even see the HTML for websites. So for instance, if I go over to harvard.edu in my browser, which I'll go ahead in just a moment here and do https://www.harvard.edu/enter, it again will pull up today's version of Harvard's website. And if I right-click or control-click on it again and go to inspect, you'll see those so-called developer tools. And earlier, we focused on the network tab, just so we could see the HTTP stuff going on. But what I glossed over earlier was the so-called Elements tab, which actually shows you the HTML underlying any web page on the internet. And so, for instance, here is the underlying HTML for Harvard's homepage as of right now. And aesthetically, some of it's been collapsed. So if I click on these various triangles, I'll see what's actually inside of. That is the children of some of these HTML tags. But here on out, if you're ever curious as to like how a web page made some feature visually, you can just literally use these developer tools built into your own browser just to see what the web developer actually did. And you can do things too like this. Like if you really like maybe, let's see, if you really like this menu in the top right-hand corner of Harvard's website, you can even right-click that or control-click that specifically, choose Inspect, and what browsers will do is jump to the HTML corresponding to that visual element on the page. And here you can see, though we've not talked about this tag before, there's a button tag, there's an ID attribute, and there's some other attributes as well that define that button. You can do other things too in the web page. Let me scroll down, for instance, here, and let's go to another one, like yale.edu here in today's theme. And suppose we want to do something like change the aesthetics of this website. Well, how about this over here, Life at Yale. Let's right-click on this, choose Inspect. That's going to jump to that part of the page. And notice what you can do here in this Elements tab. We can be a little playful in return today. Life at Harvard. And voila, we've now changed Yale's website, it would seem. So have we really? Like, hopefully hacking is not actually this easy. What did we actually do based on today's mental model? Like, I have changed the page, but yeah, I've just changed how it is for me, right? Because my browser, just like with Phyllis and Brian from the get-go, requested Yale's web page. I got back a virtual envelope containing that HTML, as we've now called it. My browser has a local copy. It's got its own tree, otherwise known as a DOM, document object model, built up in its memory. And yeah, I went to town and changed my copy of it. But of course, hopefully, I've not changed the actual server. And in fact, if I reload Yale's website now, hopefully, it will revert back to, indeed, yep, what it should be instead, Life at Yale. But this ability in your own browser, be it Chrome or Firefox or Edge or Safari, to have these built-in developer tools are very powerful because it's going to enable you to not only diagnose problems that will invariably arise in the coming weeks with your own code, but it's also going to allow you to learn from other sites, like how you can do things and tinker as well. But up until now, we focused only on tags and attributes and on the structure of a web page. Let's now focus more on the aesthetics and fine-tuning that. It turns out that HTML has very limited support for anything aesthetic, like font sizes and colors and so forth. And in recent years, people have used necessarily a second language called CSS, not a programming language, again, a markup language, if you will, to just fine-tune the aesthetics of a page, font sizes, colors, margins, and all of that. So CSS is going to allow us to define a whole bunch of properties, which is just another group of people's terminology for key value pairs. Indeed, ever since week 5, like, key value pairs are everywhere in the world, not just at like Sweetgreen and restaurants, but indeed underlying code and languages and technologies like these. So properties is the new word in CSS for what a moment ago we called attributes in HTML. But it's the same idea, just different vocabulary that you get used to over time. A few phrases I might use now and you'll hear in the coming days would be these: type selector, class selector, ID selector, attribute selector, which just refer to different techniques we're about to see that are going to allow you to control more precisely the aesthetics of specific things on the page. And the way we're going to do this is we're going to take our basic HTML, like we saw earlier, and we're going to introduce in the next few minutes just a couple of more tags and or attributes. One, we're going to introduce you to a tag called style, which, nicely named, allows you to control the style, the aesthetics, the visuals of the web page. Or we're going to introduce you to a link tag, which is very confusing amazingly, does not give you a link that you can click on. It just links to another file that then gets automatically included or imported, to borrow our language from C or in Python. But same idea. This will allow us to include secondary files. And we're going to ultimately show you how you can leverage third-party frameworks, libraries that other people wrote, so as to not get stuck in the weeds of all the fine-tuning of aesthetics and just make pretty things fast so you can focus really on the intellectually interesting part, if that's your choice, of building the content, the site out, the application out yourself. All right, so with that said, let me go back to VS Code here. And let me go ahead and create a simple example called home.html, like a very simple homepage for John Harvard, for instance. Let me give myself 3 paragraphs initially, the first of which is just going to have the person's name. The second paragraph is going to say something like, welcome to my homepage, to greet visitors. And then the third is going to be like a little footer, like copyright, how about John Harvard 1636, or something like that. All right, let me go back to my other tab as before, reload my index. There's my new file, home.html. And I'll click that. And you'll see, OK, I mean, this is sort of 1636 style web page. Super simple, all text, nothing really interesting going on there. But we can start to style it a little differently. Like if the title of the page is John Harvard, and then it's welcome to my homepage, and then this less important footer, why don't we have the text be large, then medium, then small? So something arbitrary, but a little more nuanced. So let me go back to VS Code here. And in my home.html file, let me introduce not yet the style tag, but what I'm going to call temporarily the style attribute. Both indeed exist. This one's simpler, and it's going to be correct, but we'll see in a moment, not as well designed, arguably, as is often our narrative. So inside of the style tag, you can put this language called CSS, key value pairs, otherwise known as properties. The only way you know what properties exist, what keys exist, is by taking a class, reading a book, looking at an online reference, and we're going to give you just a sampling of what's out there. So suppose I want to control the font size of this first paragraph. I can literally say font-size, in all lowercase, colon, and then a word like large. Or I can specify 12 point or 18 point or something more precise like that, like from Google Docs or Microsoft Word. And suppose I want to make this text down here medium. Well, I'll do quote unquote font size colon medium. And down here, I'll do style equals font dash size small. So I'm going to start with just these 3 key value pairs, same key, but different values. I'll go back to my page, and in a moment, I'll reload. And it's going to be somewhat subtle, but watch how the font size do change when I reload now. All right, so got a little bigger, middle one's about the same, and the last one is a little smaller. What if I want to center it? Just like many web pages have the text like this centered. Well, I can separate these key value pairs with semicolons. And I'm sorry, semicolons are kind of sort of back with CSS, but I can do text-align colon center. Strictly speaking, I don't need the last semicolon if there's no more key value pairs, but I'll just do it to be consistent. Text-align colon center, and then down here, after another semicolon, text align colon center. All right, let's go back, reload. Now it's going to be much more obvious, the change. And we now have the beginnings of a home page. Still pretty basic, but at least it's a little more interesting. Turns out we can do a little better with the copyright symbol. Like most computers actually have support for a circle with a C in it. But you can't just do that with text like this. There's different ways to do this. You could copy paste it from like a website that already has it, so you don't have to figure out the magical keystroke on your Mac or PC. But there's also in HTML what are called entities. And you can actually specify using hexadecimal or decimal codes numbers like this, #169 semicolon after an ampersand. And this is a special symbol that you can look up in any online reference for like special characters that are hard or impossible to type manually at your keyboard. And this, let me zoom in just so it's obvious. If I reload now, instead of being 2 parentheses and a C character, now it's a proper copyright symbol. So you'll see these out there. They're not necessarily that frequently used nowadays, but it's good to know that they exist. But let me go back now to my code and propose that, while correct, this is arguably not very well designed. And even if you've never seen HTML, never seen CSS before, what instinct might you have for why this is poorly designed? Yeah. there's repetition, right? In general, in the past several weeks, C, Python, SQL, like repetition, generally bad and sloppy, and it's not going to scale well. So the repetition I think you're probably alluding to is text-align center, text-align center, text-align center. Well, we can factor that out in CSS. The C in CSS means cascading. And this means that if you move some properties to like a parent or a grandparent, the children or grandchildren will inherit those properties. That is, they will cascade down the family tree, so to speak. And so let me go ahead and remove all of these, since I claim they're indeed redundant. And let me preserve just one of them by, well, let me do this. It's not quite right to put a paragraph inside of a paragraph. Like, that's just not a thing in English writing or in writing more generally. So I'm going to do one thing first. It turns out that these two are arguably not paragraphs, right? This is like a header, the body, the essence of the page, and then the footer. So if a paragraph isn't quite the right English semantics, you can actually use more generically a tag that's all over the internet called div, for division of the page. And this is just a very generic term for like a big rectangular region that divides the page again and again, just so that you can think about different regions. Now that I have div, which really has no more meaning than that, it's a division of the page, interpret as you will, now I can have multiple ones of these. And let me go ahead and open a div tag here. Let me close a new div tag here. And then just to keep everything tidy, I'm going to highlight everything in between and hit tab, and that just automatically indents everything for me. Now I have 3 divs inside of another div, and that's totally fine. This is very commonly done. Now I'm going to do this. Style equals quote unquote text align colon center semicolon or not. And now I have some cascading capabilities. Now the parent of those 3 children, John Harvard, will come to my home page, and the copyright will now all inherit that property. So when I hit reload, nothing aesthetically has changed. Whoops, sorry. Nothing. Oh, I should have done reload slightly earlier. When you use a div instead of a paragraph, it actually gets rid of the space between those paragraphs. It just sandwiches them a little closer together. I can fix this in another way. But that aside, everything is still centered, and the text is still large, medium, and small. But I should have called out that change in the paragraph spacing. But we could bring that back before long if we wanted. Now, what more could I do to maybe improve this? Well, strictly speaking, I don't really need that parent div, right? Because these 3 divs inside already had a parent. So let me actually get rid of that new div just to undo what I did. I'll highlight this, and if you haven't seen this trick, Shift-Tab will unindent nicely, which is perhaps helpful. I could just put that text align center on the body tag. So text align colon center, quote unquote. This too would work as well, so long as you go up the family tree, so to speak, reload. And now, indeed, there's nothing aesthetically that has changed this time. But it turns out nowadays the web is getting a little more sophisticated. And even though you will see so many examples online in tutorials and books using div, 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 div all over the place, there are newer semantic tags. Semantic just means they have more meaning than this generic notion of a division. And if you look up a documentation for HTML, you'll see that if you want to have a header on a page, not a heading like H1, H2, but a header, there's literally nowadays a header tag. And this is marginally better because it now says what it is. Search engines like Google and Bing can detect, oh, that's the header of the page. Maybe we should use this and give it more prominence in the search results. You can then have a main part of the page, so literally a tag called main nowadays. You can literally have a footer of the page. And again, these are often useful for screen readers to help recite things verbally for folks who might otherwise not be able to read them. And probably these screen readers might highlight the header and the main part, but maybe might not spend time for the user on the footer, which is arguably a little less important semantically usually. Or search engines, again, now know what's the header, what's the footer, what's the main part of the page, so they know what to search and analyze. So this would arguably be a better design nowadays as well. But what else remains as a problem? Well, this is now getting a little bit more subtle and takes some experience, but this practice of putting HTML and CSS all in the same file, it's a little sloppy. Why? Because it means I'm commingling my data with the presentation thereof. Like the juicy stuff I care about, like John Harvard and the phrase, welcome to my homepage, and all of the aesthetics that I might want to change over time. And honestly, because everything is currently in one big file, it's going to make it really hard for me to collaborate with a classmate or a colleague at work so that maybe I do the HTML, they do the CSS. Like, not if you're all working in the same file. It would be a nightmare. Even if you use the VS Code sharing feature like Google Docs and both are typing at the same time, like you're going to mess up somehow. It'd be nice if we could separate these two languages. Well, one way to do that would be as follows. Let me get rid of all of the style attributes that I've added up until now on all 4 now of these tags. And let me introduce the style tag that we saw on the slide earlier instead. I'm going to go up here into the head of the page, which is where technically these style tags must go so that they're already loaded into memory before the body is even analyzed by the browser. And inside of the style tag, I'm actually going to select the HTML elements that I want to stylize, if you will. So if I want to change the body's aesthetics, I'm going to literally type the name of that tag, body, and then, I'm sorry, curly braces are back also from C. Inside of these curly braces, I'm going to put text align center. So the key value pairs are the same. The only new thing I've done is I've moved some of the syntax up to this new style tag in the head. If I want to now control the header tag as well, I can use the same curly braces. This is convention to put the open curly brace on the same line, the closed curly brace on another. The browser doesn't really care, but this is a common CSS style convention. I'm going to do font size large, semicolon. Then for the main tag, I'm going to do font size medium. And then for the footer tag, I'm going to do font size small. So same exact thing, and it's admittedly a little bit more verbose. It's taking up more lines of code. It doesn't all quite fit on the screen. But if you scroll back down now, and you'll acquire an eye for this, this is just better. Like, it's just more compact. It's more readable. The content, the data jumps out, and there's no visual distractions like the CSS properties as before. Upside here, too, is that we don't actually need to this doesn't actually change the aesthetics. If I reload the same page, it still looks the same, but I've taken a step toward some slightly better design. But let me propose that there's other ways to do this too. We just selected things by way of their type. So that was a so-called type selector when I literally just specify the type of tag, body, header, main, footer. But there's other ways that now we can lay the foundation for making reusable CSS that you and colleagues and classmates can use and reuse in multiple files and even in multiple projects. So let me actually go ahead and do this. Instead of just very explicitly saying, I want the body to be centered, let me invent an adjective, if you will, and let me change this to .centered. And this new vocabulary word, centered, will literally mean text-aligned center. Let me go ahead here. And I'm just going to create a new adjective called large, a new adjective called medium, and a new adjective called small. They are deliberately consistent with what the properties do, but these are now my own vocabulary words, and they are called classes. So a class is just a collection of key value pairs, a collection of properties that you get to invent for yourself. And what it lets you do now is this. Now, if I want the whole body to be centered, I can add this tag, which we actually saw briefly in Yale's HTML, class equals centered. Down here in the header, if I want this to be large, I can say class equals quote unquote large. Down here on main, I can say class equals quote unquote medium. And down here, I can have class equals quote unquote small. Now, I have taken one step backward by re-adding some of the aesthetics to the page, but it's not the actual properties. It's not the key value pairs. It's now more semantically nice because now I just know from reading the HTML what these things are going to look like, whereas the implementation details for all 4 of those adjectives is now relegated up above. And these are literally my words. I could change it to .foo and use class equals quote unquote foo, but obviously that would not be the best choice of words in this case. All right. Any questions on this? This now is what we would call a class selector by using literally the dot, even though the dot does not appear elsewhere, but dot means this is a class. These are not always the best syntactic design decisions that the world makes. All right, well, one last trick then. Notice that this is a little annoying that I'm still working in the same file, and if my classmate wants to clean up my aesthetics, make my homepage look way better, if my colleague wants to do the same, wouldn't it be nice if we could actually move all of this code to a different file, like a Python library or a C header file? Well, you can. Let me go ahead and delete that whole style tag. Let me add a confusingly named link tag, the href of which, let's call a new file styles.css. And let's say that the relationship of that file is that of style sheet. So this is a term of art in the world of web development. A style sheet is a text file that contains lots of styles, lots of CSS properties. Let me open my terminal real fast. And let me do code of styles.css, enter. And in this file, I'm going to paste all of those same lines as earlier. But now they're in a separate file. And indeed, if I hide my terminal window and I give this file to a colleague, they can now work on the aesthetics of the page and make things a lot prettier than this, maybe use specific font sizes, maybe add colors and the like, whereas I can focus entirely on the HTML because this file now will reference that other. And if I go back to my other tab and reload, the content's going to be exactly the same, but now I'm using some separate file instead. Any questions now about these techniques here? No? All right, so with that said, let me show just one example now of what I called a moment ago frameworks. And this is where web development gets kind of fun, at least if you like this, especially if you like the sort of logical design, the presentation of information you care about, but you really don't want to struggle with like font sizes and colors and getting everything pixel perfect, so to speak. Let me propose that I open up here an example in just a moment in VS Code that I prepared in advance. And this one is going to be an opportunity to consider how you might take some of the data from last week, which we had, wherein we collected everyone's favorites, and lay it out in a really big HTML table. So I wrote this out in advance because it was a huge amount of data, but it's the same data from the Google form from last week. And you'll see already the hints of a table tag and these TRs. And I added a few other tags for aesthetics. It turns out when you have a more visually interesting header for your table, there's another tag calledthead. There's another tag called tbody. These are not all that intellectually interesting. I just read the documentation and realized, oh, to make things prettier, I need a thead, a tbody, and so forth. But what's interesting here is that if I go to my index here and open this file called favorites.html, here is all of the data from last week's Google spreadsheet, which we exported as CSV, and I manually, before class, converted to just HTML. It's indeed a table, but it's really not pretty. Like the columns are really close together. It's kind of hard to distinguish one row from another, but this is just raw HTML written by me. Now, I could use CSS and some of the tricks we just saw to maybe change font size. There's ways to change color, background color, and a lot of things like that. But honestly, surely other people in the world have presented tabular data in pretty ways, right? I've been to many websites that have prettier tables than mine. Can I maybe use someone else's framework, someone else's CSS, include it in my page, but then stand on their shoulders and just make my stuff look prettier? Well, I dare say I can. Let me go ahead here and semi-secretly open up VS Code again, and let me grab a slightly different version of favorites.html that I also opened in advance, wherein I add this line of code instead. Give me just a moment to foreground this version, and the data is all the same as before, but I've added one of these link tags. And I'm not linking to my own styles.css. I'm using a popular library called Bootstrap. And Bootstrap is just one of many popular libraries out there, free at that, that has a whole bunch of CSS files and soon JavaScript files that you can just use for free in your own projects, personally or professionally, that just make things look and behave better without you having to reinvent wheels. Now, to access their CSS, I had to read their documentation and grab this very long URL here. But it's the same idea. Link href equals quote unquote something. And I read their documentation, and they told me to add this. They told me that if I want my tables to be prettier, I have to add a class attribute to my own table tag and specify, a little weirdly, but this is what Bootstrap told me to do, a class called table. And that will make it a prettier Bootstrap table. And if I want to stripe it, like every other row is gray instead of white, just to make it pop a little more visually, I can also add a second class separated by a space called table striped. That's all I did. I added line 5 and I changed line 9, and that is it. The rest of the hundreds of lines in favorites.html are the same. But if I go back here now and reload the browser, now, thanks to Bootstrap, voila, like it's much prettier. Now I can zoom out, and that changes the font size just locally for me. And even if you don't love their aesthetics, I mean, this is easily better than my own there. And it turns out we can do even better by adding interactivity to this too. But to do that, we're going to need one final language for today. And this one is an actual programming language. And we won't use it all that much in CS50, but we introduce it here as we begin web stuff because there's just so many free libraries and professional libraries that you can use just to make your web applications fancier and more interactive. Mobile applications as well increasingly use HTML, CSS, and JavaScript to power our iPhones and Android devices as well. So a quick tour of some syntax, and then we'll conclude with just some hopefully inspiring examples to give you a taste of what JavaScript can do. So JavaScript supports conditionals, just like C and Python before it. If we rewind to our Scratch days, here, of course, is a conditional. Here is the corresponding JavaScript code as of today. It's pretty much identical to C with the syntax here. If we had an if-else, in Scratch it looked like this. In JavaScript, it's going to look like this instead. So it's a bit of a regression vis-a-vis Python. Like the parentheses are back, the curly braces are back, the semicolons I mentioned in CSS are also back in JavaScript potentially. But it's familiar is the point here. And it's a different language that's frequently used for the web, whereas you can't use Python in the ways we're about to use JavaScript. It just wasn't designed for that purpose. Meanwhile, if you have an if-else in Scratch, well, in JavaScript, just like in C, it's going to look like this instead. Variables in JavaScript, of course, are a thing too. And in Scratch, we might have initialized a counter variable to 0. In JavaScript, a few different ways to do this. And just for now, the keyword is let. It's sort of a polite way of asking for a variable. Let counter equals 0, semicolon. So you don't mention the type, but you do use a keyword here, in this case called let. If you want to increment counter by 1, few different ways. In JavaScript, you can do this, just like in C. In JavaScript, you can do this, just like in C and in Python. In JavaScript, you can also get this. So ++ is back. So maybe that counterbalances the other syntax as well. That was not the case in Python. Loops are back, of course, in JavaScript, whereas in Scratch, you could repeat 3 times like this. In JavaScript, it's pretty much just like C. The only difference here is that you say let instead of int for an example like this. Meanwhile, if you want to do something forever in Scratch, in JavaScript, just like in C, you say while true in this case. So this is to say, we're sort of comfortable spending relatively little time on JavaScript, at least for today's purposes, because syntactically, it's really the same as we've seen before, with maybe a slight variance here or there. But what's interesting today, arguably, is just what kinds of things you can do with it. So with that said, what kinds of things can we do? It all comes back to this picture. If this is a simple web page on the left, and this is the corresponding tree, or DOM, document object model, on the right, that is the tree the browser automatically creates in memory, or RAM, for you, JavaScript is now a proper programming language that lets us dynamically manipulate, like read data from this, change this, and this is how Google, for instance, implements your inbox. They might have in your inbox, it's like a table, so tr, 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 probably, something like that, or heck, maybe div, 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 div. Using JavaScript, anytime they realize someone sent you new mail, they can create a new node, a new rectangle in memory, and you, the human, see a new div or a new tr again and again and again. So with JavaScript, you just have the ability to control the user's experience instead of, like I've been doing, constantly hitting reload in the page to see some new content. To see some new content, JavaScript can be running 24/7 so that you can actually see all of these changes live. All right, so let's go about writing some JavaScript code now. Instead of writing it on the server and executing it on the server, we're going to actually use a very common paradigm, whereas JavaScript is actually executed in the browser client side. That is to say, we can actually start writing some JavaScript code inside of our own .html file so that when a user visits that web page with their browser, not only is the HTML and any CSS downloaded to the user's browser, so is that JavaScript code so that it's executed indeed client side on the browser rather than server side, as has been the case with Python in previous weeks. Well, where do we go about writing some JavaScript code? Let's go ahead and revisit hello.html, which previously was a completely static example that literally just said hello title, hello body. Indeed, if I open this up using HTTP server and view it now in a separate tab, all it said was exactly that. Hello title in the tab and hello body in the main part of the viewport, so to speak. Well, let's make this example a little more dynamic so it doesn't just say hello body, but maybe says hello to an actual person. So let's go ahead and do this. Let's go ahead and remove the hard-coded hello body. And let's actually go ahead here and use a form tag. But we're not going to use this form in the usual way, whereby the data gets sent all the way back to the server. We're going to leverage control over this form client side instead. So I'm going to go ahead and create this open form tag, close form tag. Inside of that, let me give myself a text input that's going to have autocomplete equals quote unquote off, just to ensure that what I previously typed in my examples doesn't reappear accidentally. We're going to autofocus it so that the cursor is blinking right there in that text box. And this time, I'm going to go ahead and give it, how about a placeholder of quote unquote name, to make clear that I'm prompting the user for their name. And then the type of this text box will be the default, or more explicitly here, text. And then I'm going to have, as we've seen before, a button, the type of which is submit, also our typical default. And then inside of this button is going to be the label. How about something like, how about we'll call this greet? So that's what the button will actually say. Well, let me actually go back into my browser tab. Let me reload this page. And we should now see a relatively simple form whereby I have the cursor blinking on a text input prompting the user for their name, and then a greet button that I can click. But if I click this button now, it's not going to do anything useful because I haven't written any code to tell the browser what to do when I click that button. But it turns out there's all sorts of events in the world of JavaScript that you can listen for, so to speak. In fact, here's just a list of some of them. Anytime something changes in a form field, anytime the user clicks or drags on something, anytime the user presses a key and maybe lifts their finger up, anytime the mouse goes down or over or up on top of something, or anytime a form is submitted, those are events in the same way that we talked about events back in week 0 in Scratch. And in JavaScript, just like in Scratch where you can do something when green flag clicked, in JavaScript you can write code that actually listens for any of these events or more. So with that said, let's go back to VS Code here. And let's make a couple of changes instead. Let's go ahead and add to this form a new attribute. That's not the best way to do it, but it's perhaps the simplest for version 1 here. And let's say on submit, do the following. So on submit is an HTML attribute. And curiously, its value inside of the quotes there can actually be some JavaScript code. And let's go ahead now and let's assume there exists a function in the world called greet. And what I want to do is call that function right then and there. Well, now in JavaScript, how do I go about making that function exist? It doesn't come out of the box just like print might or say might in Python or Scratch respectively. But I can do this. Let me go up into the head of this page. Inside of a script tag here, both open and close, let me actually write some JavaScript code. And just so it stands out, I'm going to give myself a couple of blank lines, though not strictly necessary. And let me define a new function in JavaScript called greet. And this is the syntax in JavaScript for creating your own function. Similar in Python, instead of saying def in JavaScript, you just say function, then the name of the function, and any arguments within the parentheses thereafter, but I'm not going to pass in any here. Then inside of curly braces, what I'm going to do is use a built-in JavaScript function that comes with any browser called alert. It's not the best or prettiest user interface, but for now, it's going to get the job done. What do I want to say to the user? Well, let's first just say something simple like hello, comma, world, close quote, semicolon, thereby alerting the user with precisely that message. Now, what I'm going to do down here is make one other change. I don't want this form to actually get submitted to the server. Just like we've seen in the past, when you submit a form, it often goes to something like google.com/search. I actually want my JavaScript code to take control over the entire user experience of this form so that I'm just using the form as a user input mechanism, not to actually send via get or post this data to some other server, including my own. So this is going to look a little ugly, but after calling greet, I'm actually going to do this, which I've read the documentation about, and I know that if you actually hard code return false here, that just tells the browser, please don't actually submit the form, only call the greet function. All right, well, let me go back to my browser here. Let me reload this because I need to download the latest version of the JavaScript code. And I'm just going to go ahead, without even typing my name, I'm going to click on the greet button. And you'll see that, albeit a little cryptically at the top, we see an alert that says hello world. There's my ugly URL of my code space there at the moment, but we do indeed see that string. But what I haven't, of course, done is taken any actual name from the user. So how can we go about doing that? Well, ideally, I want to alert the user with hello, comma, David, or hello, comma, Carter, whatever name I type into that box. So how can I go about doing that? Well, let me create a variable called name. And let me set it equal to this function call, document.querySelector. That comes with JavaScript itself. Let me then in parentheses pass in an argument that is going to be, the ID, I need a unique identifier for the thing I want to select. So let me actually go back to my HTML code here. And instead of giving this form field a name like Q for query, let me actually use another HTML attribute called ID, where now I can call this anything I want. And for clarity, I'm just going to call this input element uniquely name. Now up here in Query Selector, just like in CSS, where you can use hashes and dots and other symbology in order to select certain nodes in your DOM, that is rectangles in that memory tree, well, I can go ahead and select hash name, which again is just the syntax for uniquely selecting the element whose ID is, in this case, name. So you have the hash up here. You don't need the hash as the value of the attribute down here on line 20. And now if I want to actually get the value of that text box, I literally just say .value. So document refers to the whole web page itself. Query selector is a function that's built into that object, so to speak. And the value, accessible via .value, just like a C struct or even a Python class, allows me to go inside of that text field and get whatever the value the user has typed in. Now, as I've been able to do in languages like Python fairly readily, I can concatenate this name onto the string hello, comma, space, so as to form a complete phrase. And you'll notice here that I'm actually using single quotes in my JavaScript, double quotes in my HTML. This is perhaps a common convention. In JavaScript, the language does not care if you use double quotes or single quotes, but I dare say single quotes are just more common. And so that's what I've done here. All right, now as always, I'm going to cross my fingers, go back to this page. I'm going to reload because I've changed the JavaScript and I need my browser to download it. And now I'm going to type in my name, for instance, DAVID. Click greets with fingers crossed, and voila, now I see hello, comma, David. All right, so it turns out that while functional, this isn't the best design, and commingling your HTML with your JavaScript code, as with this onSubmit attribute, isn't particularly clean. It's better, as with CSS, to keep your HTML over here, your CSS over here, and your JavaScript now over here, so to speak. And better still, perhaps even in some separate files. So how can I go about changing this a little bit? Well, let me go ahead and let's go ahead and delete all of this code for just a moment. And let me go and get rid of this onSubmit handler down here and really just distill my HTML only into the HTML and the attributes therefore. And what I'm instead going to do now is do this. I can use JavaScript to achieve the listening for that submit event or that onSubmit event. I don't need to actually use HTML for that. I can use JavaScript entirely. So it turns out I can access some other member of this document by doing document.querySelector again. But this time, let's select the actual form tag. And it doesn't have an ID because it has no ID in its HTML, but it does have a tag name. So just like in CSS, when you can target elements by way of their name, I'm just going to select the one and only form on this page by using that same query selector function. And now I'm going to use another function that just comes with JavaScript in the context of browsers, whereby once you select an element like that form, I can call add event listener, which is similar in spirit to Scratch's when green flag clicked or any block like that. You can then tell the browser what event you want to listen for. I want to listen for the submit event. So you don't say onSubmit here. Now that we're in pure JavaScript, you just say submit. And now I can do something like this. I can go ahead and say, call the following function. And I'm not even going to bother giving this function a name, and that is allowed to in JavaScript, as we saw briefly in Python. And what I'm going to do now inside of curly braces after that keyword function is the same kind of code as before. I'm going to do let name equals document.querySelector. I'm going to select that same name ID as before and get its value. And then I'm going to do alert and then pass in hello, comma, a single quote. Again, after that, concatenate with that the name, and then semicolon. But I need to do one other thing. It turns out that this function, and if you read the documentation for this technique, actually takes automatically a special argument called by convention event. And this is just a variable, if you will, that refers to whatever event just happened. In this case, it's of course going to be submit. But in other contexts, it might be a click event, a mouse down event, or something else entirely. So this allows me now to do this, which is a little cryptic, but you get used to these conventions. I can use that event, whatever it is, and then prevent whatever the default behavior is by calling a special function called prevent default with a capital D. This is the alternative to that messier return false semicolon that I had inside of my HTML before. So all I've done here now is I've left all of my HTML as pure HTML down here, and I've put all of my JavaScript code as pure JavaScript up here. This sort of separation of concerns similar to what we started doing with CSS just a bit ago in order to keep those two languages separate too. Well, let me go back to my browser here, reload the page, and unfortunately there's a subtle mistake I've made here. Let me go ahead and type in DAVID and click greet. And unfortunately, nothing actually seems to happen. Well, maybe it's just my name, Carter, greet, and nothing seems to happen. That alert does not come up. Well, why is that? Well, let me go back to VS Code here and point out that order of operations in JavaScript matters similar in spirit to C. Because on line 7, I'm selecting the form and trying to add an event listener for submitting that form, unfortunately, the form had better exist at that moment in time, but it doesn't. Because just like in C, and in some cases Python, where the compiler or the interpreter reads the code top to bottom, notice that the form doesn't actually exist and therefore get loaded into the computer's memory until line 19. So we've got to kind of reorder these somehow. Now, maybe the simplest way to do this would just be to perhaps do something like this. Let me scroll back up to my script tag and perhaps a little more explicitly move it into the order in which I want it to be executed. So I'm going to go below my form and inside of my body, which is actually OK for JavaScript here, and just use that same code. And assuming I didn't make any typos, let's go back to the browser. Click reload again to get the latest. Type in my name again using that purely JavaScript solution. And the only change I made was I moved the code from up here to down here. Clicking greet now. And wow, it's now back. We get the alert with hello, comma, David. So those kinds of things, those kinds of principles matter, at least when we're back in this world. But there's other solutions too. And just so that you've seen it, because it's a common convention in libraries as well, let me undo that change and put that script tag back in the head, or really anywhere else in the page where it might be. And let me propose that there's one other way to solve this problem to postpone that code on lines 7 through 11 getting executed until really the whole DOM, the tree, is ready to go. And the syntax for this might be as follows. I can do document, and I can add to the document an event listener that's going to listen for something a little special. And I always have to look this up myself to remember the spelling and the capitalization. But it turns out that the browser itself, once it's done loading all of your HTML top to bottom, left to right, it will raise an event called DOM content loaded, capitalized exactly as such. And if you want to call some function, and I don't even need an event argument in this case, you can open curly braces just as before and put inside of those curly braces the code that you want to execute only once the DOM's content has been loaded top to bottom. And now let me just finish my thought with a closed curly brace, closed parenthesis, and semicolon. It gets a little annoying to visually line all of this up, but I think I'm still good. And now, even though this code is at the top of my file, or really above the form tag itself, I think we're OK. So let's go back to the browser here, reload the page, type in DAVID, and click greet, and we still get the same correct behavior. And so this is just a very common paradigm to use these kinds of events to listen and listen and listen for something to happen, and then only do something once that thing has transpired. All right, well, let's take one more step with JavaScript code before we take a look at what's really fun about this language and what you can do with browsers in particular, by just cleaning things up a little bit further. I'm going to go back into the code here, and I'm actually going to remove or cut all of this code out of the hello.html file itself. And I'm going to change my script tag to have nothing in between the open and close tag. But I am going to give it a source attribute. And let's go ahead and call this, for instance, hello.js. So .js would be the convention for the file extension for a JavaScript file. And even though this is a little weird that we have the script tag and a source attribute, then nothing in between the open and close tag, this is indeed the convention when you want to put all of your code in a separate file. And let me go ahead and do that. Let me go ahead and open my terminal window, create a new file called hello.js. And then in that file, I'm just going to paste the very code that I just cut from the previous file. So no changes to the code. All I'm doing is factoring it out. And now I'm doing something just like our CSS factorization before, which confusingly used the link tag. This uses the script tag. This just now allows me to collaborate with someone like Carter or someone else so that they can do the JavaScript code, I can do the HTML, maybe a third person can do the CSS, and indeed, maybe we can build even grander things by designing things in this way. All right, well, let me go back to my browser again, reload the page. I shouldn't see any visual changes, but if I type in my name again, David, and click greet, this still now works. And what my browser has just done underneath the hood is not only download the hello.html file as always, because there's now this script tag that's referencing the source of another file. Just like an image tag might reference the source of an image, the browser is automatically helping me out by loading that into its memory as well. And now, how about one final example? And for this one, I'm going to go ahead and not write it live, but open it up as prepared in advance, just to show you what you can do by listening for some of these other events as well, like the key up, the finger going down, the finger going up, and listening for exactly that. So as the user is typing something, you can do something interesting as well. I'm going to go back into my directory listing here, and I click on this source 8 directory, which has all of the examples that I wrote here in advance. And I'm going to scroll down to one called hello5.html, and in hello5 now we've gotten rid of the button and we just have this text box. But notice now what happens if I start typing my name as D-A-V-I-D. I'm not typing enter at all. And in fact, if I start deleting and I change my mind and start typing Carter's name, notice now that the web page, the DOM inside of the computer's memory, is now automatically updating itself. So it's not even listening, it would seem, for a submit event anymore, but maybe for a key up event instead. So let me go back to VS Code here, open my terminal window, and in my source 8 directory, let me open up hello5.html. Inside of the script tag, you'll see some code that's similar in spirit to before, whereby I'm adding an event listener to the document, waiting for the whole DOM's content to be loaded. But then inside of that function, I'm now doing this. I'm creating a variable called input and selecting from the document the one and only input tag that we saw just a moment ago. I'm then adding on line 11 an event listener for key up, which is exactly that gesture, so that I can execute some additional code anytime the human lifts their finger from the keyboard after typing a key. What do I then do? Well, I'm going to go ahead, it seems, and declare another variable called name. And I'm just going to select some p tag on the page. And now, we didn't really see a p tag, so I think it's time to look at the HTML. If I scroll down to the bottom of the page where my actual HTML is, you'll see that there's just a form tag, and no onSubmit handler anymore as before. There's just an input tag and no button at all. But there is on line 29 here an open and close p tag, just so I have an empty placeholder in which to put something like hello David or hello Carter. So that's why now on line 12, I can define a variable called name, and I can select that p tag so that what do I want to do? Well, if inside of the input there's a value, so this is essentially checking for null or the absence of a string. So if input.value does not equal nothing, that is, there is a value in that text box, well, this syntax here on line 14 is a very clever way of doing the following. Go into that name tag, that is to say the empty paragraph, change the inner HTML of it, the HTML inside of it, to be literally this, hello, comma, and then just so you've seen an additional piece of syntax, this is similar to Python's f strings. The syntax is a little weird in JavaScript. You actually use not single quotes, not double quotes, but backticks, which on a US English keyboard are typically the top left-hand key of your keyboard or thereabouts, and using $ curly braces, just like the curly braces alone in Python, allows us to plug in whatever the value is of that input. However, if there's no value there, it looks like I'm just going to say hello, whoever you are. And in fact, we can see that behavior now as I delete, 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 and nothing's there. Now, that if condition is no longer true, and so we see this default value instead. So this is only to say that by harnessing these various events that are constantly happening on most any web page, we can now register code, just like we did way back in Scratch, to actually listen for those events and do something with them. Now, it turns out we can do some interesting things even using third-party code. And just as we used Bootstrap a bit ago to make our table prettier, allow me to propose that we also take a look at this version of favorites as well. Let me go back into my source8 directory and open up favorites2, which I made in advance, which looks almost the same, though I've zoomed in here a bit. But you'll notice somewhat subtly over the leftmost column in this table, you'll see now this arrow in gray pointing up and pointing down. Previously, those were not there. All I had was a static HTML table with all of this data sorted in whatever order it was inputted the other day in that form. But now, notice what I can do. If I want to sort in one order, I can click this arrow, or the other order, I can sort in this arrow, so essentially doing it chronologically forward or backward. Now, how is that sorting happening? It's presumably based on all of the timestamps that were registered when we submitted that Google form just a bit ago when it was live. But now, using JavaScript, it turns out that we can use some logic somehow and sort this data by the same. And you don't get that automatically just by using HTML alone. Now, how did I achieve that? Well, it turns out if I go ahead and close these hello files and in VS Code, let's open up favorites2.html, you'll see that all of the HTML is actually the same if I scroll down and down through this file. But I added a little something interesting at top. I copied and pasted the appropriate URLs and HTML tags from Bootstrap's documentation. And you'll see here that I have a file called not only bootstrap.min.css, but also bootstrap.bundle.min.js, as well as a couple of other things as well that allows me ultimately, using third-party libraries, to add some special HTML attributes that those libraries told me to add. And then as soon as those libraries detect the presence of these attributes now on my own raw data, they do their thing and JavaScriptify, not a technical term, the entire table and now make it interactive and not static. So you'll see here that the aesthetics of the table are as before, table and table striped. But I'm adding now another HTML attribute called data toggle, whose value is table. And I know that only from the documentation of these libraries, indicating that that's how I can now enable this table to be interactive, as I can too by adding data sortable equals quote unquote true on specifically the timestamp column. And the only thing unfamiliar here perhaps is I'm using TH for table heading as opposed to TD as I do elsewhere. But that's all that it takes to now focus on the raw data you want to present and let someone else do the heavy lifting of actually implementing the logic. Well, let's end with just a look at what more you can do with JavaScript and just how powerful it is when you combine a language like this with the data and the user interface you want to convey. Let's go ahead and open up within source8 directory something called background.html. Now, this interface here is quite simple. It just has 3 buttons, R, G, and B. And the background, of course, notice by default is just white. But when I click on the R, the background turns red. When I click on the G, it turns green. And the blue, it turns blue. And again. So how is this working? Well, if you think back again to the available events, perhaps I'm just listening for a click on those buttons and then doing something with maybe the CSS of the page to allow me to see those different colors. So in fact, let's go back to VS Code here, and let's open up background.html. And in here, you'll see some simple HTML at the top, just 3 buttons, but I've given each a unique ID so that I can reference it in code. And then inside of a script tag here below, because I didn't bother with the DOM content loaded event here, notice that I'm doing the following. I'm creating a variable called body that lets me select the body tag. I then have in these 3 lines some code that handles red. What am I doing? Well, I'm selecting from the document whatever HTML tag has a unique ID of red, and then I'm adding an event listener for any click on that button. And anytime someone clicks on that red button, I call this function anonymously. It doesn't even have or need a name. And this syntax here is powerful because now in JavaScript, I can alter the CSS of my page by doing body, which is the tag that I selected 2 lines ago, accessing its style, accessing its background color property, and setting it equal to quote unquote red. And I do the same down below for green. I do the same down below for blue. And the only thing worth noting here is that in CSS, it turns out it's the case that the CSS property for the background color of a page is actually background-color in all lowercase with a hyphen in between. Unfortunately, in the world of JavaScript, a hyphen would be mistaken for subtraction, like background minus color, which would be wrong. So the convention in JavaScript is when you're trying to manipulate CSS, you take whatever the property name is, font size, background color, and you change it into so-called camel case here. You get rid of the hyphen and you capitalize the subsequent words like color in this case here. All right, how about another? Well, it turns out back in the day, back in my day, there was a HTML tag that would actually allow you to do this: create blinking text on a screen. It's rather unpleasant at this rate, certainly, but how might this work? Well, it turns out in JavaScript, if we take a look at the blink.html file here, we'll see that you can, in your HTML, do something literally as simple as hello world in the body. But then you can call this function here. Turns out, just like document, there's another global special variable you can use in JavaScript in browsers called window, which refers to all things related to the window itself. The window comes with a set interval function, which lets you do exactly that: set an interval in milliseconds, and after every expiration of that interval, some function will be called for you. So in this case, it's saying every 50 milliseconds, but let's actually slow that down now to 500 milliseconds, or 1/2 a second, call a function called blink. Notice I do not have parentheses after the blink name because I don't want to call blink now. I want to tell JavaScript to call the function called blink every 500 milliseconds. Now, we'll see in a moment what that code looks like, but let's go back to the page and reload, and you'll see now that it's a more pleasant blinking, if that's even the case, every half second, because I'm now firing that event. That is, I'm calling that function now every 500 milliseconds instead. How am I doing that? Well, in this same script tag, I've invented my own blink function. This has the distinction back in the day of actually being an HTML tag and among the few tags that the world removed and got rid of so that it's no longer used because it's not all that user-friendly. But down here, what am I doing? I'm getting the body of the document itself with this variable, and then I'm checking two CSS properties that we didn't talk about before, but it turns out that you can check and set the visibility of an element in JavaScript by going into that tag, checking its style, and getting its visibility property. And if it happens to equal hidden, the next line of code here, 13, sets it equal to visible instead. Else, if it's not hidden, it must already be visible. And so line 17 flips it the other way and changes it to hidden. Here, left hand, right hand, clearly not talking. No idea why the opposite of visible is not invisible. It's indeed visible and hidden. But this just allows you, every time this function is called, to change the property from one value to another, achieving that blinking effect. You can do even more powerful things that you and I take for granted every day. Let's go into source 8 and go to autocomplete.html, which I wrote in advance. And this is a page that also loads into memory a really big dictionary that you might recall from problem set 5. And if I go ahead and type in something like C, A, T, you'll notice dynamically an unordered bulleted list appearing below the text box that shows you all of the words in that dictionary from pset 5 that start with C and then CA and then T, just like the autocomplete you see every day on your phone and Google or websites like it. How is that working? Well, probably I'm listening for the key press going up. As soon as that key is pressed, I'm probably searching through a big array, really, of all of those words, maybe using linear search, maybe binary search if faster than that, and then looking for any string in that array that starts with C or CA or CAT. And then I'm generating automatically the HTML therefore. But perhaps most familiar nowadays is just how much your phone and your laptop know about you. And let me go into a final example here in source 8 called geolocation.html, which is a term of art that just refers to figuring out your geography, for instance, your GPS coordinates. Now, here we have a third and final global variable that your browser provides you with called navigator. And in navigator, there's a special object called geolocation that comes with a function called getCurrentPosition. So if you call navigator.geolocation.getCurrentPosition and then pass in a function of your own that doesn't need a name but does take an argument, in this case I called it position, as soon as the browser or as soon as the phone has figured out where in the world that user is with that browser at some latitude and longitude, the browser will automatically call that function for you, and you can do anything you want with the position that comes back, the latitude and longitude respectively. So I'm going to use a function that's not often that helpful, but for our purposes today, it's just going to write to the document itself, to my big rectangular region, whatever the latitude is, then a comma, and then the longitude as well. So if we go back with this final flourish into source 8, open up geolocation.html, you'll see that my browser first wants my permission to let this website, my own, know my location. I'm going to go ahead and click allow, crossing my fingers because it might take a moment for the phone or the laptop to figure it out. And it looks like, according to Google, I am right this moment with my Mac at latitude, longitude 42.375, comma, negative 71.11. Let's go ahead and highlight and copy that. Let's go to a website like googlemaps.com, crossing our fingers. If you've never done this, you can search for GPS coordinates too. Let's hit enter, and amazing. We are indeed in Sanders Theater, roughly there, standing on this stage on Halloween. And that then is week 8. We will see you next time. Happy Halloween. Nothing good? Buffering? Okay. Josh? Nice. Helen? Oh! Hit Moni. No, oh, wait. That was amazing, Josh. Sophie? Amazing. That was perfect. Oni? I think over to you all. Guy? That was amazing. Thank you all.
So good.
This is CS50, and this is already week 9, which is our second to last. Indeed, this is really the last week where you'll learn in this class how to program. But indeed, it's this week that's really meant to be the pedagogical climax of like all of these various languages we've been looking at, all of these various techniques, all of this syntax, so that at the end of CS50 in just a few weeks, you indeed feel that you didn't take a class on C, and you didn't take a class on Python, but you really more generally took a class on programming. Because indeed, we know already about half of you will go on to study computer science further, but half of you will not. And indeed, all of your programming chops here on out theoretically will have a foundation in what we've been doing these past many weeks, but here on out, it's really going to be up to you to learn some newfangled language when it comes out, or to follow some new trend when some language eclipses the ones we've been using as more popular, as more appropriate for problems you want to solve. And so today really is about synthesizing so many of the past few weeks, but doing it in the context of web programming, which for better or for worse is so very much in vogue nowadays, both on our laptops and phones. And indeed, the languages we looked at in recent weeks are used not only to make websites, but also full-fledged applications applications and app stores and the like. So this really will be the culmination of those past several weeks. And indeed, we'll even talk about some familiar concepts like shopping carts when you're on Amazon and these things called cookies when you're visiting websites. All of those topics, too, will come into play, and you'll have an understanding of what all that means from the ground up. So how did we get here? Well, just last week, we focused on HTML and CSS primarily, which are not programming languages. They're just about aesthetics, structuring your data, presenting your data, and so forth. And we served the web pages we wrote using this program, HTTP Server. This is just one such program. There's dozens, hundreds of different web servers that you can use out there. This is just a super simple one we pre-installed in your code space for you in VS Code so that you can just serve up web pages. At the end of last week, too, though, we teased JavaScript, a full-fledged programming language that you can use to manipulate the user's experience for the better, to make things more dynamic and interactive by actually running code in the user's browser on their Mac, their PC, their phone, as opposed to server side, which up until now is where all of our code in C and Python has been written. So you're writing code on a server, you're serving code from a server, but now with HTML, CSS, and JavaScript, it's getting executed in a browser. But today, we're going to view one final feature of Python, or really languages like it, that you can also use code on the server to generate automatically, dynamically, the HTML, the JavaScript, the CSS that you actually want the user to receive. You don't have to hard code everything as you have when making your own home page. Well, let's consider what some of the building blocks were last week. So here's a sample URL, and over here / is sort of the default page on any web server. It might be index.html. It might be something else. That's just a convention, but it refers to whatever the default actually is. You can visit, of course, with any browser, like a URL that ends in file.html or something else.html, and that literally means your browser wants this file on this server. Or, of course, we saw that it can be a folder, and inside of that folder is presumably some default file name, like, again, index.html. Or you can be more explicit, like folder/file.html. And these more generally we just called paths. And indeed, a path is just a location on your Mac, your PC, or on a server of some piece of information. But today, we're just going to rename this only to use other common terminology, but they're really just synonyms. Today, we're going to refer to those same things as routes. Because now, today, we're going to ultimately replace HTTP Server, which just serves up static content that you all write, with your own web server. Like, now you will be the ones controlling what it is the server does in response to the user's requests so that you can respond interactively and dynamically. But we're still going to see techniques like this. These were our so-called HTTP parameters. They're everything that comes after a question mark in a URL. And it can be like key equals value. And an example was what? When we played with Google, what was the key and what was the value that I first tried? Any recollection? I was searching for cats, and so the key I figured out was Q, because that's what Larry and Sergey, who created Google years ago, decided the name would be of the HTML text box that you type your query into. And if I type CAT for cat, the value of that would end up in the URL for Google as being !cat equals value. And I mentioned that it's often the case that you want to send two different inputs to a server, and this is why I propose that you just keep an eye out for ampersands. And ampersands separate these key value pairs. But again, this is the same darn paradigm as before, and we've seen this so many times, right? Key value pairs in dictionaries in Python. We've seen HTML attributes and their values. We've seen CSS properties and their values. It's all the same thing, associating something with something else, even though every language, every person seems to have their own vernacular for it. It really is just the same idea, this associating of something with something else. We'll continue to see. And here, to be concrete, were the HTTP lines of text that were in those virtual envelopes, if you will. If I were indeed trying to search for something like cats on Google, this, recall, was the message that got sent to the server by my browser in order to tell Google to please search for not dogs, but in this case, cats. Now, what has HTTP Server been doing for us? Well, it's just been serving up HTML files, CSS files, maybe some JS or JavaScript files, but it has been ignoring any HTTP parameters. Like, HTTP Server does not take user input. Why? Well, what's it going to do with it? Because you already wrote the HTML, you already wrote the CSS. Like, there's no decisions to be made until we introduce a proper programming language on the server. And so we're going to move away now from this simple HTTP Server program and introduce you to your own server that's going to handle the parsing, that is, the extraction of these key value pairs, so that you and I don't have to write Python code all of a sudden that, like, analyzes this stuff, figures out what page is requested, requested the key value pairs. All of that we're still going to get for free by just using the right framework. And so today we revisit Python, which we've now used in some form the past few weeks. And indeed, it's kind of been the glue that allows us to stitch together some of our own logic. We saw it with SQL. We're going to now see it with HTML, CSS, and even JavaScript if we want. And we're also going to see another language today, not a programming language, called Jinja. And this is going to be a common paradigm in the real world whereby different languages, different libraries, different frameworks often like borrow from each other, or they use technologies that someone else wrote just so they don't have to reinvent that wheel. So Flask is just a framework. That is a third-party library. It's pretty popular nowadays. It's relatively simple, which is why we use it in CS50. If you've programmed before CS50, Django is another popular framework or library in the Python space, but it's a little more complicated, so we focus on Flask. And Jinja, we'll see, is not a programming language. It's just going to be some syntax, thankfully familiar, with curly braces that allow us to use placeholders in our actual web pages. So again, you'll wrap your minds all eventually around where the lines are among these various technologies, but these are not the interesting ideas. The interesting ideas are the ones we'll focus on in code. But starting today, instead of running HTTP server to serve up a static website, we'll have you start running literally Flask space run in your terminal window to run your own web server that's implemented in Python using this Flask framework. So Bootstrap was a library for making your CSS and JavaScript prettier and more interactive. Flask is a framework or library for just making your Python code more pleasant to use, since you're borrowing features from someone else. All right, so how can we go about doing this? Well, if you were to write your very own web application, your own Amazon.com, your own Google.com, in Python using Flask, minimally, you need to have a file called app.py by convention, which is where all your Python code goes, and then a folder called templates, which is where all of your templates go. And for now, your templates are just your HTML files. So if we're going to now start building more interesting interactive things like Google.com or Amazon.com, we need to be able to execute code on the server. And so this is the convention. It's not index.html anymore necessarily. It's these two things at the top level. With that said, we'll quickly see that there's some other conventions. And in my examples online and in the problem set 9, you'll see another file called requirements.txt, which is just a text file that allows you to enumerate all of the third-party libraries your application might want to use. It's a convention so that the server can like automatically install things for you without you having to do it manually. And then static is going to be where literally your static content goes. So if you've got images for your web application, if you've got JavaScript files, CSS files, by convention that goes in static. These are just conventions. Like all of this can be changed, but this is like the way to do things. So we'll introduce you to the defaults. All right, so what does this mean? How, for instance, could I go about implementing my own web application using Python that somehow spits out a message like hello world? All right, well, turns out just this. Now, we'll tease this apart in just a moment, but this is the contents of a sample app.py file that apparently uses some library stuff, like familiar syntax from something, import something else. We've seen that before with CSVs and other libraries. This is somewhat new syntax, but it's kind of copy-paste for now. This is definitely new syntax and kind of weird with the @ sign here, but we'll see this again and again today. And it's just copy-paste initially until you understand what it's doing for you. But at least there's some familiar stuff here, like index.html is still going to be with us, but it's going to be up to us when and how to show it to the user. So let's make this more real. Let me go over to VS Code here, and let me go ahead and create a, how about we'll do this in hello. Let me do make dir hello to make a new folder called hello, and I'm going to cd into it just to isolate all of these files to the same directory so that we have different apps today in different folders. And now I'm going to do code of, let's do this actually. Let's do our make dir templates.html. Sorry, not templates.html. Let me rename that to templates using the mv command. This has nothing to do with web programming. This is me making typos. So if I type ls now, I've got a folder called templates. All right, in there, let's create a file called index.html that is going to be super simple and pretty much copy-paste from last week. Let me hide my terminal window, and let me just very quickly whip up a simple hello world page using my HTML tag, lang will equal English. Then inside of this, I'm going to have a head tag. Inside of this, I'm going to have a title tag, and I'm just going to call this thing hello. I'm going to then have a body. And in this, I'm only going to say something simple like hello, comma, world. And just so this is mobile friendly, recall that we touched on these meta tags. So just in case you, after class, play with your mobile device instead of your laptop, I'll do name equals quote unquote viewport. viewport, and then content equals, and I never remember this. I'm literally reading it off of a cheat sheet. Initial scale equals 1, width equals device width. And this is just this magical incantation that says to the browser, like, size things appropriately for the size of the device. It blows up the font sizes a bit. All right, so that's what I would have done last week. And I would have served this web page by running HTTP server in the same directory. And boom, I would see that HTML. But let's now start to take some control over the user's experience. And for now, it's going to be underwhelming. It's just going to always say hello world. But in a moment, version 2 is going to say hello David or hello Carter a bit more dynamically. And we'll quickly escalate from there to just more interesting applications as well, culminating with things like cookies and shopping carts and the like. So let me go back into my terminal window. And as promised, let me create another file called app.py. And this is where now I need to implement the web server I'm going to run using this Flask framework. And for now, I'm just going to kind of do some copy paste from what we saw on the slide a moment ago. From the Flask library, which we've pre-installed for you, I'm going to import a function called Flask, capital F. It's subtle, but it's important there. And I'm also going to import a few other things, a function called render template and another variable called request. And the only way I know this is from having taught this before, read the documentation, followed a tutorial. Like, you wouldn't know this unless someone told you or you read how to do this. But what this means is that this library called Flask has 3 things in it: a function called Flask, capital F, a function called render template, and a variable built into it called request. And this is going to be all the building blocks I need to implement my own web server. The convention in Flask, when you want to create a web app in Python, is you create a variable by convention called app, and then you assign it the return value of that Flask function, capital F, and pass into it underscore underscore name underscore underscore. Which is weird, but we have seen this before. A few weeks ago, anyone recall when and why we mentioned underscore underscore name underscore underscore? Yeah.
I think was it during Python at main or something?
Yeah, if we wanted to check if the name of the file was itself main, so that we avoided a situation where if you're writing your own library code, you don't want your code to be executed automatically. You want to potentially execute the main function. And that was a solution to that problem here. For today's purposes, this is just the way you do it. Underscore underscore name underscore underscore refers to the current file. And so this is just a little trick that says turn this file into a Flask application. That's all it is. And for now, that line suffices. All right, what do I want to do after that? Well, now I'm in charge of the web server. I need to write the code that decides, based on the browser's request, what file or files I'm going to send from the server to the browser. Last week, HTTP server did all of this for us, just based on the file name. But today, I'm going to take over control over that process. And the way I do that is as follows. I say app.route with, weirdly, an @ sign in front of it. This is known in Python as a decorator. And it's a feature of Python, not of Flask, that we just didn't introduce in weeks past. But it's a handy trick to do what we're about to do. The route I want to define is quote unquote slash. So that is, here is code I want the server to execute whenever a user visits / the default page of the website. Well, what code do I want them to execute? Well, I want them to execute a function, and I can therefore define in Python a function. I can technically call this thing anything I want, X or Y or Z. But because they're accessing the default page, otherwise known as the index of the site, I'm going to just more reasonably call this function index. But just a convention, you could call it anything you want, but X, Y, or Z is probably a bad stylistic choice. It doesn't need to take any arguments in this case. And the only thing this function is going to do is, for now, let's go ahead and have it return hello world, quote unquote, and that's it. All right, now let me go into my terminal window. Let me go ahead and do Flask run in the same directory that has app.py and hit enter. I'm going to see some cryptic output, but including a URL of my code space. And if I open that URL after hovering over it, I'll indeed see hello world, as you might hope. But let me do this. Let me go ahead and right-click on the page and click View Page Source, which, if you haven't done before, shows you all of the HTML for a page, however pretty or messy it is. And that's it. There's no HTML that I've spit out. It's just quote unquote hello world. Well, if I actually want to spit out a full web page, which is not a big deal here because who cares? It's just the text anyway. But if I want to spit out a whole file, let me do this. I want to return essentially the contents of index.html, which have all of the tags I want, the mobile-friendly stuff and all of that. Well, I can't just return index.html, but I can return this: render template, quote unquote, index.html. And per the documentation for Flask, this render template function will go find that file for me in my templates folder by convention. It will open it up, and then it will spit the whole thing out to the browser for me. So I can keep all my HTML in one place and all my Python code in this one place. So now if I go back to my browser and reload, I don't think I'll really see a difference because it's the same text ultimately. But if I view page source now, notice that, there is all of the HTML that was just sent to the browser. So this is only to say we have the building blocks, the puzzle pieces, if you will, via which to now store all of our HTML in one place, and presumably CSS, JavaScript, and so forth, but then serve up whatever we want, even though I'm just blindly spitting out index.html. So before we proceed, any questions on this, which again I claim is like my manual version of what HTTP Server was doing for us automatically last week. But this is how you do it yourself. Any questions? All right, well, let's make it more interesting, which we could not do with HTTP Server and HTML alone. Why don't we go ahead and do this? Let me visit the same URL, and I'm going to zoom in. And your URL will differ from my code space, but it's going to end similarly here. I'm going to do / name equals David, for instance, or Q equals Cats, or name equals Carter. Any key value pair I want, I'm going to append after a / and a question mark, thereby providing user input to the server, albeit in a very user-unfriendly way. No one's going to normally do this in their browser. Enter. Nothing changes here. It just says hello world. But wouldn't it be nice if it says hello David? Or equivalently, if I zoom in here again and change David to Carter and hit enter, wouldn't it be nice if it says hello Carter instead? So we need some dynamism there. And here's where now Python is going to be our friend. If I want to access the HTTP parameters that the user has provided via the URL, be it Q equals Cats or name equals David, I can use this special variable I already preemptively imported earlier. And I can do this. If there is an HTTP parameter called name in what I'm going to call request.args, then I'm going to go ahead and create a variable called name, and I'm going to set it equal to request.args bracket name. Else, if there is no quote unquote name key in this special variable called request.args, I'm going to just assume that the user's name is world by default. Now, what's going on here? Well, it turns out that Flask provides us with this special variable called request.args. And in there is all of the key value pairs that might have come in via the URL. So if you had to guess what type of data or what data type is request.args, that's its name, and here it is in context. Line 9 might provide a clue. In Python, what data type might request.args be? Yeah? It's not going to be an array or a list, because those are always, in every language we've seen, numerically indexed, but you're close. Someone else? It's a dictionary. So a dictionary is similar syntactically to a list in Python, but instead of numeric indices like 0, 1, 2, you can literally use strings like quote unquote name. Now, that's a bit of a white lie. It is a dictionary, but it's Flask's special fancy version of a dictionary. But the syntax via which you can access it is exactly the same. And actually, this is a typo. I didn't mean to say names there. I meant to say name singular. But otherwise, I think the code is correct. This is going to, on line 8, check if there's a key called name in request.args. And if so, it's going to set it equal to that value. Otherwise, it's going to default to world. I deliberately did not do this. I added this if else and did not do this. Why? What error might happen if I just blindly grab name? Exactly. If there was nothing at the end of the URL that was of the form $name equals someone, then there would be no name key. And this is a couple weeks back, but this would give you one of those annoying key errors when you get a traceback because you screwed up because you used a string that doesn't exist. That's why I'm just proactively trying to avoid that situation, just like I might have a couple of weeks ago. So even though it's more verbose, this is just much more defensive so that I don't accidentally index into a dictionary where there is no key. But we'll see how we can tighten this up to be not 4 lines, but 1. But I think now I can do this. Wouldn't it be nice if now in my index.html file, which recall is in my templates folder, wouldn't it be nice if I could do the equivalent in C of like a %s here, for instance, or in Python, something like this name? Well, it's close, and this is just because different humans invent different languages, invent different frameworks. The syntax for this in Flask is to actually do, 2 curly braces, and then name of the variable inside of it. Why? It's because probably someone figured, what are the odds that a normal person is ever going to use 2 curly braces at once versus just 1? So this is probably decreasing the probability that people actually want to output literal curly braces like this. So it's similar in spirit to Python's f strings. It's similar in spirit to C's %s. It's similar in spirit to SQL's question marks. Same idea, slightly different syntax. And this here is Jinja. So it's not programming code per se. It's just a template. And indeed, that's why this folder is called templates. It is sort of like a blueprint for what I want to be spit out to the user. But I've got these placeholders, like this variable, that I want to plug into that value. Now, this alone is not enough. Watch what happens if I go back to my other browser and I reload the page after changing up here. Let's do name equals David again. Enter. Nothing outputs after the hello comma. So it seems that the name variable doesn't exist yet. And that's why, indeed, if I do view page source, you can see what was sent to the browser. Something's wrong with my placeholder. But I just need to be a little more explicit as to what I want to send where. So it turns out that the render template function takes not just one argument, the name of the template you want to spit out, but it takes, after that, with commas, all of the placeholders you want to plug in. So for instance, if you want the placeholder to be this, literally placeholder inside of those curly braces, you can then specify as the second argument to render template a placeholder named argument equals whatever the name is. So name is the variable in the lines above. Placeholder is the name of my literal placeholder in the curly braces. And so now if I go back to my browser and reload this with still quote unquote, with still question mark name equals David in the URL, now I indeed see hello comma David. And if I zoom in here, and let me move over here, let me type in Carter and hit enter, now I see hello Carter instead. Now, this is a little unnecessary to explicitly call the placeholder, especially if you want to have 2 or 3 of them. So you can actually call this anything you want. And I'm going to change it back to name, which is a little more straightforward. The only weird thing here is that now you'll see that you're writing code like this. And this is correct. And this is the norm. It just looks weird. But the thing on the left of the equal sign is the placeholder you're using in the template. The thing on the right can be any value you want, including a variable. So even though I'm naming them exactly the same, which looks stupid, admittedly, like this is what people tend to do, just because it's simpler than introducing another word like placeholder. Any questions now on this? Any questions on these placeholders? No? All right. Well, let's tighten this up a little bit and see if we can't get things to be more dynamic still. Let me propose now that instead of using this condition, which made a very simple idea, like very verbose with 4 different lines, it turns out there's an easier way to do this. You can actually still create a variable called name, and you can set it equal to request.args. But instead of just blindly indexing into that dictionary, it turns out that request.args comes with a function as well called get. You can pass it an argument that tells you what value you want to get. And by default, if there is no key called name in that dictionary, this function will not throw a key error. It's just going to return none, N-O-N-E, the special value in Python. So it avoids a bug in your code, but it tightens up 4 lines into 1. But even nicer, if you read the documentation, the get function can also take an explicit default value. So if you don't want none to be on the screen, like hello comma blank, or I mean, that would be weird too, you can just put in a default value per the documentation of this function, like world. So now we've gone from 4 lines to just 1. So arguably, it's better designed. And if I go back to the browser now, still with Carter in the URL and hit reload, same thing happens. But we'll notice this. Suppose I get rid of the name parameter altogether and hit enter. Now it goes to the default instead, world. So it's just a little better designed than doing it the other way instead. All right, how about we take things up one more notch? And how about we introduce multiple routes and actually introduce perhaps a form to the mix. Because again, no normal person is going to like visit a URL and add a slash and a question mark in their name. Like that's not how browsers work. Well, that's how browsers work. That's not how humans interact with browsers. You and I use a form typically instead. So now things can get a little more interesting when making our own web application, because maybe we could do something like this. Let me go and zoom out again. Let me go back to my code here, and let me move this around and focus now on the index.html file. Instead of just this placeholder, why don't we go ahead and give ourselves a form like we've played with a little bit in the past, be it for Google or something else. And let's do this. Form, and inside of this form, let's have an input. And the name of this input will be quote unquote name. So that too is confusing, but inputs have name attributes, but this is a person's name. So I'm saying name equals name here. So just a messy world of semantics. And let me go ahead and make this a text box by default. And then let me give myself a button whose default type will be submit. And the name of this button will be greet, for instance. So let's see what happens here. But let me change app.py to just be the original simpler. I'm not passing in any placeholders now. And I'm going to even get rid of this. I'm just going to rewind to the first version of this for simplicity. Let's now change the URL to get rid of Carter and myself. So we just go to slash and hit enter. And now we have a super simple form again. All right, this is not super user-friendly, but there's some nice enhancements we can make. For instance, like we can, for instance, turn off autocomplete, especially if I want to type David and Carter manually and I don't want it finishing my thought during class. We can do autofocus, which puts the cursor there blinking by default, which is nice because then the human doesn't have to deal with that. And then we can even have a placeholder attribute. Placeholder equals name, so that it's like built-in instructions for this thing. And so now if I go back to the other tab, nothing's changed yet because I have to download the HTML again, reload. OK, now it's a little more user-friendly. It says name in light gray. The cursor is blinking. And I'm sort of ready to go. But this form hasn't been wired up to go anywhere yet. And so let's do this. Let's, for instance, say that the action of this form is not going to be something like google.com, which we did last time with for cats. I am now going to be both the front end and the back end of this website. The front end is what the human sees, the web page, the graphics, the forms. The back end is the stuff the human typically doesn't see, the Python code, the SQL code, the server itself. But now I'm in control of both sides of the experience, the HTML and also the routes. So let's just propose that we invent our own route. And instead of calling it /search like Google does, let's call it /greet. And let me specify that the method this form will use, which is technically the default, will be get. And confusingly, it is lowercase get, even though in the envelope we keep talking about virtually, it's actually capitals. Again, left hand wasn't talking to right hand when these things were decided. All right, so all I've done is create a web form that's going to submit whatever the text box value is to a route called /greet. By default, because there's no HTTP or HTTPS or no domain name, /greet is going to be assumed to be not at google.com, but whatever my own server's URL is. So whatever my code space's URL is, that's going to be the implicit prefix. This /greet is just the route. So now let's go back to VS Code's app.py file. How do I now stitch this together? Well, I think we're good to go with index.html. If index.html's purpose in life is just to spit out this form, we're done with one of my routes. But if I want to have a second route, greet, that actually spits out some greeting to the user, well, let's prepare that template too. Let me go ahead and highlight all of this HTML. Let me go back into my terminal window and into my hello directory and then into my templates directory. And let me create another template called greet.html, whose purpose in life will not be to show a form, but to greet the user with hello so-and-so. So in this file, I'm going to paste all that same HTML, but I'm going to get rid of the form and essentially revert to our previous version, hello, comma, and then using the Jinja syntax, name. So one template, index.html, is for the form. The second template now is for the greeting of hello, comma, so-and-so. But otherwise, these files, notice, are almost the same, except one has the form, one has just the hello. So now let's finish this up in app.py. Let me go down here after a couple of blank lines stylistically. Let me do app.route, quote unquote, /greet. But I could call this route anything I want. I'm just using a reasonable verb. Then let's define another function. I could call the function anything I want, x, y, or z. I'm going to call it more reasonably greet. no arguments. And then now is the code where I want to render the template. So I do return render template greet.html. But I need to do one more thing. What else do I want to do if I want greet.html to have access to the human's name? Just to recap. I think we solved this already, but I deleted it. But what do I have to add back? Yeah. Yeah, so I got to pass in the placeholder somehow. So I can do this a couple of different ways. I'm going to keep it a little more elegant this time. I'm just going to put my name argument there, and I'm going to set it equal to request.args.get quote unquote name comma world. Before I used a separate variable, but I only used it in one place, so that's not strictly necessary. So this is fine too. But if this gets a little overwhelming, notice that I can alternatively do this. I can create an actual variable called name, and then I can pass in an argument called name with a value that is that variable. But again, what's really the point here? It was kind of prettier all on one line. So these are the exact same things. I'm just trying to tighten things up further here. All right, so what just happened? If I go back to my form, this is still index.html. If I reload it, nothing has changed. If I type in my name to this form, notice again, the URL I'm currently at, this is Chrome hiding things. It's technically / by default, even though many browsers are just hiding unnecessary characters these days. But watch what happens now if I scroll over here and I click greet on this new form. Notice my URL, my route changed to /greet, name equals David, and the body of the page at top left says hello, David. So this is exactly how Google.com works, and it's how we implemented search.html last time. But instead of submitting the form to Google via the form, I'm submitting it to myself, my very own route. So I'm implementing my own backend for this same front end. All right, any questions just yet? Much less interesting than Google, certainly, but we kind of have all of the wiring now. Any questions? No? All right, so what can we do to further tighten this up and adhere to some conventions? Well, let me propose that in this version, we solve one problem. And even if you've never done this sort of thing before, I dare say we have enough weeks of CS50 where if I show you index.html again and greet.html again, odds are, to someone's mind, there's an opportunity for improvement. Why is this web app, super simple though it is, arguably poorly designed at the moment? And the answer lies somewhere in these two templates, index.html and greet.html. Yeah, they're almost the exact same except for the contents of the body. And, you know, it wasn't a big deal. There's only 2 pages. So what? I copy-pasted this once. But imagine now a normal website or even your home pages, which had 3, 4, or more pages. I mean, at this point, you're just copying and pasting everything, honestly, as you probably did necessarily for your home page. Why? Because when you have HTML only, maybe CSS, and even JavaScript, that's all you can do is copy-paste, and just make sure that you have the same structure. Maybe you have the same CSS file, the same JavaScript file, the same third-party libraries. But it makes it very, very annoying, as you might have realized already, to just make a change that affects everything. So wouldn't it be nice to like factor out all of this and all of this and just let the body change? So here too is something that Flask and really other equivalent frameworks let us do. It allows us to create what we're going to call conventionally a layout instead. So I'm going to go ahead and do this. I'm going to copy one last time all of the same HTML. I'm going to go into my terminal window, and I'm going to create, by convention, a file called layout.html. This is truly going to be a blueprint of sorts. And in layout.html, I'm going to paste all of that same code, but I'm going to use now some Jinja syntax to indicate that I don't want to plug in just a variable like name here. I want to actually plug the contents of a whole other file. So instead of just using curly braces, 2 of them left and right, I have to use slightly different syntax to say I want a whole block of HTML here from some other file. And the way to do this, even though the syntax is a little non-obvious, is you use open curly brace, %, block. Then you can call the next word anything you want. It just has to be a special type of placeholder for an actual file, not for just a variable. I'm going to call it body only because I'm in the body, so I want a placeholder to be the entire body. And then outside of this, you then say in one word, no space, end block. So it looks kind of stupid, honestly. And why do we have yet more ugly syntax? Again, just different software developers in the world are all choosing their own syntax for their own libraries. So they all kind of look different, but are all kind of similar in spirit. And you just get used to seeing the different syntax. This now is not nearly as pretty as the pair of curly braces for variables. But this is how I can say plug the contents of an entire file here. And now what does this let me do? I can now go back into my index.html file, which at the moment still looks like this, but almost all of this is copy-paste. The only lines that are interesting and different are these 4 lines here in the body. So what I can actually do now is I'm going to highlight that and cut it. And then I'm going to highlight everything else and just delete the entire file. And I'm going to use some of that same syntax and say curly brace %, extends, quote unquote, layout.html. And then I close my thought with a % and close curly brace. So this syntax, as you might just be inferring, is now saying, please extend whatever layout.html looks like. That's the original blueprint, the mold out of which I want to make this web page. And now here, the syntax is a little weird too, but similar at least from before. I can now say the body block that I want you to plug into that layout is going to be everything between these 2 tags, which we already saw earlier. But in layout.html, they're sort of giving a placeholder. In index.html, this is what I'm going to plug in to those other placeholders as well. So I'm just going to give myself some extra white space. I'm going to paste the HTML that was there. If I want to make clear what's going on, I can indent it, although this has no functional impact. But it just makes clear that just like in HTML, you can open a Jinja tag and close it. But in Jinja here, we have this here, hey Python, here comes the body of this page. Hey Python, that's it for the body of this page. And all of this stuff should be plugged into this main parent layout, if you will. So super ugly, admittedly, but now at least things get way less redundant because I'm going to do the exact same thing over here. In greet.html, it looks like this, but now I'm going to do this. Extends layout.html also, just as before. The body that I want to plug in is going to be everything inside of these tags here. And this body is just going to be hello, comma, name in curly braces like that. So again, ugly. Syntax got really ugly fast, but it's really just following these patterns now. And we have 2 types of placeholders, 2 curly braces for variables, and now this kind of syntax with the % signs and the single curly braces for like contents of actual files. And so now, in this world or in the world of a home page, if you were using Flask and Python to make your personal home page with all of those various pages, you would probably design one main layout with all of your pretty logos and colors and fonts and like what you want the site to look like. And then each of your smaller pages would now be distilled into just these smaller fragments. And whether you're using Python or Java or JavaScript or other languages too, all different programming languages have popular frameworks that do things like this. The idea is the same across all of them. All right, let's see if it works. Let's go back into the browser. Let me go back to my /route. There's that same form. Let me type in David and click greet. And indeed, I see hello, comma, David. I see that greet was automatically added to the URL by the browser when I submitted the form, followed by the key value pairs. And if I view the page source as I did earlier, you'll see that you have the entirety of that layout with hello, David plugged in. Meanwhile, if I go back to the form and view this page source, you'll see the exact same layout, but with the form tag plugged in. And here's where you can be a little less nitpicky with styling. OK, yes, this isn't technically indented inside of the body, but it was relative to the original file. So at this point in the game, you don't need to worry about your outputted HTML looking super pretty. You want your source code that the humans see to be pretty, not the browser. This is not a stylistic concern. Whew. OK, questions on these capabilities then of Flask? Or problems that we've just solved and why? Yeah? OK, so if the files in question are in different folders, for instance, if I go back into my index page, which has the form, the routes here are entirely dependent on what is in app.py. There's no notion of a folder when it comes to implementing a web application anymore. They are more generically routes. However, and we've not done this yet, you can put your static content, your images, your video files, your CSS files in a folder called static, and there can be subfolders therein, and that would affect what you use as your source attributes for images, or your source tags for video, or any of those kinds of assets. And we'll see that eventually in the problem set next. Other questions on what we've just done here? Yeah? Good question. How did I ensure that the web app starts on the form and then goes to the hello page? So whatever you decide your default index route is, like the implicit slash, that is what is going to be pulled up when a user visits the domain name where your website is hosted. So if I go back over here to app.py, because my slash route is designed to return index.html, that's exactly why that response came back. Good question. All right, so beyond this, let's consider now issues of privacy. And we'll touch on this, too, as we get to issues like shopping carts and cookies. If I zoom in on the URL here, even though the URL itself is a little long and ugly and cryptic, but when I type in my name and hit greet, of course, we keep seeing name equals David in the URL. In what sense might this be bad design? Or in what kinds of web apps might you not want the name to show up in the URL like that? Because this is what Google does, and this is what my app does. Yeah. Yeah, so if I'm logging in with a username and password, I could imagine that they show up in the URL after the question mark, where username equals Malin and password equals 12345. But then all my, like nosy siblings need to do is go through my browser history, and boom, like it's right there for them to copy paste. So that doesn't seem particularly secure. Or if someone's walking past you in a cafe, they can just look at your URL if it's revealed by the browser, and they see it too. So get is not necessarily the best verb to use, even though it's the default when submitting forms. Typically, when you've got anything remotely sensitive or anything large, so be it a password or credit card number or like an image or a video that you're uploading to Instagram or to YouTube or any such site like that, you don't want the data going into the URL. And thankfully, there's actually an easy way to fix this. I can go into my form, which is currently in index.html, and I can just change the method from get to post in lowercase here, but the verb in the virtual envelope we discussed last week would itself be capital P-O-S-T. Now, unfortunately, watch what happens here. Let me go over to my original form by going back to the slash route, and I'm reloading the page to make sure I get the latest, freshest HTML. And just as just to confirm here, yep, if I view source, method is now post. So let me go ahead and type in David now and click greet. And before we saw hello David. But now I get method not allowed. And this is somewhat subtle, but in the title of the tab, notice that it's a 405 error, which is not familiar probably. Almost all of us have seen 404, file not found. Turns out 405, a little more arcane, is the method. The HTTP verb is not allowed. Why? Because by default, my app.py only currently supports get by default. How do I support post? Well, I just need a little bit more syntax. So let me go back into VS Code here. Let me go into app.py now. And after changing the form, I just need to inform Flask that, you know what? The method I want this greet route to use should not be the default, which is only get. I want it to use these methods. And it takes a second argument called methods, the value of which is a list, the default of which is quote unquote get. So that's the default. This has not made any changes. But if I want to support post instead, I can explicitly pass a list with one string in it, P-O-S-T, instead. And now what does this mean? We didn't talk about this in any detail last week, but inside of this virtual envelope typically is that line like get slash search q equals cat after the question mark. If you want to hide that kind of information for privacy's sake or because you want to upload like an image, which just doesn't make sense to put in the URL, essentially the part of the story would be, well, the computer looks deeper inside of that virtual envelope, and anything submitted via post goes below the HTTP headers, like deeper in that envelope. So they're still there. They're just not obviously visible for prying eyes in the user's own browser. So just by making that change in the HTML, telling the browser to submit the data via post, and changing app.py to tell the route to expect the data via post, I can now go back to my other tab. Let me go back to the original page. Let me reload just so I've got the latest HTML. And indeed, view page source, it's still, yep, it's still post. But now when I type in DAVID and click greet, now it works. But, notice the privacy implication. I'm at the /greet route, but where's my name? It's not actually there. It still went to the server, but it's not in your autocomplete or your history now for privacy's sake. Questions now on post? Yeah, oh, no, just scratching. All right. Can you, the programmer, see this? Well, let me show you a couple of other features of Chrome and Safari and other browsers as well. I keep going to view page source, which just shows you like a read-only version of your HTML. But recall that last time I actually right-clicked and went to inspect or viewed developer tools. And this brings up a much fancier version of the developer tools. And under elements here, you see everything. And it's nice and pretty printed. It's hierarchical. It collapses things into these clickable triangles. But it's the exact same thing. It's just more interactive. But notice what I can do today is this. If I go to the network tab here, and let me zoom out a little bit. Let me go ahead and reload the form here and type in DAVID again and click greet. Notice now in the network tab of Chrome's developer tools, I see a few things as we saw before. One, I see that the request method is post. Two, I see that the server automatically, without me writing any code for this, returns 200 when it's successful. But I can scroll down, 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 and you'll see that eventually, after all these cookies, more on those later, if I click on payload, the second tab next to headers, you can see as the developer what was actually sent to the server. So indeed, this is going to be super useful like when doing problem set 9, maybe your final projects. If you want to see what's going from browser to server, you have complete control over all of that information. Even if you're using HTTPS, because your browser and you, the developer, can certainly see all of this. So again, these developer tools, even though there's a lot of tabs and buttons you probably won't need anytime soon, some of them like Elements and Network and with JavaScript Console are going to be super useful to start to get familiar with. All right, any questions now on this implication of post? Anything at all? No? OK, how about one final hello example that ties a few of these things together? How about now we try to tighten things up further, only in anticipation of something like problem set 9 or really more complicated web apps where you might have not 2, but 20 or maybe even more different routes. It might be ideal to just minimize how many total routes we have so we don't get a little too overwhelmed. And I dare say that these two routes are so short, maybe I can combine them into one. And maybe I can keep the user at what seems to be the same URL, but just to kind of tidy things up. So let me propose that we do this instead. Let me get rid of my greet route. And let me go into my form in index.html. And let me go ahead and just have the action of this form still be /. So I want the form to be visible at /, the index of the site. But I also want the form to submit to itself, if only because I don't want to introduce another route like /greet, which eventually, indeed, will be compelling so you don't have one route for everything you want your website to do. So technically, this is the default too. And if I omit action, the exact same thing would happen as well. But let me rewind. And let me now go into app.py to see how we can make this happen. Well, if I want my one and now only route to support both methods, I can say methods equals, and then in a list with both get and post in any order, but I'll keep them alphabetical like this. This now tells Python, hey, this route should handle both get and post requests at the same place. Let's now go into this function. I kind of want to say the equivalent of this. If get, then I want to return the form. Else, if post, I want to then return render template of greet.html with the user's name. But this is not yet complete code, but I think I can do this. I'm going to go ahead and say the following. I'm going to go ahead and say if request.method equals get, then indeed return index.html. If request.method equals post, then go ahead and return greet. .html. This isn't quite enough, though, because I still want to pass in that placeholder. So let me again add back name equals request.args.get, quote unquote name, and then a default value of world. What does this now do for me? Well, let me go back to my other tab here. Let me close the developer tools. Let me go back to the form here. Let me reload to make sure I have the latest. Let me view page source just to make sure I have the latest. And yep, I have the latest because it still says post, but it now says slash. And let's see what happens now. If I type in my name, David, previously this submitted via post, so I didn't see any name or value thereof in the URL, but I did end up at /greet. But if the action is now slash and I click greet, notice that it still kind of works. I see hello, comma, world, although that didn't quite work, so we'll come back to that issue in a moment. But notice the URL ends in just slash. And again, Chrome is hiding the slash because that's all that's there, but it does not end in name equals David in this case, or name equals world. Now notice this too. If I reload, I'm going to get this warning. Do you want to confirm form resubmission? The page you're looking for used information that you entered. Returning to that page might cause any action you took to be repeated. Do you want to continue? You might have seen this on websites you've actually visited where you hit reload and you're prompted, wait a minute, do you want to do that? Odds are you've been prompted to reload explicitly because why? Whatever you just did was post instead of get. And by convention, besides post being used for privacy, to like hide your username, your password, your credit card number, or the like, besides being used to upload bigger files like images or videos, post is also used by convention to make changes to the server, to add something to your shopping cart, to add something to the database. Whereas get, as the name suggests, is all about getting information, not posting or sending information instead. So this is Chrome being a little careful because, you know, if you just checked out on Amazon and then you hit reload, you don't want to accidentally like buy the same book again, so to speak, even though Amazon and fancy websites have other defenses for this too, to avoid this issue. Now, there is a bug though here. It says hello, comma, world instead of hello, comma, David. And it actually would have said the same a moment ago, and I just didn't retest the code and reveal as much to you. Or if I did, I didn't even notice it said hello, world instead of hello, David. It turns out that request.args is only used for get. When using get, request.args is a dictionary that contains all of your key value pairs. But somewhat confusingly, when using post with Flask, you have to go into request.form. I have no idea why these are not sort of more obvious opposites like request.get or request.form. And sorry, request.get and request.post would be sort of sensible names. In this case, though, we have request.args for get and request.form for post. All right, that's an easy fix, though. If I go back to VS Code here, let's change request.args to request.form. Let's go back to my other tab. Let me just reload. And you know what? I'm going to say OK, continue to resubmit the same form because the form was OK. It was my Python code that was buggy. Hitting Enter, now it's accessing David OK. But watch this again. If I hit reload, Command R or Control R, I get the same warning. Are you sure you want to submit the form? Yes. If I do it manually with the reload icon, I get the same warning as before. But if I want to manually induce a GET request, well, that's fine. Don't hit reload and send the same request. Instead, go up to your URL and just put the cursor up there and hit Enter. And now notice, same URL is a GET by default. So anytime you and I have typed URLs into browsers, GET is always the default. Only when you click on a button, typically, that the programmer has configured to use post, are you actually adding things to your shopping cart or the like. All right, so we are back, and if I go way back in time myself, like this is actually like the first web application I made back in 1997, I believe. So at the time, this would have been, what, my sophomore or so year. I had taken CS50. I took a follow-on class called CS51, which is a different type of programming. And then I pretty much taught myself a language called Perl, which is somewhat less popular nowadays, but it's another language like Python, like Java, like JavaScript, like others that can be used to make web-based applications. And the web was very young at the time. And the process via which students, my classmates, could register for the first year intramural sports program, aka Frosh IMs, was to grab a piece of paper and like write your name and email address on it and walk it across the yard to Wigglesworth, I believe, where the proctor lived, and you'd slide the piece of paper under the door. And like that was how we submitted forms in my day. So this was an opportunity, even back in 1997-ish, to like move things online, and the website went on to live on until I think like 2007. I found this online, and then it's become something else since. But this was a website via which people could register for sports, and people could log in the scores for various games and whatnot. And so underneath the hood, I didn't even know anything about databases at the time. It was just like CSV files that I was storing the data in, but there were HTML forms. And there was, with Perl, the language at the time, the way to do the exact kind of stuff that we've just been doing already with Flask. And so what I thought we'd do is implement a slightly less ugly version of this. Repeating graphical backgrounds were in vogue in like 1997, as you can see here. But these were the aesthetics of the day, including the so-called blink tag. So let's at least focus on the functionality of this website and not so much the aesthetics, and see if we can't implement some of the plumbing for actually solving like a real-world representative problem, be it for freshman intramural sports or something else like it, where you're getting data from users and processing it somehow. So let me go over here to VS Code. Let me create a new directory called frosh ims, just so we can keep all of this code in its own directory. Let me cd into frosh ims. Let me proactively make another directory called templates, in which our templates, our .html files, do need to live. And eventually, I'm going to go ahead and create two files, minimally, app.py and index.html. So let's do the first of those. App.py will live in my frosh ims directory. And I'm just going to recreate something very simple like we have previously. So from Flask in lowercase, import Flask capitalized, render template, and also request. So same first line as before. Let me then give myself a variable called app, set it equal to calling the Flask function, capital F, with underscore, underscore name, underscore, underscore. And then let me give myself a route for slash, as before, with an index function, though again, I could call that anything I want. And just for now, let's return render template of quote unquote index.html as though that exists. So this is not really a web application as much as it is at the moment just a recreation of HTTP server for one file. Let's now, in another tab, create a templates file called index.html. And I'm just going to save myself a few keystrokes. Let me copy paste from earlier almost all of the layout from before. I've changed the title in advance to frosh ims instead of hello. But this is essentially the same template. And for now, though, because I'm in an index.html, I'm not going to use extends or any of that fancy block stuff yet. I'm just going to go ahead and create a relatively simple form via which, back in the day, my classmates could have registered for intramural sports. So let's go ahead here. And I'll propose that we do this. In this page, we'll have a form, the action of which will be a route called /register, though I could call that anything I want. It'll be somewhat private, so I'm going to use post instead of get, just so that people don't accidentally maybe register twice by hitting reload without warning. Inside of this form, let's go ahead and give them an input. Where autocomplete will be off, as always, for demonstration's sake. Autofocus, so the cursor goes there initially. The name of this field will be literally name, because I want my classmate's name if they want to register for some sport. The placeholder will, again, be quote-unquote name, just so they see some gray instructions. And the type of this field will indeed be text as before. And then I need to give them the ability to register for a few sports. Why don't we keep it simple? Like back in the day, basketball, soccer, and ultimate frisbee were three of the sports that we supported. And so let me do this. And you might not have seen this before, unless you dabbled further with forms on your own. But I can create a select menu, otherwise known as a drop-down menu in HTML, inside of which are a whole bunch of options. And each option typically follows this paradigm: the value of the option, and then the actual text that the human sees. So the value of these options will be, how about we do basketball as 1? And I want the human to see literally the same thing. Though just like with a link in HTML, they could be different, but I'm going to keep them the same. Another option will be, let's say, soccer. And whoops, let me fix my quotes. And this human will see the exact same thing, though it could say something else. And then lastly, the value will be, quote unquote, ultimate frisbee. And the humans will see the same thing there, ultimate frisbee. All right, so this is going to create, as we'll soon see, just a drop-down menu with 3 separate options. If I want the students to be able to submit this now, let me give them a button, the type of which is submit. And this button will be like the word register on it. So I think we're pretty much good to go. Like, this is all just HTML, no Python, no Flask per se, except for the rendering of this same template. So let me go into my terminal window. Let me do Flask run inside of this directory, because I need to serve this app instead. I'm going to see some ugly output, including my own URL. URL. And if I hover over that and then open that URL, I should now see a more interesting form. It's got not only a field for their name, but also this drop-down menu with all 3 sports. Now, this isn't maybe the best user experience thus far, because I feel like I'm biasing people to registering for basketball, maybe, because it's checked by default. I mean, a lot of forms nowadays have like a blank placeholder for the form. So this is just an aesthetic thing, but I can do this. Let me go back to the same form. And let me give myself just a blank option at the top that, in fact, I'm going to disable. So you technically can't select it proactively, but I am going to select it by default. And so we probably haven't seen those HTML attributes before. But if I want to create the equivalent of like a title for this dropdown, I'm going to literally create a disabled option that's automatically selected called sport, so that you can't select it per se, but it is there at the top. So if I go back now to my other tab, reload, it's just marginally prettier than before, and I'm not biasing people toward accidentally registering for basketball alone. And if I click on this, you'll see that sport is grayed out and therefore not manually selectable, but I can select any of these other 3 still. All right, well, unfortunately, if I type in David and I try registering, for instance, for soccer and click register, I do end up at /register. And there's no question mark or name or sport, so it's probably indeed post instead of get. Those are hints, but not found. Notice the tab here very succinctly says 404 not found. Well, why is that? Just to be clear, why did /register give me a 404? What's the logic here? Perhaps just state the obvious, or... It doesn't exist, right? We haven't done that step yet. All right, so something as simple as that. And so I actually sort of belabor that point, because as you're learning like a lot of these conventions and some of this new syntax, like honestly, you're just going to make stupid mistakes. Something's not going to work. But again, go back to first principles. Well, why is it not found? All right, /register should be a template maybe called register.html. Oh, I forgot my app.route. So that should be the kind of thinking as you try to diagnose these problems moving forward. All right, so let me go into app.py. And let me give myself a second route here. So app.route, quote unquote, /route. Then let me define a function called anything I want, but I'm going to call it, oh, sorry, not /route, /register. Let me call the function, just to be consistent, register. So, but I could call that anything I want. And just for now, let's not do anything too interesting. Let's just return the rendering of a template called success.html. Let's just pretend for now that registration is successful no matter who you are or what you do. Now, I need that template, and I only have index.html at this point. So let me actually now do my best practices. Let me copy all of that. Let me, in a separate terminal window, let me do code. Let me go into my frosh.ims directory. And let me create a new template called layout.html, just like before. Let me paste all that same code. Let me delete the form and just put in that big placeholder. So block body and then end block is all I did earlier. This is just kind of boilerplate now convention. Everything else I'm going to leave the same. But if I wanted to make it prettier, I could add my CSS up top. If I wanted to add like this crazy repeating background, I could probably do that up top too. So I could make every page look as ugly as it did back in my day. But we'll focus just today on the text. All right, so now that I have layout.html, let me clean up index.html. I don't need all this redundancy. I don't need all of these tags at the top. Instead, recall, I think I just need extends, quote unquote, layout.html with the appropriate %signs and curly braces. I then have the appropriate block body, though I could call body anything I want, but I'm going to stick with my convention earlier. And I'm going to delete the tags down here that I no longer need. Why? Because if I go into layout.html, I already have all my open tags, all my closed tags. The only stuff I want in index.html is going to be what belongs in the body. So end block down here. And just to be pedantic, let me go ahead and highlight all that, hit Shift Tab, and that will like unindent it just to line things up, just to be tidy. All right, so better, even though it looks a little cryptic now, but now I've laid the foundation for making a third page, a fourth page that don't have all of that same copy paste. All right, so now let's go back into app.py. Success.html is where I left off. So OK, let me open my terminal window. Let me code up a template called success.html, whose purpose in life is literally just going to be like to say, you are registered, just so that we see some informative message on the screen. So this part I do still need, extends layout.html. So there's a little bit of copy paste still, which is a little ugly, but so be it. block body for this template. And I'm just going to say, you are registered, exclamation point. All right, and then end block. So super simple. It's just an informative message claiming that the student is registered. All right, let's go back to the original form, which is this. Let me reload to make sure my HTML has reloaded. Type in David. I'm going to register again for soccer and click register. And oh, interesting, method not allowed. So I'm not getting a 404 anymore. I'm getting 405 at /register. What's the deduction here? How did I screw up this time? 405 is progress, yeah? So it's not, the placeholder I think is OK. This is now about the underlying HTTP stuff. The method was not allowed. Say again? So get versus post thing too. So by default, all of these routes in Flask just by default assume get, because it's safe. It doesn't allow you to send information to the server in quite the same way. But if I do want to support post, recall that we changed this to be methods equals and then a list with quote unquote post in it. So I just need to enable support for that method. That is that HTTP verb. All right, let's go back to the form, reload just to make sure I haven't screwed up. Type in my name, David, select soccer from the dropdown, click register, and now I'm not only at /register in the URL, it claims that I am indeed registered. Now, of course, I've done nothing interesting. There's no database, there's no CSV file. We'll get to that in a bit, but at least I now have the plumbing in place to do something dynamic based on that sport. All right, well, how can I now improve upon this? How about we go ahead and store the actual registrants in a dictionary in the computer's memory. So instead of just claiming that they're registered, let's actually make a notation. And the simplest way, as we did weeks ago in Python, is just store things in like a variable in memory, like a list or a dictionary, a set, anything like that. All right, well, let me go back into VS Code and in app.py. And I think what I'm going to have to do here is change my register route to actually do some useful information. But before I register the user, let's consider where I want to actually put them. And so let me propose that. How about we do this? At the top of my file, let me go ahead and declare a global variable called registrants. And set that equal to an empty dictionary. So we've done this before when we were playing around previously with using dictionaries to store key value pairs. And I'm going to propose that we store the registrants as a dictionary. Why? Because I'm going to keep it simple. Like the name is going to be the student's name. Or sorry, the key is going to be the student's name, and the value is going to be whatever sport they registered for. So David in soccer and Carter in basketball. And so it kind of makes sense for like a two-column dictionary, so to speak, as we often depict it on screen. So how can I use this dictionary? Well, let me go ahead and do this. Down here under /register, let me go ahead and initially do this. How about we get the user's name from request.form.get and set it equal to whatever the value of name is. And I'm not going to give a default value now because I don't want to call the student world or something strange like that. I'm just going to assume for now that it's there. Let's then create another variable called sport and do request.form.get quote unquote sport to get the student's sport. And then let's go ahead and do this. In the registrants dictionary, let's index into it using the student's name, and let's set it equal to whatever the sport is. So I've got these variables just to keep my code tidy, and I'm now putting a key value pair in that, into that dictionary. All right, well, what do I want to now do? And I'll go ahead and say success.html, sure. Let's go ahead and do that. But now I think success.html means that. So let me go back to the form, reload. Let me type in David and soccer, register. OK. Let me go back and say Carter and basketball, registered. OK. Now let's see what I want to do next. How about I go into, let me give myself another route, and let's play around here. So app.route, let's give myself another third route called registrants, whose purpose in life is just to show me who all of those registrants are, just like you would expect from a website like this. And then let me define a function called registrants or anything else. And then let me return the rendering of a template called registrants.html. And let me pass in, this is kind of neat. I can do registrants equals registrants, which again looks weird, but what am I doing? I'm presuming to pass in a placeholder called registrants, the value of which is this dictionary that I've been collecting all of the registrations in. So similar to the name placeholder before, but it's a little more powerful because now it's a whole dictionary, not just a single string. So I think now, let me be creative here. Let me go into my templates under my templates folder. And let's do this. Let's go into my terminal window. Let's create another template called registrants.html that's actually going to do this displaying of all of the registrants for us. So extends layout.html, just so I can borrow all of the same HTML as before. And let's define block body, just like before. And inside of this, end block, I want to put, I don't know, like a bulleted list or an ordered list of all of the registrants. So how can I do this? Well, let's do an unordered list, UL. And here's where Jinja and Flask more generally get kind of interesting. Like, I want there to be something like this, an LI, and then like the student's name, and then an maybe LI, yeah, like that, and then maybe like sport, something like this. But I didn't pass in a name. I didn't pass in a sport. I passed in the entire dictionary of registrants. Now in Python, if we were just doing something in the black and white terminal window and doing a command line program, you know, I'd probably have some kind of for loop in Python. Jinja does allow you to do this. So a templating language tends to come with very lightweight mechanisms for doing placeholders, doing simple loops, doing simple conditions. So Python-like syntax, and it's almost identical. So watch what I can do. Inside of this unordered list, let me not start to manually output a single li. Let me use this syntax. The same Jinja syntax that I used for block. So curly brace, %, and I'm going to say this, for name in registrants. So this is just like Python syntax for iterating over a dictionary. And now this is going to look stupid, but the opposite of that is end for. So in HTML, you use the slash. In Jinja, you literally use the word end, no space, and then the name of the keyword. So end for is how you close this. But this is where templating gets really cool. You can now do li, and in here, I can do something like that student's name. And that's it. I'm going to leave it like that. And what I'm doing here is using really a template as templates are intended. I've got like the basic building blocks of what I want this output to look like. But thanks to this little for loop here, thanks to Jinja syntax, the curly brace and the %, I'm going to iterate over every dictionary, printing out name, 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 name. And so if I've got 2 kids registered now, I'm going to see 2 LIs, David and Carter, respectively. So let's see. Let me go back to my Frosh IMs tab here. And I don't have a link yet, so I got to do this manually, like a developer would. Let me go to /registrants, and I'll zoom out and hit Enter. And you'll see what you'll probably see, too, when making mistakes for the first time in this world. So where is the error message? Unfortunately, internal server error is not all that useful, but we do tell you see terminal window. So if I go to the terminal window, I haven't been paying attention to this for quite some time. And in fact, I have 2 terminal windows open so that I can still use commands at the prompt. But if I go back to my first terminal window, aka bash there, you'll see in your terminal window when developing web applications, like all of the mistakes you made in the terminal itself. This is one of those Python tracebacks that's related to me screwing up here. Now, let me go ahead here and let's see, type error. Function is not iterable. And block for name function is not iterable. All right, so what mistake did I make? Well, this is what happens when I don't follow my notes and make changes on the fly. So I have this variable on line 5 called registrants in all lowercase. But what did I then do on the fly here in line 22? I defined a function called registrant. So like newbie mistake, like I shouldn't have done this. I can't have a variable and a function of the same name because the symbols are literally identical. So just to make clear that this variable up here is actually global, we'll use our convention like we did in C often. When we had a global variable, we'll capitalize it all just to make it stand out like a constant value up there. And so down here, what I'm going to do is pass in registrants in all caps. So that was stupid, didn't mean to confuse there. But the reason for that error, to be clear, is that you can't have a function that's the same name as a variable. I could just change the variable name altogether. I'm going to go ahead and just capitalize it to make it really stand out that this is, in fact, a global variable up top. All right, now I'm going to go back to my browser. Let's do David and soccer. All right, but there's going to be some other mistakes here. So on line 17, let me go ahead and change this variable to be capitalized there, because indeed I want to put the key and the value in this newly named variable as all capitals registrants. Let me now go back to VS Code here. Let me go back to the form, and let me start adding some data fresh. Let me register David for soccer. Clicking register now, and we should see you are registered. But hopefully now it's indeed in the computer's memory. Let me go back and register now Carter for basketball, clicking register again, and hopefully it's now registered. If I now change my route manually to b/registrants, which is this newly added route that I made, and hit enter, now I see, thank God, now I see the unordered list containing everything in the computer's memory. So when I say you are registered, I kind of mean it now, because the server is still running, and in the computer's memory is, in this registrant global variable, a dictionary of key value pairs. Of course, we're only seeing the keys at the moment, so it might be nice to actually see the values in as well. So let me go back to VS Code. And let me go into registrants.html, and I'll just do something a little messy. I'll just say, how about, well, just to make it a sentence, is registered for, and now another placeholder, I'm going to say registrants bracket name. So just like in Python, if registrants is itself a dictionary, registrants bracket, and then the key you want to index into is perfectly valid syntax as well. So now let me go back to /registrants. Let me click reload again. So why isn't it working, everyone? What's the bug that I introduced earlier? If David is registered for none and Carter is registered for none, but David and Carter are in the dictionary, like, that's a good thing. So some of the data is in there. So why are there no sports associated? Well, the first thing I literally just did in front of you all was I went to app.py and I stared at line 17 thinking, like, how did I screw this up? I'm putting sport as the value of the key, which is the student's name. All right, line 17 looked fine to me a few seconds ago, so I looked then with my eyes at line 16. And this too looked OK. My first thought was, oh, did I use request.args instead of request.form instead? Because that would have assumed get instead of post. But no, like, that looks OK too. So then my final instinct was, oh my God, did I screw up the HTML form? And so that's why I went back over to my tab here. I went to the original form here. I then view page source. And this might not be as obvious to you if you've never seen the select menu before. What is apparently missing here that might explain my mistake? Yeah. Yeah, I didn't name this form field quote unquote sport. Now, to be fair, you haven't seen me do this as a select menu before, and it's different from this input. When you have an input tag, you literally say name equals whatever on the input tag. It turns out, I don't know why I skipped this earlier. I probably meant to come back to it. The select tag also can take a name parameter. So if I go back to the name parameter here and go back and add the name parameter, let me go into that template, which is index.html. Let me add name equals quote unquote sport in all lowercase, which is different from the visual aesthetic of this temporary disabled option that's just there to make things prettier for the human. Now, let me go ahead here, and first, I'm going to go into my terminal window. And I'm actually going to hit Control-C to stop the server altogether, because I want to throw away the contents of memory and therefore get rid of that dictionary that had David and Carter and those none values. So this is sort of me clearing the computer's memory. I'm going to rerun Flask run. I get that same URL as before, so I'm going to hover over that and open the new tab. And just to be sure, I'm going to do view page source. And here I see now, OK, now the form has both a name and a sport in it. All right, now I'm really going to cross my fingers, because I intend for this now to work. David will register again for soccer, register. Claims we are registered. I'm going to go back and do it again for Carter and basketball, register. We still don't have a link, so I'm going to manually go up to the URL and change /register to registrants as before, zooming out and hit enter. And thank God, now I'm actually registered properly for this. So, oh, thank you. So what is it, like 20 years later, I'm still struggling to implement this site? OK, so So here now we have, for the first time in Python and web stuff, like now we have a proper web application. And it's not just echoing back, hello, David, hello, Carter. This could now work for any of you. And it's currently served privately. But if I made this URL public, I could put this on the web now and let anyone in the world register. But there's kind of some issues here. There's some security flaws potentially. And so for instance, let me go back to the web form here. And let me open up the Inspect tab, the developer tools, and just remind you that anyone on the internet, not only you, the developer, but an adversary, can see all of your HTML, see all of your CSS, see all of your JavaScript. But more importantly, because this is all client-side in the browser, there is literally nothing technically stopping them from changing the HTML, or at least their copy of it. And I did that last week with Yale. I changed their website. But no, I changed my copy of their website. But when forms get involved, you could maybe be actually malicious now. Because even though this drop-down menu only has basketball, soccer, and ultimate frisbee, suppose I really want to register for, how about, let's say, name your favorite sport. Volleyball. We really want to register for volleyball, but like this website won't let me. Well, there's nothing stopping me from going under the Elements tab in my browser, going into this select menu here. And you know what? Ultimate Frisbee. Let's change this to volleyball. And let's change this to volleyball. Enter. I'm going to close the inspector now. And as requested, now we support volleyball in the form. Now, it's not changed on the server, to be fair, but think about how HTTP works. When I fill out this with, say, let's see, Bernie's name, Bernie really wants to register for volleyball as well. At the moment, my code is just going to trust that what's in request.form is what was in the original form itself, no matter whether the human adversarially actually changed it. So if I actually submit this form and click register for Bernie and volleyball, even though that's not one of the supported available sports, if I now go to registrants, my website nonetheless has trusted that Bernie and perhaps you are registered for volleyball. So what's the implication of this? This has surely happened in the past when like really poorly implemented websites allow you to specify the price of an item, for instance, in your shopping cart, and they just trust that when you click submit or add to cart, it adds the price to the back-end server. If you're not validating the price and making sure, as with a database, that, wait a minute, that price is valid, or wait a minute, those sports are valid, like who knows what people are going to do to your site. And it's that simple to actually hack a website accordingly. Now, we can very easily fix this with some week 6 style Python. We really just need to do a bit of logic here. And so let me propose this. Let me go into app.py here. And at the very top, let me also create, how about a global variable called sports in all caps. And I'm going to set that equal to, in square brackets, the list of sports I actually want to support. So I'm going to put in basketball here. I'm going to put in soccer here. And I'm sorry, no volleyball officially. I'm going to put in ultimate frisbee here. So I've got this global list of supported sports. Now, think about how I made this form a while ago. I just hard-coded these sports here. Well, I don't have to do that. I can sort of draw upon my own official list of sports instead. So let me scroll down to my index.html rendering template here. Let me say that the sports I want to support are these. So just using the same placeholder trick as before, but I'm now telling the template what sports we currently support. Now, if I go back into index.html, I don't have to manually do any of this. Let me get rid of all 3 of those options, which I manually inputted earlier. Let me use my new trick with Jinja syntax and say for sport in sports. Then let me proactively say end for, just to finish that thought. And then in here, let me do option value equals, in curly braces, sports. And then so that the human also sees the same words, I'm going to say sport out here. So I've completely changed what was hard-coded, manually typed, to something now that's completely dynamic. So now it's not going to stop someone adversarially like me from changing the HTML. But watch this. The behavior on the form, if we go back, is still now the same drop-down as before. So aesthetically, it looks the same. But you know what? Why don't we be clever now? And let's go into app.py and the /register route. And why don't we say this? If, how about sport, not in sports, then let's return render template failure.html. Now, this template doesn't exist yet, so let me just quickly make this real fast. I'm going to copy that code from before. Let me create a code file in failure.html. I'm just going to paste this here so I have a super simple error message. And I'm going to say you are not registered. That's what we mean by failure. And now in app.py, consider what logic I've added. Sports, in all caps on line 22, is that same global list as before. By asking Pythonically, if sport, not in sports, well, then you hacked me. Like you tried to inject volleyball or some other sport into request.form. So I'm just going to say, no, failure, not letting you register. And I can do this a little more verbosely too. Why don't I also say this? If not name. So if the name is blank, let's similarly return a render template of failure.html. In other words, if you didn't give me a name, you left it blank, that's not useful for me running the sports program. Let's also consider that to be a failure. So if I go back to this tab now, I'm going to reload just to make sure I have the latest client side. Let me be lazy and just click register. Enter. You are not registered because I didn't give it an actual name. All right, well, let's go back. How about I now type David, but I'm not going to choose a sport. I just want to register myself. Nope, that did not work now. Let me go ahead here and choose soccer. This, I think, does work. Let me go back now and try this hacker trick whereby I go into the drop-down menu. I go into the select menu. I change, as before, Ultimate Frisbee to volleyball. And I'll change this one here to volleyball. Let me close the tab now. This looks like it's available now. But when I click register this time, it says you are not registered. And this is much better than relying on other techniques you might see or have seen online with regard to HTML, because there's also this trick. Let me go back to the screen here. Let me go back to index.html. And you might have seen online, or you might eventually see online, that there's other attributes you can use, like required. You can literally tell the browser, this field is required. You cannot leave it blank. If I go back to the browser now, reload, and I, again, presume to be lazy, and I don't type in any name and click register, OK, so that's kind of nice. Like now the browser is being a little more helpful for me, saying, no, this is required. You have to fill this out. But again, if you know what you're doing, OK, well, I disagree with your requiring a name of me. Let me go in here. Let me go over to this tag. Let me delete the required attribute. And now I slip through. But I didn't slip through on the server. And so there's a difference here, and an important distinction. And so many people in the real world still screw this up. There's client-side validation, like actually checking that the data is as you expect on the client side, the browser. And there's server-side validation. And even though client-side validation, like adding that required attribute, makes things more user-friendly, right? Like that was a pretty little pop-up. It tells me that it's required. It just looks better than the previous version. It is not trustable. You cannot trust any input that ever comes from the user, because clearly with like an hour or so of CS50, like they can learn how to turn all of these defenses off. So even if you like the user interface better client side, you have to do server side validation always. Users are not to be trusted. And as soon as any app or website you make becomes popular, unfortunately, then you have to deal with all of the adversarial possibilities as well. Oh, good question. Could the adversary potentially access things sensitive like app.py? Theoretically, no. Like if Flask itself is buggy, then sure, maybe. If you're running some other software on your server, on your laptop, then sure, it's possible. However, if your server's properly configured, theoretically, they should not be able to get access to that. With that said, we'll soon see, or you might with your final project, if you do something web-based, you're never going to want to write like usernames and passwords in your actual code. You can put them in what are called environment variables. So sort of in the computer's memory, but not in your code, just in case you or someone screws up. There are still ways to defend against those kinds of possibilities, however slim. Yeah? A good question, and this comes back to first principles, just like in C and in Python. As soon as you return from a function, that's it. Nothing below that line of code executes. And so to summarize the question, even though I'm returning this failure.html template, how am I making sure we still don't accidentally put volleyball in that global dictionary? It's because, for instance, if you don't give me a name on line 22 at the moment, I'm returning the failure template, and that's it. Lines 23, 24, 25, 26, 27 never execute. In particular, 26 never executes, and that's where I would have been saving the name. Similarly, if we get an invalid sport that is either blank or not in the original authoritative list, we return failure.html as a template in line 25. We never get to line 26. So it just boils down to return and what that means in Python 2. Good question. Other questions as well? No? All right, how about we make one more enhancement here or so, because the problem with storing everything in this global dictionary might be what? We've got it all working, finally, but why is probably a global dictionary not the place to store Frosh.im's registration data? What's the implication of this? OK, might slow the whole process down, but RAM is actually good. Memory is actually generally a good thing. So not going to be a deal breaker here. Why might I not want to store that data, though, in that variable? You can perhaps infer how I fixed something earlier. Yeah, and back. Yeah, the memory gets deleted, garbage collected, if you will, as soon as Flask stops running. So if you so much as hit Control-C, like you've just lost all of your freshmen who registered for the sport, probably not a good thing. I did this deliberately a moment ago, and I hit Control-C because I did want to clear the dictionary, but trusting that your server will never crash and your code will always work and the power will never go out, like that's not the right way to build any kind of web application with persistent data. So what we probably want to do is reintroduce CSVs, and we've played with those in C and in Python. Could totally use CSVs, but we also now have SQL at our disposal. And let me propose that we do this in SQL instead. And for this, let me go ahead and open up a version of the program that I wrote in advance. So let me go ahead and close these templates, which will look very similar but a little different from the ones I wrote in advance. And let me go ahead and open up let me go into source 9. Let me go into Frosh.im's, how about version 4, technically, in the versions online. And let me go ahead and open up app.py as follows. So here is an already made version that does just a little something different. At the very top, I'm importing CS50 SQL library, which you might recall we used a couple of weeks past just to write Python that talks to a SQL database. And this feels like an opportune moment to bring that idea back. Down here on line 8, I'm creating a DB variable that opens up a file called Frosh.ims.db using syntax that we've seen before. I did create this Frosh.ims DB file in advance of class just so that we have a couple of columns in which to store names and sports and such. Here's that same global array, a global list called sports. And let's just see what's going on down below. If I scroll down to index, this is the same as before, as we wrote together on the fly. Let's skip deregister for a moment and go now into register. So this one's a little different, but let's see what I've done. I've got some comments in here because I wrote it in advance. And I think this logic is pretty much the same, though I tightened it up. And I'm asking two questions at once using on line 38 the or keyword here, just to say if there's not a name or the sport is not in sports, that is what we'll call now a failure. But what's fun now is that on line 42, I'm using the CS50 SQL library to execute some actual SQL. And I'm going to insert into a table called registrants 2 columns, name and sport. What names and sport? Well, these 2 values with placeholders, plugging in name and sport. Notice I'm using the question marks. Absolutely necessary so we don't get one of those SQL injection attacks, because that too could be possible if someone typed in some dangerous words or keywords like delete or single quotes or semicolons in the form. Here, I'm letting the library sanitize the data. And then this is a trick we haven't yet seen, and it's really going to start tying things together. I can also use a redirect function in Flask that has the effect of doing the if you will, safetyschool.org trick again, whereby after the user registers, if I want to automatically show them now everyone who is registered at /registrants, I don't have to manually expect that they'll change the URL like I've been doing for the past few minutes. I can just redirect them anywhere I want on my app, or heck, I could redirect them to any URL on the internet using this function call. And it's just a nice way to send them to a different route if you want them to see, in this case, those registrants. So let me do this. In the same directory, let me increase my terminal window size. Let me do SQLite 3 of Frosh.ims.db, and let me type .schema. And you can indeed see it wraps onto 2 lines here, that each registrant has an ID, which will be automatically assigned 1, 2, 3 on up, a name, which is not null text, and a sport, which is also the same. And the primary key is just going to be this unique identifier. So that I made in advance. But if I do select star from registrants, semicolon, there's no one currently registered for any sports. But let's try now running this. Let me go ahead and close my old version, which we wrote together. And I'll close that tab. Let me do Flask run in this version 4 here. All right, I'm going to see some similar output. I'm going to open the URL now. And you'll see that I made a couple of changes before. Instead of using a select menu, I used what are called radio buttons now, which is a reference to old school radio buttons that were mutually exclusive in cars back in the day. And we'll see how to do this, but it's just an alternative to a select menu. And I'm going to go ahead and type in my name again here. So I'll do David. I'll do soccer by selecting this radio button. And I'm going to click register now. And notice what happened. It's a little ugly, the formatting, but so again was this 20 years ago. Here I have now at the /registrants route, instead of an unordered list, I'm just using a simple HTML table. So I'll show you what this looks like in just a moment too. And I'll show you this deregister button, which is sort of unnecessarily large. I also have functionality we'll soon see for how you can unregister someone from a sport as well. So take your name out of contention. Well, let me go back to my terminal window here. And I'm going to click the plus to give myself a second terminal so I can go back into source 9, frosh.ims 4. I'm going to do SQLite of frosh.ims.db. I'm going to do select star from registrants now. And now you'll see that, indeed, there's David registered for soccer. And in fact, if I quit the Flask program with Control-C and rerun it again, no big deal, because that next version of Flask will just use the database as well. So I'm persisting, keeping the data in SQLite, whereas I'm actually grabbing it using my Python code in Flask. All right, let's put one more person in here so we can delete one of us too. Carter for basketball. Register, and now we see both of us here. All right, so let's see how we did this. Let's go back over to VS Code. Let me shrink down my terminal window. Let me go into the, actually, let's go into the templates directory, and let's look at, for instance, index.html. So previously, we were using a select menu. Turns out radio buttons use the input tag, but instead of having an input of type equals text, like for the human's name, you have type equals radio. And so long as each of your radio buttons has the same name, the same name, the same name, that's what makes them mutually exclusive. So checking one radio button turns off the others because they have the same name. The value I want to assign to each of these radio buttons is just the sport placeholder. This is what the human sees on the screen. So it's almost the same as the select menu. It just looks aesthetically different. But there's my same button. So that's all the difference I made there. And I added a heading tag, h1, just to say register to make clear what it is. But let's take a look at another file. This one now being, how about the /registrants route? So if I open up registrants.html, here now, it's way more verbose than my unordered list, but this is just kind of boring HTML. Here's my table tag, table head, table row, table heading. This makes things bold as the first row of the table. Name, sport are my 2 columns. I've got a third empty column just so I can fit that button, as we'll soon see again. T-body for table body. Here's the same for loop trick again, so that I can output for every registrant a whole table row. And there's this weird form in there, but we'll come back to that. But there's the registrant's name. There's the registrant's sport. But notice the slightly different syntax here. Recall that CS50's execute function, when it returns to you a list of dictionaries, you can then get at the individual columns by way of those keys. So let's go to the /registrants route. Let me go back to app.py, scroll down here, and it's actually super simple. Here, I have a /registrants route that first executes select star from registrants. So just old SQL stuff. Give me everyone from the registrants table. Let me then render the template called registrants.html and just pass in this list of dictionaries. And we haven't quite done this yet, but if you go back to registrants.html, how do you iterate over each dictionary in that list? Well, the syntax is just for registrant in registrants. That makes this a dictionary, one at a time in the list, just like in Python. So registrant.name and registrant.sport is just another syntax for using the square bracket notation. It's just a little cleaner and slightly more succinct than having quotes and square brackets everywhere. And then the rest of this is just HTML. So what happens now if I want to, like Carter's been cut from the basketball team, if you will. So how do we do that? Well, we want to click this button, deregister, next to Carter's name. But how does this work? And think about now any website you visited that has something like a shopping cart where you can remove things from your cart or update quantities or add more quantities to your shopping cart on Amazon or anything else. Well, let's actually look at the HTML that my app has spit out. Let's actually look at this here, and we'll see the following. We'll see that we have here in the HTML that reached the user, not only is David in the first column, soccer in the second, notice that my registrants.html form is also spitting out a tiny little web form of its own. It's ugly, but I only care about its functionality for now. And notice what I'm doing here. Every registrant in this database gets their very own deregister button. And that form has a button that says deregister. But notice what else each of those forms have. There's no text box. There's no drop-down menu. There's no radio buttons. Rather, you have a hidden input field here. So there is a way with HTML to have a form that will submit information, but you don't have to give the user the ability to change that information. You can just go ahead and tuck it inside of the form invisibly, if you will, hidden in fashion. And so what's going to happen is if I click the deregister button next to Carter, his primary key is 2. Mine is instead 1. So what's going to happen if I click his deregister button, it submits a form with a ID parameter whose value is 2, and it submits it to the deregister route. So what does that mean? Well, if I go to VS Code and I go to app.py, let's look at the deregister route that I skipped over. So if you access the deregister route via post, this code gets called. I grab from request.form the ID that was submitted in hidden fashion. If there's indeed an ID, that is, it's not blank, it's not 0, it's an actual number like 1, 2, 3, or more, I execute delete from registrants where ID equals that value with a question mark placeholder. And then I redirect the user back to registrants. Now, if I go back to this form here, I click deregister, we'll see that in action. Gone is now Carter. And in fact, if I go back to my terminal window here, I open up SQLite 3 of frosh.ims.db and rerun select star from registrants, Carter is now gone. So again, using very simple HTML forms, you can get buttons and links and other such UI mechanisms to like do things on the server that you want. But there is a danger here. This now is really meant, this example is like an administrative website like it was some 20 years ago just for us internal staff to be doing things. Technically, this is dangerous, what I've just done too. Even though Carter's ID is 2 in hidden and mine is 1 in hidden, what could this allow an adversary to do if they had admin access to the same site? Any thoughts? Yeah. Oh. Yeah. Yeah, they could change the value of that hidden attribute by opening up Chrome's like developer tools, change the number in the HTML. They could delete anyone, deregister anyone they want from the database. Now, in this case, I claim this is fine because this is only meant for us staff who were running sports back in the day, but it's indeed a risk. So wouldn't it be nice if we could actually ensure that only those users who are authorized are allowed to execute certain actions? I think for this capability, we're actually going to need to introduce something a bit more. And so here, of course, is an opportunity to talk briefly about really what you and I do all day long, every day. We log into one or more websites or apps, or at least until you're logged out automatically and you have to do it again. So here, for instance, is a screenshot of Gmail. When you type in your username, you type in your password, maybe your two-factor code that gets texted or sent to your phone, then you're logged in. And thankfully, you're not prompted to log in again typically for a number of hours or days or weeks, depending on the website. Like Gmail keeps you logged in for ages. Your bank probably logs you out within an hour or so for safety's sake. So that is completely configurable on the server. But how does Gmail know, how does Google know that even as you're checking different mails again and again and again, how do they know that you're still the same person who logged in? Well, it turns out that using these same building blocks as today, HTTP and HTML and more, you can actually implement the notion of a login feature by doing the equivalent of something with something called cookies. Essentially what happens when you first log into a website for the very first time successfully with your username and password, a cookie, so to speak, is planted on your computer. And metaphorically, this is kind of like taking a hand stamp, and your hand is now stamped, in this case a smiley face, so that every other time you click on a link on that same website, google.com, gmail.com, whatever, unbeknownst to you, your browser is constantly presenting that hand stamp, just like going into a club or an amusement park or something like that, where they don't want to check your ID again, they don't want to check your ticket again, they just want to quickly see the same hand stamp. And so that is one of the things that a browser is always doing for you once you're logged in. Any cookies that have been planted, so to speak, in your Mac or PC or phone are constantly represented to the site every time you click a link or make another request to that website. And mechanically how this works, not just metaphorically in ink, essentially this is what happens. Here is an example of an HTTP request to something like Gmail. And suppose, for instance, that you've logged in. Typically, as of last week, we said that coming back from the server would be another virtual envelope containing like a 200 OK message, and then like the actual web page or the picture of a cat or whatever it may be. But Google can also, if they've verified that you have some username and password correctly inputted, they can do the equivalent of stamping your hand. And the way they do this is they send an additional line of text in that virtual envelope from the server to your browser, literally using another HTTP header, not content type, which just mundanely tells you what kind of content has come back. They literally send an HTTP header called set-cookie. And then they set a key value pair on your Mac or PC. This is the technical equivalent of the smiley face hand stamp. And what your computer is designed to do, because your computer and in turn browser are supposed to implement HTTP, anytime you click another link on Gmail or click on another mail or the like, your browser, unbeknownst to you, presents that hand stamp. And how it does it technically is in the envelope it sends to Google from your browser, it doesn't send set cookie, it just sends cookie, colon, and the exact same thing. And so long as Google is smart and they have a database or something of all of the session values. Session is the technical term for this maintenance of information across HTTP. So long as Google has a big database that knows that my cookie value is 123 and your cookie value is 456, they can infer from this virtual hand stamp whose emails they should be showing, mine or yours or the like. So this is just scratching the surface, but if I really wanted to enable only Carter to deregister himself, I just have to make sure that I log him in somehow, username, password, and all of that. I stamp his hand, or really put a cookie on his computer, and only if his cookie lines up with the user ID he's trying to deregister should he be allowed to, in fact, do so. So all of this is quite possible, and indeed the technical term for this is session. And what we thought we'd do in our remaining time today is show you some examples of exactly how some of the most familiar web functionality is implemented today, some of which you'll use in your own problem set 9, which itself will be a web app, or perhaps even your final project. So let me go ahead and do this. Let me close my previous tabs and all things Frosh IMs, and let's move on to implementing some notion of login. So in just a moment, I'll switch over here to VS Code. And what I'm going to do is, indeed, in my source9 directory, I'm going to go into a login directory. And if I type ls here, you'll see app.py, requirements.txt, which just refers to libraries I want to automatically install, and a templates folder as well. I'm going to go ahead and stop the previous server and close that terminal window. And I'm going to open up this version of app.py. So there's a few new lines here, and we'll give you these lines for problem set 9. But I've got some of the familiar stuff up here, including this new redirect function we just used. And I have a session variable that comes with Flask 2. So what's nice, again, about Flask is that it deals with all of this cookie stuff for you. It sets the cookie, it checks the cookie, and what Flask does for you is it gives you the abstraction of a variable called session, so that anything you put in the session variable, which itself is a dictionary, will be there again and again and again whenever that same user comes back. A session is how you implement, essentially, like the proverbial shopping cart. If I'm logged into Amazon, you're logged into Amazon, Amazon knows which of us is which by way of that cookie. And Amazon, if they're using Flask, provides the programmer with a dictionary called session. And Flask makes sure that when Carter's visiting the site, the code uses his session object. When I'm visiting the site, it uses my session object. But it's all implemented with those same cookies. This is the same as before. These lines are new, and you'll see these in problem set 9. This is how we enable sessions in a web application. And I'll just wave my hands at the detail. There's different ways to implement sessions, whether you use cookies on the server, cookies on the browser, or other things. These just ensure that we're storing the session information, the shopping cart, on the server itself. Now down here, let's go ahead and do this. Let's go ahead and run Flask run so I can see what this app does. If I do this and visit the URL that gets outputted, you'll see a very simple web page here. And if I type in, for instance, my name, I'm not going to bother with a password and click log in, you'll see that you are logged in as David. And now I can log out. So I'm going to go ahead and click log out. And now it seems to know that I'm not logged in again. I can log in as Carter because I didn't bother implementing passwords for simplicity. But now the site knows I'm logged in as Carter. Better yet, if I reload, or click this button again and again, notice it still knows that I'm Carter until such time as I log out. All right, well, how is this working? Well, let's go back to VS Code here. And let me scroll down to first this route. This is a very common paradigm here whereby I'm checking for the index route. If there is not a name in the session, redirect the user to /login. Now, what does that mean? Well, let me go back to VS Code here. Let me go to the /route. So again, your URL will be different, but I'm just going to go to / and hit enter. Notice that I got automatically redirected to login. And so many websites do this. If you go to a website and you're not logged in, you're very often redirected to /login or /account or something like that where you're prompted. The code for doing that is right here. If there's no name in the session, if there's no name in the shopping cart, if you will, go ahead and return the user to login, that route. Otherwise, implicitly, if they are logged in, show them index.html. So let's go down that rabbit hole. Let me open up in VS Code a second terminal window. Let me go into source 9 and go into this same login demonstration. And let me open up the template called index.html. And here's all this is. There's some layout, but who cares at this point? It's just the boilerplate generic HTML. Here's the body block. I have this, and this too is Jinja because of the curly brace and the %sign. If there's a name in the session, this is just Python syntax, then say this sentence. You are logged in as whatever name is in the session, in the shopping cart, if you will. And then I just have this HTML link for logging the user out. Else, if there is no name in the session, logically, just say you are not logged in and give them a manual link for logging in instead. So that's all this particular template does. But how does the /login work? Well, let's go into this other template, code of login.html, to which I'm redirected. Super simple. This is just copy paste from HTML before. I've got a login form that's going to have an action of /login, submits for privacy's sake just via post. And then the rest of this is just a simple form. And I'm using an input type equals submit instead of button equals type equals submit, but same idea here too. And if I go back to app.py, well, let's see how login works. All right? It's a lot all at once, but they're relatively simple reapplications of the same idea. So if the user visits /login via get or post, call this function login. If the user has submitted via post, and we saw this technique before, go ahead and do this on line 23. Store in this special session variable that comes with Flask a name key and store in it the user's own name. So quote unquote name will have a value of David or Carter or the like. And as soon as you do that, redirect the user back to / just so they see the home page again. And this is how Amazon and all these other websites work too. Otherwise, if they visit this page implicitly via get, and even though I didn't say equals get anywhere, that's sort of the implication. Because if you can only get here via get or post, and we already handled post, logically all that remains is get, well then just show them the login screen instead. But there's half a dozen ways we could express that same logic. And then for logout, this is kind of straightforward. If the user clicks that logout link and ends up at /logout, this route, well, just change the value of that key in the session to be none. Effectively, no, Carter's gone. David's gone. There's no one logged in. So that is all that's required to actually implement the notion of logging in and logging out of a website, plus the password thing, which should probably involve a database, but one thing at a time. And really, session is sort of like the code version of a shopping cart, whereby if I visit this same code, I get my own session object. If Carter visits the website, he gets his own session object. And the way Flask keeps us straight is they put one cookie on my computer, a different cookie on his computer, and uses those to line up with, making sure the right session gets shown to the right actual user. Questions on this notion of sessions? No? All right, how about a couple final examples just to tie this all together? Let me go back into VS Code here. Let me quit my previous version of Flask. Let's go into Source 9 and go into Store, which is a separate app altogether. And let's start by just running Flask to see what it does. Let's hover over the URL and open it in another tab. And this is pretty ugly too. Let me zoom in. But it's a very simple bookstore, like an early Amazon.com for each of these 7 books here, each of which seems to be like, maybe this is H1, this is H2, 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 and then there's a button underneath each. Well, now let's use this as an opportunity to kind of infer, like for any website, how this thing works. Let me go ahead and do view page source. And you can do this for any website on the internet. Let's try to figure out how this bookstore adds things to a cart. Well, here's the H1 tag, uninteresting, H2, H2, H2. So the juicy part is in these forms. Each of these forms has an action of /cart. So that's the route that's going to be interesting in a moment. And it uses post for privacy's sake. Each of these forms, like the deregister feature for Carter, has an ID attribute, an ID parameter that's hidden visually that has a value of 1 or 2 or 3. So like the unique like barcodes for the books, if you will, but super small numbers in our case. And then each of these other forms each of these other books has an identical form except for the value of this here. Now in this case, this isn't such a big deal that a user could technically hack the HTML of this bookstore, Amazon.com, and change the IDs. Because, whoa, what's the worst they're going to do? Like buy more books by adding more IDs to their shopping cart? Like that's not a problem. There's no prices here. It's just the unique IDs of books. So whereas the deregister was maybe worrisome because you're changing the server, I think it's OK because the user can only, at worst, buy more books than they might via the buttons alone. So how does this now work? Well, let's go into VS Code again here. Let me give myself another terminal window. And in source 9/store, let me open up app.py, which is where all the logic is. So I'll flip through most of this quickly because we've seen this before. These imports are pretty much the same as before. This line is the same. This line is almost the same, but the database now is called store.db instead of frosh.ims.db. This is the boilerplate code for just enabling sessions, this notion of a shopping cart. And so let's see how the index works. How is it I'm seeing all 7 books at once? Well, in this index function, I'm using on line 19 select star from books to get all the books from the database. And then I'm rendering a template called books.html, passing in as a placeholder all of those books. All right, let's go down that rabbit hole for a second. Let me open up books.html in my templates directory. And here again, even though it's new today, it's probably increasingly familiar syntactically. Here's the H1. Here is my loop. Here's the H2, which is going to output the current book's title in that loop. Here's the form. Here's the ID of that book that's going to be outputted in the form. So I didn't manually type out 7 long forms. I just did 1 in this template so that it gets generated automatically, literally what a website like Amazon would do to show you 10 books at a time or 10 search results or more at a time. All right, well, let's go to /cart, which was the juicy one. And this one's longer, but let's see if we can reason through it. If the user submits via get or post to /cart, well, we first do this. And this is just necessary in some boilerplate rewrote. We're going to use the session object to store a variable called cart that in this case is going to be a list. So session, again, is just a dictionary. You can put anything in it you want. Previously, we put students' names and sports. Now, what I want to do is previously we put the student's name, the user's name in it. Now, I'm going to actually store a cart key whose value is a list. Why? Because I want to aggregate more and more books in this list. All right, so that just makes sure that I have at least an empty shopping cart the very first time the user does this. If they visit this form via post, Let's go ahead and get the ID of the book that they posted. If it is not empty, if there is a number like 1 or 2 or 3, let's go ahead and go into the shopping cart, which is a list per this line, and just append that ID. So this list of books in your shopping cart is going to contain like 1, 2, 4, 6, whatever books you're actually buying. And then the user gets redirected to cart. What if, though, the user got here via get and not post? Well, this one's relatively straightforward. If you just visit /cart, we select star from books, where ID is in. OK, so this is interesting. This list. And this is syntax you might not have seen before. But if you read the documentation for CS50's library, if you select something and use a question mark placeholder, and the placeholder itself is a list, we output a comma-separated list of values, just like you would use maybe in problem set 7 for doing SQL queries on your own. So this just means show me only those books in my shopping cart, not Carter's, not someone else's, not in the whole database. Only show me the books in my shopping cart, and then render it as such. So we only saw what the catalog here looks like at /books. Let's go ahead and let's go ahead and add maybe the first book to my cart. And now I see at /cart only that first book whose ID is 1. Let me now go back to the bookstore here, scroll down to maybe the 7th book, and add that to my cart. And now I see this here too. Meanwhile, all of this information is stored in my session. And so when I reload this cart again and again, the reason I'm only seeing my 2 is because we're checking only the list in my session. And Flasks makes sure, again, that my session is different from your session, is different from Carter's session as well. But you write the code once, and it works for thousands, millions of people in parallel. Any questions on this? Yes, in the back. Sorry, say a little louder. So to recap, so users will never have the same session values. Theoretically, the cookie that gets planted does not look like a smiley face for everyone. Each of us gets a big random number that's assigned to us. So it would be like each of us gets a completely unique hand stamp that no one else can see. The reason no one else can see it is because if the website's using HTTPS, every time this hand stamp is shown, every time this cookie is sent back and forth, it's all encrypted as well. So each of us can, even if we have the same contents by coincidence, because we like the same book,